Whoa, wait, it's hard to talk from way up here. Let me land. Okay, that's better. I'm just on my fall migration, heading east. I know, it would be easier if I just took a jet, but they don't tend to let geese on board planes. That's why I take a different type of jet, called a jet stream, which just means a current of fast-moving air that's in the atmosphere. Now, the current is actually pretty high in the atmosphere, like 5 to 9 miles up, or 8 to 15 kilometers, and is found in the tropopause, which is the boundary between the troposphere and the stratosphere. The troposphere and the stratosphere are just layers in the atmosphere. I know! Who knew so much happened way up there? And a current just means a chunk of air that is flowing within a larger piece of air. So I can jump into one of these jet streams and it pushes me along so I can get to where I need to go. And in addition to helping me get to my destination, jet streams are also used to help predict weather. So, you're probably wondering why jet streams exist. I mean, it sounds pretty strange. One clump of air is moving within another clump of air, but once I explain it to you, you'll probably be like, oh yeah, that makes total sense. The sun doesn't share all of its heat equally, so the equatorial regions get a lot more heat energy than the poles. So the equatorial air gets really warm, whereas the air near the poles stays relatively cool. The warm air from the equatorial regions meets up with the cooler air from the poles, which creates air pressure and temperature gradients. You're probably wondering what in the world a gradient is, right? Don't worry, I'll explain. Warmer air is less dense and exerts less pressure than colder, denser air. If you were to look at the molecules in the cold air, they would be closer together than the molecules in the warm air. Because the molecules are closer together in the cold air, they exert more pressure per unit volume compared to the warm air. This difference in pressure and temperature creates a gradient, which just means the change in pressure and temperature over a specific distance. Air will flow down this gradient, specifically from areas of high pressure, or the colder air, to areas of low pressure, or the warmer air. Remembering this will help you navigate all sorts of weather information. So here's a little rhyme I picked up chatting with some other geese last summer. Winds blow from high to low. Now, let me quickly explain why this occurs. Warmer air, as mentioned moments ago, is less dense, so it tends to rise, and colder air is denser, so it tends to sink. When the air is warmed and rises, the cold air rushes in to replace the warm air. This causes wind. But that's only part of the story. The Earth is rotating, so that changes the air's route from high to low pressure. This is caused by the Coriolis force. So, in the northern hemisphere, the air is deflected to the right, and in the southern hemisphere, the air is deflected to the left. So for me, a goose currently in the northern hemisphere, my jet stream is running west to east. I should add, the greater the gradient, meaning the greater the difference between pressure and temperature between the two air masses, the faster the jet stream. But how fast? Well, typically 80 to 140 miles per hour, or 129 to 225 kilometers per hour. But sometimes they can really get cruising and reach speeds up to 275 miles per hour. Yeah, I know, like a real jet. Now you can see why I want to hitch a ride. I'm still pretty tired from my migration, so I guess I can keep talking about jet streams with you for a little while. Plus, I still need to tell you about the polar front. Remember when I told you the equator gets more heat from the sun? Well, the polar front is the area between warm equatorial air and the colder air north and south of the equator, and it occurs mid-latitude. As you might expect, there's a huge difference between the temperature of the polar air versus the equatorial air. So guess what happens? Yep, a jet stream. The polar jet stream, also known as the mid-latitude jet stream, is currents of wind that are above the polar front. You can see here that there are other jet streams, and you can also see the polar jet stream is at a latitude of about 50 to 60 degrees north and south. That's why it's also sometimes called the mid-latitude jet stream. The polar jet stream, like other jet streams, has been described as a superhighway of air flowing in the atmosphere, and that is certainly the case for me. Wind speeds vary, but you can see here that the really fast winds are red and the slower ones are blue. There are jet streams in the northern and southern hemisphere, but the ones in the northern hemisphere have faster winds. Before I catch a ride on the polar jet stream, let's review some things so you don't forget about me. Jet streams are like rivers of air in the atmosphere where air currents travel at high speeds. Specifically, jet streams are currents of fast-moving air high in the atmosphere that can reach speeds up to 275 miles per hour, so they really are like jets. They are the result of warm air meeting with cold air. This creates a temperature and pressure gradient which results in air currents. The direction is also affected by the Earth's rotation, or Coriolis forces. There are several different jet streams, including the polar jet stream, which can be found above the polar front, or the area between the warm equatorial and cold polar air. The polar jet stream can be found at about 50 to 60 degrees latitude. It certainly has been nice chatting with you, but it's time for me to get home for the winter. But maybe we can talk again when I pass through on my next migration. Today, you are going to get the unique opportunity to follow a teeny tiny particle of air through the atmosphere. And by following this particle around, you will learn all about Rossby waves. In order to keep our particle separate from all of the other particles, let's call our particle Paul particle. Paul is going to be traveling high in the atmosphere in a jet stream heading east. Jet streams are superhighways of fast-moving wind that form when cold polar air meets warm equatorial air. Paul is happily traveling with his jet stream friends when, boom, he hits a mountain. This changes his trajectory, and now Paul is heading north. Will Paul keep heading north and be subjected to cold, frigid temperatures the rest of his life? Nope. Due to the Coriolis effect, or the deflection of air due to the rotation of the Earth, Paul is not destined to live a life at the North Pole. As the Earth rotates, everything on Earth goes along for the ride. This includes you, me, and even Paul. But everyone isn't spinning at the same speed. What? I know. Crazy. In order to understand this, you need to imagine the Earth with an imaginary pole running through it. This imaginary pole is actually called an axis, and it is what the Earth rotates around. The Earth is a spherical shape, so its widest point is the equator, and it gets thinner as you go north or south of the equator. Now visualize Paul at the equator. In a 24-hour span, the time it takes the Earth to rotate around its axis once, Paul is going to travel a huge distance. Now picture Paul at the North or South Pole. He won't travel at all during that 24-hour period. So, Paul travels faster at the equator since he's covering a huge distance in that 24-hour period of time, whereas Paul travels slower at the poles where he doesn't really move at all in that 24-hour period. Now that you have some basic Earth rotation under your belt, let's get back to Paul, who's been flung northward by the mountain. Paul is still rotating at the same rate he was when he was in the equator, which is faster than the rotation at his new northern latitude. So what happens? Because his rotation is different than that of his current location, he gets flung south. But he actually gets flung further south than his original location, so his rotation still doesn't match the rotation of the Earth at the latitude. Again, his rotation doesn't match the latitude he is at, so he gets flung northward again. Guess what? Yep, the new position still doesn't match his rotation rate, so he gets flung southward. This keeps happening and results in a zigzag pattern as he heads east in the jet stream. And this movement is known as Rossby waves, or horizontal waves that are found in winds at high altitude. In Paul's case, the winds are part of a fast-moving jet stream. And it's not just Paul that gets flung north and south. In fact, all of Paul's air particle buddies are part of this zigzag pattern, as you can see here. Now, the focus of this lesson is Rossby waves in the atmosphere, but they can also exist in the ocean too. Wild! Rossby waves sound like a pretty neat phenomenon, don't you think? But they actually influence weather patterns, including cyclones, which are winds that travel in a circular motion and have a low pressure center. It's worth noting that the winds of a cyclone are counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Cyclones often cause rain or snow and generally poor weather. Let's go back to Paul and his friends that are high in the atmosphere. Remember, Paul meanders up and down as he heads eastward in the jet stream. These ridges and troughs from the up and down movement can cause areas of high pressure and areas of low pressure. In fact, the ridges create high pressure systems and the troughs create low pressure systems. The low pressure systems become the center of the cyclone, whereas the high pressure systems become the center of an anticyclone. Here, you can see areas of convergence and divergence take place on the wave. You're probably wondering what convergence, divergence, and anticyclone all mean, right? Let's start with anticyclone. Like the name implies, it's the opposite of a cyclone. So, an anticyclone has a high-pressure center surrounded by spinning air, and, unlike a cyclone, is responsible for calm weather conditions. Anticyclones blow clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Let's quickly talk about convergence and divergence, which both are terms coined to describe airflow. In convergence, more air is entering an area than is leaving an area. This can cause the extra air to be forced upwards or downwards, depending on if it's occurring at the surface of the Earth or high in the atmosphere. Divergence, on the other hand, occurs when more air leaves an area than enters. This causes the air to spread out and take up more space. Convergence and divergence are responsible for creating pressure systems. Following Paul around and learning about Rossby waves and cyclones was fun, but it was a lot of information, so let's take a moment to review the main points. Paul and his air particle friends became Rossby waves when they traveled in the jet stream and hit a mountain. This caused them to get pushed northward, but due to the rotating Earth, Paul was pushed southward, then northward, then southward. This up and down motion is the Rossby wave, or horizontal waves that are found in winds at high altitude. The ridges and troughs from the Rossby waves cause convergence and divergence of air. This helps create pressure systems. The high pressure systems develop into anticyclones and the low pressure systems developed into cyclones. Wow, for a teeny tiny particle, Paul does get around. About 65% of the world's population lives in regions affected by monsoons, and the rain that comes from the monsoons impacts the food sources in those areas. In fact, in India and other parts of Asia, the monsoons are so linked to crops that there are two sets of crops, those grown during the wet monsoon season, or the Kharif crops, and those grown during the dry season, or Rabi crops. Although the terms Kharif and Rabi might be foreign to you, I bet you would recognize some of the plants grown during each crop. For example, the Kharif crops include rice, peas, corn, and millet, whereas the Rabi crops include barley, wheat, and oats. And farming is big business in India, with 70% of Indians either directly or indirectly affected by farming. So you might get that monsoons are pretty important. But what are they? Well, for starters, they are winds that change direction depending on the season. This wind change also brings a change in weather. These changes in weather bring rains, which allow Kharif crops to flourish, or dry weather, which allow Rabi crops to be successful. Although monsoons can bring welcomed rain, they can also cause dangerous flash floods and landslides, which can kill people, crops, and livestock. And India isn't the only place in the world that has to deal with monsoons. In fact, other parts of Asia, Africa, South America, and, believe it or not, even North America have monsoons. But India experiences the most intense monsoons, so you can say it's the poster child for monsoons. But what causes a monsoon? Well, it might not seem like the land and oceans would have much to do with the wind and the air, but they're all connected. Let's zoom in on India to investigate how monsoons form. We'll focus on the circulation of air between a landmass and the ocean. Let's take a look at the landscape, since that impacts whether or not a monsoon will form. We'll focus on two monsoonal circulations, summer and winter. Let's start with summer. You'll notice there's an ocean along with a large landmass, and you might also notice it's a sunny day. In fact, in this region, it is actually early summer, which you may have already gathered. It looks like that hot sun is warming up that landmass, which in turn is radiating out and heating up the air. As the air warms, the molecules that make up the air start to move faster and get further and further apart, so the warm air becomes less dense. Because the molecules are further apart, they exert less pressure on their surroundings, so they create an area of low pressure. Now, let's check out the ocean. During the early summer, the land heats quicker than the ocean, so the air above the ocean is cooler and denser than the air above the landmass. This creates an area of high pressure. This is because the air molecules are moving slower and are closer together, therefore exerting more pressure on their surroundings. So, what does all of this high and low pressure have to do with the monsoon? Well, you may have heard this somewhere already, but air will flow from areas of high pressure to areas of low pressure, and this flow of air is actually wind. If you check out our ocean and landmass, you can see that air is going to flow from the colder, denser ocean air to the warmer, low-pressure air on land. But that's only part of the monsoon story. The warm air above the land is going to rise because it is less dense, and when the cold, moist air from the ocean flows inland, the warm air carries the cold air up with it. As the cold air rises, it cools even more and reaches saturation, meaning it can't hold any more water vapor. When this happens, clouds form, and then rain. This is the start of the Indian wet season as well as the Kharif crop season, or the summer monsoon. And India receives about 75% of its total annual rainfall during this monsoonal season, so you can see why it's important to those water-loving crops. Now, let's look at another monsoonal circulation, or what happens in late fall or early winter. The ocean is going to warm faster than the landmass, so things are going to flip. The air over the ocean is warm, which creates a low-pressure system, while the air over the landmass is cold and dense, which creates a high-pressure system. Remember, wind blows from high pressure to low pressure, so the wind's going to be blowing from the land to the ocean. When the cold air from the land reaches the warm air from the ocean, it's forced upward with the warm air. As it rises, it cools and becomes saturated, so clouds and precipitation form. This keeps the land dry with precipitation falling over the ocean. And for India, this is the Rabi season, so Indian farmers make the best of the summer and winter monsoonal circulations. Monsoons, or seasonal winds that bring a change in weather, are a welcoming relief in many parts of the world, but they can also wreak havoc in the form of flooding and storms. Let's take a moment to review the summer and winter monsoonal circulations for India. In the early summer, the land heats up quicker than the ocean, which creates a low-pressure system on land and a high-pressure system in the ocean. Wind blows from high to low pressure, so wind blows inland. As this cooler air blows inland, it's forced upward by the warm rising air above the land. As it rises, the air cools, reaches saturation, forms clouds and precipitation. Now, in the late fall or early winter, this is reversed. The ocean is warmed more quickly than the landmass, so the high-pressure system is now above the land and the low-pressure system is above the ocean. And since wind blows from high to low pressure, wind blows out to the ocean. As the colder land air blows to the ocean, it's forced upward by the less dense, rising warm ocean air, and as it rises, it cools, reaches saturation, forms clouds, and precipitation. People around the world have come to depend on these seasonal winds for crops, as you witnessed with the Kharif and Rabi crops of India. So, the next time you drink some soy milk or have some rice with dinner, you can think of India and the monsoons. Tonight on Whirlwind Romance, we're going to interview two different types of winds in hopes of finding our eligible bachelorette, Marley the meteorologist, a match. Now a little on Marley before we start. Marley's trying to find a nice wind who can keep her warm at night. And, as a meteorologist, Marley studies the weather, so you can see why she is interested in dating wind. Before we bring out our two eligible wind bachelors, let's explain what wind is and how it forms. Wind is simply air in motion that is caused by differences in pressure. Uneven heating of the earth causes this difference in pressure. Air that is colder is denser, thus creating greater pressure. If you take a look at this parcel of cold air, you can see that when more molecules are close together, they're going to bump into their container more often, which results in higher pressure. And in this parcel of warm air, you can see that the molecules are further apart. Therefore, it is less dense, resulting in lower pressure. Air flows from areas of high pressure to areas of low pressure, and this airflow is wind. I could go on, but our guests are becoming impatient, and we don't want them to blow away and leave Marley all alone. So let's bring out our first guest, the Chinook wind. Welcome to the stage, Chinook wind. Now Marley can't see you, but she will be able to hear about you. So let's get started. I understand that Chinook actually means snow eater, so I'm guessing you're a warm wind that causes snow to melt? Yep, it sounds like it. So on your bio it says Chinook winds are warm and dry foehn winds that blow down the eastern slope of the Rockies. These warm winds can be a brief reprieve from the cold, harsh winters found in the Canadian Rockies. But what in the world is a foehn wind? Well, Chinook winds are a type of foehn wind, and foehn is German and translates into hair dryer. So, as you might expect, foehn winds are dry and warm winds that can be found on the leeward side of a mountain. Well, you might not have expected the leeward mountain bit, but like a hair dryer, foehn winds blow dry, warm air. And, by the way, the leeward side of a mountain is the side protected from the prevailing wind. So it's usually the eastern side of a mountain because wind typically blows from west to east. In order to give Marley some background information to ensure you're the right wind for her, let's learn a little bit more on how you form. I see here that foehn winds, like you, form when moist air hits a mountain. In your case, Chinook winds form when this moist air comes off of the Pacific Ocean and hits the Canadian Rocky Mountains. When this moist air hits the mountain, it's forced upward where it starts to cool. Now, as it cools, it reaches its saturation point, meaning the air mass can't hold any more water vapor, so the water vapor starts to condense, forming clouds and precipitation, thus releasing the excess water. The air mass dries out, passes over the mountain peak, and then slides down the leeward side of the mountain as dry, warm air. Certain areas might be a temperate rainforest on one side of the mountain, where the air is saturated and condenses causing precipitation, and dry on the other side of the mountain because the air has released much of its water content. So, I can see how you get the nickname Snow Eater because you melt the snow. You must also give relief to the people living on the eastern side of these cold mountains. Other than the Canadian Rockies, where can foehn winds be found? It looks like in the United States, the Rockies, in Europe the Alps, and even in China, in the Qingling and Tian Shan. Wow, quite the world traveler. Now for the part of the show I don't love. We went ahead and pulled up your police record to see if you've caused any problems. Chinook winds, like you, can cause red belts, or strips where the temperature fluctuation kills trees. Not to mention, the snow melt can cause problems for animals that depend on the extra insulation in the brutal winter months. And other types of foehn winds can cause droughts and make forest fires worse. You know, even with that record, I think you sound delightful for Marley. But it wouldn't be fair unless we gave our second guest some time on the stage. So goodbye for now, wind of many names, Chinook, foehn, and Snow Eater. Welcome to the stage, Santa Ana wind. And, like our first guest, the Santa Ana winds are dry and warm winds. But, unlike the Chinook winds, these winds blow westward toward the coast and are found in southwest California. Remember, the Chinook winds blew down from the leeward side of the Rocky Mountains, so they went from west to east. And on your bio it says you're seasonal, so you only occur during the spring, fall, and winter, often peaking in December. It also says you're a type of katabatic wind, which is a Greek word meaning going down. That must have something to do with how you blow. Okay, I see here that katabatic winds are winds that move down a slope due to gravity, and this typically occurs at night when the ground cools and causes the air to cool. But as it flows downhill, it warms due to the adiabatic process. The adiabatic process means as air contracts, it warms, and as it expands, it cools. In a nutshell, there's greater pressure as air descends, causing the air mass to contract. This causes air molecules to bump into each other more often, thus increasing the heat. So now that we have a brief understanding of katabatic winds, let's get back to our eligible bachelor, the hot and dry Santa Ana. In the Great Basin, or the area between the Sierra Nevada and Rocky Mountains, air becomes cool at night. Remember, the Santa Ana winds form when it's cooler out, so the spring, fall, and winter, but not the summer. This cold, dense, high-pressure air sinks and starts to flow down the mountainside. Remember, as it descends, it warms due to the adiabatic process. The Santa Ana winds can blow really fast because they get channeled through mountains and canyons. And the downside to this, Bachelor? Like the Chinook winds, we went ahead and pulled the police record for Santa Ana. The major complaint was that these warm, dry, fast winds exacerbate forest fires, which has definitely been a problem in California. And because these winds are so fast, they can be extremely destructive. So, does Marley go with the Chinook wind or the Santa Ana wind? She sure has a lot to think about, so let's help her out and recap some highlights from our bachelors, starting with the Chinook wind. Now, Chinook was a type of Feen wind and was dry and warm. He formed when moist air off of the Pacific Ocean hit the Canadian Rockies and was forced to ascend up the mountain slope. As he ascended, though, he reached his saturation point, and the water vapor had to condense, forming clouds and precipitation. After he released most of his water, he continued over the mountain, and then he slid down the leeward side, warming as he descended. He sounded dreamy, except he did cause some problems ranging from forest fires to killing trees. The second bachelor was equally dreamy. The Santa Ana wind was a type of katabatic wind and formed when air cooled in the Great Basin and then moved down the slope due to gravity. As it moved down the slope, it warmed and blew into southwestern California. Again, this wind could exacerbate forest fires in the region. So, who does Marley pick? It looks like she's leaving the studio with both winds. Wow, I didn't see that coming. Marley's about to get blown away. And until next time, good night from Whirlwind Romance. Think about all of the ways you use the word breeze. I'm going to breeze through my test tomorrow, or let's have coffee and shoot the breeze, and even baking that cake was a breeze. Yeah, breeze has a lot of meanings, but the most important meaning, at least for this lesson, is what it means with regard to air. A breeze, as you probably already know, is a light wind. But did you know there are actually different types of breezes? Let's explore each type and go on a breeze tour, so pack your bags and get ready. Don't worry, you won't be gone long, and the trip should be a breeze. One more thing before we depart, though. Breezes are named based on where they originate, and breezes blow from high to low pressures. We'll talk more about these two things as the lesson proceeds, but keep them in mind. Let's start our breeze tour along the Cuban coast, which, like a lot of coastal regions, gives us a fantastic example of a sea breeze, which is a breeze that comes from the ocean onto the land. You're most likely to witness a sea breeze during the spring or summer because, during this time, the land and the ocean have a bigger temperature difference than other parts of the year. And why does this temperature difference matter? I'm so glad you asked. In order to answer your question, I'll need to explain how a sea breeze forms. It's a hot, sunny day and the sun is warming up the land and the ocean. However, the land is heating up faster than the water, so there's a temperature difference. This difference results in a temperature difference for the air as well. The air above the ocean is cooler than the air above the land. Before we go on, there's something you should know about air temperature and pressure. In warmer air, the molecules are further apart, so the air is less dense. Because there are fewer molecules within a certain volume compared to the cold air, the warm air exerts less pressure. So, warm air creates an area of low pressure, whereas cold, dense air creates an area of high pressure. Air flows from areas of high pressure to low pressure, which results in a breeze. Remember from the start of the lesson, this high to low pressure thing will keep popping up, so it's worth taking a moment to memorize. Okay, so the breeze will blow from the cold, dense, high-pressure area above the ocean to the warm, low-pressure region on land, and there you have it, a sea breeze. The breeze will be stronger if the temperature difference between the air and water is greater. But wait, there's more. At night, the reverse happens, and this is referred to as a land breeze, or when there is a breeze from the land to the ocean. At night, the land cools faster than the ocean, so cold, dense air forms over the land, which causes high pressure. Meanwhile, the air above the ocean is warmer and less dense, so a low-pressure system develops. And if you remember from before, air moves from high to low pressure. So, the air will move from the land to the ocean. Now remember, I also told you at the start of the lesson that winds are named based on where they originate? So, a sea breeze comes from the sea, and a land breeze comes from the land. Remembering this will make learning about breezes, well, a breeze. So, our tour of Cuba and the sea and land breezes is coming to an end, but realize you can see sea and land breezes along most coastlines or even land masses that are near a large body of water. So, before we go to our next breeze, why don't you make a few stops to see if you can find any more sea and land breezes. Check out Florida, then move up the East Coast, and maybe breeze up the West Coast. That looked fun, but it's time to check out our next breeze, the valley breeze, or a breeze that flows from the valley up the mountains. And where will we go to witness this breeze? Let's try to find some mountains and valleys. You know, it might be fun to go to Costa Rica. It's a sunny, hot day, and the sun is heating the mountains quicker than the valley floor. Ah, yes, again, unequal heating. Sounds similar to our sea and land breezes, doesn't it? The air on the mountains becomes warmer and less dense, thus creating areas of low pressure. Meanwhile, the air above the valley floor is cold and dense, so it creates an area of high pressure. Remember our rule. Yep, the breeze will flow from high to low, so the breeze will go up the mountain from the valley, and we have a valley breeze. But it's starting to get dark and the sun is setting. Now, the mountains cool faster than the valley, so the air above the mountains becomes cold and dense, forming an area of high pressure. And you guessed it, the air above the valley is warm and less dense, so it creates an area of low pressure. And we know the air will flow from the high pressure to the low pressure, or from the mountains down into the valley. This is called a mountain breeze, or a breeze from the mountains into the valley. Before we head home, we can experience mountain and valley breezes elsewhere. Just look for a valley with mountains. But we probably should stop shooting the breeze and head home. Now that you're done from your trip, let's review what we know about breezes. Remember, a breeze is a light wind, and you may be getting a little confused with sea, land, mountain, and valley breezes and how they form. So let's review a couple of tips. Breezes are named from where they originate, so a sea breeze blows from the sea to the land. A land breeze blows from the land to the sea. A mountain breeze blows from the mountains to the valley. And a valley breeze blows from the valley to the mountains. And breezes blow from areas of high pressure to areas of low pressure. All of the breezes we talked about occur when there is an unequal heating, whether that be between mountains and valleys or the ocean and the land. The colder, denser air creates areas of high pressure, and the warmer air creates low pressure areas. Well, that was a good time. You can go ahead and unpack your bags because I bet you can witness a breeze outside your own home. So maybe we didn't need to travel the world to find a breeze, but it sure made it fun. Hey there! My name is Sally Salmon, and I'm here to tell you all about some strange stuff that happens in the ocean and how it affects me and my salmon buddies. I'll tell you all about El Niño, La Niña, and the Walker circulation. Let me start with what happens when everything is normal. When there isn't an El Niño or La Niña event and everything is normal, you have a Walker circulation, or the cyclic movement of air above the equatorial regions in the Pacific Ocean. And if you can grasp the Walker circulation, you'll have a better idea of how El Niño and La Niña work. Normally, the waters in the equatorial region of the western Pacific Ocean are nice and warm. This warm surface ocean water warms the air above it, which causes an area of low pressure. This is because the molecules in warm air are further apart and they exert less pressure compared to colder, dense air. In addition to warming, the warm Pacific water adds moisture to the air. This warm, moist air rises, reaches its saturation point, meaning it can't hold any more water vapor, and clouds and precipitation form. After the air releases its water, it becomes dry and heads eastward, where it eventually cools and sinks above the cooler waters of the eastern Pacific. This cool, dense air forms areas of high pressure because, in cold air, the particles are closer together and exert more pressure. Wind blows from high pressure to low pressure, so this air in the eastern Pacific blows back to the low pressure areas in the western Pacific. These winds are known as the trade winds. Once the air gets back to the West Pacific, it rewarms, rises, and repeats. This cycling of air is the Walker circulation. So, what does any of this have to do with Sally the salmon? Right now, I'm living in the North Pacific Ocean, and I migrate throughout my life, so I get to check out a lot of the North Pacific Ocean. Something that me and my salmon buddies really don't like is called El Niño, which is a weather phenomenon where warmer than average temperatures are found near the equator in the Pacific Ocean. Even though I don't live near the equator, El Niño impacts weather all around the world. The white on this image represents warm water, so you can see that El Niño really does change the temperature of water in the Pacific. Let's take a moment to explore how El Niño works. A really quick note first, though. You may be wondering how it got the name El Niño, which means boy in Spanish. I mean, is there a boy swimming around in the ocean, magically warming it as he goes? A while back, there were some fishermen near South America who noticed the water temperature was warmer than normal, and this coincided with Christmas. So they named it El Niño, which translates into boy in Spanish. They chose to name it El Niño after baby Jesus, since it was observed near Christmas. So, remember, there isn't a little boy swimming in the ocean, but it's still called El Niño. Okay, back to how it forms. Remember, normally the trade winds blow from the east to the west due to high and low pressure differences, and this is called the Walker circulation. But during an El Niño year, the trade winds subside or even change direction. This diminishing of the trade winds causes the warm water in the Pacific Ocean to stay put and stay warm along the South American coastline. So you're probably thinking, big deal! How can a little warm water near South America impact the world and Sally salmon? Well, let me start with how it impacts temperatures in North America. El Niño can cause cold winters in Canada, less snow and mild winters in the Midwest United States, and wetter conditions in the Southwest and Southeast United States. Worldwide, El Niño is blamed for tons of problems, like flooding in Peru and droughts in other parts of the world, including Australia and Indonesia. And when there's an El Niño year, a lot of marine critters move into areas they don't usually inhabit. For example, some species move further north, like the rockfish, whereas other species can die. In fact, scientists found that salmon around Washington and Oregon had high mortality rates and reduced growth rates following an El Niño event. And another study found that the ocean temperature in the Bering Sea rose 10 degrees Celsius following an El Niño year and resulted in the deaths of millions of sockeye salmon. I know! Sad for salmon like me. Wow, talking about all that salmon death is bringing me down. Let's move on. Next there's La Niña, which translates into girl in Spanish and is otherwise known as the anti-El Niño. So, if it's the anti-El Niño, I bet I don't even need to give you a definition, but I will. La Niña is a weather phenomenon where colder than average temperatures are found near the equator in the Pacific Ocean. And this is good for salmon, like me. Let me quickly describe how La Niña forms and its effects on the world's climate. When there is a La Niña event, the trade winds near the equator are really strong, which causes warm water to blow westward. This leads to upwelling, which means that deep cold water rushes to the surface to replace the warm water. This cold water can be found along the South American coastline. The colder than normal ocean temperature causes changes all over the world. For example, in the United States, La Niña winters are characterized by dry and warm conditions in the south, wet conditions in the Pacific Northwest, and colder than normal conditions in the Northeast. Worldwide, La Niña is blamed for wet conditions around northern Australia, sometimes causing dangerous floods in the region. In addition to Australia, La Niña causes increased precipitation in northern Brazil and Southeast Africa. It also causes more intense monsoons in India and dry conditions along the west coast of South America. But not only is La Niña better for me, it's also better for fish living along the coast of South America. The upwelling of cold water also brings yummy food to the surface for all of those fish to eat. But back to me. My salmon friends and I really like cold water, so scientists find that there are greater salmon returns after a La Niña event. I realize that was a lot of information. It's worth noting weather changes like cold winters or increased precipitation in certain areas, but all of that information can become overwhelming, so let me review some take-home messages. The Walker circulation is the cyclic movement of air around the equator, where warm air in the western Pacific rises, becomes saturated, and releases its water as rain. Now that the air is dry, it heads eastward where it cools, sinks, and then blows westward as trade winds. This cycle repeats itself. The Walker circulation occurs when there isn't an El Niño or La Niña. El Niño is when warmer than normal temperatures are found in the equatorial regions of the Pacific Ocean. This is because the trade winds diminish or even change direction, which causes the Pacific Ocean surface waters to stay put. This is rough for a lot of marine critters like me. La Niña is when colder than normal temperatures are found in the equatorial regions of the Pacific Ocean and is due to stronger than normal trade winds that blow warm surface waters of the Pacific Ocean away, which results in upwelling. This upwelling cools the surface temperature and is great for fish species because it brings nutrients to the surface. I realize I'm a long way from these equatorial regions, but El Niño and La Niña can be felt around the world, not just near the equator.
The ocean's children. You've probably heard of El Niño and La Niña before. They mean little boy and little girl in Spanish, and collectively they make up the ENSO cycle, which stands for El Niño Southern Oscillation Cycle. This cycle describes abnormally warm and cool ocean temperatures in the eastern tropical Pacific. The cycle is natural, and El Niño is the warm phase of the cycle, while La Niña is the cold phase of the cycle. We get El Niño and La Niña episodes every 3 to 5 years, and El Niño happens more often than La Niña. They may last as little as 9 months, about as long as it takes an actual little boy or girl to develop before being born, or as long as a couple years. They usually form in the summer between June and August, get strongest around December, and then wither away between May and July of the next year. If you've ever been to the Pacific Ocean along the west coast of the U.S., you know that this water is very cold. This is because the winds along the equator in the Pacific blow from east to west, pushing the warm surface waters along with it. This leaves behind cooler water in the eastern part of the Pacific Ocean. During an El Niño event, the winds blowing east to west are not as strong as normal, so a lot of that warmer water gets left in the eastern part of the ocean. What's really interesting is that as the water gets warmer, it weakens the winds even more, which then leaves more warm water in the eastern part of the Pacific, which then weakens the winds even more, and we get a self-perpetuating cycle. So what stops this cycle? Well, as El Niño grows large enough to reach the middle of the ocean, it creates Rossby waves. These are similar to tidal waves where large amounts of water move in the same direction toward land. In a Rossby wave, the top part of this massive ocean wave moves really slowly in one direction, and the bottom part of the wave moves in the other direction. How slowly does this wave move? About 100 times slower than a walking pace. It takes months for Rossby waves to reach shore, and when they do, they get bounced back towards the ocean again. This slow-moving return wave from shore is called a Kelvin wave, and it brings enough cool water with it to cancel out the warming from the El Niño event. If enough cool water tags along with the Kelvin wave, we may get a La Niña event. For this reason, La Niña often follows an El Niño, but this isn't always true. Though we tend to think of El Niño and La Niña as brother and sister, La Niña can occur independently. If those winds from before grow stronger instead of weaker, we get the opposite result. Colder waters are more prevalent in the eastern Pacific Ocean, and we get La Niña instead of El Niño. Though they occur in the ocean, the effects of El Niño and La Niña are not confined to this space. And just as this brother and sister duo have opposite effects on water temperature, they also have opposite effects on weather patterns on land. Because both events tend to build to their peaks during the winter months, this is usually when we see the greatest effects. In the U.S., La Niña winters create drier conditions in the southwest, wetter conditions in the northwest, and very cold conditions in the northeast. El Niño produces the opposite effect: wetter conditions in the southwest, drier conditions in the northwest, and stormy, snowy weather in the northeast. Other parts of the world, especially in the tropics of the Pacific, are also greatly affected by ensocycles. During La Niña, Australia and Indonesia are more likely to experience drought, but will have heavier than normal rainfall during El Niño. Just like children, both El Niño and La Niña are complex, and their processes are not fully understood. However, scientists do have some tools available to help predict these impactful events. While prediction is not easy, it is important because El Niño and La Niña affect people all over the world when they occur. Predicting the effects of ensocycles such as cold spells, drought, heavy rains, severe snowstorms, and other weather changes can help people plan and prepare. This may not only save lives, but also prevent the loss of municipal funds, crops, and livelihoods. Little boy and little girl. El Niño and La Niña are the ocean's children. They're part of the overall ensocycle, the El Niño Southern Oscillation Cycle. The El Niño part of the cycle is the unusual warming of the eastern Pacific Ocean, and La Niña is the opposite, the unusual cooling of this part of the Pacific. Both are naturally occurring events that happen about every 3 to 5 years. They normally last about as long as it takes a real little boy or girl to grow in the womb, so about 9 months, but they can last as long as a few years. And just like children, the majority of their time present is about that of a typical school year, beginning around August, peaking in December, and ending around May. El Niño develops when the winds that normally blow warm Pacific surface waters from east to west weaken. This allows the warm waters to stay in the eastern part of the ocean, which then weakens the winds even more, and the cycle continues like this until stopped by an outside force, such as a Kelvin wave. Kelvin waves result from Rossby waves, which are giant, slow-moving waves heading toward land. The return wave bounced back from shore is the Kelvin wave, which carries cooler water and cancels out the warm water from the El Niño. Just like a sister, La Niña acts opposite to her brother. La Niña is when the winds blowing across the tropical Pacific strengthen, which creates cooler than normal surface waters in the eastern Pacific. She may follow after her brother if the Kelvin waves bring too much cold water back with them, or she may occur independently. Both parts of the ensocycle have effects on land as well as water. In the U.S., La Niña winter conditions will be drier in the southwest, wetter in the northwest, and colder in the northeast. The opposite is true for El Niño. Winter conditions will be wetter in the southwest, drier in the northwest, and stormy and snowy in the northeast. La Niña creates conditions similar to the southwest along the tropical Pacific, and places like Australia and Indonesia tend to experience extreme drought. El Niño rains down heavy on these areas, creating wetter than normal conditions as it cycles through.
Imagine a giant blob that lurks in the Pacific Ocean, killing seabirds, damaging the food chain, and causing some species to relocate. So, what is this blob? An oil slick? Toxic waste? Garbage? Nope. Scientists, who actually call it the blob, describe it as a giant chunk of warm ocean water that was first noticed in 2013. Estimates of its size vary, but some say it was 1,000 miles wide by 1,000 miles long by 100 yards deep in 2014, but it continues to grow. Scientists aren't sure what is causing the blob, but some are blaming the Pacific Decadal Oscillation, or the PDO. The Pacific Decadal Oscillation, remember, PDO, is the cycling change in the surface temperature of the North Pacific Ocean and can be divided into the warm phase and the cold phase. Scientists started gathering data for this oscillation in 1900 and have records through today. Scientists are unsure what causes the PDO, but they do know each phase of the cycle can last for years, sometimes lasting 20 to 30 years, And the change of ocean temperature also affects winds, temperatures, and precipitation levels on land. Let's take a moment to briefly look at each phase in the PDO, starting with the warm phase, which causes a rise in the average temperature of surface waters along the Pacific coast all the way from Alaska to the equator. But the warming is only half of the story. While the coastline warms, the waters further away from the coast actually cool. The warm coastal waters form a sideways U around the cooler waters. In addition to warming the surface ocean temperatures, the warm phase of the PDO also influences temperatures and precipitation levels on land. For example, during the winter months, the warm PDO causes colder temperatures in the southeast United States, warmer temperatures in the northwest parts of North America, and warmer temperatures in the northeast. Finally, there is less winter precipitation in the northwestern parts of North America. The cold PDO, on the other hand, causes the waters off of the Pacific coastline to cool, and these cold waters form a sideways U around warmer waters further away from the shore. And like the warm PDO, the cold PDO influences weather on land, causing colder winters in the northwestern parts of North America and warmer winters in the southeastern United States, as well as increased winter precipitation in the northwestern parts of North America. You may have heard of other weather phenomenon that warm and cool surface ocean waters, such as El Niño and La Niña. So, you may be wondering what the difference is between the PDO and these phenomenon. So far, we know that the PDO is a cyclic change in water temperature in the North Pacific Ocean, and it can affect winter temperatures and precipitation levels. El Niño is the warming of surface ocean waters near the equator in the Pacific Ocean. From this NASA image, you can see the warm areas as white during this El Niño year. This increased ocean surface temperature in turn causes weather changes on land. Yep, so far it does sound fairly similar to the warm phase of the PDO, doesn't it? For El Niño, the weather changes include warmer temperatures in parts of the continent like Western Canada and the U.S., drier conditions in the Pacific Northwest, and increased precipitation along the Gulf Coast in the U.S., just to name a few. And it's worth noting there is a La Niña, which is the opposite of El Niño, bringing colder ocean surface temperatures in the Pacific Ocean near the equator, which in turn brings a change in temperature to North America, specifically colder winters in the northwest and warmer temperatures in the southeast. La Niña shares some similarities with the cold phase of the PDO. Now, let's look at how the PDO differs from El Niño and La Niña. For starters, the PDO can last decades, whereas El Niño and La Niña are much shorter, lasting around a year. Both El Niño and La Niña can affect the North Pacific, but the main areas they affect are the lower latitudes, while the PDO primarily affects the North Pacific. Finally, the PDO is divided into two phases, where the cold phase is similar to La Niña and the warm phase is similar to El Niño. But El Niño and La Niña don't have phases. I realize this is probably a lot of stuff to take in. Take a moment to pause the video and review the table so you can take in all of that information. An interesting tidbit though, when the PDO is in the warm phase, scientists believe it intensifies El Niño, and when it's in the cold phase, it intensifies La Niña. So, back to that blob from the beginning of the lesson. Scientists aren't sure if the PDO is to blame, but they're seeing strange things as a result of this increased water temperature, such as species that are not usually found in Alaskan waters showing up, like tuna, sunfish, and pygmy killer whales. And some species, like the copepod, which are small critters at the base of the food chain, are moving further north, which is causing problems for marine animals that feed on them. Although this ocean warming might not end up being part of the PDO, scientists did conduct a study on the PDO and how it affected salmon species. They found that the salmon did better during the cold phase, whereas they declined during the warm phase. So it isn't a stretch to think the PDO may be having some effect on marine life. But back to the blob. In addition, this mysterious ocean warming has caused some strange weather in the Pacific Northwest, like increased thunderstorms and forest fires. And in California, there's been an increase in droughts. So, the jury's still out on whether or not the PDO is causing the ocean warming at this time, but understanding the PDO, El Niño, and La Niña will help scientists better understand the blob and what its long-term effects may be on the Pacific Ocean. The Pacific Decadal Oscillation, is the cyclic fluctuation of surface ocean temperatures in the North Pacific and can last for decades. In addition to impacting some marine animals like salmon, this fluctuation can cause precipitation and temperature to deviate from the average on land. There are hot and cold phases of the PDO. El Niño is similar to the warm phase of the PDO, but it is warming of surface waters near the equator of the Pacific Ocean, and it can also affect the North Pacific. La Niña is similar to the cold phase of the PDO and is a cooling of surface ocean temperatures near the equator of the Pacific Ocean. While El Niño and La Niña are short-lived, the PDO is not. And while El Niño and La Niña mainly impact equatorial waters, the PDO's impact is mostly in the North Pacific. When you say Arctic, a lot of things come to mind, like cold weather and maybe even the North Pole with flying reindeer, elves, and Santa Claus. But Arctic Oscillation probably isn't one of the images that pop into your brain. So, what is this Arctic Oscillation? Picture a teeter-totter. First one side is up and the other is down. Then one side is down and the other is up. The Arctic Oscillation is a lot like a teeter-totter, but instead of people bouncing up and down, you have changes in pressure and weather. The Arctic Oscillation, or AO, can be described as changes in pressure between the Arctic and mid-latitudes. These pressure changes result in wind and weather changes. There are two different phases in the Arctic Oscillation, the positive phase and the negative phase. You can think of the positive phase on one end of the teeter-totter and the negative phase on the other end. These phases oscillate, or teeter, back and forth all of the time. A couple of things before we delve into these phases. Wind blows from high to low pressure, and the greater the difference between the pressures, the faster and stronger the wind. If you can remember winds blow from high to low, you will have an easier time navigating the oscillations in this lesson. Finally, winds are named based on where they originate. So, if you have westerlies, you can assume the winds blew from the west. Okay, let's get started. The Arctic Oscillation is based on two pressure systems, one over the Arctic and one over the mid-latitude region. Now, a little on the Arctic pressure system before we go on. There is a continual pressure system in the Arctic known as the polar vortex. In the positive phase, the polar vortex is strong, meaning there's a strong low-pressure system in the Arctic. Meanwhile, the pressure system at the mid-latitudes is high. Remember, winds blow from high to low, so this causes winds to blow from the mid-latitudes to the Arctic. This causes fast-moving westerly winds and northeasterly trade winds, which traps the cold air in the Arctic. Before we check out how the positive phase of the Arctic Oscillation impacts Santa and his crew, let's check out the negative phase. During the negative phase, the polar vortex is weak, which means the pressure system is higher than normal in the Arctic, and the high pressure system in the mid-latitudes is lower than normal. Because the difference between the high and low pressure systems isn't as great as it is in the positive phase, the winds are not as strong or fast. Also, because the high pressure system is now in the Arctic and the low pressure system is in the mid-latitudes, the wind will flow from the Arctic to the mid-latitudes. Because both of these factors, the winds lollygag along, which causes ridges and troughs. This allows the cold Arctic air to flow southward. Now that you have a little background, let's see how these phases impact the weather. It's worth noting that this list of weather patterns doesn't address every weather pattern impacted by the Arctic Oscillation, but it does allow you to get the general patterns. Let's start in Canada and Greenland and work our way across the globe. Check out the table to help you keep all of the weather patterns straight. During the positive phase, Canada and Greenland experience colder than normal temperatures because the cold Arctic air gets trapped. During the negative phase, however, the cold air travels further south, so western Greenland and eastern Canada experience mild temperatures. Next, let's head over to Asia and northern Europe. During the positive phase, these regions experience warmer temperatures and increased precipitation. However, during the negative phase, they experience colder than average temperatures. Next, the Mediterranean experiences droughts in the positive phase and increased storms in the negative phase. Finally, let's head to the United States. In the eastern United States, there are warmer temperatures during the positive phase and colder temperatures with storms on the northeastern coast. And on the west coast, a positive phase causes warm and dry conditions, and the negative causes cold conditions. And we can't forget about Santa. Because he's in the Arctic, he will experience colder than normal conditions during the positive phase and warmer than normal conditions during the negative phase. Believe it or not, the Arctic Oscillation isn't the only weather pattern that acts like a teeter-totter. The North Atlantic Oscillation, or NAO, is another weather pattern, but it's the fluctuation in pressure over the North Atlantic Ocean. It affects weather patterns around the world. Like the Arctic Oscillation, the North Atlantic Oscillation has a positive and a negative phase. The North Atlantic Oscillation has two pressure systems, one over the Azores, which is a high pressure system, and one close to Iceland, which is a low pressure system. During the positive phase, the Icelandic low pressure system, also termed the Icelandic low, gets really strong, and the Azore high pressure system, also termed the Azores high, gets really strong. This causes a huge difference between the high and low pressure systems, which causes the westerlies to get really strong. The strong westerlies prevent cold air from blowing south. Instead, the cold air heads towards North America. Sounds familiar, doesn't it? Even though it's a different part of the world, the North Atlantic Oscillation works in much of the same way as the Arctic Oscillation. A negative North Atlantic Oscillation occurs when the Icelandic low is higher than normal and the Azores high is lower than normal. Both of these pressure systems are much weaker than they were during the positive phase. This causes less of a difference between high and low pressure, so the winds are weak. The weak winds allow cold air to escape southward. Let's see how the North Atlantic Oscillation impacts the weather. Again, this table doesn't address every single weather pattern associated with the Arctic Oscillation, but it will give you the general idea. In the eastern United States, a positive North Atlantic Oscillation results in warmer temperatures and less storms, whereas a negative phase results in colder than normal temperatures and increased storms. Remember, it's like a teeter-totter, so you can expect the phases to create opposite weather effects. When it's hot during one phase, it'll be cold during the other phase. In northern Europe, the positive phase brings warm temperatures, increased storms, and increased precipitation. And if the negative phase is opposite, you can probably guess how it impacts northern Europe, right? Yep, colder than normal temperatures with less storms and precipitation. Finally, southern Europe experiences decreased precipitation and fewer storms during the positive phase, and warmer temperatures with increased storms and precipitation during the negative phase. From a chilly Santa Claus at the North Pole to a pressure system over the Azores, the teeter-tottering oscillations create changing weather patterns all over the Earth. Let's take a moment to review these oscillations. The Arctic Oscillation occurs due to changes in pressure in the Arctic and mid-latitudes, and can be divided into the positive and negative phase. The positive phase occurs when the polar vortex has a strong low-pressure system and the mid-latitudes have a strong high-pressure system. This causes strong winds that trap cold air in the northern latitudes. The negative phase is the opposite of the positive phase, and the polar vortex has a higher than normal system and the mid-latitudes have a lower than normal pressure system. This allows cold air to blow southward. Remember, these phases cause a variety of weather patterns, so take a moment to review the table. It gets a little confusing, but a general rule is that a positive phase causes cold weather in the north and warmer weather further south. A negative phase causes warmer weather in the north and colder weather in the south. So I guess it's safe to assume Santa prefers the negative phase. Next, we looked at the North Atlantic Oscillation, which is caused by changes in pressure above the North Atlantic Ocean. In this case, the pressure systems are located near Iceland and above the Azores. During the positive phase, both the Icelandic low and Azores high are strong. This causes strong winds that prevent cold air from traveling southward. The reverse happens during a negative phase, so the Icelandic low is higher than normal and the Azores high is lower than normal. This causes cold air to escape southward. Like the Arctic Oscillation, the North Atlantic Oscillation impacts weather. So take a moment to review the table. Again, it gets a little confusing, but remember, when it's a positive phase, cold air gets trapped further north, but when it's negative, the cold air escapes southward, just like it did in the Arctic Oscillation. Depending on where you live, you might be wishing for different phases of both of these oscillations.
Weather is controlled by a variety of factors. One of the most important is Earth's air masses. Air masses are huge parcels of air with specific characteristics. What's interesting about the characteristics of an air mass is that not only do they describe the air mass, but they also tell you where you can find that air mass on Earth. Let's look at the different types of air masses found on Earth to see how this works. Air masses can be divided into two main categories based on whether they are found over land or water. If the air mass is found over land, this is a continental air mass. If the air mass is found over water, this is a maritime air mass. This makes sense. Continental air masses occur over the continents. Maritime air masses occur over the water or marine environments. These categories are represented by a lowercase c for continental or m for maritime. The source region of the air mass helps us classify it even further, and for this we have three categories. Arctic air masses occur over Arctic regions like Greenland and Antarctica. Polar air masses occur a little bit farther from the poles like in Siberia, Canada, and the northern Atlantic and Pacific Oceans. Finally, tropical air masses occur in the tropics, so along the equator and over Mexico and the southwest U.S. Makes sense, right? These categories are represented by the first letter of the source region, but this time we use an uppercase letter. So A stands for Arctic, P for polar, and T for tropical. That's pretty easy to remember. Each source region can also be either continental or maritime, and to represent this, we simply combine the category letters. This gives us 6 total types of air masses on Earth: maritime Arctic, MA, maritime polar, MP, maritime tropical, MT, and continental Arctic, CA, continental polar, CP, and continental tropical, CT. You can understand a lot about weather from air masses just by looking at the name. Maritime air masses are going to produce moist weather because they occur over oceans, and oceans are filled with water. The air blowing over the ocean regions, either Arctic, polar, or tropical, picks up that moisture as it travels along. In maritime Arctic and polar regions, this moist air is cool, as you probably expected, and the maritime tropical air mass produces the warm, humid conditions you would expect along the tropics, like Florida and the Caribbean. In contrast, continental air masses produce dry weather. This is because the continents just can't compete with the oceans when it comes to moisture. The continental Arctic and polar air masses produce dry, cold weather in the winter and pleasant weather conditions in the summer. If you've ever been to the Northeast U.S., you know what this weather is like. If you can make it through the bitter dry winter, you get heavily rewarded with a wonderfully cool and beautiful summer. Continental tropical air masses produce hot, dry conditions like you see in the southwest U.S. and Mexico. Just because air masses are found over a region of Earth doesn't mean that they stay put. In fact, they can move both horizontally and vertically. When air masses move, we can have some drastic changes in weather. One way that air can move vertically is through convectional lifting. Convection is the cyclical process of warm air rising and cool air sinking. This happens because just like your black t-shirt absorbs sunlight better than your white t-shirt, some spots on Earth absorb solar radiation better than others. When air comes in contact with these unusually warm spots, it heats up and rises. As it rises, it expands and cools, and then sinks back down to the ground. Thus we have the convection cycle. If there is moisture in the air, it creates a cumulus cloud when it rises. These are the big, fluffy clouds you can identify different shapes and objects in. As the air sinks, the cloud dissipates, which is what creates all that empty sky between cumulus clouds. Think about it. You usually see a bunch of cumulus clouds in the same area, but not one large, continuous one. The cloud is where the air is rising and releasing moisture. The space in between is where it's sinking back down to the ground. Each cloud is a convection cycle. If a cumulus cloud grows tall enough, it can turn into a thunderstorm cloud. So you can see that convectional lifting has the power to change the weather just by air rising or falling in the same place. Another way that air masses affect weather is when the air is lifted up over an obstacle, like a mountain. This type of lifting is called orographic lifting. Orographic lifting is responsible for the different weather conditions you see on opposite sides of a mountain. As the air rises up over the mountain, it cools and expands, and any moisture in the air is pushed out. You now know that this forms a cloud, and if there's enough moisture, the cloud may produce rain. The rain occurs on the windward side of a mountain because this is the side the wind is traveling up. The leeward side of the mountain is the opposite. The air falling back down is dry because it left all its water in the cloud on the other side. Finally, when air masses meet, they create fronts. Fronts are the contact zone between two different air masses. They may differ in pressure, temperature, density, and moisture, but usually it's a combination of all these factors. Air masses are like people with differing opinions. One may eventually win over the other, but the disagreement itself creates storms and changes along the zone of contact as the air masses fight it out. Air masses are large parcels of air with distinct characteristics, and they occur all over Earth. They're classified based on where they're found. Continental air masses are found over land, like the continents, and maritime air masses are found over water, like marine environments. We can also classify air masses based on their source region, Arctic, polar, or tropical. When these two classifications are put together, we get very specific descriptions of the type of air and weather that are produced. Continental air masses produce dry conditions, while maritime air masses produce wet conditions because they can draw water from the oceans they blow over. Similarly, you would probably expect Arctic and polar air masses to be cold and tropical air masses to be hot. Put together, you can have dry, cool air, continental Arctic or continental polar, moist, cool air, maritime Arctic or maritime polar, dry, warm air, continental tropical, or moist, warm air, maritime tropical. Air masses are not stationary, and their movement affects weather. When air masses experience convectional lifting, or the rising of warm air and sinking of cool air, we get cumulus clouds. If they grow large enough, cumulus clouds can turn into thunderstorm clouds and produce some pretty intense storms. Orographic lifting is when an air mass is lifted over an obstacle, usually something like a mountain. The warm air is lifted, and as it rises, it cools and expands. The water in the air creates a cloud and rain over the windward side of the mountain, where the wind initially blows up, and dry conditions on the leeward side. Fronts occur where two different air masses meet. The type of front depends on which air mass is advancing onto the other. Along the zone of contact, we get changes in weather, such as storms, rain, and clouds. Fronts are very much like a disagreement between two people with opposing viewpoints. One may eventually win over the other, but the argument itself can create some serious friction between the two.
We have all seen a weather map before at some point, most likely on the morning news. The meteorologists talk of high and low pressure systems moving across the country, sometimes bringing severe weather with them. These areas indicate changes in atmospheric pressure, the force exerted on the ground by the weight of the air above it. If you are standing at sea level, you are feeling the greatest amount of possible atmospheric pressure, since there is the most possible air sitting on top of you. Someone standing on the top of a very tall mountain would be experiencing lower air pressure, less air on top. But air pressure is not necessarily so simple. It routinely fluctuates throughout the atmosphere and across the surface. Pressure is affected both by factors that frequently change, temperature for example, and factors that do not change, The presence of land and ocean. As you know, we live on a spherical planet. Earth's shape has a major effect on how it is heated, which in turn has a major effect on how air moves across it. Because the equator absorbs more solar radiation than the poles, the atmosphere is warmer there. If you've ever worked with a convection oven, then you know that convection occurs when warm air rises and cool air sinks. The same thing happens in Earth's atmosphere. That warm equatorial air rises. Due to the Coriolis effect, air is pulled with Earth's rotation and deflects away from the equator, moving towards the poles and creating cells of updrafts and downdrafts, where warm air rises and cool air sinks. When warm air rises, it creates a low pressure system, where air has risen upwards, leaving less air pressure at the surface. Likewise, when cool air sinks, it creates a high pressure system, where cool air has dropped down to the surface, bringing increased pressure. Because air tends to have water vapor in it, especially warm equatorial air, low pressure systems tend to include lots of precipitation and stormy weather, when that warm vapor cools and condenses. High pressure systems, likewise, are usually associated with fair weather, as that cool air from way up in the atmosphere tends to be drier. So next time you watch weather on the news, see if you recognize this connection between pressure systems and what kind of day can be expected. Now that you've seen how temperature can affect pressure in the atmosphere, we can also take into account the role of land in affecting the movement of air. If you ever spent a nice, relaxing summer by a swimming pool under a hot sun, you've likely noticed how the concrete around the pool can become scorching hot and even burn the bottoms of your feet. And yet, even though it is being heated by the same sun, the water in the pool never gets quite that hot. This is because different materials have different specific heat capacities, the amount of heat necessary to change the temperature of the material by 1 degree. Water has a very high specific heat capacity, almost 5 times that of concrete. That means that water can absorb a lot of heat before it actually changes temperature, whereas concrete requires much less heat in order to heat up. The same applies for soil, grass, rock, and basically all other materials that make up land. So air sitting on top of land will also heat up a lot quicker than air sitting on top of water. That warm air will rise, creating lower pressure areas over land than the areas over water. The placement of continents and oceans, therefore, have a big impact on the movement of air in the atmosphere by affecting the pressure distribution within the atmosphere. Glider pilots have to understand this concept very well if they are to fly safely. They know that flying over bodies of water likely means a downdraft followed by an updraft once they fly over land again. They essentially surf the waves in the air that we can't see. It's all about how air rises and sinks based on its temperature. Changes in atmospheric pressure are greatly influenced by the distribution of land and oceans across the planet. While the Coriolis effect combined with convection cycles moves atmospheric heat from the equator to the poles, high pressure systems and low pressure systems can be generated due to differences in specific heat capacity between land and water. Air warms quickly over land and rises, creating low pressure areas, while air over water will tend to stay cooler and not rise, creating an area of relatively higher pressure. These differences, though not visible to the human eye, drive weather patterns that affect our everyday lives.
The Earth's surface is covered with fluids, namely air and water. These fluids are separated by density, with the dense cold waters making up the bottom, and the thinnest, lightest air masses making up the top of the atmosphere, where air meets space. The movement of air and water across the planet is known as circulation, and has many different variables driving it. Because Earth is a spinning ball, the gases that make up the atmosphere and the water that makes up the oceans are forced into motion. As Earth rotates to the east, the air sitting on top of it is pulled along, but more slowly than the planet itself. This means that air seems to be moving westward along the equator and then changes direction in different latitudes to the north and the south. This deflection of air due to Earth's rotation is called the Coriolis effect. The Coriolis effect also applies to ocean surface currents, which deflect in the same manner along the equator, creating surface currents moving westward. Air and water do not just move laterally. Because of differences in temperature among the fluids, air and water masses also rise and sink vertically. If you have ever used a convection oven, you have witnessed the process of hot air rising and cool air sinking. This happens in Earth's atmosphere and in the oceans. Warm fluids rise, cool fluids sink. Vertical air movement combined with lateral movement makes up cells of circulating air, known for bringing consistent wind patterns in various parts of the world. This rising and sinking is not just about the temperature. The composition of the fluids also affects their densities. Seawater salinity is a measure of the amount of dissolved particles, or the saltiness of the water. The higher the salinity, the denser the water becomes. So the densest water on Earth is very cold and very salty. Water moves vertically in a process called thermohaline circulation, a system of currents driven by changes in temperature, thermo, and salinity, haline. When surface water is at the equator, some of it evaporates, leaving saltier water behind, which changes the water's density. When warm currents move towards the poles, they cool off, also changing the density, in this case causing those currents to sink. This also involves the release of latent heat, the heat given off as a water mass cools, which has a big impact on the climate of whatever landmass or region the body of water is near. For example, Great Britain has a relatively temperate climate given how far north it is. This is thanks to the warm Gulf Stream current, which runs along the east coast of the United States, arriving in the North Atlantic where it cools and sinks, giving off the latent heat that keeps northwestern Europe from being much, much colder. The changes in thermohaline circulation throughout Earth's history have marked extreme climate changes, often happening very quickly. If Earth's surface was covered exclusively with water, no land masses, the surface currents would flow in very consistent directions with nothing to get in their way. But Earth has many land masses, continents. This means that surface currents are also deflected when they run into land. Atmospheric circulation is also influenced by land masses. As we've already seen, warm air rises and cool air sinks, just like that convection oven. Because they differ in conductivity, land tends to reflect heat, whereas water tends to absorb heat. Similar to how seawater rises and sinks with changes in temperature and salinity, air masses will rise and sink with changes in temperature caused by the presence of land or water. Glider pilots are experts at analyzing these changes, riding the updrafts over warm land and downdrafts over cool water. Oceanic and atmospheric circulation drives climate and weather patterns across the globe. The lateral and vertical movement of air and water can partly be attributed to the Coriolis effect, creating air cells thanks to the Earth's constant spinning. It is also controlled by differences in temperature and composition, affecting the densities of these fluids. The vertical movement of ocean currents, known as thermohaline circulation, transports latent heat around the surface and largely determines regional climates. The presence of land influences how air rises and sinks in the atmosphere, as well as how ocean currents deflect and change direction. Circulation patterns are definitely complex and a critical part of weather and climate patterns, as well as seawater movement.
Where does the water that forms rain come from? How about fog? Where does that come from? Have you ever been asked these questions by people, especially those kids who keep asking, why? Has someone ever told you that the water falling as snow has always been here? Or that the water we use was once dinosaur blood? Or that we are drinking someone's sweat, or worse yet, drinking someone else's gulp? How can this be possible? Is it possible? How does water move around the Earth, and where does it come from? The water cycle, also known as the hydrologic cycle, is the process by which water moves from place to place above, on, and below the Earth's surface. This is the process by which water moves around the Earth to different places. The total amount of water on the Earth is relatively unchanging, and it has remained about the same since our planet's formation. As the planet cooled, water vapor present at its formation condensed to fill the oceans and other places, like inland lakes and rivers. The Earth's surface is 75% water and 25% land. Of the water, 97% is salt water, a surprisingly high percentage, leaving only 3% as fresh water. Most of that, 2/3 of the fresh water on Earth, is frozen in snow and ice and glaciers, ice caps, and the like. That leaves only about 1% of all the Earth's water as liquid and fresh, making it a very scarce natural resource. If that wasn't enough, most of the liquid, fresh water is stored underground in aquifers. Groundwater is just what the word sounds like, water stored under the surface of the Earth. But like rocks or other types of matter, water on the Earth is not static. It constantly is moving around the hydrosphere, the layer of the Earth where water is present. It moves around by changing in 3 different processes that make up the water cycle. Let's begin the water cycle journey with water on the surface of the Earth. That's where most of the liquid water on the surface is, right? Evaporation is the process by which water is converted from its liquid state to the gaseous state, also known as water vapor. In other words, water leaves the Earth's surface and enters the atmosphere as a gas. In fact, the United States Geological Survey, the USGS, says that up to 90% of the water vapor in the air comes from surface water, including oceans, lakes, and rivers, with the rest coming from plants. When this happens, anything that is in the water, dissolved or undissolved, remains behind. This includes salt, rocks, minerals, and other materials that often end up in the surface water. Evaporation is a purifying process. One of the ways you can purify seawater is to heat it, so it evaporates, and then collect the steam. The steam is pure water, and getting it back to a liquid requires our next phase of the water cycle. Condensation is the process by which water vapor is changed back into liquid water. Condensation is very important to our weather and climate because it is what is responsible for cloud formation. Without clouds, we would not get to the 3rd phase called precipitation, which we will talk about in a minute. Clouds form when water vapor condenses around small particles like bits of dust or smoke in the air. Depending on the size of the drops, these particles may or may not be visible. Even on a clear, cloudless day, water vapor is always present in the atmosphere, but it does vary in amounts. We know it is present on a very humid day. It often feels like we need to swim through the air. Fog is condensation near the ground. Fog forms when moist, warmer air comes in contact with cooler air near the surface. Just like when the bathroom mirror gets all foggy during a shower because of condensation, fog also forms because of this warm air contacting a cooler air mass. The fog forms drops in the air rather than on the surface of your mirror. Precipitation, the next phase of the water cycle, is water that falls from the atmosphere in the form of rain, sleet, snow, hail, or freezing rain. Clouds are required for precipitation because the raindrops are the drops of the clouds that have condensed enough water to begin falling. The cloud particles do not have enough mass to fall, but as condensation continues to add water to those particles, gravity eventually pulls them towards the Earth as precipitation. According to the USGS, millions of cloud particles must coalesce in order to form one raindrop. Temperature determines the type of precipitation that falls from the clouds. Cooler weather means more ice and snow, and also more hazardous driving. Yikes! Evaporation, condensation, and precipitation are the 3 main parts of the water cycle, but there are some other stages that water can cycle through. These different things occur mainly after water has fallen on the earth. We know that water can become runoff when it flows along the surface into lakes, rivers, and streams. It could absorb into the ground and become groundwater, or get absorbed into plants. Groundwater is any water under the ground, usually collecting in the aquifers that contain most of the liquid fresh water we mentioned earlier. Plants use water to help make energy, and they also lose some water to the surrounding air through the process called transpiration. Transpiration is a plant losing water through its leaves. It is just like we humans lose water to the air through our breath. Eventually, most surface water will either be absorbed as groundwater, evaporate from the surface, or make its way to the ocean to eventually evaporate. So, to recap, water moves through a cycle on Earth called the water cycle, sometimes referred to as the hydrologic cycle. The water cycle begins with surface water, which is represented by rivers, lakes, and oceans. Next, it moves through evaporation, or the process by which water is converted from its liquid state to a gaseous state called water vapor. This is followed by condensation, which is the process by which water vapor is changed back into liquid water. Then, water becomes precipitation, which is water falling from the clouds as rain, freezing rain, sleet, snow, or hail. Water is constantly moving through all living things as well as through the ground and atmosphere. New water is not created in any significant amount by these processes, so the water we have cycles through living and non-living things, and it has done so since the earth was created.
Water is pretty special. Water is what makes Earth different than all the other planets in our solar system because it is what allows life to exist. It's also unique because it's found in all three phases: liquid water in oceans, lakes, and streams, frozen ice as polar ice caps and glaciers, and gaseous water in the atmosphere. Water really likes to move, too. It moves around the world, but it also moves through different phases. As it travels around the planet, it goes through the water cycle. This is the natural cycling of water through phases and locations on Earth, and it's one of the most important cycles we have on Earth. Each of the different components of the cycle contributes in its own way and is vital to the success of the overall cycle. Water may condense in the atmosphere, which is when water vapor in the air turns back into liquid and forms clouds. Once in the clouds, that liquid water may fall back to Earth as rain, snow, and sleet, which is called precipitation. Once that precipitation hits the ground, it may infiltrate into the ground, which is when it seeps into the soil in the ground, or it may flow across the surface of the ground as runoff. Evaporation and transpiration are two other critical components of the water cycle because they are the processes that put water into the atmosphere in the first place. We'll explore each more in detail in this lesson, but it's important to keep in mind that the water cycle is not circular like running around a track. It's more like a web where phase changes can occur in any order and in any location. Evaporation and transpiration both put water into the air as a gas, but in different ways. Evaporation is a process you are likely familiar with because it is the changing of liquid surface water to a gas. You've evaporated water every time you've boiled a pot of water on the stove for pasta. As you heat the water, it gets filled with energy. Once it gets energized enough, it's too excited to stay as a liquid, so it turns into a gas and flows up into the air. This is why if you boil the water long enough, you will eventually run out of water in your pot. You see the same thing if you let water sit out long enough uncovered. You can even try this at home. Set a bowl of water out without a lid on it and wait a day or two. Eventually, you will return to the bowl to see that the water is all gone. It has evaporated into the air as a gas. This just takes a little longer because you're not adding as much heat as when you cook it on the stove. On Earth, evaporation occurs over the oceans, lakes, rivers, and streams on the surface. This is one reason we find the rainforests of the world near oceans, which provide a large amount of surface water. The air around the tropics is especially warm, which helps the water heat up and change phase, evaporating into the air as water vapor. It then falls over the rainforest as precipitation, and since the oceans are such a large source of water, the clouds in these areas have a lot of rain to drop back down to Earth. Evaporation is affected not only by the surface area of the water body, but also the amount of sun exposure, as seen in the tropics, air temperature, and wind speed. You know that sunshine and warmer air temperatures speed up the evaporation process, but wind also helps because as it blows over the water, it picks up water along the surface and puts it in the air. The other way that water gets into the air is through transpiration, which is water evaporation through plants. Plants drink water from the soil, and as they take it up, they use it for biological processes, just like your body does when you drink a glass of water. Both your cells and plant cells are mostly made up of water, so they need to keep hydrated in order to function properly. Plants also need to take in carbon dioxide in order to photosynthesize or turn sunlight into chemical energy. Basically, this is how plants eat. They collect sunlight and convert it into a usable energy source. To take in carbon dioxide, though, plants need to open small holes on their leaves called stomata. This is where the plant breathes as it takes in carbon dioxide and releases oxygen as a waste product from photosynthesis. Unfortunately, plants also lose water through their stomata as they exchange these gases, which makes the stomata like the sweat glands of a plant. While plants don't like to lose water, we should be thankful that they do, because it provides a lot of water to the water cycle. Moisture in the soil would just stay there without transpiration, and we need transpiration to occur so that water can be returned to the atmosphere and precipitate back down to Earth and recharge our surface waters. The rate of transpiration is also affected by various factors. When air is more humid, plants will transpire less because the air already has water in it. Warmer air temperatures will increase transpiration because, like the pot of water on your stove, the water leaving plant stomata is heated as it hits the air and turns to water vapor. Wind has the same effect on plant transpiration as it does on surface water and increases the rate of liquid water turning to water vapor in the air. Wind easily picks up and carries water away from the plant leaves as it blows by. The water cycle is an important and natural cycle of how water changes phase and location on Earth. Without the water cycle, all of the rivers, lakes, and oceans would dry up, plants would have no water to drink from the ground, and we would have no weather like rain or snow that help regulate temperatures on Earth. There are several components to the water cycle, such as condensation, which is when water vapor in the air turns back into liquid and forms clouds, and precipitation, which is when that liquid water falls back to Earth. Once the water has come back to the ground, it may infiltrate, which is when water seeps into the soil, or it may flow across the surface of the ground as runoff. Two very important components of the water cycle are evaporation and transpiration. These processes return water to the atmosphere as gaseous water vapor. And though they are similar processes, the water comes from different sources. Evaporation is when water vapor comes from liquid surface water, such as streams, lakes, rivers, and oceans. Like boiling a pot of water, heat from the sun energizes the water on the surface, which turns it from liquid to gas. Transpiration is when water vapor comes from liquid water excreted by plants. Plants breathe by exchanging carbon dioxide for oxygen through small openings in their leaves called stomata during photosynthesis. However, during this exchange, they also lose water that they drank from the soil that originally came down as precipitation. Places that are warmer, drier, and windier will experience more evaporation and transpiration. This is because warm air energizes liquid water faster than cool air, drier air has less moisture to begin with, so it's happy to take from others, and wind easily picks up water as it travels by. It is important to remember that the water cycle is not circular. It's more like a web. Condensation, evaporation, precipitation, and all the other components do not happen in a linear manner. They may occur at the same time, at different times, and in multiple locations all over Earth.
Ever heard the phrase, "It's not the heat, it's the humidity"? People say this because humidity, which is the amount of water vapor in the air, can make hot temperatures even more unbearable than they already are. Humidity is actually a broad term, and we can describe different types of humidity in different ways. Humidity is an important thing to understand because it affects both weather and climate, as well as global climate change. Humidity also affects indoor environments, so understanding it can help you determine the best place to store your books, clothing, and other important items in your house. You've probably heard about relative humidity in weather reports. This is the amount of water vapor in the air relative to what the air can hold. Think about it this way. If you have a cup that is half full of water, the cup contains 50% of what it can hold. Air works the same way. Let's say that a certain parcel of air, or a clump of air that shares similar properties, can hold 30 grams of water vapor per cubic meter of air, but it only has 15 grams of water vapor per cubic meter of air. We simply divide the amount of water present by the amount of water possible. So 15 divided by 30, and then multiply it by 100 to get a percent. In this case, 15 divided by 30 equals 0.5, multiplied by 100 gives us 50%. So the relative humidity is 50%. Which means the air contains about half of the total water vapor it could possibly hold. It's important to know that warm air can hold more water than cold air. You can think of different temperature air like different sized cups. Smaller cups hold less water than larger cups, right? In this case, cold air is a smaller cup, and warm air is a larger cup. So when the air is colder, the same amount of water vapor will produce a higher relative humidity than the same amount of water vapor in warmer air. This is because we have to consider the amount of water vapor relative to what the air can hold. Let's look at an example. You have two cups, one that can hold a maximum of 12 ounces and one that can hold a maximum of 24 ounces. Now put 6 ounces of water in each cup, and you'll notice that the smaller cup is fuller than the larger cup, even though they have the same amount of water in them. There are 6 ounces of fluid in the 12-ounce cup, so 6 divided by 12 times 100 equals 50%. There are 6 ounces of water in the larger cup as well, but this cup can hold a total of 24 ounces, so 6 divided by 24 times 100 equals 25%. If the 12-ounce cup represents cold air and the 24-ounce cup represents warm air, the relative humidity for the cold air is 50%, but for the same amount of water in warm air, the relative humidity is only 25%. How full the cup is relates to how much the cup can hold overall. When we apply this to air, we can see that for the same amount of water vapor, the relative humidity will be higher for cold air than for warm air because the cold air is fuller from the same amount of water. When the air becomes saturated, this means that it contains the maximum amount of water vapor possible. Just like relative humidity differs with different air temperatures, saturation is also temperature dependent. Remember our cups from before? Saturation occurs when the cups are completely full of water. Just like the smaller cup needs less water to become full, cold air becomes saturated from less water than it takes to saturate warm air. And just like if you kept filling your cups even though they were already full, the water would have to go somewhere, so it would spill out of the cup and fill the surrounding area. Dew is when water condenses at ground level because the air is saturated. Just like the water spills over the side of the full cup, when air is saturated, the excess water spills over and builds up on leaves, cars, buildings, or anything else that is surrounded by the saturated air. Therefore, the temperature at which saturation occurs is called the dew point. You most commonly see dew in the morning because air temperature goes down overnight. And remember, cold air can't hold as much water. So it's like you're taking the larger cup, warm air, and pouring it into the smaller one, cold air. There's simply not enough room, so it spills over as dew. Interestingly, this same condensation process occurs in the sky, but when this happens, clouds are created. Clouds are water condensation above ground level due to air saturation. So when you see condensation on your patio furniture in the morning, this is dew. However, when you see it floating by as a white puffy shape in the sky, this is a cloud. Humidity plays an important role in both weather and climate on Earth, and we should be thankful that it does, because it makes our planet hospitable for us. Water vapor is a key greenhouse gas, which helps block harmful UV rays from the sun, as well as traps heat on Earth that makes life possible. Water vapor in the air comes from water on land and in the oceans. It evaporates into the air, which is an important part of the water cycle on Earth. Without this step, we would have no rain or snow, which help cycle water back to the ground and feed our rivers, lakes, and streams that we depend on for drinking water. However, because it is such a powerful greenhouse gas, water vapor can be quite the double-edged sword. Like a nice blanket on a cool day, we depend on water vapor in the atmosphere to give us just the right amount of protection and warmth. But if someone comes along and adds more blankets on you when you don't need them, This will likely make it too warm for you to be comfortable. The same thing happens to Earth when too much water vapor is in the air, but Earth can't remove the extra blankets and simply continues to warm all over. This feeds a vicious cycle on Earth because as the planet warms, the humidity increases. But with more humidity comes more warming, which then leads to more humidity, and so on. If you've ever visited the southeast U.S., you know how humid it gets there. Sometimes the air literally feels like you're walking through a swamp. Humidity describes the amount of water vapor in the air, and the more water vapor that is present, the more humid it is. Most weather reports don't tell you the humidity, though, because the relative humidity is more relevant. This is the amount of water vapor in the air relative to what the air can hold. This is just like figuring out how much water is in a cup relative to the total amount of water that cup can hold. If a cup has 6 ounces of water in it, but it can hold 12 ounces, we would find that 6 divided by 12 equals 0.5. To make this number meaningful, we multiply it by 100 to get a percent, which would give us 50% for our cup. If we did this calculation for a parcel of air, the air would be at 50% relative humidity because it contains 50% of the total amount of water vapor it can hold. And just like you might have different size cups, different temperatures of air can hold different maximum amounts of water vapor. Warm air is like a larger cup because it can hold more water, and cold air is like a smaller cup because it can't hold as much water. This also means that the same amount of water will produce different relative humidities for different air temperatures. Just like you can fill the cup full of water, air can also be filled. When the air contains the maximum amount of water vapor possible, we say that it is saturated. You can keep adding water, but it won't get taken up by the air because, like a full cup of water, there's simply no room left, and it spills over. When saturation occurs at ground level, we get dew. This is the water you've seen condensing early in the morning on plants, cars, and other items outside. You see this in the morning because the air becomes cooler overnight, so it's like pouring a larger cup of water into a smaller one. Because dew occurs when the air is saturated, the temperature at which saturation will occur is called the dew point. The same process occurs to create clouds, but these are formed from saturation of the air in the sky instead of on the ground. Clouds also provide us with things like rain and snow, which are essential sources of water for our lakes, rivers, oceans, and even groundwater. Water vapor in the air plays a critical role in our global climate and weather patterns. Water vapor is an important greenhouse gas, so like a large blanket in Earth's atmosphere, it protects us from harmful UV radiation from the sun, as well as traps beneficial heat on Earth. However, because Earth can't remove this blanket if it becomes too warm, water vapor can trap too much heat on Earth, which in turn increases global temperatures. This perpetuates a vicious cycle of warming, because as Earth warms, humidity in the atmosphere increases. But as humidity increases, more heat is trapped from the increased water vapor in the air, which increases global temperatures on Earth even more.
Think of all of the things you've measured in the past week. 4 cups of flour for your bread, 1/4 of a gallon of gas for your chainsaw, a 5-mile trail for your run, and a 32-inch belt for your waist. So I know you're a bread-baking, chainsaw-wielding runner with a nice belt, but I don't know if you can measure water vapor. Well, don't worry, I'm here to help. Water vapor is water that is a gas. In fact, it's floating all around you right now. Even though you can't see it, I'm sure you've noticed it before. For example, when it's humid out, there's a lot of water vapor in the air, so you probably felt it. Or when you see dew, fog, or clouds, water vapor has condensed or become a liquid. Measuring water vapor can help scientists make predictions about weather. So how in the world do you measure water vapor? A ruler? A measuring cup? Let's start with vapor pressure, which is the atmospheric pressure due to water vapor molecules. Now, depending on where you read, this definition can get a little more complicated, but for the scope of this lesson, let's keep it simple. You might not realize these water vapor molecules are exerting pressure, but they are constantly bumping into you. Since you can't see these water vapor molecules, how do you measure vapor pressure? Excellent question. You can measure vapor pressure by using a manometer. No, that isn't a man-thermometer hybrid. Instead, it's a U-shaped tube usually filled with mercury. As the pressure on one side of the tube increases, it pushes the mercury to the other side. So now you can be a bread-baking, chainsaw-wielding runner with a nice belt and a manometer. Before we move on, how do you think vapor pressure is related to the number of water vapor molecules in the atmosphere? Well, if you have a lot of water vapor in the air, they would be exerting more pressure, so you would have a high vapor pressure. Okay, on to humidity. When you think of humidity, what comes to mind? Being sweaty? Hot? Your hair going crazy? You probably already know that humidity has something to do with how much water vapor is in the air, but there are several ways to measure humidity. There is relative humidity, absolute humidity, and specific humidity. Let's look at each. Relative humidity measures how close the air is to saturation. Saturated air is air that's full of water vapor and can't hold any more. So relative humidity is water vapor in the air divided by how much water vapor the air could hold. Relative humidity is measured as a percentage. So if the relative humidity is 100%, it means the air is saturated. Sometimes it's hard to wrap your mind around definitions, so let me give you an example. Let's use cups to represent air and water to represent water vapor. Our first cup is 5 ounces and is holding 5 ounces of water. To make that a percentage, like relative humidity, I'd take 5 divided by 5 times 100. We'd say this cup has a relative humidity of 100%. Our second cup is 50 ounces and is holding 5 ounces of water. To make that a percentage, I'd take 5 divided by 50 times 100. We'd say this cup has a relative humidity of 10%. In our analogy, the small cup represents cold air, whereas the big cup represents warm air. Warm air can hold more water vapor without filling up or becoming saturated, hence the bigger cup. Now, technically, the warm air isn't holding more water vapor, but realize that warmer air has more water vapor molecules without becoming saturated. Another measurement of humidity is called absolute humidity, which measures the mass of water vapor in a certain volume, or the density of water vapor. So here you can see one of these has more water vapor molecules within a certain area, so you could say it has a greater absolute humidity. Finally, specific humidity is calculated by taking the mass of the water vapor divided by the total mass of all of the air. So you know how each type of humidity is measured, but are there tools to help you out? Yep. For example, there's a tool called a psychrometer, which is a type of hygrometer. A hygrometer, by the way, is a tool that can be used to measure moisture in the atmosphere, like humidity or dew point. This particular type of hygrometer, the psychrometer, works by having 2 thermometers. One bulb, or the bottom of the thermometer, is wet, while the other is dry. The wet bulb has water evaporating off of it, which cools it. Think about when you sweat and water evaporates off of you and then cools you. The difference in temperature between the 2 thermometers is directly related to how much water evaporates off of the wet bulb, which is related to how much water vapor is already in the air. Less evaporates if the air is already full of water. So the psychrometer gives you the relative humidity, or how close the air is to being saturated. So now you're a bread-baking, chainsaw-wielding runner with a nice belt, a manometer, and a psychrometer. Or you can just use formulas that use the vapor pressure, among other things, to calculate the specific humidity, relative humidity, or the absolute humidity. So you can add a calculator to your ensemble. Before we move on to mixing ratio, you can pause the video and take some notes on this table to study later. Hey, maybe this table can be one of your tools. Next, let's see how you can measure the mixing ratio, or the mass of water vapor divided by the mass of dry air. Although this definition sounds similar to specific humidity, you'll notice the mixing ratio looks at the mass of dry air, whereas specific humidity looked at all air. Like I mentioned for humidity, there are formulas you can use to help you calculate the mixing ratio. We won't get into the specifics, but you know which tool you'll need to do all of that math. The last measurement we're going to discuss is the dew point. This is the temperature air needs to be cooled to in order for saturation to occur, at a specific temperature and pressure. In other words, the temperature where the air cannot hold any more water vapor, which results in condensation. Dew is condensation on objects, hence the name dew point. You can measure dew point by using another type of hygrometer made out of a mirror, a light beam, and a light detector. The light beam shines into the mirror and then bounces off and is read by the detector. When the mirror is cooled, dew forms on its surface, which makes the beam less bright, which is noted by the light detector, and voila! The dew point is recorded. Now you have another hygrometer to add to your collection. So you're a bread-baking, chainsaw-wielding runner with a nice belt, a manometer, a couple of hygrometers, including one psychrometer, some math formulas, a table, and a calculator. But let's take a moment to review all of the ways we can measure water in the air. You probably remember that water vapor is water that's a gas in the air, but did you remember what vapor pressure measured? Vapor pressure is the pressure exerted by water vapor molecules that are in the atmosphere. Humidity measures how much water is in the air, and you can measure it several different ways. The mixing ratio sounded similar to specific humidity, but it was actually a little different. Let's take a look at a table that summarizes humidity and mixing ratio. Relative humidity is calculated by taking the water vapor in the air divided by how much water vapor the air can hold. Absolute humidity takes the density of water vapor, which is the mass of water vapor, divided by the volume. Specific humidity takes the mass of water vapor divided by the total mass of the air. The mixing ratio takes the mass of water vapor divided by the total mass of dry air. Last but not least, there was the dew point, which is the temperature the air must cool in order for dew to form. And remember all the tools you can use: formulas, tables, calculators, manometers, and hygrometers, including one called a psychrometer. So now that you're armed with a whole new set of tools, you can spend all of your free time measuring the water vapor in the atmosphere, and think of all the things you'll be able to tell your friends. When dew will form, how saturated the air is, or what's the humidity today? You're about to go on a whirlwind adventure following a water molecule around. Now, all water molecules look the same, so we'll need to keep track of your water molecule, so let's call him Wally Water Molecule, or just Wally for short. It's probably hard to believe, but Wally is going to become lots of things, from water in a lake to an ice crystal in the atmosphere. Before we head out, let's get a few things straight about water. You probably already know that water can exist as a solid, or ice, a liquid, and as a gas, or water vapor. But did you know that all three forms can exist in the atmosphere? I know it's strange to think of ice in the atmosphere, but it can happen, as you'll see shortly. Let's start our tour in the lake, where Wally and his friends are all liquid. It won't take us long to observe some evaporation, or the change from a liquid to a gas. And just like that, some of our lake water is water vapor, a gas. You'll notice Wally is happily bouncing around in the atmosphere now. You might also notice some of Wally's friends undergoing condensation, or the change from a gas to a liquid. You can see condensation as dew on plant leaves, or even as water droplets on the outside of a cold mug on a hot day. Condensation and evaporation are going on all of the time, but at some point the air becomes saturated, meaning the rate of evaporation is the same as the rate of condensation. In other words, the air can't hold any more water vapor at that temperature and pressure, so if any liquid water molecules become water vapor, the same amount of water vapor must condense and return to a liquid. As the air gets closer to becoming saturated, it feels more and more humid. So, what causes the air to become saturated? Good question. There are actually a few ways air can become saturated, so let's take a moment to investigate each. Air becomes saturated due to evaporation. Of course this makes sense because in order for water vapor to enter the atmosphere, evaporation needs to occur. Evaporation is impacted by temperature, so if it's hot, the molecules move faster and are more likely to become a gas. Air can also become saturated if it's cooled. Colder air can hold less water vapor, so if you cool some hot air that is not saturated, it will eventually become saturated. Now technically, this is a little more complicated, and it's not the air that holds the water vapor, but more water vapor can be found in warmer air versus colder air, which is the take-home message. Air can cool for various reasons. For example, after the sun sets, the ground cools, which cools the air close to the Earth's surface, causing it to reach saturation. Or, As a parcel of air rises, it will cool and expand as it gets higher in the atmosphere, thus reaching its saturation point. The mixing of two unsaturated air masses can create a saturated air parcel. In this case, the two air masses are not saturated, but when they mix, they become saturated. For example, let's say you have cold air sitting above a warm body of water. As the water evaporates, it adds more water vapor to the cold air, causing it to become saturated. Before this mixing, the cold air was not saturated, nor was the air with the water vapor from the lake. But after mixing, the cold air gained enough water vapor to reach saturation. Let's talk a little more about condensation. In order for our water vapor to condense, a couple of things need to occur. 1. Air needs to be cooled to its saturation point, where the air can't hold any more water vapor molecules. 2. There needs to be something for the water vapor to condense on. For example, we mentioned the dew and the water forming on the mug from before. Both the plants and the mug are the things the water condensed on. But what happens when condensation happens in the atmosphere where there are no plants or mugs? Let's check back with Wally, who is still happily bouncing around in the atmosphere. Sometimes Wally and his friends can bump into nuclei in the atmosphere. Nuclei are tiny particles like salt, pollen, bacteria, ash, or dust that give water vapor a surface to condense on. The nuclei acts like the plant or the mug back on the ground. There are different types of nuclei depending on what type of particle forms. For example, there are condensation nuclei and ice nuclei. The condensation nuclei are tiny particles that water vapor can condense on to form liquid water, whereas ice nuclei are tiny particles that the water vapor or liquid water can freeze on to form ice crystals. Both condensation nuclei and ice nuclei help nucleation to occur, or the changing from one state to another due to nuclei. So what happens when water vapor in the atmosphere condenses or freezes? Well, Wally might become the starting material for a cloud or ice fog. He might even become rain, snow, or hail. Ice nucleation, or the change from water vapor or water to ice, can occur via several different methods, so let's follow Wally through each one. Deposition nucleation occurs when water vapor goes directly from a gas to a solid when it comes into contact with ice nuclei. In this case, Wally and his friends are in supersaturated air. This means the air is actually beyond saturation, but no water vapor molecules have started to condense yet. When Wally bumps into an ice nucleus, he freezes immediately. Freezing nucleation occurs when a liquid water droplet is supercooled and freezes. Supercooled water is when water is cooled below its freezing point, yet remains a liquid. Although it doesn't sound possible, it can happen with small amounts of water. So here, Wally is a really cold liquid, but then he changes into an ice crystal. There are two types of freezing nucleation, immersion and contact. Immersion nucleation occurs when ice nuclei are inside of a droplet of supercooled liquid water, which causes nucleation of other water molecules. Here, Wally has a nucleus inside of him, and other water molecules can nucleate on top of him. Contact nucleation occurs when ice nuclei bump into supercooled water droplets, which causes ice nucleation. In this case, a supercooled Wally bumps into an ice nucleus, and he becomes ice. So we followed Wally from a lake and into the atmosphere where the possibilities are endless. Will he become part of a cloud or form an ice crystal? Let's take a moment to review some of the stops on Wally's journey. Water can evaporate and condense, changing from a gas to a liquid and liquid to a gas. When the atmosphere becomes saturated, it can't hold any more water vapor molecules, so for every water that evaporates, one must condense. Air can become saturated due to evaporation, the mixing of two unsaturated air masses, or by cooling the air. Water vapor in the atmosphere condenses when it becomes saturated and bumps into condensation nuclei. Nuclei are particles. Water vapor and liquid water can condense onto these nuclei. There are condensation and ice nuclei depending on what product is formed. Water vapor and water can become ice in the atmosphere in several different ways, including deposition and freezing nucleation, which includes immersion and contact nucleation. Well, that about covers it. And I hear Wally is about to become a snowflake, so I'd better let him go. Don't be sad, though. Maybe you'll see Wally the next time it snows.
Have you ever noticed how many different types of clouds appear in the sky? There are large, fluffy ones, thin, gray ones, light, wispy ones, and even ones that seem to cover the entire sky. Though they look different, all clouds are condensed water droplets in the air. They form when warm, moist air rises upward. As the warm air rises, it cools. Cool air can't hold as much water as warm air, so it's like pouring a large glass of water into a smaller one. Except instead of spilling over the glass, the water in the air condenses around dust particles that are floating around. As these droplets build up in the sky, they form a cloud. Clouds are usually grouped into different types based on their altitude, how high they are in the sky, and their shape. There are 10 cloud shapes that fall into 4 major altitude groups. High clouds are just what they sound like, clouds that are at high altitudes. These usually form about 6,000 meters in the sky. There are 3 types of high clouds, all containing the word cirrus. The word cirrus means wispy hair in Latin, and these clouds definitely live up to their name. Cirrus clouds are thin and wispy, sometimes called horsetail clouds. Cirrocumulus clouds are the big puffy clouds that look like a big head of curly hair. Cirrostratus clouds are like big sheets of thin clouds covering the sky, and this makes sense because the word stratus means sheet-like, so this last type of cloud is a big wispy sheet in the sky. You probably guessed where middle clouds hang out. These are clouds at mid-level altitude. Usually found between 2,000 and 6,000 meters, middle clouds get the prefix alto because alto means middle. There are 2 types of middle clouds. Altostratus have that word stratus in them, so we know these are large sheets of cloud. They are gray in color, cover the entire sky, and are often so thick that they disrupt sunlight coming into the ground so much that shadows aren't produced on the ground. These usually form before a storm, so head inside if you see these. Altocumulus are like the cirrocumulus in that they are puffy, note that same suffix cumulus, but these are very dark in color and tend to form puffy masses in parallel bands across the sky. Low clouds are clouds at low altitude, usually below 2,000 meters. There are 3 types of low clouds, all called stratus. You now know this means they cover the entire sky, but this time much closer to the surface of the Earth. Stratus clouds are what you see on a dreary, hazy day. Stratocumulus are also low and gray, but since they have the word cumulus in them, this means that they have a bit more shape to them. These are lumpy layers across the sky, though they rarely produce rain. Nimbostratus clouds are the ones that make you want to just stay inside all day. They are dark and wet-looking and often produce a decent amount of rain. Finally, we have vertical clouds, which are clouds that form vertically instead of horizontally. There are 2 types of vertical clouds, cumulus and cumulonimbus. Since they both have the word cumulus in them, we know that they are both big, fluffy clouds. Cumulus clouds are the ones you can see shapes in when you look up at them in the sky. Remember the nimbostratus clouds and how dark and foreboding they were? Well, think of nimbus as a cloud to stay away from, since cumulonimbus clouds are also dark and rainy. Cumulonimbus clouds often turn into thunderheads, which is when a cloud develops into a thunderstorm. Clouds come in all shapes and sizes, but they all form from water droplet condensation around particles in the air. When warm, moist air rises upward, it cools. But, like a smaller glass, cool air can't hold as much water as warm air, so the water condenses around particles floating around. If enough water droplets and particles build up, we get a cloud. There are 10 types of clouds based on their shape, and they fall into 4 main categories based on their altitude. The names of the categories tell you where you can find them in the sky. High clouds are clouds at high altitudes, above 6,000 meters. Middle clouds are clouds found at mid-level altitudes between 2,000 and 6,000 meters. Anything below 2,000 meters, so clouds found at low altitudes, are low clouds. The final category is vertical clouds, and these are special because they form vertically instead of horizontally. There are three types of high clouds. They all contain the word cirrus because cirrus means wispy hair, and this is just what these clouds look like. Cirrus clouds are also called horsetail clouds because they are like thin wisps of hair high in the sky. Cirrocumulus clouds look like a curly head of hair floating about, and cirrostratus clouds are thin and sheet-like because this is what stratus means. There are two types of middle clouds, both called alto clouds. This is because alto means middle. Altostratus clouds are mid-level sheet-like clouds that are bluish-gray and cover the entire sky. Altocumulus clouds have that word cumulus, so these are puffy clouds, but they tend to form in large bands across the sky. Low clouds come in three forms, and all have the word stratus in their name because they cover the sky like a gray sheet. Stratus are what you might see on a hazy winter day. Stratocumulus have our cumulus descriptor in their name, so we know these have some shape. They're lumpy gray clouds that do not usually produce rain. Nimbostratus are dark looming clouds that are wet-looking and do produce rain. Two types of vertical clouds exist. Cumulus clouds are the ones that you can look up at and see shapes. They grow taller than they do wide and are like a big cotton ball in the sky. And just like nimbostratus clouds are dark and foreboding, cumulonimbus clouds are also dark and stormy. Thunderhead clouds are formed from cumulonimbus clouds, so if you see one in the sky, you may want to rethink that afternoon picnic.
Well, hi there. My name is Claudette Cloud, but my friends just call me Claudette. I'm here to tell you all about how I formed. Now, there are a couple of processes involved in cloud formation, specifically the adiabatic process and the diabatic process, which are sometimes referred to as adiabatic or diabatic cooling or warming. Before we delve into each process, though, let me just give you a brief overview on how I formed. I'll start from the beginning. If you check out that puddle over there, you might see some water evaporating or changing from a liquid to a gas. Or, if you check out those leaves over there, you might see some dew, which is a result of condensation, or changing from a gas to a liquid. Water is continually evaporating and condensing. At some point, the air becomes saturated, meaning the air is full and can't hold any more water vapor molecules. And for every water vapor molecule that evaporates, one must condense. This coincides with the dew point temperature, which is the temperature where the air is saturated. As the air cools, it can hold less water vapor before it becomes saturated. So as the air cools, it becomes saturated. This whole process is a little more complicated, and air isn't holding water vapor, but it's important to know that colder air has less water vapor than warm air. Okay, back to that dew point temperature and saturation. When the air is saturated, water vapor will condense on condensation nuclei, or tiny particles like dust, ash, pollen, or bacteria that are floating around in the air. This condensed water creates water droplets suspended in the air, and when you get a bunch of these droplets together, you get me, Claudette the Cloud. So we know the air cooled and became saturated, but what caused the air to cool in the first place? Let's talk about those two processes I mentioned at the beginning of the lesson, starting with the adiabatic process. Let's follow the adiabatic process to see how I was formed. Look over there. I see a parcel of air, which is just a clump of air that shares similar properties. Now that parcel of air is ascending into the atmosphere. There is less pressure the higher you get in the atmosphere, so there will be less pressure exerted on the parcel as it ascends. It may be hard to visualize this, so let me give you an example. Pretend you let go of a helium balloon and it starts to float away. As it gets higher in the atmosphere, there is less pressure, so the air inside of the balloon isn't contained by the pressure. The higher it goes, the bigger the balloon will get, and eventually it'll pop. The same thing is going to happen to that parcel of air. As it goes up, less pressure is exerted on it, and the parcel expands, taking up more room. Of course, the parcel won't pop since it isn't surrounded by plastic like the air inside of the balloon. Now, that parcel is made up of molecules that are bouncing around. As the parcel ascends and spreads out, the molecules are less likely to collide with one another. Since they don't collide as often, there is less energy. Believe it or not, when those molecules collide, energy is exchanged. So, if they aren't colliding as often, it'll cause a temperature drop. This temperature drop causes the parcel of air to reach the dew point temperature, and you know what happens from there, right? Yep, water vapor condenses onto condensation nuclei, and you get me. So, to sum up, the adiabatic process is the cooling of a parcel of air as it ascends due to a change in pressure. It's important to note that the adiabatic process deals with a pressure change, not heat entering or leaving the parcel, or the parcel mixing with another parcel. And one final note before we move on to the diabatic process. The adiabatic process works in reverse too, meaning as air descends, the pressure is greater and the parcel warms. Now, let's look at the other process, the diabatic process. Unlike the adiabatic process, this process does involve our air mixing with substances outside of the parcel. Let's follow the diabatic process for the formation of my friend, Clarence Cloud. Clarence started as a parcel of air that floated over a cold body of water. Because of its proximity to the cold water, this parcel cooled to its dew point temperature. Water vapor condensed on condensation nuclei, and Clarence was born. So, in a nutshell, the diabatic process is the heating or cooling of a parcel of air due to a heat exchange. You'll notice I said heating in that definition. Yep, if that parcel of air had blown over a warm surface, the parcel would have heated due to a diabatic process. But if that happened, it probably wouldn't have reached its dew point temperature and Clarence wouldn't have been formed. Before Clarence and I go, there are a few more things to discuss. Let's take a moment to contrast the adiabatic and the diabatic processes. First, diabatic processes are the result of a heat exchange, whereas adiabatic processes are the result of contraction from a lot of pressure being exerted on an air parcel, and expansion from less pressure being exerted on an air parcel. Second, diabatic cooling or heating is not reversible. For example, the parcel that created Clarence will not re-warm unless it comes into contact with something to warm it back up, like the warm ground or a warm body of water. However, adiabatic cooling or heating is reversible because if the parcel ascends or descends, it cools or warms. Finally, diabatic is the result from heat leaving or entering the parcel, whereas in adiabatic, no heat leaves or enters. I've sure enjoyed sharing my life story with you, and I know Clarence feels the same way. Before you run off, let me give you some reminders so you won't forget us. Clouds form when air reaches its dew point temperature and water vapor condenses on condensation nuclei. Air can cool through adiabatic and diabatic processes. Adiabatic processes are due to the expansion and contraction of an air parcel as it ascends or descends in the atmosphere. As the parcel ascends, it expands and the molecules collide less and less, thus reducing the amount of heat energy and resulting in a cooler parcel of air. Diabatic processes are due to a heat exchange. For example, a parcel of air might blow over a cold body of water, which causes the parcel to cool. Okay, well, it looks like Clarence and I are starting to warm up, so we might dissipate soon, but that's another lesson. Bye now.
Believe it or not, air is actually a fluid. This is because a fluid is any substance that flows and has an indeterminate shape. This is different from a liquid, which is a specific phase of matter. All liquids are fluids, but not all fluids are liquids because gases are also fluids. Air, which is a mixture of various molecules in their gaseous phase, definitely flows. Think of something like wind. That's just air flowing around horizontally. Air also flows vertically, which we call lift. But air doesn't lift all by itself, it needs help. There are 4 main processes that lift air, known as lifting mechanisms. When air does flow upward, we get some pretty interesting weather processes like cloud formation, precipitation, thunderstorms, tornadoes, and hurricanes. The first way that air is lifted is through orographic lifting. This is when air is lifted over an obstacle like a mountain. As air moves across an area, it sometimes runs into obstacles like mountains, and of course it has nowhere to go but up. As the air is forced up the side of the mountain, it cools and condenses, which means it gets more compact. Most of the moisture in the air gets forced out as the air condenses, which forms a cloud over this side of the mountain, known as the windward side. It's called the windward side because this is the side of the mountain the wind first encounters. The cloud is full of moisture, so it's also pretty rainy on the windward side. Once the air goes over the top of the mountain, it sinks back down again, and as it sinks, it warms up. However, it left most of its moisture on the windward side, so this air flowing down the backside of the mountain, also known as the leeward side, is not only warm, but very dry. Areas like the western U.S. know this phenomenon quite well. As the wet air coming from the Pacific blows into the mountains in this area, the side that the wet air first hits stays pretty wet, while the other side is dry and warm. So Oregon and Washington are wet and rainy, but New Mexico and Nevada are warm and dry. Another way that air is lifted is through frontal lifting. A front is where two different air masses meet, so frontal lifting is when one air mass along a front gets lifted up over the other. A cold front occurs when a cold air mass advances onto a warm air mass. A warm front is the opposite, when a warm air mass advances onto a cold air mass. A cold front is like jumping into a lake in the middle of winter. Your body is quickly shocked by the change in temperature, and the warm air experiences something similar. It's quickly and forcefully pushed upward. Because of this, we get clouds forming quickly as well, and they form vertically instead of horizontally. These make the best thunderstorm clouds, so cold fronts tend to bring dramatic changes in weather too. Warm air along a warm front is quite different. It gets slowly lifted up instead of the dramatic lift we see with cold fronts. It's more like getting into a hot tub, slowly stepping in and letting your body adjust to the change in temperature. Since air is lifted so slowly along a warm front, cloud formation is more horizontal than vertical. This means that while the weather does change, it's much less dramatic than with a cold front, and you'll likely experience mild rain over a wide area. Next, we have convergence, which is when air converges in the center of a low-pressure area. As air flows horizontally and meets along the surface of Earth, it's forced upward since that's the only place it can go. It can't go into the ground, right? Convergence is responsible for some well-known weather events like hurricanes and cyclones. In fact, these storms only survive if wet air continues to converge in the center. If it stops, they die out. The eye of a hurricane is the low-pressure center where the air comes together, and as the air rises, it brings up moisture from the ocean it formed over. This is also why a hurricane can't form over land. It needs water just like we need food. The wet air converges, rises up through the low-pressure center, and as you now know, it cools and condenses as it is lifted up. Condensation releases a lot of energy, and this is the very energy that drives the storm along its path. As long as there is moist air being drawn up into the eye, the storm continues to soldier on. The final way that air is lifted is through convective lifting. Convection is a process that applies to all fluids, so both liquids and gases. It's the overall process of warm particles moving upward and cool particles sinking downward. Convective lifting is therefore the lifting of air particles due to convection. As the sun hits Earth's surface, it warms it. You've felt this if you stood outside on a sunny day. However, the warming of the surface is not uniform, so some places get warmed more than others. These hot spots are perfect places for convection to occur since the air is especially warmed here. As the air is warmed, it rises, but then as it rises, it cools and condenses. If the air is fairly stable, then we get big, puffy clouds in the sky, the kind you can look up at and see various shapes and objects. However, if the air is unstable, the convective lifting will create clouds that form vertically, and as you now know, these are the clouds that thunderstorms form from. Convection also involves air sinking back down, though, and as the cool sinking air falls, it picks up moisture again. Sometimes this moisture cycles through the cloud, keeping the cloud the way it is, or it leaves the cloud and falls to the ground as precipitation. Because air is a fluid, it flows freely around Earth. Much of the time it flows horizontally, which creates wind, but sometimes it flows vertically, which is known as lift. Air is lifted through four main processes known as lifting mechanisms. Orographic lifting is when air is lifted over an obstacle, like a mountain. When air hits a mountain, it has nowhere to go but up, so up it goes. As it rises, it cools and condenses, which forces most of the moisture out and creates wet conditions on the windward side and dry conditions on the leeward side. Frontal lifting is when air is lifted along fronts, which is where two different air masses meet. Like jumping into a cold lake and shocking your system, a cold front shocks warm air upward very quickly. Warm fronts are quite the opposite, more like slowly stepping into a hot tub. The warm air is slowly lifted over the cold air, creating less dramatic weather changes. Convergence is just what it sounds like, air converging at a low-pressure center. Horizontally moving air gathers up on the surface and is forced upward because it sure can't go down into the ground. As the air is pushed upward, it cools and condenses, providing energy to the cloud that will likely form in this low-pressure eye. Convective lifting is air lifting by convection. Convection occurs in all fluids and is the process of warm particles rising and cool particles sinking. Convection is most likely to occur in hot spots on Earth's surface because these areas get warmed more than others. The warm air rises, cools and condenses, and depending on how stable the air is, either forms beautiful puffy clouds or dark, foreboding thunderstorms.
Get ready. You're about to go up, up, up into the atmosphere. But why, you ask? Well, you're about to explore lapse rates, which are the rates at which the temperature changes with altitude. 3, 2, 1, here we go! You're going to be traveling within a parcel of air, which just means a clump of air that shares similar properties. As you go up, you might notice it gets colder, so go ahead and put on that scarf and hat. We are going to examine the three types of lapse rates: dry adiabatic, wet adiabatic, and environmental. But before you ascend any further, why don't you hover for a minute so we can get some background information under our belt. When air is saturated, it means the air cannot hold any more water vapor at that pressure and temperature. Water is evaporating or changing into water vapor and condensing or changing from a gas to a liquid all of the time. When the atmosphere is saturated, it can't hold any more water vapor, so for every water molecule that evaporates, one must condense. So the dry adiabatic lapse rate is dealing with air that is not saturated. The name dry is a little misleading. Just because the air isn't saturated doesn't mean it's dry. Okay, let's start to ascend with the parcel of air. You'll notice the higher you go, the pressure decreases, and your ears might pop. As the pressure decreases, the parcel of air is able to spread out and cool. But why? Well, with less pressure, the molecules are able to take up more space because the pressure isn't keeping them contained. If you had a balloon with you, you'd notice the balloon would get bigger and bigger as the pressure decreased because there's less pressure pushing inwards on it. Eventually, it would pop. Back to those molecules. As they spread out, they are less likely to collide with one another, thus reducing the amount of heat energy exchanged between molecules. This causes the parcel of air to cool. The dry adiabatic lapse rate is the rate at which unsaturated air cools or warms as it changes altitude. And here is that rate. For every 1,000 feet the air ascends, the temperature will decrease by about 5.5 degrees Fahrenheit. This is the same for descending too. Meaning for every 1,000 feet the air descends, the temperature will go up by about 5.5 degrees Fahrenheit. And for you metric folk, for every 100 meters it changes by 1 degree Celsius. But let's keep going up and see what happens. Man, I bet you're getting cold. It looks like you're about to reach the atmospheric dew point, where the air is cooled enough to become saturated and it will start to condense. You might notice this by seeing some clouds forming. So now that the air is saturated, the lapse rate will change, hence the wet adiabatic lapse rate. This lapse rate is the rate at which saturated air cools or warms as it changes altitude. Because the air is condensing, which releases heat, the rate of cooling will slow. Unlike the dry lapse rate, the wet adiabatic lapse rate can vary. This is dependent upon how much water vapor the air parcel had before it started to rise. But here are some ranges. For every 1,000 feet ascended, there is a 3.2 to 2.2 degree Fahrenheit decrease in temperature. And for every 1,000 feet the air descends, there is a 3.2 to 2.2 degree Fahrenheit rise in temperature. And for you metric folk, the wet adiabatic lapse rate average is about 0.5 degrees Celsius for every 100 meters. You might be wondering why the air became saturated when it cooled. Why don't you hover again while we go over the details? Warm air can hold more water vapor without becoming saturated, whereas colder air holds less before becoming saturated. Now, technically, it's a little more complicated than this, and air doesn't hold water vapor. But for the scope of this lesson, just know warmer air has more water vapor without becoming saturated. Okay, keep going. Up, up, up. Eventually, all of the water inside of your air parcel will condense out and the air will revert back to the dry adiabatic rate. We don't want you to float away too far, so why don't you come back down to Earth, for now. There are some things you need to know about adiabatic before we go into the environmental lapse rate. The adiabatic lapse rates are theoretical, meaning there are certain criteria that must occur in order for those lapse rates to hold true. Let's briefly go over those criteria. It stipulates there is no mixing between air parcels. And there is no heat exchange, meaning no heat leaves or enters the parcel. Even though parcels of air are often large, so mixing or heat exchange may be minimal, the parcels aren't sealed off from one another. So there is an environmental lapse rate. This is the rate change in temperature with altitude at any given location and time, meaning a real-world lapse rate without the stipulations seen in the adiabatic lapse rates. Both the dry and wet adiabatic rates are theoretical and can be calculated mathematically. So how do scientists determine the environmental lapse rates? This is determined by releasing weather balloons and measuring the temperature at different altitudes. In 1953, a bunch of organizations and scientists in the United States developed the U.S. Standard Atmosphere, which gives data for temperatures, pressures, and densities at different altitudes. It was calculated by using environmental lapse rates, satellites, and rocket data, as well as looking at mathematical expressions. The U.S. Standard Atmosphere was revised several times, the last in 1976. The U.S. Standard Atmosphere changes depending on the altitude, but up until about 6.8 miles, the rate is a change of 3.57 degrees Fahrenheit for every 1,000 feet. The international community also developed a standard atmosphere, sometimes called the International Standard Atmosphere, which agrees with the U.S. Standard Atmosphere until an altitude of about 19.8 miles. Now that you're back on the ground, why don't we take a moment to review everything we learned about lapse rates, or the rates at which temperatures change with altitude. There are dry adiabatic lapse rates and wet adiabatic lapse rates. The first is the rate at which temperature changes when the air is unsaturated, meaning the air can still hold some more water vapor. The latter is the rate at which temperature changes when the air is saturated, meaning the air can't hold any more water vapor. Both of the adiabatic lapse rates are theoretical. The environmental lapse rate is the rate at which temperature changes with altitude at any given place at any given time. Scientists came up with the standard atmosphere, which is the temperatures, pressures, and densities at different altitudes. There is a U.S. standard atmosphere and an international standard atmosphere, which are about the same until 19.8 miles. Who knew so much happened way up there? Air expanding, cooling, and condensing. How exciting! It's a warm spring day and you're enjoying your weekend camping at the beach. Warm sand, clear skies, blue water, and a cold iced tea. You can't help but notice the outside of your iced tea is covered in water droplets. Where did those water droplets come from? What if I were to tell you they came from the air? You can't see them, but there are millions of tiny water molecules floating around you right now. When they bump into your cold iced tea glass, they cool down and undergo a phase change, meaning they change from water vapor into liquid water, or from a gas to a liquid. This phase change is called condensation. Wow, I spent all that time talking about condensation and the sun is setting. Better head inside your tent for the night and I'll see you in the morning. Welcome back. I know it's early, but you're going to need to hurry out of your tent in order to see some condensation. If you look around, you'll notice there is water everywhere. Take a look. I see some on your tent and some on the plants behind your tent. It didn't rain last night, so where did all of this water come from? Believe it or not, it actually came from the air and is a type of condensation called dew. Dew forms when the temperature drops below the dew point temperature, which means the temperature is dropped to a point where the air can no longer hold any more water vapor molecules, so they condense. When the air cannot hold any more water vapor, it's saturated. You may notice that the air became saturated after the temperature dropped. As it turns out, warmer air can hold more water vapor molecules compared to cooler air. So, as the air cooled, it could hold less water vapor and therefore became saturated. Now, technically, the air isn't holding the water vapor, but realize that more water vapor molecules can be present in warm air versus cold air without the air becoming saturated. So dew is just water vapor from the atmosphere that is condensed into water droplets because the air has become saturated. These water droplets condense onto a cool surface, in this case your tent and the leaves of the plants. Fortunately for you, it isn't below freezing at your campsite, but let's take a moment to look at what can happen if it's really cold. If it is below freezing, the dew can freeze. In some cases, the water vapor can go from a gas directly to a solid in what is called deposition. When this occurs, you have frost, or water vapor that has turned directly into ice crystals. So how can you tell frozen dew apart from frost? Frost appears whiter with ice crystals, whereas frozen dew is more solid and not as white. Oftentimes people confuse frozen dew with frost, but it's important to note they're formed differently. Okay, back to your campsite. If you look over the water, you'll notice fog has formed. Fog is a cloud that is close to the Earth's surface. And as you look around, you see fog everywhere. Over the ocean, next to your tent, and on the mountains next to the beach. Where did all of this fog come from? Fog forms in the same way as clouds. As you know by now, there are millions of water vapor molecules floating around in the air. So far, you've seen what happens when those water vapor molecules condense on objects, like your tent, your iced tea glass, or the leaves of plants. But what happens when they condense in the air? As mentioned previously, the air can only hold so much water, and when it becomes saturated, the water vapor needs to condense. Well, in the air, the water condenses on condensation nuclei, or tiny particles like dust, pollen, salt, ash, or even bacteria that provide a surface for water to condense on. Fog forms when all of these liquid water droplets are suspended in the air. There are actually quite a few different types of fogs, so let's take a moment to explain each one, as well as give an example of where you can find it, other than your campsite. Radiation fog occurs on cool, clear nights when the Earth's surface cools, causing the air near the surface to condense. As the Earth's surface cools, the air near the surface will also cool. If you remember, cooler air can hold less water vapor than warmer air, so as the air cools, it becomes saturated, and if condensation nuclei are present, the water vapor will condense and you'll get fog. Radiation fog is fairly common and is found near the ground. The fog you witnessed above the ocean is called advection fog. This type of fog occurs when warm air moves across a cooler surface. That cooler surface may be the ground, snow, ice, or water. As the warm air moves across the cold surface, it cools and reaches its saturation point. This may sound similar to radiation fog, but it's a little different. Advection fog is the result of warm air moving over a colder surface, so you may notice advection fog moving horizontally across the ground. Another difference is advection fog can last several days, can occur when it's windy, and when clouds are present. You might find this fog over the ocean or other bodies of water. For example, it's often seen along the California coastline. The third type of fog you witnessed is called upslope fog, which forms when moist air is pushed up a hill or mountain by wind. This is the fog that is near the mountains behind the beach. As the moist air goes up the mountainside, the temperature decreases so the air cools and can hold less water vapor, thus becoming saturated. As you might guess, you'll see this fog on hills or mountains. For example, it's common in the Rocky Mountains of the United States. Now, lucky for you, you didn't witness any ice fog or freezing fog on your camping trip. Ice fog forms in polar regions when water vapor freezes into ice crystals. In the interior parts of Alaska, ice fog is fairly common in the winter months. Finally, there is mixing fog or evaporation fog. Here, two parcels of air that are not saturated mix together to create a saturated air mass. For example, let's say you have a cold parcel of air that moves over a warm body of water. As the water evaporates, it rises and mixes with the cold air. This causes the warm air to cool and reach its saturation point, thus causing condensation to occur. Although there isn't any mixing or evaporation fog at your campsite, you may have seen it elsewhere. For example, a type of mixing fog called steam fog can be seen near hot springs. Who knew your beach camping trip would turn into a lesson on condensation? Let's take a moment to review what we have learned so you can get back to enjoying the beach. Condensation is when a gas turns into a liquid and can be seen everywhere, from the water droplets forming on your cold glass to the fog forming by your tent. Dew is water vapor that is condensed on a surface, while frozen dew occurs when it's below freezing and the dew turns to ice. Frost occurs when water vapor turns directly into ice crystals. Fog forms when condensation occurs in the atmosphere. In order for fog to form, condensation nuclei must be present. There are many different types of fog, including radiation fog, advection fog, upslope fog, ice fog, and mixing fog. That was probably enough information to ensure you don't get foggy when it comes to condensation knowledge. Get it? Wally Water Molecule is back to teach you all about cloud droplets. You don't remember Wally, you say? Don't worry, I'll introduce you. Like his name implies, Wally Water Molecule is a water molecule, and he can exist as liquid water, solid water, otherwise known as ice, and a gas, or water vapor. He is quite the world traveler and can be found in lakes and oceans, in the air, in clouds, in rain, and even in snow. In fact, you might even see him change from a liquid to a gas through evaporation, or change from a gas to a liquid through condensation. Today you're in for a special treat. Wally is going to become a cloud droplet. A cloud droplet is water vapor that is condensed onto condensation nuclei. When you get a bunch of cloud droplets together, you have a cloud. But what are condensation nuclei? Well, let's start from the beginning. Once upon a time, Wally was hanging out in a beautiful blue lake. But, like all water molecules, Wally wasn't content just sitting around, so as soon as he had enough energy, he evaporated and became water vapor. Meanwhile, some of Wally's fellow water molecules were condensing. You might see some of them as dew on plants, or as water droplets forming on a cold glass on a hot day. Okay, back to Wally. The air can only hold so many of Wally and his buddies before it becomes saturated, which means the air is full of water vapor and can't hold any more. And for every molecule of water that evaporates, one must condense. But what causes the air to become saturated, or full of Wally and his friends? Let's take a look. Number 1, evaporation. If the rate of evaporation has increased, there is more water vapor in the air. Therefore, the air can become saturated. And number 2, the air is cooled. As air is cooled, it can hold less water vapor before it becomes saturated. Technically, it's a little more complicated, but the basic explanation is that more water vapor is found in warm air than in cold air. Okay, so now you know what saturated means, and a couple of ways saturation can happen. So let's check back with Wally, who's still bouncing around in the atmosphere. Wally is now in saturated air, so he really wants to condense. But there's nothing to condense on in the atmosphere. Or is there? Uh-oh! It looks like Wally's about to bump into something. Look out! Wally just collided with condensation nuclei, or tiny particles like dust, pollen, ash, or bacteria that are floating in the atmosphere. And when Wally collides with these tiny particles, he's able to condense, turning into liquid water that is suspended in the air, otherwise known as a cloud droplet. So, cloud droplet formation just means water vapor condensed on condensation nuclei. If Wally and all of his friends become cloud droplets, they will collectively become a cloud. I'd like to say Wally and his friends lived happily ever after in that cloud, but all good things must come to an end. Unfortunately for that cloud, it's becoming a bright, sunny day. Wally and his friends are about to disappear, and the cloud is going to dissipate. When the cloud droplet dissipates, it just means the cloud droplets evaporate. But what causes a cloud droplet to evaporate? I'm so glad you asked. Number 1. The cloud's temperature increases. When the temperature of the cloud increases, water evaporates at a faster rate, so Wally is more likely to evaporate. Many things can increase the temperature of the cloud, like the sun or warm air radiating off of the ground. That's why low fog and clouds tend to disappear as it warms up during the day. Number 2. The cloud and the drier air mix together. This drier air causes evaporation to increase, thus causing the droplets to dissipate. You can see where this type of mixing has occurred with the cloud because the outer edges are wispy. Number 3. The air within the cloud descends. When the air descends, it warms. This is due to the adiabatic process, which means as an air parcel, like a cloud, descends, there is greater pressure being exerted on it. This increase in pressure causes the molecules to bump into each other more often, which results in an increase in heat energy, which warms the cloud. This increase in temperature results in evaporation. Back to our story. Today is turning out to be really hot, so the temperature inside of the cloud is increasing. Wally and his friends are starting to get really warm, and oh no, some of Wally's friends are disappearing. And boom! There goes Wally! Enough cloud droplets evaporated that the cloud has dissipated. But don't worry, Wally isn't gone forever. By now you should know that Wally just changes forms a lot, so he's still in the atmosphere, but now he's water vapor again and not liquid water. So, for now, that's the end of this Wally water molecule tale. However, I'm sure you'll see Wally again really soon. Before we go, let's take a moment to review some important parts of our story. Water is continually changing states or forms. In this story, Wally evaporated, condensed, and then evaporated again. When the air can't hold any more water vapor, it is saturated, and for every water molecule that evaporates, one must condense. Water can become saturated in several ways, including evaporation and when air cools. When water vapor condenses in the atmosphere, it does so on tiny particles called condensation nuclei. Liquid water that is condensed on condensation nuclei can form cloud droplets, and when you have enough cloud droplets, you get a cloud. Clouds dissipate when the cloud droplets evaporate, which can happen for several reasons, such as a temperature increase in the cloud mixing with dry air, or the cloud descending. Take a look at that! I think I see Wally and he's formed another cloud droplet. Wait, there's some of his friends. Wow, they're forming a giant cloud. Go, Wally, go! There's a reason why Earth is called the blue planet. About 71% of the Earth's surface is covered by water. There are 3,094 cubic miles of water in the atmosphere. Each day, 280 cubic miles worth of water evaporates and transpires into the atmosphere, and about 7 million cubic miles of water can be found as ice in glaciers and ice caps around the world. But how does that water mainly water vapor, impact climate variability on the blue planet. Before we get into that, we need to understand the words climate, temperature, and climate variability. Temperature refers to conditions at a specific time and place. For example, today in Fairbanks, Alaska, it's currently 40 degrees Fahrenheit and sunny, whereas climate refers to the pattern of weather over a long period of time. For example, for this date, Fairbanks has an average temperature of 27 degrees Fahrenheit. Climate variability refers to the yearly variation in climate compared to the long-term average. For example, some winters are colder than normal, some have more precipitation, whereas others are warmer and drier. This lesson will focus on climate, and more specifically, how water vapor affects the climate. Water cycles through the earth in the water cycle, evaporating and transpiring into the atmosphere and then returning to the ground through precipitation, ending up in plants, in the oceans, in freshwater ponds, and then evaporating. Well, you get the general idea. So, if you had to guess, do you think more water vapor in the atmosphere would make the temperature rise or decline? Well, let's take a look. It's a hot, sunny day and the ground and water are warmed from the heat of the sun. At night, when the sun sets, it starts to cool off. Now, without water vapor and other greenhouse gases, the heat from the ground and the lake would radiate back into space and the earth would get really cold at night. But greenhouse gases, like water vapor, capture that heat energy and then radiate it back. So you can see how greenhouse gases get their name. They act like a greenhouse, trapping the heat. So, the more water vapor that's in the atmosphere, the more heat energy gets radiated back to Earth. So, to answer our question from before, more water vapor makes the Earth warmer. You've probably already heard about climate change, or the change in climate patterns, and you've probably heard of global warming, or an increase in the world's average temperature, but you may not be familiar with water's role in climate change and global warming. Water is affected by global warming and in turn leads to increased warming of the Earth. In fact, water vapor is responsible for about 60% of the warming. But why? As the overall temperature on Earth increases, more liquid water evaporates. When the temperature increases, water molecules get more energy and are more likely to evaporate. With more evaporation, there is more water vapor in the atmosphere, which causes more heat to be radiated back to Earth. When more water evaporates into the atmosphere, several things can happen. First, warmer air can hold a greater amount of water vapor. In fact, for every 1.8 degree Fahrenheit, or 1 degree Celsius, rise in temperature, the air can hold about 7% more water vapor before it becomes saturated, or full of water vapor. A greater amount of water vapor in the atmosphere not only leads to more heat being trapped and radiated back to Earth through the greenhouse effect, but also more precipitation. So, there are areas in the world that are experiencing more rain and snow than they had in previous years. Yet another impact from increased water vapor is the intensity of storms. For example, cyclones are also impacted by water vapor in the atmosphere. In order for a cyclone to intensify, it needs certain conditions including warm ocean water, specific wind conditions, and a lot of water vapor in the atmosphere. So, with an increase in water vapor in the atmosphere, scientists are finding cyclones are intensifying. The increased evaporation can cause droughts in other parts of the world. So, while some areas are getting an increase in precipitation, other areas are getting less precipitation. Or when it does rain or snow, they get an all or nothing effect, meaning they go long periods of time without anything and then a bunch at once, which can lead to flooding. You can think of climate and water vapor as a continuing cycle. Each is impacted by the other. Let's review why. As the yearly temperature average varies from year to year, you can assume the amount of water vapor in the air will also vary too. An increase in temperature results in more water vapor in the atmosphere for two reasons. First, higher temperatures result in more water evaporating. Second, there is more water vapor found in the warmer air versus colder air. More water vapor in the atmosphere, in turn, raises the temperature of the Earth. This is because water vapor is one of the greenhouse gases, so it radiates heat energy back to the Earth and prevents it from radiating out into space. An increase in temperature causes more water to evaporate, which can cause droughts in some areas, whereas the increased water in the atmosphere can result in increased precipitation and more intense storms in other areas. So, you can see water vapor is directly related to the temperature and climate variability. Depending on the yearly average temperature, you can expect different amounts of average water vapor in the air. This can vary from year to year, causing droughts in some areas or increased storms in other areas. However, as the world's average temperature increases, you can expect more water vapor to be in the atmosphere each year.
Believe it or not, a heavy downpour in the
And the forecast calls for 2 days of precipitation. Today, warm but rainy. Tomorrow, hot with a chance of thunderstorms in the afternoon. Depending on how much you love rain, you might be thinking about how the rain will affect your plans to go have fun outside. What you might not be thinking is, why is it going to rain? Precipitation occurs when water droplets or crystals condense out of air saturated with water vapor and fall from the sky to the ground. It may occur when evaporation causes the amount of water vapor in the air to increase, or when air cools and its capacity to hold water decreases. Precipitation comes from clouds. Clouds are areas of the atmosphere where moisture has condensed into tiny water droplets or small grains of ice. All clouds are made out of water, but not all clouds produce precipitation. There are 2 ways that air cools: at night when temperatures drop, or as the air rises. In this video, we'll focus on the mechanisms that lead to air rising, often known as uplift mechanisms. Cumulonimbus clouds and cumulus clouds may look pretty different, but they're produced by the same oven-like effect: convective uplift. Convective uplift occurs when air near the ground is warmed by the sun and begins to rise. The air rises and cools in a process known as adiabatic cooling. This leads to the formation of clouds and, sometimes, precipitations. For me, it is helpful to think of a conventional oven when remembering the process of convection. For one, the processes are similar. In a conventional oven, energy is added to heat up the air inside, which cooks the food within. Plus, the names are similar: conventional oven and convection. When the ascending air mass is stable, or the same temperature as the surrounding air masses, the result of convection is nice, puffy cumulus clouds. However, if the ascending air mass is unstable, or warmer than the surrounding air masses, the result of convection is a cumulonimbus, or thundercloud. This happens because the warmer air keeps rising and expanding, disturbing the air masses at high altitudes. Next time you're watching the Weather Channel and hear a phrase like, "There's a cold front coming in," you can expect to see some clouds and maybe even some precipitation. Here's why. Cold fronts are made of cooler, denser masses of air. When they encounter a warm mass of air, the warm air is forced up, over the top of the cooler air. As the warm air rises, water vapor in that air condenses and cools. As it does so, clouds form, eventually leading to precipitation. A similar thing happens with warm fronts. A warm front approaching a colder air mass will rise on the back of the dense mass of cold air. As the warm air rises, it cools, eventually leading to precipitation. Generally speaking, frontal uplift occurs when 2 different air masses interact. I remember this definition because the uplift occurs at the front of one of the air masses. Our final uplift mechanism is a phenomenon that you can actually observe. Look at these photos of orographic uplift. Based on your observations, what do you think is responsible for the formation of these clouds? Mountains. In orographic uplift, air is forced upward by a topographic obstacle. In other words, a mountain or large hill, where it rises and cools. The cool air condenses into clouds, eventually leading to precipitation. Orographic uplift is common on the west coast of America, where winds moving eastward push air up against the Sierra Nevada mountains. If you live on the east coast, orographic uplift is common in the Appalachian Mountains, when air currents moving from Ohio and Tennessee run into them. Precipitation occurs when water droplets or crystals condense out of air saturated with water vapor and fall from the sky to the ground. It may occur when evaporation causes the amount of water vapor in the air to increase, or when air cools and its capacity to hold water decreases. Mechanisms that lead to air rising are known as uplift mechanisms. Convective uplift occurs when air near the ground is warmed by the sun and begins to rise. Air rises and cools, forming clouds and precipitation. Frontal uplift occurs when two different air masses interact. Cold fronts force warm air up where it cools, forming clouds and precipitation. Warm fronts climb up the backside of cooler air masses. The rising warm air cools to produce clouds and precipitation. Orographic uplift occurs when air is forced upward by a topographic obstacle, like a mountain. Rising air cools to form clouds and precipitation.
Chances are you're pretty familiar with a water cycle. Water is evaporated from streams, rivers, lakes, and oceans, undergoes condensation in the clouds, and finally falls to the earth as precipitation. In fact, you may even be familiar with the impact of geography on this cycle. After all, the rain shadow created by high mountains can block the other side of hilly terrain from getting any rain at all, while the side closest to the water gets plenty of precipitation. This helps to contribute to deserts in places like Africa, Arabia, and South America. However, did you know that there are global phenomena at work as well? In this lesson, we'll look at the impact of wind currents and pressure changes on precipitation. Additionally, we'll look at the results of what happens to precipitation when wind currents and pressure systems cooperate to create a perfect storm. Everyone has felt a windy day before. If you've been to the beach, you've probably noticed how storms blow in and blow out, with heavy wind on either side of the system. However, what you're feeling are only the edges of the wind. Hundreds of feet up is where the real action happens. Here, massive wind currents blow weather systems around the world. Amazingly, some of these wind systems are pretty regular. For example, we know that the Gulf Stream will blow up from the Caribbean, across the eastern coast of North America, then over past Iceland on its way to the British Isles. This is one of the reasons that, despite its relatively high latitude, Britain is so relatively warm. However, this is not the only weather system affected by changes in the wind. The monsoons of South Asia blow regularly in one direction for half the year, then promptly change and blow in almost the exact opposite direction. Not only does this permit for regular trade since ancient times, but also it means that these regions experience a wet and a dry season, corresponding with how the wind is blowing. Of course, all that precipitation would simply be bumped out of the way if certain pressure systems had their way. Pressure systems act as either barriers or encouragement for the development of precipitation. High-pressure systems like those found typically over the coast of Southern California or Morocco limit the amount of rain that can develop in those regions because the rain systems can't get in due to the pressure. Meanwhile, low-pressure systems encourage precipitation systems, while high-pressure systems are like a slippery hill. Low-pressure systems allow precipitation systems to slide into them easily. Low-pressure systems frequently congregate off the coast of Western Africa, near Liberia. In short, high-pressure systems limit precipitation, while low-pressure systems encourage it. Sometimes these systems can work with each other to make or break very impressive storm systems. Have you ever wondered why hurricanes are so rare in Europe but so common in the southeastern United States? In short, it's the perfect combination of wind systems and pressure. Winds run west from Africa to the Caribbean, including right past one of the most common low-pressure areas of the globe. That means that any storms that form here are carried west, gaining strength over open, warm water. By the time they reach the United States coast, they are often full-blown hurricanes. High-pressure systems protect the coast of Britain and France from many hurricanes. In fact, only when low-pressure fronts sit over Europe for extended periods of time do hurricanes tend to go northeast instead of west. This same pattern explains why hurricanes, which are called typhoons in the southwest Pacific, form near Mexico before striking west towards Hawaii and Asia instead of turning east and north. In this lesson, we look at how wind currents and pressure systems affect global precipitation. We started by reviewing the water cycle, then jumped right in with how wind moves precipitation systems around the map. In particular, we focused on the Gulf Stream, moving from the Caribbean to Canada and on to Europe. Further, we examined the impact of high and low pressure on precipitation. Specifically, we learned how high pressure limited precipitation, while low pressure encouraged it. Finally, we combined the two ideas to explain how hurricanes and typhoons form. In particular, we examined why hurricanes in California and Europe are both relatively rare.
It's a gorgeous sunny day and you've just settled down by the pool. There's not a cloud in the bright blue sky, when suddenly the sky grows a bit darker. You look up to see a cloud blocking the sun. Not only that, you hear the rumbling of thunder. As the pitter-patter of rain begins, you are forced to go inside. Rain is a form of precipitation, or water that falls from the sky to the surface of the earth. Precipitation may be in liquid form, like rain, or in solid form, like snow. It's easy to get disgruntled by rain or snow on a day when you'd rather be outside getting some sunshine. But the phenomenon of precipitation is actually quite cool. Literally. To better understand how precipitation forms, let's imagine that we are up in the atmosphere and only about 10 micrometers large. Just in case you don't remember, 1 micrometer is 1/1000th of a millimeter. Though you may not see them, you are surrounded by countless gaseous water molecules known as water vapor. When the air becomes saturated with water vapor, meaning there is more water vapor than the air can hold, clouds will form. This usually happens at high altitudes, but it can happen at lower altitudes. Ever been in a fog? The state of being saturated is similar to being in a really crowded room. Every available space is occupied. Once the room is too crowded, you and other people might be forced to leave. In the case of cloud formation, water vapor is forced to condense into water droplets or ice crystals. Collectively, all these droplets and ice crystals make up a cloud. A cloud is a region of atmosphere where moisture condenses, forming tiny water droplets or grains of ice. As you're looking around, you see water droplets that range from 1 to 10 times your size. All of the droplets inside the rain cloud are falling, but movement is so slow that air currents are strong enough to push them back up. In our cloud, we can also see small grains of ice. Their individual shapes vary, however, all bear semblance to a hexagonal structure. Water vapor molecules have condensed onto condensation nuclei, which are minuscule solid or liquid particles floating around in the atmosphere. The tiny water droplets we see collect other surrounding water molecules. This basic process is known as growth by condensation. Once the weight of the droplet is too much for the atmosphere to support it, it will fall from the sky. Let's say we're suspended in a cloud that's warm. Well, relatively warm. To be a warm cloud, temperatures just need to be above freezing. Inside our warm cloud, there are tiny water droplets. These droplets are constantly colliding with each other, and sometimes they stick together after colliding. This process of collision and coalescence leads to the growth of raindrops. Droplets can grow to 1,000,000 times their original size through collision and coalescence. Once the drops are too big, they will fall from the cloud. On the way down, these drops will collect other droplets. If drops become too big, however, resistance from air will cause them to break down into smaller drops. If drops pass through hot or dry air, they will evaporate before hitting the ground. If the air is above freezing, the drops will fall as rain. But if the air is below freezing, the raindrops will freeze into sleet. When temperatures drop below freezing, our surroundings change a bit. Inside a cool or cold cloud, both ice crystals and supercooled water can exist. Supercooled water is water that is below freezing, but is still in a liquid state. Ice crystals are tiny bits of frozen water. Under these conditions, precipitation may form through the Bergeron process. When I think this process, I think Bergeron because it involves supercooled water and ice crystals. In the Bergeron process, super tiny ice crystals attract water vapor to themselves. The water vapor particles bond to the ice crystals, leading to a drop in surrounding vapor pressure. This, in turn, leads to the evaporation of the surrounding water droplets, transforming them from their liquid state into water vapor. These vapor particles stick to the growing ice crystals. From our perspective in miniature, we see hexagonal shapes slowly forming around us. Ice crystals in a cloud will collide with one another. At temperatures of -5 degrees Celsius or above, the ice crystals are slick or sticky enough that collisions lead to crystal growth in a process known as aggregation. Continuous aggregation will produce a familiar phenomenon, snowflakes. Like growing raindrops, snowflakes will eventually get too heavy and fall from the cloud. Snowflakes descending through cold air, below freezing, will fall as powdery snow. Snowflakes falling through warmer air, approximately freezing, will aggregate more into clumps. If the air is above freezing, the snow will turn into rain. Occasionally, we might observe a phenomenon called riming or accretion, which happens when droplets of water freeze to the surface of ice crystals. Instead of the nice hexagonal shapes we observe during the Bergeron process, we see clumping. The end product of this is often graupel, a form of precipitation that looks like miniature snowballs. Let's review all the vocabulary we've learned in this lesson. Precipitation is water that falls from the sky to the surface of the earth. Water vapor consists of gaseous water molecules. When the air becomes saturated with water vapor, clouds will form. A cloud is a region of atmosphere where moisture condenses, forming tiny water droplets or grains of ice. Condensation nuclei are minuscule solid or liquid particles floating around in the atmosphere. Growth by condensation happens as water vapor condenses onto water molecules. Collision and coalescence occurs in warm clouds when water droplets crash into each other and stick. Supercooled water is water that is below freezing but is still in a liquid state. The Bergeron process occurs when tiny ice crystals attract water vapor to themselves. At temperatures of -5 degrees Celsius or above, the ice crystals are slick or sticky enough that collisions lend to crystal growth in a process known as aggregation. Riming or accretion happens when droplets of water freeze to the surface of ice crystals.
Location, location, location. This is especially important when we're talking about ocean storms because the location of the storm determines what we call it. For example, if the storm occurs in the Atlantic Ocean and Northeast Pacific, it's called a hurricane. If the exact same type of storm occurs in the Northwest Pacific, this is a typhoon. And if we find those same storms in the South Pacific and Indian Ocean, these are called tropical cyclones. Cyclone refers to any spinning storm that rotates around a low-pressure center. The low-pressure center is also referred to as the eye of the storm, which is well known for being eerily calm compared with the areas under the spinning arms of the storm. You could say that the eye is watching what's going on down below, so it needs a clear path. But the arms are where all the action happens because this is where the storm is throwing out all of its rain and wind. The term cyclone actually refers to several different types of storms. They occur in different places, and some occur over land while others occur over water. What they all have in common is that they are spinning storms rotating around that low-pressure center. Tropical cyclones are what most people are familiar with because these are cyclones that occur over tropical ocean regions. Hurricanes and typhoons are actually types of tropical cyclones, but they have different names so that it's clear where that storm is occurring. Hurricanes are found in the Atlantic and Northeast Pacific. Typhoons are found in the Northwest Pacific. If you hear tropical cyclone, you should assume that it's occurring in the South Pacific or Indian Ocean, but for this lesson, we'll use it to refer to all types of tropical ocean cyclones. We can also further describe tropical cyclones based on their wind speeds. They're called Category 1, 2, 3, 4, or 5, increasing with intensity and wind speed as the number increases. A Category 1 cyclone is the weakest, with wind speeds of 74 to 95 miles per hour. A Category 5 cyclone, on the other hand, is extremely dangerous and has the potential for major damage. Category 5 cyclones have wind speeds of 155 miles per hour and above. Polar cyclones are cyclones that occur in polar regions like Greenland, Siberia, and Antarctica. Unlike tropical cyclones, polar cyclones are usually stronger in winter months. As you can see, these storms really do prefer the colder weather. They also occur in areas that aren't very populated, so any damage they do is usually pretty minimal. A mesocyclone is when part of a thunderstorm cloud starts to spin, which may eventually lead to a tornado. Meso means middle, so you can think of this as the midpoint between one type of storm and the other. Tornadoes all come from thunderstorm clouds, but not all thunderstorm clouds make tornadoes. In order for a tornado to occur, part of that cloud has to spin, And though you can't really see this happening, this is the intermediate or meso step from regular cloud to dangerous spinning cloud running along the ground. Even though they form over different areas, cyclones tend to come about in the same way and revolve around that low pressure eye. Warm air likes to rise, and as it rises, it cools. Cool air can't hold as much moisture as warm air, so that water gets squeezed out of the condensing air and a cloud begins to form. If the warm air rises very quickly, this creates an updraft. Likewise, if the water in the cloud builds up enough, it may fall back to the ground as rain and draw cool air down with it as a downdraft. When they work together, that warm updraft and cool downdraft create a storm cell. As this process continues, the cloud grows and we eventually get a large thunderstorm cloud. This thunderstorm cloud is now ready to diversify into other storms like tropical cyclones and tornadoes. But this can't happen unless the air in the cloud starts spinning horizontally. If this occurs over the tropical ocean, this is called a tropical depression. This is like a baby tropical cyclone with wind speeds less than 39 miles per hour. If it starts spinning even faster and has wind speeds between 40 to 73 miles per hour, we have a tropical storm. If the storm grows even larger over the tropical ocean and has wind speeds above 74 miles per hour, we have our full-grown hurricane, typhoon, or cyclone, depending on where that storm is found. If the spinning occurs over land, we now have our mesocyclone. If the mesocyclone gets spinning fast enough that the cloud starts reaching toward the ground like a long arm, this is the beginning of a tornado. If the cloud's arm reaches all the way to the ground and grabs hold, this is now officially a tornado, ready to suck up everything in its path like a giant vacuum cleaner hose. No matter what type of cyclone you're talking about, there's always a great potential for damage to human life, livelihoods, and the environment. Tornadoes have indiscriminate paths, and the cyclones themselves can be several miles wide. They take no prisoners as they skate along the ground, destroying everything they come in contact with. Tropical cyclones not only bring strong winds, but also torrential rains and storm surges. A storm surge is like a giant wall of water that the storm pushes along the ocean as it travels, and it can literally wash away large buildings and shorelines when it hits land. The heavy rains from tropical cyclones can also cause flooding. The damage in New Orleans from Hurricane Katrina wasn't so much from the storm itself as it was from the levees failing. All that water had built up behind them, and at some point they just couldn't hold it back any longer. Cyclone can be a confusing word because it refers to many different types of storms. However, all cyclones are spinning storms that rotate around a low-pressure center. This means that hurricanes, typhoons, and tornadoes are all types of cyclones. What makes each cyclone unique is its location. Tornadoes occur over land, polar cyclones occur in polar regions, and tropical cyclones over tropical oceans. What's not unique is how these storms develop. Warm air rises, and it likes to take water along with it. When that warm, moist air rises quickly, we get an updraft. However, cool air isn't as fond of water as warm air, so the water in the air gets pushed out as the warm, rising air cools. This condensation forms a cloud in the sky, and if enough condensation builds up, it falls back to the ground. As the rain falls, cool air is drawn down with it as a downdraft. When the updraft and downdraft team up, they form a thunderstorm cloud, which is like a diving board for cyclone formation. If the air in the cloud starts to spin horizontally, we have the beginnings of a cyclone. On land, this is a mesocyclone, and over tropical oceans, this is a tropical depression. No matter what type of cyclone develops, they all have the power to inflict great damage. Tropical cyclones and tornadoes have literally wiped out cities and shorelines. Even tropical storms, which are a midway point between a tropical depression and a tropical cyclone, can bring heavy rains, strong winds, storm surges, and floods. These dangerous conditions may take lives, destroy livelihoods, and even reshape landscapes as they spin along their paths.
Every day, we all experience different kinds of weather. Have you ever noticed that there is a pattern to those changes in weather? Depending on where you live, there could be different reasons for that. But if you live anywhere in the mid-latitudes, there is a specific weather phenomenon that is the primary cause of your weather changes. This phenomenon is the mid-latitude cyclone, and the result of its formation and decline greatly affects mid-latitude weather. So how does this happen? The polar front theory of cyclogenesis was developed in the early 1900s to explain the formation of mid-latitude cyclones. But what is a mid-latitude cyclone, and why is it important? A mid-latitude cyclone is a large-scale, low-pressure system that travels eastward around the planet between 30 and 70 degrees latitude. It is crucial to day-to-day weather changes and to bringing rain and storms to much of the planet. The polar front is the boundary between the cold winds from the poles and the warm winds from closer to the equator. The cold winds blow from the east between 60 and 90 degrees latitude and are called the polar easterlies. The warm winds blow from the west between 60 and 30 degrees latitude and are called the westerlies. These winds cause mid-latitude cyclones. Cyclogenesis is when a mid-latitude cyclone goes from origin to maturity to dissipation in a series of stages. It occurs when the cold air blowing down from the poles meets warm air blowing up in the mid-latitudes. These winds of different temperatures meet at the polar front in the mid-latitudes. Cold polar air blows from the east, and warm tropical air blows from the west. Normally, the winds blow right past each other in a straight line at the polar front. This is known as the stationary front stage. However, certain conditions cause the straight, smooth polar front to develop a buckle or wave shape, usually where there is a sharp temperature difference. These conditions include the air passing by mountains or other irregularities in the landscape, or the air passing over a temperature contrast between ocean and land or over ocean currents. This is known as the wave stage. The wave deepens and causes a low-pressure area. The warm air from the tropics and cold air from the poles begins to flow counterclockwise around the low pressure, forming a cyclone. This is the open stage or mature stage of cyclogenesis. During the mature stage, a very distinct cold front forms at the front edge of the cold polar air. At the cold front, heavy precipitation and cloud formation occur. Also, a well-formed warm front develops at the front edge of the warm mid-latitude air. Light precipitation and cloud development form at the warm front. During this time, there is a sector of warm air wedged between cold air on either side. The mature stage will not last forever, though, mainly because the cold front and air behind it is moving faster than the warm air. Eventually, the cold front catches up to the warm front to begin the partially occluded stage. Occlusion is when the cold front meets the warm front, pinching off the sector of warm air. Because the cold air is denser than warm air, cold air sinks below the warm air, forcing it higher into the atmosphere. This continues until the warm air is pushed completely off of the surface of Earth, and a short period of heavy precipitation follows. This burst of activity is the occluded stage. Finally, storm activity slows down and weakens, and this is the dissipated stage. Eventually, the cyclone gets completely cut off from the polar front, and the life cycle of the cyclone ends. There are several characteristics of cyclone movement, occurrence, and distribution that are pretty consistent. Cyclones, or storms, move across the mid-latitudes from west to east at about 20 to 30 miles per hour. This means a storm can cross the United States in about 3 or 4 days. However, this does vary with the seasons, since cyclones tend to move faster in winter than in summer. Even though they move west to east, their routes are not in a straight line and tend to be a little erratic. The counterclockwise movement of cyclones affects wind direction for a large area. Wind all around the center of the storm converges into its center of low pressure. This means that as it passes over you, wind switches direction pretty suddenly. Also, the movement of the cold and warm fronts associated with the cyclone determine what type of precipitation you'll be getting. The warm front advances slowly, and it brings clouds and light rain. So for a longer period of time, that's the weather you'll have as it passes by. The cold front moves faster and brings heavy rains. So the more severe part of the storm moves by fairly quickly. The location and frequency of cyclones across the planet are also pretty consistent. At any given time, there are 6 to 15 cyclones happening at one time in the northern hemisphere, and just as many in the southern hemisphere. Their positions are scattered and irregular, but all happen within the mid-latitudes. During the wintertime, the temperature difference between polar and tropical winds is greater, so the cyclones form more frequently, are more developed, and move more quickly. The greater temperature difference just intensifies the process of cyclogenesis and makes it happen more often and faster. There is also a difference between northern and southern hemispheres. The wind blowing from Antarctica is colder all year long compared to the wind from the North Pole, so cyclones in the southern hemisphere happen as often in the summer as in the winter. They also tend to develop a little closer to the South Pole, so they form mostly over water. Even though they are more numerous and stronger, they have less of an effect on people than northern hemisphere cyclones do. Cyclones in the southern hemisphere rotate clockwise. The polar front theory of cyclogenesis explains the formation of mid-latitude cyclones. A mid-latitude cyclone is a large-scale, low-pressure system that forms at the polar front, where cold polar air and warm mid-latitude air collide. Cyclogenesis is when a mid-latitude cyclone goes from origin to maturity to dissipation in a series of stages. Generally, the cold and warm winds just blow past each other in the stationary front stage. But under certain conditions, a wave forms in the polar front that leads to the wave stage. The wave deepens into a low-pressure center. Winds begin to rotate counterclockwise, distinct cold and warm fronts develop, and a sector of warm air gets wedged between cold air. This is the mature stage. The cold front is the fastest moving part of the storm, and it eventually catches up to the warm front to begin the partially occluded stage. Occlusion is when the cold front meets the warm front, pinching off the sector of warm air. Then all the warm air is forced upward as the fronts meet completely in the occluded stage. The storm finally weakens in the dissipated stage, and the cyclone gets cut off from the polar front and dies. There are a number of characteristics associated with cyclones. They move from west to east through the mid-latitudes, and the storms are very big. The counterclockwise rotation affects wind direction over large areas, and the cold and warm fronts bring rain and clouds. At any time, there are several cyclones happening at once in both the northern and southern hemispheres. In the winter, the cyclones move faster and form more quickly because the temperature contrast is greater. In the southern hemisphere, the storms are mostly over ocean, so they affect people less than in the northern hemisphere.
You know those really nice days when there isn't a cloud in the sky? Those kinds of days feel sunny and warm outside with no wind blowing, and all you want to do is spend your day outside walking your dog or going to the park. You experience this type of weather when high pressure or an anticyclone has set up over the area where you live. But what causes this type of weather to develop? Because the atmosphere is constantly moving and mixing, it experiences differences in temperature and composition. These result in changes in pressure. Atmospheric pressure can be thought of as the weight of the air piled above. The higher the air is piled up, the greater the pressure. An anticyclone, or high-pressure area, is associated with sinking air that results in fair and dry weather. It is caused by several things working together, including wind, the pressure gradient force, the Coriolis effect, and friction. The first factor, wind, is when air moves horizontally from place to place. Where air moves to is caused by differences in atmospheric pressure. A good way to understand wind flow is to picture air pressure on a map. Areas of high pressure are like mountains, and areas of low pressure are like valleys. The air movement, or wind, goes from high pressure to low pressure. So if you think about it like elevation, the wind blows from the high pressure at the top of the mountain to the low pressure in the valley. This is what creates wind, and the mechanism that causes it to happen is the second factor in the development of anticyclones. This factor is called the pressure gradient force, or the movement of air from high to low pressure. This is what makes air move from the center of an anticyclone outward. Wind high above the surface of the Earth has nothing in its way to prevent it from moving in a straight line, except for what's known as the Coriolis effect. Because Earth rotates from west to east, any object that is moving along in a straight line appears to deflect to the right in the northern hemisphere. For example, if you're standing at the North Pole and fire a rocket toward Texas, it would actually land to the west of Texas, maybe in California. That is because while the rocket was in the air, the Earth rotated beneath it. From your perspective at the North Pole, it would look like your rocket drifted to the right in an arced pathway. Any object in the northern hemisphere appears to go in an arc to the right. The southern hemisphere is a mirror of the north, and movements are opposite, so everything appears to veer to the left. The Coriolis effect is what causes air to spin to the right around a high-pressure center in the northern hemisphere. The final factor in the formation of an anticyclone is friction. In the lower atmosphere, wind drags across the ground, and the influence of the Coriolis effect is reduced. This means that the air on the surface doesn't arc to the right as much. The result is that the wind ends up flowing in a clockwise circle around an anticyclone. Now that you know how anticyclones develop, how exactly do they affect the weather? The weather under an anticyclone is almost always clear, warm, and calm. There are rarely any clouds or rain, it is sunny, and there is very little wind. Both in winter and summer this is the case. Sunny, warm, nice days happen when an anticyclone or high-pressure system moves into your area. The reason for this is that air has piled up high in the atmosphere, and the weight of this air is pushing down toward the surface, or sinking. Clouds and thunderstorms that lead to unfavorable weather form when air is able to rise from the ground to above the freezing level in the atmosphere. The sinking of air in an anticyclone prevents this from happening, and nice weather prevails. An anticyclone can bring you nice weather for a few days or even weeks until, eventually, a cold front overcomes it and moves in with clouds or rain. An anticyclone is a high-pressure area that produces warm, sunny weather. 4 factors together result in anticyclone development. The first is wind, or the horizontal movement of air. Second is the pressure gradient force, or the movement of air from high to low pressure. Third is the Coriolis effect. This phenomenon occurs because of Earth's rotation. Anytime an object or air is moving above the surface, Earth rotates beneath it, making it appear to arc to the right in the northern hemisphere instead of going in a straight line. The fourth is friction. As wind drags across the surface, it lessens the Coriolis effect and causes an anticyclone to rotate clockwise. The importance of anticyclones is how they affect the weather. With high pressure, air has piled up high in the atmosphere and is pushing or sinking down toward the surface. This stops air from rising to create clouds or storms, and it creates warm, sunny weather with no clouds or wind. In March of 1993, a huge mid-latitude cyclone brought intense cold air and severe thunderstorms to the United States. These storms and cold air drastically affected the East Coast and brought snow as far south as the Florida Panhandle. Many southern states received as much as 10 inches of snow, and dangerous flooding and tornadoes killed hundreds in northwest Florida. Almost half the population of the U.S. was affected by this massive storm, and it became known as the 93 Superstorm. So, how does weather this devastating develop? A mid-latitude cyclone is a large-scale, low-pressure system that travels eastward around the planet between 30 and 60 degrees latitude. In this lesson, you will learn how it is affected by air movement patterns of Rossby waves high in the atmosphere, including divergence and meridional flow. Mid-latitude cyclones are crucial to day-to-day weather changes and to bringing rain and storms to much of the planet. The polar front is the boundary between the cold winds from the poles and the warm winds from the mid-latitudes. When these winds meet at the polar front, they cause mid-latitude cyclones at the surface of the planet. The warm mid-latitude winds at the surface tend to blow from west to east but are slowed down by friction. However, high up in the atmosphere, there is almost no friction from the surface, so winds blow very persistently from west to east. In fact, near the polar front, there is an area of very fast wind speed high in the atmosphere that is called the polar front jet stream. The pattern of the flow of this jet stream is what is important in affecting our weather, and one pattern that is particularly important is called a Rossby wave. Sometimes the polar front jet stream flows in a straight path from west to east around the planet, and this is called zonal flow. But the jet stream is not always in a zonal flow. Instead, there are often changes in latitude that are up and down wave-like movements in the jet stream. This is called meridional flow. So it wanders quite a bit north and south, and the waves can be quite large, dipping far down into lower latitudes. These large waves in the jet stream are called Rossby waves, and they are a product of meridional flow. At any time, there are usually 3 to 6 Rossby waves within the jet stream in each hemisphere. Since the jet stream separates cold polar air from warm mid-latitude air, each oscillation of a Rossby wave moves cold air down toward the equator and warm air up toward the poles. This brings severe, frequent weather changes to the mid-latitudes. In the United States, a big Rossby wave can bring down enough cold air for a severe cold spell that covers half the country. So, how does this type of airflow high up in the atmosphere affect the weather we have here on the surface? Rossby waves in the polar front jet stream have a very real effect on major weather disturbances in the mid-latitudes. If you remember, the jet stream is high up in the atmosphere. But when Rossby waves develop, they can be such a powerful phenomenon that surface weather is drastically affected. As a Rossby wave dips down, it creates a trough. To the east of the trough, or downstream in the flow of the jet stream, divergence occurs high in the atmosphere at the jet stream. Divergence just means that airflow is spreading away from the jet stream, and as it does, it pulls air upward from the surface, creating instability. It is sort of like all the air pulls away, or diverts, from the jet stream, leaving a sort of hole. This hole must be filled, so air from the surface is pulled upward to do that. This leads to instability and the development of a mid-latitude cyclone that forms a large storm system on the surface. But how exactly does divergence and airflow in Rossby waves influence a cyclone from beginning to end? The polar front jet stream and Rossby waves directly influence the life cycle, development, and trajectory that a mid-latitude cyclone goes through. At the polar front and the jet stream, winds blow right past each other in a straight line during zonal flow. Cold polar air and warm mid-latitude air are separated and flowing right past each other. This is the beginning of the formation of a mid-latitude cyclone. However, certain conditions cause the straight, smooth polar front to develop a kink or wave at the surface, usually where there is a sharp temperature difference. While that is happening at the surface, in the upper atmosphere, winds are diverging in the Rossby waves to the east of a trough. Both factors combined lead to further development of the mid-latitude cyclone. The wave or kink at the surface deepens and causes a low-pressure area. The warm air from the tropics and the cold air from the poles begins to flow counterclockwise around the low pressure, forming a cyclone. This starts the mature stage of cyclone development. During this mature stage, a very distinct cold front forms at the front edge of the cold polar air where there is heavy precipitation and cloud formation. Also, a well-formed warm front develops at the front edge of the warm mid-latitude air that leads to light precipitation and cloud development. During this time, there is a sector of warm air wedged between cold air on either side. The mature stage will not last forever, though, mainly because the cold front and air behind it is moving faster than the warm air. While the cyclone is in full development, the entire storm, including the cold and warm fronts, are moving to the northeast along the path of the jet stream. Eventually, the faster-moving cold front catches up to the warm front, pinching off the sector of warm air. This continues until the warm air is pushed completely off of the surface of Earth, and a short period of heavy precipitation follows. Finally, storm activity slows down and dissipates. Eventually, the cyclone gets completely cut off from the polar front, and the life cycle of the cyclone ends. From beginning to end, the life cycle of the cyclone is driven by the divergence of air at the jet stream in the upper atmosphere. The path that the storm follows, including the cold and warm fronts, is to the northeast in the direction that the jet stream is flowing. A mid-latitude cyclone is a large-scale, low-pressure system that is an important phenomenon that brings storms to much of the planet. The polar front is the boundary between the cold winds from the poles and the warm winds from the mid-latitudes, and is where mid-latitude cyclones form. High up in the atmosphere, winds blow very persistently from west to east in an area of very fast wind speed that is called the polar front jet stream. When the jet stream flows in a straight path from west to east around the planet, it is called zonal flow. When airflow in the jet stream changes in latitude in up and down wave-like movements, it is called meridional flow. These waves in the jet stream are called Rossby waves, and they move cold air down toward the equator and warm air up toward the poles. As a Rossby wave dips down, it creates a trough. To the east of the trough, divergence, or airflow spreading away from the jet stream, occurs. This leads to the formation of a mid-latitude cyclone. In the first stage of the cyclone, cold polar air and warm mid-latitude air are separated and flow right past each other. Conditions cause the polar front to develop a kink or wave at the surface while air is diverging from the jet stream, and these lead to advancement of cyclone formation. The wave deepens and causes a low-pressure area where air begins to flow counterclockwise around that low pressure to form a cyclone. This starts the mature stage of cyclone development. Then, a cold front forms at the front edge of the cold polar air, and a warm front develops at the front edge of the warm mid-latitude air. During this mature stage, the entire storm, including the cold and warm fronts, are moving to the northeast along the path of the jet stream. Then the cold front catches the warm front, forcing all warm air up into the atmosphere and ending the life of the cyclone. From begin to end, the life cycle of the cyclone is driven by the divergence of air at the jet stream in the upper atmosphere.
Have you ever seen lightning, then counted until you heard the thunder to see how far away a storm is? This is not just a game for children to play. It's actually a very real way to estimate the distance. Lightning travels at the speed of light, but thunder travels at the much slower speed of sound. So, a 5-second delay between lightning and thunder means that a storm is about 1 mile away. This is actually very handy information because lightning is quite a danger to humans. There are over 8.5 million lightning bolts a day that are 100,000 times the power we use in our houses, so it is a very real danger when thunderstorms are around. But what exactly is lightning, and how is it formed? Lightning is a very quick electrical discharge that occurs between a cloud and the ground, between two clouds, or within a cloud. It can be seen as a bright flash and is followed by the sound of thunder. Lightning is usually associated with thunderstorms. To understand how lightning forms in a storm, you must first understand how a thunderstorm develops. A thunderstorm is a localized storm that has lightning and thunder and is short-lived. In the beginning of a storm's development, air rises in updrafts above the freezing level in the atmosphere. The water droplets in the cloud freeze, get heavier, and begin to fall, creating a downdraft. The droplets leave the bottom of the storm as heavy precipitation. This is the part of the storm when severe weather can occur. During this stage, both updrafts and downdrafts occur, which are what start the development of lightning. So this stage is when lightning and thunder may occur. Eventually, the updraft stops and only the downdraft remains. The storm weakens and finally ends. Lightning is a bit of a mystery because the exact way electricity develops in a storm is not very well understood by scientists. But what we do know is that the way a thunderstorm develops causes electrical charges to be separated. This is known as charge separation. The updraft of air in a storm carries positively charged water droplets with it. The downdraft of precipitation carries negatively charged water drops downward to the bottom of the cloud. The negative charges on the bottom attract positive charges on Earth's surface directly below the thunderstorm. The difference in charges on the bottom of the cloud and on the ground grows stronger and stronger until there must finally be a release. A finger of negative electricity known as a leader shoots down from the cloud searching for a way to meet the positive charges on the ground. Usually, the leader can't make a connection the first time, so this happens repeatedly until a finger of positive electricity shoots up from the ground to meet the leader. Once this occurs, a conduit or tunnel for electricity to pass from cloud to the ground opens up. This is when the lightning stroke occurs, and a surge of electricity strikes downward and is visible for us to see. This may happen several times in rapid succession until all negative charges are gone from the bottom of the cloud. These are known as flashes, and they happen so quickly that we can't see each individual stroke. Instead, the lightning appears to flicker. The kind of lightning just discussed is called cloud to ground. It only makes up about 20% of lightning in a storm, but it is the most destructive. Some other categories of lightning that occur within a storm are intra-cloud lightning within the same cloud, and cloud to cloud between two clouds. The separation of the charges in the same cloud or different clouds forms lightning in storms in the same way as cloud to ground, only the discharge doesn't go to the ground. There are also other more unique types of lightning that occur in storms. Forked lightning happens when the leader breaks into several branches, making the lightning look like a fork. Sheet lightning is a bolt within a cloud that can't be seen by itself and instead lights up the whole cloud. Heat lightning happens when the cloud is so far away that we can only see a flash and not see a bolt or hear thunder. Ribbon lightning forms when strong wind accompanies the storm, causing a very wide lightning bolt to form. Types of lightning that occur at very high altitudes at the top of storms are called sprites, and they look like giant red jellyfish. Also, blue jets form when charged particles are thrown from the top of a storm, and they look like fountains. Many other types of lightning also occur, and not all are caused by the formation of a thunderstorm, but all are caused by the same basic mechanism as lightning in a thunderstorm. For example, St. Elmo's fire is a type of lightning. It occurs around ship masts or airplane wings. The wing of a plane may become negatively charged. If it passes through a positively charged cloud, and the charges are strong enough, a discharge of electricity can occur. It appears as a blue glow and has a buzzing sound. Ball lightning appears as a spherical, electrically charged ball of air about the size of a basketball, but its formation is not completely understood. Air discharge lightning develops in very dry climates. Lightning can even occur in a volcanic eruption. The different sized particles of ash in the eruption, accompanied by friction, cause positive and negative charges to develop, which can lead to lightning. Lightning is a strong and fast discharge of electricity from a thunderstorm to the ground or within the cloud. A thunderstorm is a localized storm that has lightning and thunder and is short-lived, and it develops in stages. During a thunderstorm, negative charges are brought to the bottom of the cloud, and this is known as charge separation, which leads to lightning. As lightning forms, a finger of negative charges shoots down from the cloud, known as a leader. The leader opens up a tunnel from the cloud to the ground, and a lightning stroke occurs where a surge of electricity strikes downward that is visible to us. This may happen several times in rapid succession and appears to us as flashes or flickering. There are specific categories of lightning associated with storms: intra-cloud, cloud to cloud, forked, sheet, heat, ribbon, sprites, blue jets. Also, there are many other types of lightning that are not associated with storms: St. Elmo's fire, ball lightning, air discharge lightning.
Did you know that Florida has more thunderstorms per year than any other state in the U.S.? Or that if you're male, you are 4.6 times more likely to get struck by lightning than if you are female? Or that sound travels 1 mile in 5 seconds, so if you hear a lightning strike, you can figure out how far away it was by counting the seconds until you hear the thunderclap? Thunderstorms are amazing and interesting events. Thunderstorms can occur almost anywhere and are the beginnings of some other dangerous storms like hurricanes and tornadoes. But just what is a thunderstorm and how does it form? A thunderstorm is a storm with lightning and thunder. They are caused by an updraft, which occurs when warm, moist air rises vertically into the atmosphere. The updraft creates a cumulus cloud, which will eventually be the thunderstorm cloud. Updrafts can occur anywhere warm, wet air rises quickly, which is why most people, no matter where they live, have experienced a thunderstorm at some point in their life. However, some places, like Florida, are more prone to thunderstorms because the conditions that create thunderstorms are more common. A warm updraft is just the beginning of a thunderstorm, though. Once the air rises into the atmosphere, it begins to cool. Cool air can't hold as much water as warm air, so as the air cools, the water in the air gets kicked out as condensation, and may eventually fall back to the ground as rain. In order for this to happen, though, the cumulus cloud has to grow very tall. Think about it this way. If you're playing a game of Red Rover and try to break through the human wall on the other side by yourself, you may not be very successful because there's only one of you. But if you get all of your friends to crash into that line of people with you, you'll have greater success because you are a large group with a greater force. The same is true for water in the thunderstorm cloud. By itself, that single water droplet is not heavy enough to fall back to the ground as rain. But if the cloud is tall enough, that one little droplet will pick up other droplets with it and eventually grow into a large enough water droplet to break through and fall back to Earth. Just like the updraft was warm air rising upward in the atmosphere, a downdraft is cool air sinking back to the ground. Downdrafts are created by the falling water droplets because they don't just drag other water down with them as they fall, they drag cooler air down with them as well. The combined warm updraft and cool downdraft create a storm cell. As the process of warm air rising and cool air sinking continues, the cloud grows vertically into the shape of an anvil, which is called an anvil head cloud. This is now a full-fledged thunderstorm cloud, ready to storm away. As you're probably aware, thunderstorm clouds can produce a lot of thunder and lightning. What you may not know is that these are both produced from the same event. Lightning is what you see, thunder is what you hear. They appear not to occur at the same time because light travels faster than sound, so the image of the lightning reaches your eyes before the sound it creates reaches your ears. Here's how it works. As the water droplets in the cloud fall downward, they bump into each other, which gives the cloud an electrical charge. The charge, however, is not uniform within the cloud. There's a negative charge in the warm area and a positive charge in the cool areas. Eventually, electricity builds up and electrical energy is released, flowing to the points of opposite charge because opposites attract. Much of this occurs within the cloud, but sometimes it leaves the cloud and heads toward the ground because the ground holds an opposite charge to the lower part of the cloud. When this happens, we get lightning. If you've ever touched a light bulb that has been on for a while, you know that light produces a lot of energy as heat. When the electrical energy leaves the cloud as lightning, it also releases energy as heat, which warms the air around it. When things heat up, they expand, and as the air expands, it releases a giant sonic boom, the thunder you hear. So you can see that while you may have lightning without thunder, you certainly won't get thunder without a lightning strike. Most of us are familiar with thunderstorms, which are storms that produce thunder and lightning. These can pop up out of nowhere or warn us that they're coming with a dark cloud-filled sky. Thunderstorms are common, but are also the basis of many more dangerous storms, such as tornadoes and hurricanes. Thunderstorms begin with a thunderstorm cloud, which develops from an updraft of warm, moist air rising vertically into the atmosphere. As the air rises, it cools, and as it cools, it pushes out the water it holds, creating a cumulus cloud full of condensation. If the water droplets in the cloud have far enough to fall, they drag along other water droplets as well as cool air. If the water droplets collect enough backup, they fall back to the ground as rain. The cool air falling back to the ground with it is called a downdraft. When an updraft and a downdraft work together, they create a storm cell, which is the fully developed thunderstorm cloud. Thunderstorms create a lot of thunder and lightning, which happens because the water droplets bump into each other and create electrical differences in the cloud. If this electricity builds up enough, it releases electrical energy, usually within the cloud itself. Sometimes, though, it may leave the cloud and head toward the ground. When this happens, the lightning cuts through the air like a knife, heating it and causing it to expand. The thunder you hear is the sonic boom from the air cracking. While thunder and lightning do come from the same event, the reason you see lightning before hearing thunder is because light travels faster than sound. Knowing this will also help you calculate the distance of the lightning strike, but you may want to figure this out indoors so you don't get caught in the rain.
Have you ever experienced a perfect summer day when suddenly, in the late afternoon, the sky gets dark out of nowhere? Before you know it, a cloud forms and a storm develops. It starts pouring rain and lightning, but only a few minutes later, the rain turns to drizzle. Soon after that, the sky is completely clear again. This is a common occurrence, and it's a special type of storm. It's called an air mass thunderstorm, and it is a non-severe storm that forms where moist and unstable conditions exist in the atmosphere. Air mass thunderstorms are considered garden variety or ordinary, and there are many things about them that are different from other storms. They are associated with warm, moist, unstable air masses, hence the name. They are also considered to be single-cell storms. That just means that they are isolated, or they are just one storm rather than a whole line of thunderstorms. The air mass thunderstorm is usually caused by solar radiation or the heating of the earth by the sun. This is why they are likely to happen in the late afternoon when we have the hottest temperatures of the day. The result is a storm that is weak rather than severe. It usually has a brief period of heavy rain, some lightning, and possibly small hail. They also move slowly and last only an hour or less. Because they tend to pop up suddenly, they are also hard to forecast. They are most common in the tropics and mid-latitudes in the summer. For example, they are extremely common in Florida and other Gulf Coast states. So how does an air mass thunderstorm develop? There are 3 stages to the life cycle of an air mass thunderstorm. But first, there are a few conditions that must be in place for the process to begin. There needs to be vertical air motion, humidity, and instability. In the case of an air mass thunderstorm, it usually starts due to the heating of the ground by the sun. Since heat rises, this begins upward vertical air motion. The heating and vertical motion cause an updraft of air that begins the storm's formation. The first stage is called the cumulus stage. Air rises in updrafts above the freezing level in the atmosphere. The water droplets in the cloud freeze and begin to fall, creating a downdraft. The air and droplets leave the bottom of the storm as heavy precipitation, and this begins the mature stage of the thunderstorm. During this stage, both updrafts and downdrafts occur, and the storm continues to grow. This is when the storm is most active, when the rain, wind, hail, lightning, and thunder may occur. Eventually, the updraft stops, and only the downdraft remains. This is when the final stage, the dissipating stage, begins. The storm continues to lighten up until it finally ends. To review, an air mass thunderstorm is a special kind of storm that occurs when the air is humid, warm, and unstable. They are single-cell or isolated storms that are caused by the heating of the ground from solar radiation. This is why they tend to happen during the hottest part of the day. These types of storms are usually weak and only last a brief period of time. They also move quite slowly and are hard to forecast. Air mass thunderstorms develop in 3 distinct stages. The first is the cumulus stage, where air starts to rise and form a cloud. The second is the mature stage, where precipitation falls and a downdraft occurs. This is the most active stage, when lightning, thunder, and hail may occur. Eventually, the updraft stops and the storm is in the final dissipating stage until it ends. At 6:23 p.m. on May 3, 1999, a mile-wide tornado touched down near Oklahoma City, right in the middle of rush hour. It traveled through Oklahoma City for 38 miles and stayed on the ground for 85 minutes. Wind speed of the storm was measured at 301 miles per hour, and this was the highest wind speed ever recorded on Earth. After it was over, 36 people had lost their lives, and $1 billion in damage had been done. The tornado was ranked an EF5, the most severe type of tornado, based on wind strength and amount of damage. EF5 tornadoes are strong enough to rip entire buildings off of their foundations. In this lesson, you will learn about the different types of severe storms that can cause this kind of destruction. The most basic type of thunderstorm is a single-cell or isolated thunderstorm. Generally, they form in unstable conditions where there is warm, humid air. Single cells develop when the sun warms the earth, causing air to rise. This is called an updraft, and it forces the air to rise above the freezing level of the atmosphere. The moisture in the air begins to freeze, and a storm cloud starts to form. The frozen particles of moisture start to join together, forming bigger and heavier particles. Once the particles become too heavy to stay in the air, they fall back to Earth as precipitation and bring air down with them. This falling air is called the downdraft. Rain, hail, and lightning can occur during a single-cell thunderstorm. Eventually, the downdraft overpowers the updraft and the storm ends. These types of storms only last for a short time and aren't usually severe. Severe thunderstorms form in a similar way, but under even more unstable conditions and with a more powerful mechanism to start the updraft. Severe thunderstorms usually develop along cold fronts and are often multi-cell storms. This just means that more than one storm forms along the front, so they are not isolated like single-cell storms. The key to their formation is strongly rising warm, humid air in an unstable environment. One way they develop is through convergence, which is when air streams flow into one another. For example, as a cold front moves east across the United States, it brings cold wind with it that is blowing down from the north. That front meets warm winds that are blowing up from the south. When the winds from the north and south meet each other, the air piles up. Then there is nowhere for the air to go but up. Air rising in this way can lead to the development of potentially severe thunderstorms. Another way that they can form is through orographic lifting, which happens when a cold front is forced to move from a low elevation to a higher elevation as it moves over terrain, usually mountains. This is why severe weather is common east of the Rocky Mountains. As cold fronts approach the Rockies, the air is forced to rise over them, causing storms to develop. However, there are a couple of types of multi-cell storms. Mesoscale convective complexes are groups of thunderstorms that form in a large cluster that can span an entire state. Usually they develop from a thunderstorm outbreak in the area of unstable air that is warm and humid. In the areas where they form, there is enough heat and moisture for air to rise and storms to form. Individual storms form in close vicinity of each other, and the storm cells feed off the outflow from other nearby storms. The result is a nearly circular, large cluster of storms that are often severe. They form in the late afternoon due to daytime heating and last into the night. But the most severe weather happens fairly early in storm development. The storms can travel great distances before they dissipate and last at least 6 hours. Another group of severe storm systems is called squall-line thunderstorms. Squall-line thunderstorms are a large number of single-cell storms arranged in a line. They are similar to mesoscale convective complexes in that they are a cluster of storms, but instead of a circular-shaped cluster, they form in a multi-cell linear cluster. Squall lines form along cold fronts or as far as 80 miles ahead of a cold front. They form in a similar way to mesoscale convective complexes. If the air at or in front of the cold front is unstable, humid, and warm, squall-line thunderstorms can develop. They usually have heavy precipitation, strong winds, small hail, and lightning. In some rare cases, tornadoes can develop. There are other severe storms that can be isolated. Supercell thunderstorms are large single-cell storms that can be very severe. Compared to other storms mentioned so far, these storms are the least common and can produce the most severe weather. They usually create a lot of heavy rain, strong wind, hail, and even tornadoes about 15% of the time. Supercells typically have a diameter of 12 to 30 miles and a lifespan of 2 to 4 hours. Supercells are different from other types of storms primarily because they have a rotation that leads to severe weather. There is a strong updraft, typically in the southwest part of the storm where the rotation occurs. This rotation is caused by differences in wind direction or speed around the storm, and the southwest area where it occurs is called a mesocyclone. This is the part of the storm where a tornado may develop. In this southwest region of the supercell, a hook shape called a hook echo often forms. The presence of the hook echo on a weather radar suggests that a mesocyclone is present and that a tornado is possible. If you see a hook echo on a storm that is headed in your direction, you might want to find shelter right away. The other thing that makes supercells so severe is how long they last. If you remember, thunderstorms end when the downdraft overcomes the updraft that is feeding the storm. Supercells are usually so large that the updrafts and downdrafts are far apart from each other, so it can take them a long time to fizzle out and die. Although there are several different types of severe thunderstorms, they all develop in a similar way. They develop where there is warm, humid, unstable air. The warm air rises above the freezing level, where ice crystals form, creating an updraft. The ice crystals get heavier as they clump together until they eventually fall, bringing cold air down with them. This is a downdraft, and once it develops, the storm is fully developed. This is when rain, hail, and lightning occur. If the updraft that starts storm formation is strong enough, storms can be severe. Convergence, or when air flows collide, and orographic lifting, as air moves over a mountain, are two common ways strong updrafts develop. A lot of time when a cold front is involved, more than one thunderstorm develops along the edge of it. These are called multi-cell thunderstorms. One type of multi-cell cluster is called a mesoscale convective complex. It develops when a cold front stalls and meets warm, moist air. It causes multiple storms to form in a state-sized cluster that is circular in shape. They develop in late afternoon, last for many hours, and travel long distances. Other multi-cell storms are called squall-line thunderstorms. These are similar to mesoscale convective complexes, except they form in a line, not a cluster, that is out ahead of a cold front. They usually have heavy rain and strong wind. Another type of severe storm that is not a multi-cell storm is called a supercell thunderstorm. Supercells are the most severe kind and cause strong wind, heavy rain, and tornadoes. They can be very large and last several hours. The difference between supercells and other severe storms is a rotation of winds within the storm called a mesocyclone. It is within a mesocyclone that tornadoes can develop. The mesocyclone shows up on a weather radar as a hook shape that is called a hook echo. The presence of a hook echo suggests a tornado might be developing.
Everyone knows what kind of damage a tornado can do, but did you know that there are other phenomena caused by thunderstorms that can be just as hazardous? Downbursts, microbursts, derechos, and haboobs are some of the dangerous phenomena that you'll be learning about in this lesson. While these things can occur with any type of severe thunderstorm, they most commonly occur in squall-line storms. Squall-line thunderstorms are a large number of thunderstorms arranged in a line. They form in this line at the edge of a cold front, or as far as 80 miles ahead of a cold front. If the air ahead of the cold front is unstable, humid, and warm, squall-line thunderstorms can develop. These conditions cause the air to rise and form clouds and precipitation, which leads to storm development. When the storms become fully developed, rain falls from the cloud, pulling air down with it. This is known as a downdraft, and it can be responsible for some very severe weather. Squall lines usually have heavy precipitation, strong winds, small hail, and lightning. They travel because they are pushed forward by winds in the upper atmosphere. Sometimes these winds are not the same speed along the whole line. If the winds driving the squall line are stronger along one portion of it, that part of the squall line will be pushed forward more quickly. This causes what's known as a bow echo to develop. A bow echo is an image that appears on a weather radar as an archer's bow. It reflects the shape that the squall line has taken due to different upper-level wind speeds. When a squall line takes the shape of a bow echo, the storms can be quite severe. There are a number of damaging phenomena that can occur in these cases. Sometimes the downdraft from the storm is so strong that it creates a downburst. A downburst is when the downdraft from the storm spreads out horizontally in all directions when it reaches the ground. The wind it creates can be as strong as 150 miles per hour and can cause damage similar to what a tornado can do. Downbursts may be just wind with no rain and are called dry downbursts. Sometimes the wind is accompanied by rain, and those are called wet downbursts. Downbursts are also different based on their size. Smaller downbursts that are less than 2.5 miles in extent are called microbursts. Microbursts are small, strong downbursts that are particularly violent. The winds can get up to 165 miles per hour in speed before reaching the surface and spreading out horizontally. Sometimes they only last a few seconds, but they can last for minutes at a time. The winds they create are strong enough to knock over trees, and they're particularly dangerous in the vicinity of airports as airplanes land and take off. They've even led to fatal plane crashes in the past. Another phenomenon associated with squall lines is a derecho. Derechos are straight-line winds associated with a downburst. They blow out in front of the squall line and are the strongest winds created by the downburst. This happens because the movement of the storms is already in that direction. Derechos can be as large as 200 miles wide and 1,000 miles long. They can last up to 12 hours or more and are associated with very strong straight-line winds. Derechos can knock over trees and power lines and cause rain and lightning to come from all directions. This can all happen very suddenly, so it is very dangerous to be caught outside in a derecho. A type of storm associated with a derecho is called a haboob. Haboobs are dust storms or sandstorms created by very strong winds. They were first noticed and named in the Sudan in Africa, but they can occur anywhere with a dry climate and loose sand or dirt. Some of the places they are common besides Africa are the Middle East and Australia. In North America, they occur in Arizona, New Mexico, and Texas. They usually develop like a derecho. The strong winds formed by the downburst blow sand or dirt up from the ground high into the air, creating a wall of dust that can be up to 60 miles wide. The winds may blow 20 to 60 miles per hour. Oftentimes, haboobs are different from typical storms in that no rain falls. This is because they occur over hot, dry areas, and the rain simply evaporates before it reaches the ground. Haboobs are very dangerous and can cause eye and lung damage. If you are ever in a haboob, you should seek shelter immediately. Squall-line thunderstorms are a line of storms that develop at the edge of a cold front or up to 80 miles ahead of a cold front. They are often associated with severe weather phenomena like downbursts, microbursts, derechos, and haboobs. The storms develop when the air is warm, humid, and unstable. The air rises to create a storm cloud and precipitation forms. When the precipitation falls to the ground, it pulls air down, creating what's known as a downdraft. If the downdraft is strong enough, it can cause severe weather phenomena. Squall lines travel because they're being pushed forward by winds in the upper atmosphere. If these winds are not the same speed along the squall line, part of it will be pushed forward more quickly. The result is a bow echo shape, which makes the squall line look like an archer's bow on a radar. A bow echo means that the storms may be quite severe with strong downdrafts, so damaging weather phenomena may occur. One of these is called a downburst. A downburst occurs when the downdraft from a storm spreads out horizontally in all directions when it reaches the ground. The wind it creates can be very strong and can cause damage like a tornado. A downburst that is small in size is called a microburst. A microburst is just a very strong downburst. The wind created by it is so strong that it can knock over trees and is a danger to airplanes. The winds created by squall lines are strongest out in front of the squall line. These winds along an entire squall line can cause a derecho. Derechos are straight-line winds associated with the downburst. Derechos can be very large and last for a long period of time. They can cause a lot of damage and be very dangerous. Another type of storm that is associated with a derecho is called a haboob. Haboobs are dust or sandstorms caused by straight-line winds. They occur in places that are very arid with loose dirt or sand, and they develop the same way a derecho does. The strong winds pick up loose dirt and sand, creating a wall of dust. The blowing sediment can be very dangerous to people.
The air gets thick and still. The wind stops. The sky turns green. And then you hear the siren warning you to take cover. If you ever lived in a place where tornadoes occur, this is a familiar sequence of events. Tornadoes are spinning funnel clouds produced by thunderstorm clouds. Acting like an arm that reaches down from the thunderstorm cloud, these violent rotating funnels extend from sky to ground. In fact, in order for a funnel cloud to be officially classified as a tornado, it has to be touching both the source cloud and the ground. Tornadoes are dangerous events. These storms can be several miles wide and have wind speeds as fast as 300 miles per hour. They have indiscriminate and unpredictable travel routes and act like giant vacuum cleaners picking up everything in their paths. Tornadoes form from thunderstorm clouds, which form when warm, wet air rises very quickly. As it rises, the cool air condenses into a large cumulus cloud. Like adding fuel to a fire, More rising warm air builds the cloud larger and larger. Eventually, the water in the cloud falls back to the ground as rain. As it falls, it brings some of that cooler air back down with it. The warm air rising is called an updraft because it's traveling upward, and the cool sinking air is called a downdraft since it's falling back down to the ground. When these two work together like this, they create a storm cell. Some thunderstorms stay like this, but some grow even larger and become supercells. But a tornado doesn't begin to form until the air starts to spin. Scientists are not exactly sure how this happens, but it seems that one way this is possible is when winds at different altitudes within the supercell travel at different speeds. You can try this at home and see how it works. Take a round object, like a ball, and put one hand on each side. Now move both hands forward at the same speed. The ball moves, but it doesn't spin. Now move both hands forward, but have one hand move faster than the other. The ball moves and spins. This is what scientists believe happens in the supercell that creates the spinning funnel cloud. And just like the rain brings down cool air as it heads toward the ground, it also brings down the funnel cloud and turns it into a tornado. Remember Dorothy and her poor dog Toto? They were ripped from Kansas in a wild tornado and taken far from home. While it's doubtful that you'd actually get taken to Oz if you were caught in a tornado, Kansas is in fact well known for its high frequency of this type of storm. So are other states in the area, such as Texas, Oklahoma, Nebraska, South Dakota, Missouri, and Iowa. Collectively, this area is known as Tornado Alley because tornadoes are so frequent, especially in the summer. Tornado Alley exists because the Great Plains get very hot in the summer. Updrafts are all too common, which as we now know creates thunderstorms and supercells. Florida is also well known for its frequent tornadoes for this very same reason. Florida has more thunderstorms than any other state in the country, and all that warm, moist air creates the perfect conditions for supercells and tornadoes to form. Tornadoes are very dangerous to study because if you get too close, they can suck you right up into the funnel, and the chances of you making it out alive are pretty slim. But tornadoes still need to be described and classified, so scientists use the damage on the ground as a measure of the storm's intensity. The Enhanced Fujita Scale is a rating for tornadoes based on the damage surveyed, and has been used to classify tornadoes in the U.S. since 2007 and in Canada since 2013. This scale is based on the original Fujita-Pearson scale, which was developed in 1971 by Tetsuya Fujita and Alan Pearson. There are 6 categories in the Enhanced Fujita Scale, EF0 to EF5, and EF stands for Enhanced Fujita. EF0 is the least damaging, while an EF5 tornado is something like the 2.5-mile-wide tornado that recently devastated Moore, Oklahoma. The EF scale lists wind speeds in its classifications, but these are really just very good estimates since, as mentioned before, it's difficult to get accurate data from tornadoes. Dorothy wasn't thrilled to be in Oz, but she should have been very happy that she made it out of the tornado alive. Tornadoes are dangerous spinning funnel clouds that form from thunderstorm clouds. This cloud extension acts like a giant vacuum cleaner arm, reaching down to the ground and sucking up everything in its path. Though scientists don't know for sure, they believe that one way a tornado develops is from different wind speeds at different altitudes in the thunderstorm cloud. Like your hands moving a ball faster on one side than the other, the cloud starts to spin, and as rain falls, it pushes the funnel down to the ground. Once it touches the ground, it's officially a tornado, ready to wreak havoc anywhere it goes. Tornadoes develop more often in certain places than others. Areas like Florida and the Great Plains of the U.S. are prime spots for tornadoes because their hot summer air rises quickly and causes large and frequent thunderstorms. The area over the Great Plains is also known as Tornado Alley because so many tornadoes occur here every year. Though difficult to study, scientists have come up with a way of classifying a tornado based on the damage done by the storm. The Enhanced Fujita Scale classifies tornadoes as EF0 through EF5, 0 being the weakest storm and 5 being something like the Moore, Oklahoma tornado. The EF scale also includes wind speeds in its classifications, but because we can't actually get inside a tornado to see what's going on, these are really just very good estimates.
Did you know that at any given moment in time, there are about 2,000 thunderstorms that exist on Earth? Considering storms can be very dangerous due to strong wind, lightning, tornadoes, and hail, that many thunderstorms at one time sounds pretty scary. But where are all these storms at? There are actually certain areas of the planet where you'll find lots of storms and other areas where there are hardly any. In this lesson, you'll learn about where and when all these thunderstorms occur. A thunderstorm is a localized storm that has lightning and thunder and is short-lived. Some factors that are necessary for thunderstorm development are vertical air movement, humidity, and instability. Air that has a lot of moisture in it must be forced high into the atmosphere for formation to begin, and this only happens when the weather is unstable. Several things can cause the necessary lifting of air that forms a storm. This lesson will look at the reasons for thunderstorms. One way that thunderstorms are created is through convection, or the vertical movement of air due to density differences. Warm air is less dense than cold air because as it absorbs heat, the molecules expand, making it less dense, or lighter than cold air. Think of a hot air balloon. As soon as the air inside the balloon is heated up more than the air around it, it starts floating upward. Convection can happen simply from the air near the ground being warmed up by the sun on a hot day. Convection plays a very important role in several places around the world that have warm climates. The latitudes near the equator are heated by the sun all year long, and this heating warms the surface of the planet. The warm ground, or ocean, heats the air above it, causing the air to rise and creating instability. The rising air leads to cloud formation, rainfall, and thunderstorm development. These latitudes are called the Intertropical Convergence Zone, or ITCZ. This is just an area near the equator where winds blowing from the north and south collide and rise upward to create instability and thunderstorms. Convection also causes thunderstorms and rain in some coastal areas where it leads to a shift in wind direction. These types of storms are known as monsoons, or a seasonal reversal of winds. Certain times of the year when heating at Earth's surface is the greatest, the terrain and specific conditions of land masses and oceans causes a persistent wind to blow from the ocean onto land. When coastal land is heated by the sun, wind blows from the ocean onto land where thunderstorms and heavy rain occur. There are two major monsoon systems. One is the South Asian monsoon in the Indian Ocean, and the other is the East Asia monsoon in the Pacific Ocean off the coast of China. There are also two minor monsoons. One is off the northern coast of Australia, and the other off the west coast of Africa. Monsoons are very important because over half the world's population live where they occur. Agriculture, meaning both food production and cash crops, depends on the rains. Without the monsoons, there could be widespread hunger problems or economic disasters. But there are other things that can cause air to rise and thunderstorms to develop. Thunderstorms are often produced when a cold front moves into an area. A cold front is the leading edge of a cold air mass. Because cold air is denser than warm air, when the two mix, the cold air stays close to the ground and pushes the warm air upward, causing thunderstorms to develop. These kinds of storms are often more severe than those caused by simple convection. We see these types of storms in places where warm and cold air mix, like in the mid-latitudes at about 30 to 60 degrees north or south latitude. Cold air blows down from the polar regions and warm air moves up from the tropics. It is only when the two meet that a cold front forms and storms develop, and this only happens in the mid-latitudes. Lastly, orographic lifting is another reason thunderstorms develop. If air moving across a landmass runs into a mountain, it has nowhere to go but up, forcing it to rise and causing thunderstorms. Imagine a cold front in the Pacific Ocean as it starts to move eastward across the United States. It moves along, bringing cold air with it until it reaches the Rocky Mountains. The tall mountains force the air high into the atmosphere, creating strong thunderstorms that move east across the Great Plains. That same phenomenon happens across the world, but it is a very localized occurrence. Thunderstorms form in this way in various places on Earth given these conditions. So far, you've learned where thunderstorms form frequently, but just as important is where they do not form. In the cold polar regions, thunderstorms rarely develop. There's just not enough moisture available, and the air is too cold to rise up and create the instability needed for storm development. Thunderstorms also occur more often over land than ocean. This is because the ground heats up much more quickly than water, so unstable rising air develops more over land. Finally, thunderstorms rarely occur over the deserts of the world. There are areas in each continent with constant high-pressure systems that prevent air from rising, so there is no instability. Plus, there is simply not enough moisture available for storm development in an arid desert. It is not only important to understand where thunderstorms form, but also when they do. Most importantly, they develop during the warm season of the year, which includes spring and summer. This is because the heating of the ground that leads to convection is greatest during warm months. So thunderstorm frequency varies depending on the hemisphere of Earth. When it is summer in the northern hemisphere and there are a lot of storms, it is winter in the southern hemisphere, where there are fewer storms. The opposite is true when it's winter in the northern hemisphere. This basic idea also affects precisely where the storms associated with the ITCZ near the equator are. The ITCZ shifts north or south by about 4 to 9 degrees of latitude depending on whether it is summer in the northern or southern hemisphere. The exception is the area around Africa, Asia, and Australia. There, the ITCZ shifts north as far as 25 degrees latitude during the northern hemisphere summer and creates the monsoons in Asia. Likewise, the ITCZ shifts as far south as 20 degrees latitude during the southern hemisphere summer, creating the African and Australian monsoon. A thunderstorm is a localized storm that has lightning and thunder and is short-lived. Several things can cause the necessary lifting of air that forms a storm. One is convection, or the vertical movement of air due to density differences that happens when the sun warms the surface of the earth. Also, a cold front forms when a cold air mass meets a warm air mass and pushes warm air upward. Lastly, orographic lifting, or air being forced upward because of a mountain, is another reason thunderstorms develop. Convection is important where the latitudes near the equator are heated by the sun all year long, and this area is called the Intertropical Convergence Zone, or ITCZ. It also causes thunderstorms and rain in some coastal areas where it leads to monsoons, or a seasonal reversal of winds. These happen in southern and eastern Asia, northern Australia, and western Africa, and are vital to the growth of crops. A cold front forms when cold polar air meets warm tropical air in the mid-latitudes, causing the lifting of warm air. Orographic lifting is a localized occurrence of storms that happens in places like the Rocky Mountains. Thunderstorms do not happen often in the polar regions and deserts because there is no moisture and rising of air, and they happen more over land than ocean. Thunderstorms happen most during the warm season of the year, which is opposite in the northern and southern hemispheres. The ITCZ shifts north of the equator during a northern hemisphere summer, creating monsoons in Asia, and it shifts south for the southern hemisphere summer to cause monsoons in Africa and Australia.
Even if you don't live in an area where hurricanes hit, you probably know what this image is. Hurricanes have caused a lot of devastation and destruction. You can likely name some recent hurricanes in the U.S. that did major damage and killed many people. Hurricane Katrina in 2005, Hurricane Irene in 2011, and Superstorm Sandy in 2012 are just a few. Hurricanes don't develop out of thin air, though. They begin as small storms that grow into larger, more dangerous ones. In its infancy, a hurricane starts as a tropical depression, which is a tropical spinning storm with wind speeds less than 39 miles an hour. As it grows into adolescence, the tropical depression develops into a tropical storm, which is a tropical spinning storm with wind speeds between 40 and 73 miles per hour. If it develops into a full adult storm, it becomes a hurricane, which is a tropical spinning storm with wind speeds above 74 miles per hour. After becoming a hurricane, the storm is further categorized as a 1, 2, 3, 4, or 5, increasing with danger and damage as the number increases. A Category 1 storm is the weakest hurricane with wind speeds of 74 to 95 miles per hour. On the opposite end, a Category 5 hurricane is a very strong storm. Category 5 hurricanes are very dangerous and do extensive damage. These storms have wind speeds of 155 miles per hour and more. Hurricane Andrew in 1992 was a Category 5 hurricane. It's important to remember that all hurricanes, even Category 1 hurricanes, can be dangerous and damaging. Hurricanes follow the path of least resistance, which is why they travel west across the Atlantic, and also why hurricanes rarely hit the west coast of the United States. The tropical winds blowing across the Atlantic blow from east to west, originating in Africa and then moving toward the Caribbean, Mexico, and southeast United States. There's also a reason why Oklahoma doesn't get hit by hurricanes, but Florida does. Hurricanes only develop over oceans and tend to dissipate once they hit land. Over the tropical ocean regions, warm, moist air rises straight upward, which creates thunderstorms. The water from the air cools and condenses, eventually falling back to land as heavy rain. However, if at some point on its way up the wind gets diverted horizontally, it begins to spiral. Once it gets spinning fast enough, we get that baby hurricane or tropical depression. As water from the ocean condenses in the air, it releases energy as heat. This is the very energy that will intensify and drive that baby storm into a tropical storm or a full-on hurricane. The condensation is also what produces all the rain that comes with a hurricane, and the heat released helps the storm itself rise in the air. As it rises, it sucks up surface air, which creates a low-pressure area in the center, also known as the eye of the hurricane. This is why if you're under the eye of the storm, the weather is eerily calm compared to the strong winds and heavy rain you would experience under other areas of the storm. A hurricane is like a giant self-sustaining heat engine. It keeps itself going unless the process is stopped. Condensation of the ocean water releases heat, which draws moist air from the ocean up into the eye of the storm. The moist air cools, which means there is more condensation, which leads to more heat being generated. This brings additional moist air up from the ocean, which cools and condenses, and you can see how this would continue on indefinitely. But we know that hurricanes don't continue on forever. They are eventually stopped. And this happens one of two ways. Either strong winds disrupt the flow of the storm while it's over the ocean, or the storm moves over land. Once it moves over land, the hurricane runs out of fuel because it runs out of water to perpetuate the cycle. The ocean is like a food source for a hurricane. It provides it with energy to grow big and strong. Once over land, though, the food source runs out and the storm is deprived of the energy it needs to keep going, essentially starving to death. Think about Oklahoma again. No hurricanes, right? This is because Oklahoma is too far inland. A hurricane needs a continuous supply of energy to soldier on, so once it hits land and quickly runs out of fuel, it has no hopes of making it much farther inland than the states that border the Gulf of Mexico and Atlantic Ocean. Hurricanes are like living storms. They start out as small baby storms, develop into adolescent ones, and may eventually become full-sized adult storms if they get enough energy to build up that large. Hurricanes develop from tropical winds over the ocean. Most of these winds move vertically and create thunderstorms. Sometimes, though, the winds get diverted horizontally and start spinning. If the spinning winds pick up enough energy, they may become tropical depressions, which have winds less than 39 miles per hour, or even tropical storms, which have winds between 40 and 73 miles per hour. If the winds of the storm are more than 74 miles per hour, this is a full-fledged hurricane. Once it becomes a hurricane, it's further classified by its wind speeds. A Category 1 hurricane is the least dangerous, with wind speeds of 74 to 95 miles per hour. As it grows, it may become a Category 2, 3, 4, or 5 hurricane. If it reaches Category 5, this is an extremely dangerous storm with wind speeds of 155 miles per hour or more. All of these storms get their energy from ocean water, which acts as a food source for the storm. Water condensation from the air releases heat, which provides energy. The condensation also creates all of the rain that generally comes with a hurricane. The heat that's produced from the condensation warms the air, which causes it to rise. As it rises, it sucks up surface level air and creates the low pressure eye of the storm. This cycle continues until the storm is disrupted by stronger external winds, or, as is more often the case, it hits land. Just like you would starve to death without food, the hurricane starves without water. There's no longer an energy source for it to continue its cycle, and it eventually dies out. Because hurricanes need water, you will not experience this type of storm if you don't live along the coast. Louisiana, Florida, South Carolina, and other southeastern states experience hurricanes because they provide a buffer wall that hurricanes hit, causing them to die out before they can go farther inland. States like Oklahoma, Colorado, and Tennessee are too far inland to experience the wrath of hurricanes because they're too far from the ocean, the ultimate source of energy for these dangerous storms.
On August 23, 2005, a tropical storm named Katrina moved northwest out of the Bahamas. It strengthened to a Category 1 hurricane before crossing over to Florida. The storm intensified over the warm waters of the Gulf of Mexico and moved north. It continued to grow stronger for a couple of days until it became a Category 5 hurricane, the most severe and devastating kind. Wind speeds were over 170 miles per hour. It hit the Gulf Coast on August 29th near New Orleans, Louisiana. They received over 15 inches of rain in some places, and Katrina produced at least 2 tornadoes. The most devastating part of the storm, however, was the massive storm surge, or water pulled on shore by the hurricane. As much as 28 feet of water covered the city, and thousands of people were trapped in the floods. Loss of life in the tragedy is unknown, but it is thought to be over 1,200 people. Tens of thousands of survivors had to leave their homes. Despite the tragedy that Hurricane Katrina was, it could have been much worse if hurricane forecasting and warning systems were not as advanced as they are. In this lesson, you will learn how a hurricane develops and how scientists use this information to forecast and warn people in time to save lives. Hurricanes are very intense, low-pressure disturbances or storms that have a very strong wind speed. They develop in the middle of the ocean in the warm water tropics near the equator. The moisture and warm temperature of the water create an unstable environment that allows air to rise. The rising air creates low pressure that can develop into a large storm that we know as a hurricane. As air rises within the disturbance, it moves to a higher and cooler part of the atmosphere. When the air is cooled, condensation allows water vapor to form, and this moisture causes clouds to develop and precipitation to fall. This starts a cycle that powers the storm by allowing more air to rise faster, and the whole disturbance becomes more unstable. As the storm becomes more unstable, it begins to pull in more and more warm, moist air. It is this process that causes a minor disturbance to become a full-blown hurricane. But there are many things about hurricanes that make them quite different from other types of storms, starting with their size. Hurricanes can be very large. They are often 300 to 400 miles in diameter, but they can be as big as 600 miles across. That is as big as 2 or 3 states. Because they are so big and powerful, it is very important to have an accurate forecasting and warning system to save lives. Even though hurricanes are large, destructive storms, they start as a small disturbance in the ocean. Locating and tracking these small disturbances is the key to accurate forecasting. An easterly wave, or a very weak low-pressure system that forms near the equator in tropical and warm weather, is often how a hurricane begins to develop. In the northern hemisphere, most easterly waves form over Africa and move across the Atlantic Ocean. Almost all of them just die out, but a few get stronger and stronger until they become hurricanes. If conditions are just right, an easterly wave will form rotating winds. If the wind speeds become greater than 74 miles per hour, the storm can officially be called a hurricane. Because hurricanes can be deadly and destructive due to high winds, torrential rain, and severe flooding, monitoring and forecasting hurricanes is essential to saving lives and protecting property. Several organizations across the world monitor hurricanes in different parts of the ocean. The National Hurricane Center, NHC, in Miami, is responsible for hurricanes in the Atlantic and Eastern Pacific that affect North America. It is the job of the NHC to predict how strong and big hurricanes will become and to track the path these storms will take. The NHC uses information received from satellites, ships, buoys, airplanes, and radars to track and forecast hurricanes. It is important to have as much information as possible from several sources to make the best predictions. When the storm is in the middle of the ocean, satellites are the main source of information. But when hurricanes get closer to the coast, radars on land read wind speed and precipitation information. But this is just the way that information about hurricanes is collected. Before any predictions can be made, all of the collected information is fed into computer models that can then be used to make a forecast. It is only after the computer model results are compared with current information about the weather and environment that the NHC makes a forecast about strength, location, and direction of a hurricane. Then the NHC gives a forecast to emergency personnel and the media so the public can know and take necessary precautions. The same process is repeated every few hours until the hurricane dissipates. When the forecast is released to the public, an advisory is released along with it to give instructions on how to prepare for the storm. The advisory is either a hurricane watch or a hurricane warning. A watch just means that the weather is right for hurricane conditions to occur, so be on the lookout and ready. A warning, however, means that a storm has definitely been spotted and to expect hurricane conditions in your area soon. In case of a warning, you should take action and seek shelter or evacuate. Based on the severity of the conditions, emergency personnel will give instructions on what actions you need to take if a hurricane warning is issued. Because wind and rain conditions can worsen quickly in a hurricane situation, making it difficult to evacuate or find shelter, authorities announce hurricane warnings at least 36 hours ahead of time. Some of the important information in an advisory includes latitude and longitude, distance away, wind speed, predicted track, and information about potential rainfall and flooding. Also associated with advisories is the strength of a hurricane based on the Saffir-Simpson hurricane scale. It ranks a hurricane from values 1 to 5 based on pressure in the eye, wind speed, and storm surge or flooding. The least severe hurricanes are ranked at 1 and have the highest pressure in the eye, weakest winds, and least amount of flooding. In this case, the outsides of buildings may be damaged, electricity lost for a few days, and trees may fall over. The most severe, or a Category 5, had the lowest pressure, strongest wind, and most rainfall and flooding. Category 5s result in a majority of homes being completely leveled, power outages for weeks, and the affected area may not be habitable for months. These categories are important when telling the historical importance of different hurricanes. Categories 1 to 5 make it easy to recognize how destructive a hurricane was. In 2005, a Category 5 hurricane named Katrina caused deadly flooding that resulted in deaths and lost homes in New Orleans. Despite the damage, it could have been much worse if hurricane forecasting and warning systems were not used. A hurricane is a very large storm with strong winds that develops in the tropics. Warm water causes the air to rise, then cool in the upper atmosphere and fall as precipitation. Once the process gets started, more air gets pulled into the storm, allowing a minor disturbance to become a hurricane. Hurricanes often start as an easterly wave over the ocean that is just a weak low-pressure system. If conditions are right, they develop rotating winds and become a hurricane. Then the National Hurricane Center, NHC in Miami, can track and predict the storm in an effort to save lives. They get information about the storm from satellites and radars so that they can feed it into a computer model to make predictions about the strength and direction of the hurricane. Then they give the predictions to emergency personnel and the media. The information may be either a hurricane watch, which means to be on the lookout, or a hurricane warning, which means to evacuate or find shelter. Associated with the advisories is the Saffir-Simpson hurricane scale, which is used to rank how serious a hurricane is from 1 to 5, with 5 being the most destructive and deadly.
Think about all the different types of habitats you have been to or have seen on television. The Earth is covered in many different types of habitats that vary by climate and by the animals and plants that live there. One very interesting and unique type of habitat is a desert. Deserts are defined as regions with very low rainfall, usually less than 25 centimeters of rain per year. Due to the limited rainfall, deserts often have very dry soil or sand that is easily moved around by wind. This results in a continuously changing landscape. Although deserts are characteristically dry, in some regions, when it rains, it pours. In many desert regions, it will rain once or twice per year, but will dump more than 13 centimeters of rain in a short time period. The landscape cannot absorb the large amount of rain, and the result is often a flash flood, when large quantities of water flow over the land for a short period of time. Another unique characteristic of deserts is the unique organisms and plants that live there. Although at first glimpse a desert may look sparse or abandoned, there is actually a great deal of life present. There are many specialized plants that have developed adaptations that make it possible for them to live in such a harsh and dry climate. These plants survive by storing water in large root systems and by having small waxy leaves to reduce water loss. A cactus is a great example of a desert plant that has adapted to life with limited water. There are even some plants in the desert that look dead for most of the year, but will become green and flower when it rains. There are also many animals that live in desert habitats. Similar to plants, these animals have developed adaptations to help them survive. Many desert organisms live in deep, cool burrows underground. They use these burrows to avoid the heat, and some even hibernate in the ground during periods of extreme drought. Some desert animals are only active at night when it's cooler. Camels survive life in the desert by drinking large amounts of water when it is available and storing it in their body for later use. Due to this adaptation, some camels can survive for weeks without drinking. The location of deserts is directly related to the atmosphere, which is the combination of the gases that surround the Earth. The hydrosphere, which is the water on the Earth's surface, is also involved in the creation of deserts. Water from the hydrosphere evaporates and travels into the atmosphere. The air above oceans and lakes is often very moist due to the large amount of water that is in the air. The atmosphere can cause the air and water particles to move around the globe. The global pattern of air circulation controls where air moves around the planet. If the moist air travels over land near the equator, it will rise, expand, and cool, which causes precipitation. Due to the large volume of precipitation that occurs, the air becomes dry as it travels north or south of the equator. This air will later sink, compress, and warm, and will not be able to form precipitation over the land. Additionally, the dry air will cause increased evaporation, contributing to the formation of a desert. Due to the global pattern of air circulation and the relation to the atmosphere, most deserts are found within a belt centered on the 30° north and 30° south latitude lines. These regions are characterized by having a great deal of sunlight, minimal rain, and high levels of evaporation. Although most deserts are within this latitudinal belt, there are some exceptions. There are deserts found in other regions of the world that are created due to interactions with the land and geological setting. Some deserts are formed within rain shadow zones, which are the downward sides of mountains that receive limited rainfall. As moist air passes over a mountain range, it often causes precipitation, leaving the air that moves down the other side of the mountain to be void of moisture. This creates a dry habitat. Some deserts are formed because they are an extreme distance from oceans. Land deep within the interior of a continent receives very dry air that has already lost the majority of its moisture while traveling from a distant ocean. Deserts can also be formed on tropical coasts that receive cold ocean currents. Colder air cannot carry as much moisture as warm air, so when the cold ocean currents cool the air above, the air becomes very dry. When this air reaches land, it causes more evaporation than precipitation, which results in the formation of a desert. Although most deserts are warm, not all of them are. Some deserts are referred to as polar deserts because they are formed in very cold regions where cold, sinking air contains no moisture. The entire continent of Antarctica is a polar desert because it receives very limited rainfall each year. Now, let's review deserts, their location in relation to the atmosphere, and their distribution. Deserts are defined as regions with very low rainfall, usually less than 25 centimeters of rain per year. Some common characteristics of deserts include dry soil, a changing landscape, and risk of flash floods, which are when large quantities of water flow over the land for a short period of time. Deserts are also characterized by their unique assemblage of plants and animals that have developed adaptations to survive in dry regions. Deserts are directly influenced by their location in relation to the atmosphere, which is the combination of the gases that surround the Earth. The location of deserts is also influenced by the hydrosphere, which is the water on the Earth's surface. Water from the hydrosphere evaporates into the atmosphere and travels around the globe based on global circulation patterns. When air travels away from the equator, it sinks, compresses, and warms, which causes dry air to pass over land with little precipitation, forming deserts. Most deserts are distributed around the globe based on the global circulation patterns and are located along a belt centered on the 30° north and 30° south latitude lines. Other geological settings that can cause desert formation are extreme distance from oceans and cold ocean currents. Deserts can also form in polar regions, which are called polar deserts, and within rain shadow zones, which are the downwind sides of mountains that receive limited rainfall. Despite the large variation in geological settings that cause the formation of deserts, they all share the characteristic of limited rainfall and are considered harsh conditions in which to survive. If you were to travel around the United States, you would encounter a variety of different habitat types, including rainforests, mountains, coastal areas, plains, and deciduous forests. In the southwestern United States, the majority of the land is considered desert. Deserts are defined as regions with very low rainfall, usually less than 25 centimeters of rain per year. This region of the country is dominated by desert conditions, partially because it is located near the 30° north latitude line. Land near this latitude line is prone to desert conditions due to global air circulation patterns that bring in very dry air. This dry air gives the region the general characteristics of having a great deal of sunlight, minimal rain, and high levels of evaporation. The formation of deserts in the southwestern United States is also a result of rain shadow zones, which are the downwind sides of mountains that receive limited rainfall. As warm, moist air passes over a mountain range, it cools and expands, which causes condensation and precipitation. This leaves the air that moves down the other side of the mountain to be void of moisture and creates a dry habitat. There are several mountain ranges, including the Sierra Nevada range, that create rain shadow zones in the southwestern United States. Although the entire desert region shares common characteristics, you would notice some major differences if you were to travel across it. The region is actually divided into two areas, the Colorado Plateau and the Basin and Range Province. This division is based on major differences in geologic structures. The Colorado Plateau is one of the two desert regions in the southwestern United States. This region is centered around a spot known as the Four Corners, where you can stand in Utah, Colorado, Arizona, and New Mexico all at once. The Colorado Plateau has the nickname Red Rock Country because of the large, brightly colored rock formations that cover the land. This region is dominated by plateaus, which are large, flat-topped areas that are elevated above the surrounding ground and have cliffs at their edges. These plateaus can be formed from layers of rocks such as sandstone and limestone, or layers of lava flow. Plateaus can reach over 1,500 meters above sea level and are very vulnerable to erosion due to their high level of exposure to the natural elements. Over time, as a result of erosion from moving water or wind, a plateau can be transformed into different types of geologic features. First, as erosion removes rocks from the base and cliffs of the plateau, some areas of land are left behind, resulting in the formation of a mesa. A mesa is a broad, flat-topped hill with cliff edges. Mesas are basically a small isolated portion of elevated land that was once connected to the larger plateau, but now stands separated. If erosion of a mesa continues, it will eventually break up into smaller areas of land. These geologic features are known as buttes, which are very narrow hills with a flat top and steep sides. If a butte continues to erode, it will eventually be worn down to the flat ground and no longer be elevated. The Colorado Plateau is also known for a unique geologic feature known as monoclines. Monoclines are step-like folds in the rock layers. Instead of the land having a gradual slope, the monocline creates more rigid layers that resemble steep steps. The Basin and Range Province is the other major desert region in the southwestern United States. This region covers the majority of Nevada and portions of Southern California, Utah, Arizona, New Mexico, and the western tip of Texas. The region is dominated by mountain ranges that are separated by flat valley floors. The multiple mountain ranges cause many rain shadow zones and the resulting dry climate. The alternation between mountain range and flat valley floor is caused by faults, which are fractures in the ground where movement occurs. Movement along the fault lines has caused the valleys between the mountains to drop down. Similar to the plateaus in the Colorado Plateau region, the mountain ranges in the Basin and Range Province are susceptible to severe erosion. In this region, the majority of erosion is due to heavy rains that fall as clouds pass over the mountains. This heavy rain causes erosion of the steep mountain slopes and carries the deposits down to the base in a flash flood or mudslide. The eroded sediment causes the creation of alluvial fans, which are large, fan-like piles of sediment. As erosion continues and alluvial fans grow in size, they can create a bajada, which is a broad, gently sloping surface formed by the joining of individual alluvial fans. As erosion continues, a pediment will eventually form, which is a gently sloping surface covered in gravel and large rocks. This formation will occur high up the mountain, above the bajada, and will be clear of fine sediment that has already washed down the mountainside. Over long periods of time, a steep mountain slope will be transformed due to erosion and will shape the landscape of the desert. Like the mountains, the valleys of the Basin and Range Province also go through changes. When excess water from heavy rain collects on the bottom of the valley, it creates a playa lake. These are shallow, temporary lakes that contain fine clay from the mountainside. When the water evaporates after a few days, it will create a playa, which is a flat surface of hard, mud-cracked clay. This cracked surface is a characteristic that is very common in this type of desert. Now, let's review deserts of the southwestern United States. First, deserts are defined as regions with very low rainfall, usually less than 25 centimeters of rain per year. The deserts of the southwestern United States are formed due to their location near the 30-degree north latitude line and as a result of rain shadow zones, which are the downwind side of mountains that receive limited rainfall. This large desert region shares a common climate, but is divided into two different regions based on geologic features. The Colorado Plateau is centered around the Four Corners and is dominated by plateaus, which are large, flat-topped areas that are elevated above the surrounding ground and have cliffs at their edges. As a result of erosion, over time a plateau can be turned into a mesa, which is a broad, flat-topped hill with cliff edges, and eventually a butte, which is a very narrow hill with a flat top and steep sides. The Colorado Plateau is also known for a unique geologic feature known as monoclines, which are step-like folds in the rock layers. The Basin and Range Province is the other major desert region in the southwestern United States and covers the majority of Nevada. This region is characterized by mountain ranges separated by flat valley floors. The alternation between mountain range and flat valley floor is caused by the movement of faults. Erosion of mountain ranges results in the formation of sediment deposits known as alluvial fans, which can combine into bajadas. Extreme and continued erosion can result in the formation of a pediment, which is a gently sloping surface covered in gravel and large rocks. Heavy rainfall causes playa lakes to form in the valleys, which evaporate and leave cracked clay surfaces known as a playa. Although both the Colorado Plateau and the Basin and Range Province are both considered deserts, they have their own unique physical features and landscape based on their geologic features. If you visit the deserts of the southwestern United States, you will get to see two very different habitats that share a common desire for a rain shower. Think about a tornado or a storm so strong it knocks down trees. These are just two examples that demonstrate the great strength of wind. Wind is very powerful and can drastically change a physical environment. Wind erosion, which is the process of breaking down and dispersing particles by wind movement, is one way that wind can alter an environment. A historic example of wind erosion is the Dust Bowl of the 1930s. During this period, many states in the Great Plains region of the United States experienced severe drought, which resulted in extremely dry soil. Strong winds would then blow and pick up the dry soil, causing a dust storm. The soil was carried high in the air and transported long distances. These dust storms were so large and overwhelming that they often blocked the sun completely. Wind erosion has the greatest impact on areas with dry soil because it is easier for wind to pick up and transport dry, light soil than it is to pick up wet soil. Like the drought-ridden Great Plains during the Dust Bowl, desert regions are also very susceptible to wind erosion. Characteristically, deserts have dry soil or sand that is easy to transport. Also, deserts often have fewer physical barriers, such as hills, trees, or other structures that can slow the wind movement. Due to this lack of physical barriers, desert winds have less slowing them down or stopping their movement, and are able to transport particles easier and farther. Wind erosion can occur by two different methods, which are abrasion and deflation. These two methods of wind erosion both involve the erosion and dispersal of particles, but they shape the desert landscape in very different ways. Wind abrasion is the process of the wearing away of a solid object due to the impact of particles carried by the wind. The wind picks up particles and moves them. When the particles collide with a solid object, the impact causes small pieces of the object to break off. This can cause the object being hit with particles to become smooth or worn. This type of wind erosion is similar to sandblasting. During sandblasting, a person uses compressed air or some other force to push sand at a high velocity over an object in order to roughen or clear the surface. Wind abrasion is a natural form of sandblasting. In deserts, wind abrasion shapes the rocks and boulders. In areas where strong winds consistently pick up sand and carry it, rocks and boulders in the wind's path can be impacted by wind abrasion. If the wind blows over low-lying rocks, it will cause them to become flattened on the upwind side. The sand particles that collide with the rock will break away small pieces of the rock until it loses its round shape and becomes flat. When the wind direction changes and particles collide with a different side of the rock or boulder, it can cause the creation of another flat surface. Rocks with flat, wind-abraded surfaces are referred to as ventifacts. For low-lying rocks or boulders, the wind creates a flattened rock surface. But for larger or taller boulders, the wind abrasion causes a very different change to the rock. In most cases, the wind velocity is not strong enough to pick up sand particles and carry them high in the air. Instead, the particles are transported more closely to the ground. For large boulders, this means that the wind abrasion will occur at the base. This process will result in the formation of pedestal rocks, which are rocks that are narrower at the base and have a larger top. They get their name because they look like a pedestal holding an object. These types of rocks also resemble a mushroom with a stem and cap. Deflation is the removal of loose sediment from the flat land surface by wind. When deflation occurs in barren areas, it can cause most or all of the loose sediment to be removed and dispersed. This process often lowers the the land surface a great deal. This can create a blowout, which is a depression on the land surface caused by wind erosion. Blowouts often look like craters in the sand. Sometimes when a blowout occurs, a pillar is created, which is a remnant of the former land that is left behind at the center of the blowout. In some cases, deflation can result in the land surface being lowered so drastically that large rocks that were once covered in sediment become exposed. Over time, more large rocks become exposed as deflation removes any loose particles around the rocks. This leads to the creation of desert pavement, which is when exposed rocks cover the ground surface and prevent the sediment below from being eroded. The desert pavement will protect the sediment below it from deflation as long as it is not disturbed. If the protective rock layer is disturbed, such as by construction, the sediment below the rocks will be exposed and quickly removed by deflation. Now, let's review wind action and the impact it can have on a desert landscape. Wind erosion is the process of breaking down and dispersing particles by wind movement. Wind erosion occurs by two different methods, which are abrasion and deflation. Wind abrasion is the process of the wearing away of a solid object due to the impact of particles carried by wind. When wind abrasion occurs on low-lying rocks, it creates ventifacts, which are rocks with flat, wind-abraded surfaces. Large, tall boulders that are exposed to wind abrasion often result in the formation of pedestal rocks, which are rocks that are narrower at the base and have a larger top. Pedestal rocks often resemble a mushroom. Deflation is the removal of loose sediment from the flat land surface by wind. Deflation lowers the land surface and can create a blowout, which is a depression on the land surface caused by wind erosion. Sometimes when a blowout occurs, a pillar is created, which is a remnant of the former land that is left behind at the center of the blowout. If deflation is extreme, it can lead to the creation of desert pavement, which is when exposed rocks cover the ground surface and prevent the sediment below from being eroded. This desert pavement creates a unique rock surface that protects the sediment below as long as it is not disturbed. These two methods of wind erosion are responsible for creating some of the physical features of deserts that make them such unique environments and interesting places to visit. Imagine you are walking through a desert and the wind begins to blow around you. When the wind settles, you see piles of sand. You might wonder what these piles are and how they got there. Mounds of loose sand grains that are piled up by wind movement are referred to as sand dunes. There are many sand dunes located within the deserts of the southwestern United States. You can also see sand dunes along beaches where sand blows inland and creates a dune that separates the water from the habitat. In the Sahara Desert of Africa, the sand dunes are so large they are referred to as sand seas. The sand dunes move with the wind and resemble a moving sea. Most sand dunes are considered asymmetrical, meaning that if you cut down a central line, they are not identical on both sides. The side of the sand dune that faces the direction of the wind movement normally has a gentle slope, while the downwind side has a steeper slope. The downwind side of the dune is referred to as the slip face. Sand grains are blown up the gentle slope of the dune, and when they reach the top, they fall onto the slip face. When enough loose sand settles on the slip face, it can cause a small sand avalanche to occur as the sand slips down the dune. Over time, entire sand dunes move as wind erodes the upwind side and moves it to the slip face. This results in the sand dune slowly moving in the downwind direction. On average, a dune can move around 10 to 15 meters per year. Although this may not seem like much, if you think about sand dunes along a beach, 10 to 15 meters can make quite a difference in the landscape. Sand dunes stop moving when they become overgrown with vegetation. In beach areas where sand dunes can move towards houses, vegetation is often planted on the dunes to stop them from moving. The roots of the plants help stabilize the sand and prevent it from blowing in the wind. There are a variety of different types of sand dunes found around the world. The different types have certain characteristics based on the velocity and direction of wind, the sand supply, and how vegetation covers the dune. One type of sand dune is called a barchan. A barchan sand dune is a crescent-shaped dune with tips that point in the downwind direction and has a steep slip face. Individual barchan dunes are separate from each other and gradually move along the barren desert surface. This type of sand dune is created when sand is limited. If the sand supply increases, ridges will form if barchan sand dunes start to grow and connect to each other. In some cases, these ridges lose their crescent shape and become straight, forming a second type of sand dune. Transverse dunes are straight, long dunes that are oriented perpendicular to the wind direction and have steep slip faces. The third type of sand dune shares the crescent shape with the barchan dune, but is inverted. The parabolic dune is crescent-shaped with vegetation-anchored tips that point in the upwind direction and has a steep downwind slip face. This type of sand dune requires a large amount of sand and strong winds. The fourth and largest type of sand dune is the longitudinal dune. Longitudinal dunes are large, symmetrical ridges of sand that form parallel to the primary wind direction. These dunes are straight and regularly spaced, with barren ground in between each dune. Longitudinal dunes require strong winds from two directions in order to create such long and straight lines. There is a primary wind direction and also a crosswind. Due to the alternation of wind direction, the location of the slip face also changes with the wind. The longitudinal dunes in the Sahara Desert are more than 120 kilometers long and can reach as high as 200 meters. There are numerous hypotheses as to how exactly these dunes are formed, and research is ongoing to solve the mystery. The fifth type of sand dune is very unique. Star dunes are dunes with 3 or more ridges radiating from a center point. These dunes are formed in areas with large amounts of sand and strong winds that blow in a variety of directions over the course of a year. These dunes also vary from the others because they have a continuously changing slip face, and they do not migrate over time. Instead, they simply grow larger in size. Now, let's review sand dunes and the different types. Sand dunes are mounds of loose sand grains that are piled up by wind movement. Most sand dunes are asymmetrical, which means that if cut down a central line, they are not identical on both sides. They have one side that faces the wind direction, which has a gentle slope. The other side of the dune has a steeper slope and is referred to as the slip face, or downwind side of the dune. Sand dunes can gradually move over time as sand is blown from one side of the dune to the other. Most sand dunes stop moving only when vegetation grows on the dune and prevents the wind from blowing the sand. There are 5 different types of sand dunes that vary based on the velocity and direction of wind, the sand supply, and how vegetation covers the dune. A barchan sand dune is a crescent-shaped dune with tips that point in the downwind direction and has a steep slip face. If the sand supply increases and barchan dunes become large and connect to each other, they can transform into transverse dunes, which are straight, long dunes that are oriented perpendicular to the wind direction and have steep slip faces. The parabolic dune is crescent-shaped with vegetation-anchored tips that point in the upwind direction and has a steep downwind slip face. The largest and somewhat mysterious dunes are longitudinal dunes, which are large, symmetrical ridges of sand that form parallel to the primary wind direction. Star dunes are dunes with 3 or more ridges radiating from a center point, and are unique because they require wind that moves in several different directions throughout the year. Sand dunes are features that make a desert habitat very unique and interesting. Most sand dunes are moving and result in a constantly changing and beautiful landscape. We live in a world where climate change is often a hot topic of discussion. You often hear about temperature changes, sea level rising, and shifting climate zones. However, something that we don't hear so much about is that over recent years, there has been an increase in the amount of land that is classified as a desert. Many lands that were once covered in vegetation are now barren and dry deserts. This overall change is known as desertification, which is the conversion of habitable and fertile land to uninhabitable desert. Desertification occurs due to a decrease in vegetation. This can happen naturally due to a drought or can be caused by human activities. The lack of plants can cause changes to the land. Plants help shade the soil, so when plants are removed, the soil will be exposed to the sun and will dry out more quickly. The roots of plants often help hold soil in place. If plants are removed, the soil will have nothing protecting them, and it will be more susceptible to erosion by wind. This will reduce fertility of the land because the top layer of soil that will be blown away by wind is often the richest in nutrients. Once this top layer of soil is removed, the land will no longer be fertile and will be unable to support the growth of vegetation. Eventually, the land will become so dry and devoid of vegetation that it will be classified as a desert. The process of desertification can force people to move to new land. People rely on vegetation for food, to feed their livestock, and to heat their homes. If the land can no longer support vegetation, life for humans will be more difficult. This often results in people migrating to a different location where vegetation is still supported. If desertification continues, people may be forced to move away from warmer regions where desertification is more likely and closer to polar regions in order to find land that is habitable and fertile. Although desertification can occur naturally due to extreme droughts, there are many situations where the process of desertification has been caused or accelerated by human activities. Humans often divert rivers from their natural path in order to use the water for agriculture. The land along the original river path will become vulnerable to desertification. This area will no longer have a water supply, and vegetation will likely die off and lead to desert conditions. Poor irrigation techniques on farms can also lead to desertification. If farmers use too much water or use water inefficiently, they will reduce the overall water supply in the area. This can lead to vegetation loss and eventually desertification. Overgrazing and deforestation are two additional human activities that can lead to desertification. Overgrazing occurs when farmers allow livestock to graze to the point where they damage the vegetation. This can happen when farmers have too many livestock in a small area or when they keep livestock in an area for a long period of time. Deforestation is the process of removing trees and transforming a forest into cleared land. This is often done to make room for farming or housing for the growing human population. Both overgrazing and deforestation can lead to desertification because they remove or damage the vegetation that is protecting the land and keeping it moist and fertile. The process of desertification is permanent and cannot be reversed naturally. Once the land becomes a desert, it will stay a desert. This is of great concern because as more land becomes desert, there is a reduction in the amount of fertile land that we, as humans, can depend on to grow our food. Due to these factors, it is extremely important to stop desertification from occurring and to save the land that is at risk. Desertification is occurring worldwide, and the United Nations is actively involved in combating this process. In 1994, the United Nations Convention to Combat Desertification, also known as the UNCCD, was established. The UNCCD is an international agreement addressing the relationship between human development and sustainable land management, with a focus on areas that are at risk of desertification. The goals of the UNCCD are to create a global partnership to reverse and prevent desertification and land degradation. They work to improve the living conditions of people who live in areas at risk of desertification or areas where it has already occurred. They also try to maintain and restore the land by adding nutrients and increasing fertility. The UNCCD makes an effort to include local people in the effort to combat desertification. They try to teach people how to prevent desertification by reducing or changing human activities that cause desertification. Annually, on June 17th, the United Nations organizes the World Day to Combat Desertification and Drought. On this day, they try to bring attention to the issues associated with desertification and aim to gain support for their goals. Now, let's review desertification and how humans influence this process. Desertification is the conversion of habitable and fertile land to uninhabitable desert. When a habitable and fertile land loses its vegetation due to natural drought or human activity, the land begins to change. It will become drier due to lack of plants to shade the ground. The fertile top layer of soil will also start to blow away because the roots of the plants that used to hold the soil in place are no longer there. The land will start to develop characteristics of a true desert and will no longer be a suitable habitat for humans to live. Desertification is often caused by human activities. Two such activities are diverting rivers from their natural path for agriculture use and poor irrigation techniques that waste water. Overgrazing, which is when farmers allow livestock to graze to the point where they damage the vegetation, and deforestation, which is the process of removing trees and transforming a forest into cleared land, are also ways that humans cause desertification by removing vegetation. Due to the large-scale impacts of desertification, there has been a global effort to combat it. The United Nations Convention to Combat Desertification was established to create a global partnership to reverse and prevent desertification and land degradation. Although there are efforts to combat desertification, it is a problem for all humans, plants, and animals that needs more global attention and action to stop it before it is too late.
The Earth has been described as the blue planet, a blue dot in space. That's because while there is a lot of land here, there is far more water. 71% of the Earth's surface is covered by water, and it is vital for all life on Earth. Without water, we wouldn't exist. Neither would the plants or the animals. Maybe somewhere in the universe life exists that doesn't need water, but right now we can't imagine how that would be possible. Water is everything, and water on Earth is mostly found in the oceans, seas, and gulfs. But what are oceans, seas, and gulfs? An ocean is a very large expanse of seawater, especially between continents. A sea, on the other hand, is any expanse of salt water. But why do we call some things oceans and some things seas? Well, that's usually determined by the land. If the water is partially enclosed by land, it's usually called a sea. And if it isn't very enclosed, it's considered an ocean. A gulf is a deep inlet of the sea almost surrounded by land, with a narrow mouth. A gulf is mostly enclosed by land, but a sea is not quite so enclosed. However, unfortunately, this isn't an exact science. There are seas, like the Black Sea for example, that are completely enclosed. As usual, humans aren't always very consistent. It's important to be able to name and locate all the major bodies of water on a world map. So let's go through them, starting with the oceans. The Atlantic Ocean can be found here, and the Pacific Ocean here. The Arctic Ocean is in the north, and the Southern Ocean is in the south. Then last of all, there's the Indian Ocean, south of India. Those are the biggest named bodies of water in the world. Now we can get smaller, seas and gulfs. There are at least 97 bodies of water with the name sea, and another 17 or so gulfs. We couldn't possibly go through them all, but here are a few of the most well-known ones. The Adriatic Sea is here, and the Caribbean Sea is over here, south of the USA. The North Sea is up here in the north, and the Gulf of Mexico is the Gulf that's near Mexico. The Persian Gulf is here, in the Middle East, and so is the Red Sea. In the Pacific, you might have heard of the South China Sea, or the Tasman Sea near Australia. And as I mentioned, there are a few fully enclosed so-called seas, 4 in all, like the Caspian Sea, the Black Sea, and the Dead Sea. Based on these names, you could probably conclude that enclosed seas are depressing places. So there you have it, some of the most famous oceans, gulfs and seas in the world. If you know where all of these are and can point them out on a map, you're doing pretty well. 71% of the Earth's surface is covered by water, and it is vital for all life on Earth. Without water, we wouldn't exist, neither would the plants or the animals. Water is everything, and water on Earth is found mostly in oceans, seas and gulfs. An ocean is a very large expanse of seawater, especially between continents. A sea, on the other hand, is any expanse of salt water. If the water is partially enclosed by land, it's usually called a sea, and if it isn't very enclosed, it's considered an ocean. A gulf is a deep inlet of the sea, almost surrounded by land, with a narrow mouth. A gulf is mostly enclosed by land, but a sea is not quite so enclosed. Though it isn't an exact science, unfortunately. There are seas that are completely enclosed. The Atlantic Ocean can be found here, and the Pacific Ocean here. The Arctic Ocean is in the north, and the Southern Ocean is in the south. And last of all, there's the Indian Ocean, south of India. Those are the biggest named bodies of water in the world. There are at least 97 bodies of water with the name sea, and another 17 or so gulfs. So there are the most famous oceans, gulfs and seas in the world. If you know where all of those are, you're doing pretty well.
When you are active, you are always on the go and have a lot of energy. When you're passive, you tend to lie around and things happen slowly. Planet Earth behaves in a similar way. It has active areas where earthquakes rattle the ground and volcanoes erupt, and it has passive areas where sediment slowly deposits and few earth-shaking occurrences happen. In this lesson, you will learn about these active and passive areas of the world as you take a look at active and passive continental margins. To understand active and passive continental margins, it's important to gain a basic understanding of the way our planet is put together. The Earth is not a solid clump of rock. Instead, it has different layers comprised of different materials. You can relate the main layers of the Earth to a hard-boiled egg. The yellow inner yolk of the egg relates to the Earth's core, which is a very hot place. The white part of the egg relates to the Earth's mantle, which is the largest layer and also pretty hot. The mantle is mostly solid, but the rock and material within the mantle can melt and form magma, which is the hot molten rock that we associate with volcanoes. The shell covering the egg relates to the Earth's crust. Like the egg shell, the Earth's crust is relatively thin and can break into sections of crust or plates. The continental crust is the part of the Earth's crust that makes up the continents. The oceanic crust is the part of the Earth's crust that underlies the oceans. The continental crust is less dense than the material that makes up the underlying mantle, so it tends to float on top of the mantle and move around. Of course, even though we live on the continental crust, we do not feel this movement because it's very slow, in the range of about 1 to 10 centimeters during the course of a year. The continental crust is also less dense than the oceanic crust, so the oceanic crust does not move as much. But because the continental crust is moving, it can knock into the oceanic crust at a place called the continental margin. We can define the continental margin as the zone that separates the continental crust from the oceanic crust. So as you can imagine, just about anywhere there is a large landmass meeting up with a large body of water, we would find a continental margin. But not all continental margins are created equal. Some are active and some are passive. Active continental margins are continental margins that are tectonically active. When we look at the term tectonics in geology, we see that it refers to the study of the deformation of the Earth's rocky crust and the forces that cause this deformation. So an area of the world that is tectonically active would be an area where the rocky crust folds or deforms, as seen in mountain building. It would also be the site of earthquakes and volcanoes. The west coast of the United States is a good example of an active continental margin. Earthquakes have been known to shake California and other West Coast states, and the Aleutian Islands of Alaska have many highly active volcanoes. Active continental margins tend to have a narrow continental shelf, which is the submerged border of the continent. So the continent drops off quickly along an active margin and meets up with the more dense oceanic crust. Because the oceanic crust is heavier, it gets forced underneath the continental crust, carrying lots of rock toward the hotter mantle of the Earth, where it can melt. This area where plates converge and one plate is driven below the other is called a subduction zone. This contributes to the earthquakes and volcanic activity that we see associated with active continental margins. Passive continental margins are continental margins that are not tectonically active. So instead of seeing mountainous areas prone to earthquakes and volcanoes, with passive continental margins, we see gently rolling flat land and a wide continental shelf that slopes slowly into the ocean. The east coast of the United States is a good example of a passive continental margin. The East Coast has long beaches from New Jersey down to Florida, where the continental shelf is so wide in some areas that visitors to the beach can wade far out into the ocean and still touch bottom. Because subduction zones are not common, tectonic activity is low, and we see passive processes such as coastal erosion and the passive depositing of sand and sediment dominate these landscapes. Let's review. The outer layer of the Earth is called the crust. The continental crust is the part of the Earth's crust that makes up the continents. The oceanic crust is the part of the Earth's crust that underlies the oceans. The continental margin is the zone that separates the continental crust from the oceanic crust. Active continental margins are continental margins that are tectonically active. Tectonics is the study of the deformation of the Earth's rocky crust and the forces that cause this deformation. So an area of the world that is tectonically active would be a mountainous area with earthquake and volcanic activity. The west coast of the United States is a good example of an active continental margin. Passive continental margins are continental margins that are not tectonically active. These areas have flatlands and have a wide continental shelf, which is the submerged border of the continent. The east coast of the United States is a good example of a passive continental margin. Active continental margins tend to have narrow continental shelves. A subduction zone is the area where plates converge and one plate is driven below the other. This contributes to the earthquakes and volcanic activity that we see associated with active continental margins. These zones are not common in passive continental margins, so coastal erosion and the passive depositing of sand and sediment dominate these areas. About 70% of the planet's surface is made up of ocean basins, which are the regions that are below sea level. These areas hold the majority of the planet's water. In fact, it will help you to recall this term if you remember that a basin is a large bowl, much like your kitchen sink. So an ocean basin can be thought of as a large bowl that holds ocean water. The floors of our world's oceans contain features that you might recognize as being similar to some structures on land. In this lesson, you will learn about these features, including undersea mountains and trenches, and how they are formed. Ocean basins can be either active, with a lot of new structures being created and shaped, or they can be inactive, where their surface is slow to change and does little more than collect sediment. The Gulf of Mexico is an example of an inactive ocean basin, where the main change that happens is the slow depositing of sand and sediment. Active ocean basins undergo change mainly due to plate tectonics. Plate tectonics is the theory used to explain the dynamics of the Earth's surface resulting from the interaction of the overlying rigid plates with the underlying mantle. According to the theory, the Earth has a rigid outer layer called the crust. This crust is somewhat fragile, and like the shell of a hard-boiled egg, it can crack and break into plates. The Earth's crust breaks due to heat and pressure from the layer beneath the crust called the mantle. These plates move very slowly and meet at their boundaries. These boundaries are common areas of tectonic activity, which is the deformation of the Earth's crust due to movement of tectonic plates resulting in activity such as earthquakes, volcanoes, and mountain building. So an area of the world that is tectonically active, whether it be on land or under the water, would be a mountainous area with earthquakes and volcanic activity. This creates many of the ocean basin features. Plates can spread apart by moving away from each other. This creates gaps where hot molten rock, called magma, from the Earth's mantle can rise up. When the magma seeps through the gaps, it solidifies as it cools, creating a new layer of ocean crust. This creates structures such as oceanic ridges, which are continuous mountain chains located under the surface of the sea. You can think of their creation in much the same way as a scab gets created over a wound. For example, when you cut your finger, it bleeds. The blood flowing out of the cut relates to the magma flowing out of the gap between the spreading plates. The cut will form a raised scab on your finger, and as the magma cools, it will form a raised layer of crust on the sea floor. An abyssal hill is another raised feature found within ocean basins. It is defined as a small elevated landform that rises from the great depths of the ocean. It might help you to recall this term by remembering that an abyss is something that is very deep. So an abyssal hill is a hill found on the deep ocean floor. An abyssal hill has sharply defined edges, but will remain relatively small, generally growing not much larger than 500 feet in height and a few miles in width. A seamount is a large submerged volcanic mountain rising from the ocean floor. Seamounts can be very large, reaching heights of up to 10,000 feet, yet they remain submerged under the surface of the water. A guyot is similar to a seamount, but it is a submerged volcanic mountain with a flat top. Guyots receive their flat top after years of erosion caused by waves and other erosive processes. We have looked at some ocean basin features that rise up from the ocean floor, but we also see depressions in the ocean floor, such as oceanic trenches. These trenches extend down below the normal level of the ocean floor and are the deepest parts of the ocean. Unlike oceanic ridges that form when plate boundaries separate, oceanic trenches form when plates push together. When plates abut up against each other, one plate subducts or slides under the other, carrying rock down into the mantle where it is heated and can melt. This can increase volcanic activity near oceanic trenches. Trenches vary in depth, with the deepest oceanic trench being the Mariana Trench in the Pacific Ocean, which reaches a depth of over 36,000 feet. Let's review. Ocean basins are the regions that are below sea level. They can be either inactive and collect sediment, or be active. Active ocean basins undergo changes mainly due to plate tectonics. Plate tectonics is the theory used to explain the dynamics of the Earth's surface resulting from the interaction of overlying rigid plates with the underlying mantle. These plates found on the outer layer of the Earth can move and meet with other plates at their boundaries. These boundaries are common areas of tectonic activity, including mountain building, earthquakes, and volcanoes, and the areas where ocean basin features are created. When plates spread apart, they create gaps where magma from the Earth's mantle can rise up and cool to form structures such as oceanic ridges, which are continuous mountain chains located under the surface of the sea. An abyssal hill is a small elevated landform that rises from the great depths of the ocean. A seamount is a large submerged volcanic mountain rising from the ocean floor, and a guyot is a submerged volcanic mountain with a flat top. Oceanic trenches are depressions in the ocean floor. Oceanic trenches form when one plate subducts or slides under another. The regions below sea level, that we refer to as ocean basins, contain the majority of the planet's water. If you were to drain all of that water, it would reveal an ocean floor that is far from smooth. In fact, you would see a continuous mountain chain located under the surface of the sea called the Oceanic Ridge System. This vast mountain range runs through all of the major oceans of the world and in this lesson you will learn more about its location as well as how it is formed. When you stand on the coast and look out over the ocean, you can't see the ocean floor, but that doesn't mean there's nothing happening down there. In fact, ocean basins are constantly being shaped due to tectonic activity. Tectonic activity is defined as the deformation of the Earth's crust due to the movement of tectonic plates. Tectonic activity is the process that leads to the building of oceanic ridges, so it will be beneficial for us to take a closer look at this process. To strengthen our understanding, let's take a quick look at how the Earth is put together. The Earth has an outer crust. When you look at a continent or the ocean floor, you are looking at the Earth's crust. Beneath the crust is the mantle. The crust and the upper part of the mantle make up the lithosphere, which is the outermost shell of the Earth. The lithosphere extends approximately 60 miles below the Earth's surface and is fractured into sections. These plate-like sections of lithosphere are called tectonic plates or lithospheric plates. Below the lithosphere, there is a zone of mantle that consists of semi-solid rock that is very hot and deformable, known as the asthenosphere. Because this layer is hot and deformable, the plates of the lithosphere are able to slide over top of it, somewhat like pucks slide over top of an air hockey table. If the plates move away from each other, a gap is created. Hot molten rock called magma from the asthenosphere can push up through this gap, and this is the beginning of the formation of an oceanic ridge. Magma is the molten rock material that we associate with volcanoes, and essentially what is happening when magma rises up through gaps between the tectonic plates is an underwater volcano. Because these volcanoes erupt into the relatively cool ocean waters, the magma solidifies along the ocean floor and creates new layers of ocean crust. As the magma continues to flow, layers of cooled magma continue to build, forming the Rocky Mountain-like oceanic ridges, or mid-ocean ridges, as they are sometimes referred to as. It might help you to recall how oceanic ridges are formed by relating the newly formed rock to a newly formed scab over a cut on your finger. If you cut your finger deep enough, blood will flow out of the wound. This flow of blood is much like the flow of magma from the gap on the ocean floor, caused by the separation of the lithospheric plates. As the cut heals, it forms a raised scab. As the flow of magma cools, it forms a raised layer of crust on the ocean floor. The oceanic ridges of the world are connected and combine to form the Oceanic Ridge System, making it the longest mountain range in the world, with a total length of approximately 50,000 miles. The continuous Oceanic Ridge System is distributed around the globe, and parts of it can be found in every ocean. The ridge system travels down the center of the Atlantic Ocean, but in the other major oceans it tends to meander on a course that is at times off-center and somewhat near land masses. Let's review. The Oceanic Ridge System is a continuous mountain chain located under the surface of the sea. Parts of this vast mountain range can be found in all of the major oceans of the world, including the Atlantic Ocean, where its course follows a path down the middle of the ocean. The Earth contains an outer crust that covers a deeper layer called the mantle. The lithosphere is the outermost shell of the Earth and is composed of the crust and the upper part of the mantle. Tectonic plates, or lithospheric plates, are plate-like sections of the lithosphere. Below the lithosphere, there is a zone of mantle that consists of semi-solid rock that is very hot and deformable, known as the asthenosphere. Tectonic plates can slide on top of the asthenosphere. At the boundaries between these plates, we see tectonic activity, which is the deformation of the Earth's crust due to the movement of tectonic plates. If the tectonic plates move away from each other, magma from the asthenosphere can push up through the gap, causing an underwater volcano. The magma cools and solidifies, creating new layers of ocean crust that continues to build, forming the oceanic ridges. Did you ever wonder why ocean water is so salty? Did you know that the freezing point of ocean water is not 32 degrees Fahrenheit like ordinary fresh water? Did you know that ocean water is actually layered and that dense ocean water sinks to the bottom while lighter water floats on top? Ocean water has some unique properties, and in this lesson you will learn about the properties of ocean water, including salinity, temperature, and density. Now, if you look at Earth from space, you will notice that much of the planet is covered in water. The vast majority of this water, about 97%, is found in oceans, and we cannot use it for drinking, cooking, or watering our flowers. The reason this water is not useful in these ways is because it has a high salinity, which is the amount of salt dissolved in water. In other words, ocean water is salty. If you ever went swimming in the ocean and accidentally took a big gulp of ocean water, this fact was unpleasantly obvious. But why is ocean water salty? Well, most of the salt that ends up in the oceans originated on land. Rain, as well as moving water in rivers and streams, washes over rocks containing the mineral sodium chloride, which you know as common table salt. The salt is then carried into the oceans. Salt can also find its way into oceans through underwater volcanoes that stir up salt and other minerals from deep layers of the earth. The salt in oceans becomes more concentrated over time as water from the surface of the ocean evaporates, leaving the salt behind. Salt is the main chemical ingredient in ocean water, but it also contains other chemicals such as magnesium, sulfate, calcium, and potassium. Many scientists believe that life began in the oceans, so it's not surprising that chemicals found in seawater are important chemicals needed to sustain life. There are also gases dissolved in ocean water, including nitrogen, oxygen, and carbon dioxide. Nitrogen is found in fertilizer and used to enhance the growth of plants in a farmer's field. If nitrogen-containing fertilizer runs off of farmers' fields and makes its way into ocean waters, it can cause some ocean plants to grow like crazy. These plants end up using more than their fair share of dissolved oxygen, which can suffocate other ocean creatures such as crabs and fish. This illustrates one way human activities impact the oceans. Oceans act as carbon sinks, which means that they are natural environments that absorb and store carbon dioxide. So oceans remove carbon dioxide, which is a greenhouse gas, from the atmosphere, making them important players in the study of global climate changes. Oceans have a wide range of temperatures. The temperature is highest at the equator and grows increasingly colder as the water approaches the poles. Compared to air, ocean water has a very high heat capacity. This means that there is more energy required to change the temperature of water. In other words, it takes a long time for the sun's energy to heat the ocean waters, and once the ocean is heated up, it takes a long time for the water to fully release that heat. We also see that the freezing point of ocean water is lower than that of fresh water. Ocean water freezes at about 28 degrees Fahrenheit, which is a few degrees colder than the 32 degrees it takes to freeze fresh water. The reason for this goes back to our discussion on salinity. As the amount of salt in a body of water goes up, the freezing point goes down. Another physical property of ocean water to consider is its density, which is the relative weight of water with a constant volume. Ocean water density depends mainly on its temperature and salinity. Very salty ocean water is denser than less salty ocean water, and cold ocean water is more dense than warm ocean water. So cold, salty water will be denser or heavier and sink to the bottom of the ocean below less dense water layers that float on top. Let's review. Ocean water has a high salinity, which is the amount of salt dissolved in water. Besides the high concentration of sodium chloride, ocean water also contains chemicals such as magnesium, sulfate, calcium, and potassium, as well as dissolved gases including nitrogen, oxygen, and carbon dioxide. Ocean waters range in temperature and have a very high heat capacity, which means that there is more energy required to change the temperature of water. We also see that the freezing point of ocean water, which is about 28 degrees Fahrenheit, is lower than that of fresh water due to the higher salinity of ocean water. Ocean water density, which is the relative weight of water with a constant volume, depends mainly on its temperature and salinity. Cold, salty water is denser and sinks to the bottom of the ocean below less dense water layers that float on top. When you look out over the ocean, it appears to be nothing more than a big basin filled with water. So it's hard to imagine that under the surface of the water there is a rich, biologically diverse community of organisms.
These ocean-dwelling organisms, known as marine organisms, live in a variety of underwater habitats, and the habitats vary based on the chemical and physical properties of that section of ocean.
In fact, properties such as the salt content of the water, temperature, light penetration, and ocean currents dictate where different marine organisms live within the vast oceans of planet Earth. In this lesson, you will learn about the varied and somewhat bizarre organisms that inhabit the world under the sea. Oceans are home to all sizes of creatures, from microscopic organisms to the world's largest animals. Let's start our discussion with some of the tiniest marine organisms there are, called plankton. Now, if you watch a lot of cartoons, you know Plankton is a fictional character that has a recurring role on the TV show SpongeBob SquarePants. But in marine biology, plankton are described as small or microscopic organisms that float in collective groups near the surface of the water. Plankton are at the mercy of the ocean currents because they do not have the ability to swim. In fact, it might help you to recall the definition of these tiny organisms by remembering that the word plankton comes from the Greek language and means wandering. Basically, plankton wander or drift along near the water surface and try not to get eaten by bigger marine organisms. Some plankton are tiny plants, and like plants on land, they use sunlight for photosynthesis. Photosynthesis, you may recall, is the process that uses sunlight to make food from carbon dioxide and water and generates oxygen as a byproduct. Other plankton are tiny animals or immature stages of larger marine animals. Now, you have likely heard of seaweed before and maybe have even eaten some wrapped around a sushi roll. But did you know that seaweed is actually a type of marine algae? Seaweed and many other types of marine algae have large flat surfaces that make them well suited for capturing sunlight, which they use for photosynthesis. There is a great diversity of plants and algae that grow in the ocean environments. Non-algae plants, such as grasses and mangroves, can be found growing in shallow ocean waters and provide habitats and foraging sites for coastal animals. Many of the more unusual creatures of the sea are classified as invertebrates. The prefix "in" means lacking, and the suffix "vertebrate" refers to having a backbone, so invertebrates, by definition, are lacking a backbone. Invertebrates are abundant in the ocean waters, and this might be because the ocean waters buoy them, making a backbone an unneeded feature. Invertebrates seem to glide and move with fluidity through their watery environment, and they come in many varieties. We see the classification of marine invertebrates include the slithering sea worms, the umbrella-like jellyfish, and the colorful sea anemones. Invertebrates also include shellfish, squid, octopus, and starfish. Even though starfish have the word fish in their name, they are not actually fish because fish have backbones, making them vertebrates. There are many varieties of fish in the marine environment, including the tasty sardines and anchovies, as well as sharks and barracudas. Even though fish are varied, they share many features that allow them to live underwater. For example, they have fins that they use for propulsion, gills to extract oxygen from the water, and protective scales covering their bodies. Many fish also have swim bladders, which are like internal air balloons that they can use to control buoyancy as they move to different depths within the water. Ocean waters can get mighty cold, so it's surprising to learn about just how many warm-blooded mammals make their homes in the oceans. Marine mammals, including whales, dolphins, manatees, sea otters, seals, and walruses, share many characteristics with land-dwelling mammals, including you and me. For instance, All mammals, whether they live on land or under the water, give birth to live young and feed their young with milk. But marine mammals have some adaptations that allow them to live in the harsh ocean environments. These adaptations include fur and a high fat content for warmth. They also have skin that is impervious to the salty seawater. A discussion of marine organisms would not be complete without mentioning reptiles and seabirds. Although few reptiles and seabirds live in or spend long periods in the oceans, many rely on oceans for food. Seabirds, such as albatross and gulls, develop adaptations that help them thrive in marine environments, such as long legs that help them wade along the shallow water's edge and long bills for digging up shoreline creatures to eat. Reptiles, such as sea turtles, crocodiles, and marine iguana, feed in marine areas and also lay their eggs on the ocean shores. Let's review. Marine organisms are ocean-dwelling organisms. They live in different underwater habitats that are based on properties such as the salt content of the water, temperature, light penetration, and ocean currents. Some of the tiniest marine organisms are plankton, which are small or microscopic organisms that float in collective groups near the surface of the water. Some plankton are tiny plants and use sunlight for photosynthesis, while other plankton are tiny animals or immature stages of larger marine animals. Plants and marine algae, such as seaweed, also capture sunlight for photosynthesis. Plants such as grasses and mangroves can be found in shallow ocean waters. Invertebrates are lacking a backbone and can be found in abundance in the world's oceans. Marine invertebrates include seaworms, jellyfish, sea anemones, shellfish, squid, octopus, and starfish. Fish are vertebrates that are found in marine environments. Examples of ocean fish include sardines, anchovies, sharks, and barracudas. Fish have features that allow them to live underwater, such as fins, gills, scales, and swim bladders. Ocean waters are also home to a variety of marine mammals, including whales, dolphins, manatees, sea otters, seals, and walruses. Marine mammals have some adaptations that allow them to live in the harsh ocean environment, including fur, a high fat content, and skin that is impervious to the salty seawater. Seabirds, such as albatross and gulls, have adaptations such as long legs and long bills to help them feed from ocean environments. Reptiles, such as sea turtles, crocodiles, and marine iguana, feed in marine areas and also lay their eggs on the ocean shores.
The ocean is a very complex system, and it is never at rest. Ocean currents travel around the planet and go through a lot of ups and a lot of downs along their journey. Because ocean waters are so good at holding heat, and because the currents are constantly circulating massive amounts of water, oceans are major players in any discussion on global climate. In this lesson, you will learn about the patterns ocean currents take and how they affect climate. Ocean currents travel at both the surface of the ocean as well as deep within the ocean basin. Currents are influenced by factors such as wind, the rotation of the Earth, differences in the water's salt content, temperature, and density, and even the shape of the ocean floor. Surface ocean currents are strongly influenced by the wind. Prevailing winds, which are winds that blow predominantly from a particular direction, flow across the ocean surface, pushing the water in large circular ocean currents, called ocean gyres. It might help you to recall this term if you remember that the word gyre is Latin for circle, which is the pattern these surface currents take. Or maybe you played with a gyroscope when you were a kid, which was a wheel-shaped science toy that could spin on its base in all kinds of crazy ways without falling off. Ocean gyres are present in every ocean and move water from the poles to the equator and back again. The water warms at the equator and cools at the poles. Because ocean water temperatures can transfer to the air, the cold and warm waters circulated by the gyres influence the climate of nearby land masses. Gyre circulation is influenced by the Coriolis effect, which is a phenomenon created by the rotation of the Earth that causes rotation in a clockwise direction in the northern hemisphere and counterclockwise in the southern hemisphere. Along wind-blown coastlines, we may see areas of upwelling. Upwelling is the rising of cold, nutrient-rich water to the surface. As winds blow along the coast, they move the relatively warm surface water. This allows colder and nutrient-rich waters from the ocean floor to rise up and take its place. The ocean's bottom waters are rich in nutrients because sea plants and creatures decay and release their nutrients onto the ocean floor. As these waters rise up, they feed marine organisms in the area, so upwelling areas are usually rich in marine life. Deep ocean currents are strongly driven by the density of the ocean waters, and the density of ocean water is mainly dependent on the water's temperature and salinity, or salt content. Basically, the colder and saltier the ocean water is, the denser it will be, making it sink toward the ocean floor. Thermohaline circulation is the largest ocean circulation pattern and is directly related to temperature and salinity. In fact, if you break the word thermohaline down, you see that the prefix thermo refers to temperature or heat, and the suffix haline refers to salinity. So the thermohaline circulation pattern is driven by changes in water temperature and salt content. The thermohaline circulation is sometimes referred to as the global ocean conveyor belt because it moves water on a path through the world's oceans as if it were on a giant conveyor belt that travels the entire globe. As you can imagine, this current moves a massive amount of water and distributes heat along its way, which in turn influences the global climate. Now, we mentioned that the thermohaline circulation is dependent on the temperature and salinity of the water, and we know that cold, salty water is more dense or heavier and therefore sinks. With this knowledge, we can understand how the water flows in this circulation pattern. The pattern begins in the frigid northern waters near Iceland, where the ocean water is cold and salty. This cold, salty water is dense and starts to drive the current. The current moves on a path southward across the equator and down the coast of South America. Along its travels, the current builds and picks up momentum, and by the time it nears Antarctica, it is massive. The current moves along the bottom of the world and splits, with one branch entering the Indian Ocean and the other entering the Pacific Ocean. The branches of circulating water warm in these oceans and then rejoin as they turn west and get drawn back up to the polar regions where they began their journey. And quite a journey it is. If you were an individual water molecule traveling the thermohaline circulation, it would take you nearly 1,000 years to go from start to finish. This is a long time, but the thing to remember is that there is a continual cycle of heat and energy that affects everything from the climate around the world to your local weather forecast. Let's review. Prevailing winds, which are winds that blow predominantly from a particular direction, flow across the ocean surface, pushing the water in large circular ocean currents called ocean gyres. The circulating waters transfer heat to the air, which affects the climate of nearby land masses. The gyres are directed by the Coriolis effect, which is the phenomenon created by the rotation of the Earth that causes rotation in a clockwise direction in the northern hemisphere and counterclockwise in the southern hemisphere. Along wind-blown coastlines, we may see areas of upwelling, which is the rising of cold, nutrient-rich water to the surface. Thermohaline circulation is the largest ocean circulation pattern and is directly related to temperature and salinity. This current moves a massive amount of water and distributes heat along its way, which in turn influences the global climate. The circulation pattern begins in the cold, salty waters near Iceland. It moves south toward Antarctica and then moves along the bottom of the world before splitting into branches that travel into the Indian Ocean and Pacific Ocean. The branches of water rejoin as they turn west and get drawn back up to the polar regions where they began. The shoreline is the line along the edge of the ocean where land meets the water. It is a dynamic place that is always changing due to forces acting upon it from waves, currents, and winds. These forces erode rocky coastal structures and deposit sand and sediment in characteristic patterns, making shorelines a fun place to explore for young and old alike. In this lesson, you will learn about the different features found along shorelines and how they are molded and formed by these forces. Many shorelines are irregularly shaped with frequent outcroppings of rock separated by carved inlets of water. A headland is a narrow strip of land that projects out into a body of water. These outcroppings are often rocky, and because they project out into the ocean, they are subjected to the constant pounding of waves. Waves cut into the headlands, leaving behind caves, notches, and cliffs. If you ever watched a cliff diver leap into the ocean or a pirate movie where the treasure was stashed in a cave along the ocean, then you were most likely looking at a headland that had been carved and shaped by ocean waves. The eroded material from the headlands is carried into bays, which are recessed bodies of water along the shoreline. Because waves have lost a lot of their energy by the time they enter bays, sand and sediment is allowed to settle in these areas. This can create a beach, which is an area at the edge of the shoreline that is covered with sand or pebbles. Beaches are the areas where most people spend their time when they vacation at the shore. These are the areas where you can plant your beach umbrella in the sand and build sandcastles. But beaches themselves have some characteristic features. The foreshore is the area of the beach that lies between the low and high tide marks. It rises out of the water and abuts up against the next feature known as the beach berm, which is the area of the beach mostly above water that is formed by different levels of wave activity. On a broad beach, there may be different levels of beach berms, each created by a different wave condition. A beach berm flattens out and achieves a somewhat horizontal or backward sloped position as it projects toward the back area of the beach. Some beaches may also contain sand dunes farther inland. Sand dunes are mounds of sand formed by the wind. Newly formed sand dunes are constantly molded and altered by the wind, but older and more established sand dunes are stabilized due to vegetation that grows on them and holds the sand in place. Sand dunes can protect inland areas from the harsh ocean conditions. How sand and sediment is deposited on a beach is in large part due to the longshore drift, which is the process by which sand and sediment is transported along the coast. The longshore drift is influenced by the angle of waves hitting the shore and currents along the shore. It can carry large amounts of sediment along the length of the shoreline and create offshore sandbars. For example, a spit is an elongated sandbar that extends from the coast into the mouth of an adjacent bay. It gets its shape thanks to deposits of sand carried by the longshore drift. If sand settles between two land masses, it may form a tumbelow, which is another shoreline feature that can result due to the movement of sand and is defined as a mound of sand that joins an island to the mainland. If you have ever walked out to an island from the mainland, you were walking on a tumbelow. If wave and current conditions deposit sand and sediment out in the ocean, a barrier island might form. A barrier island is a sandbar that runs parallel to the coast but remains separated by water. If you stand on the shoreline and look out into the ocean at a barrier island, it's easy to imagine it looking like a wall or barrier protecting the mainland from the harsh ocean waves. This makes it easy to recall its name. Because barrier islands are separated from the shoreline, they can create a separate body of water known as a lagoon. A lagoon is defined as a shallow body of water separated from the ocean by a barrier island or sandbar. Lagoons may be fed by inlets cut through the barrier island that allow water to enter and exit the lagoon, but because they are somewhat protected from ocean waves, they are calm and quiet bodies of water. Let's review. The shoreline is the line along the edge of the ocean where land meets the water. Many shorelines are irregularly shaped and contain an outcropping of rock known as a headland, which is a narrow strip of land that projects out into a body of water. These outcroppings are subjected to the constant pounding of waves. The eroded material from the headlands is carried into bays, which are recessed areas of water along the shoreline, where wave energy is low. This low wave energy allows sand to deposit and can create a beach, which is an area at the edge of the shoreline that is covered with sand or pebbles. Beaches have some characteristic features, including the foreshore, which is the area of the beach that lies between the low and high tide marks. It rises out of the water and abuts up against the beach berm, which is the area of the beach mostly above water that that is formed by different levels of wave activity. Some beaches may also contain sand dunes farther inland. Sand dunes are mounds of sand formed by the wind. The longshore drift is the process by which sand and sediment is transported along the coast. It can create sandbars, such as a spit, which is an elongated sandbar that extends from the coast into the mouth of an adjacent bay, a tombolo, which is a mound of sand that joins an island to the mainland, and a barrier island, which is a sandbar that runs parallel to the coast but remains separated by water. Because barrier islands are separated from the shoreline, they can create a separate body of water known as a lagoon, which is a shallow body of water separated from the ocean by a barrier island or sandbar. Ocean waves are powerful forces that erode and shape the world's coastlines. Most are created by the wind. Winds that blow over top of the ocean create friction between the air and water molecules, creating a frictional drag that shows up as waves on the surface of the ocean. The more forcefully the winds blow, the larger the waves grow. Ocean water is always in motion. Yet it is interesting to note that an ocean wave is not representing a flow of water. While ocean waves transport energy over vast distances, only a small amount of water within the wave is actually moving in a horizontal direction. Instead, the water within the wave is simply moving up and down. This is why a buoy set out in the middle of an ocean bobs up and down, but does not travel with the waves. In this lesson, you will learn more about the features of waves as well as the different types of waves and their erosive effects on coastlines. Now, if you blow across the top of the coffee in your coffee cup, you are creating miniature waves. Look closely and you will notice that the waves of coffee rise and fall. The highest point of the wave is called the wave crest, and the lowest point of the wave is called the wave trough. Waves vary in size due to the force and speed of the wind blowing over the surface. Yet they move together in groups that move across the fluid surface at the same speed and in regular intervals. This movement of waves as a group is known as a wave train. There are different types of ocean waves. The waves we have been discussing so far are referred to as wind waves, or simply waves that are created by wind. These wind-driven waves begin as ripples, which are small and have the shortest period of time between successive wave crests. They increase in size if wind gets stronger. If heavy winds from tropical storms or other wind systems drive the waves, they can create ocean swells that are capable of traveling long distances over entire ocean systems. Ocean swells are defined as mature undulations occurring in open ocean waters. Even though swells often get their start from storm winds, they can be found far distances from the region where the waves were first generated. And while they can range in size from small ripples of water up to 10 or more feet, they are generally what you think of when you imagine a fishing boat or buoy bobbing up and down in the open ocean waters. A tsunami is a type of wave that is not started by the wind. It is defined as a series of waves caused by an earthquake, underwater volcanic eruption, landslide, or other abrupt disturbance. Tsunamis can result in massive destruction when they arrive on shore. This fact became evident in March of 2011 when Japan was struck by a large tsunami that was triggered by a 9.0 magnitude earthquake. The tsunami claimed the lives of more than 15,000 people, damaged several nuclear power plant reactors, and caused billions of dollars in damage. A tidal wave is another type of wave, and it's sometimes confused with a tsunami. A tidal wave is a wave caused by the tides. Because tides are predictable events that are created by the moon's gravitational pull, tidal waves, unlike tsunamis, are predictable events. As the different types of ocean waves reach the shallow waters near the shore, they begin to interact with the ocean floor, causing the waves to slow down and increase in height. As the waves continue towards shore, they become less stable and eventually break. There are two main types of breaking waves, and their classification depends on the slope of the shoreline. A spilling breaker is a type of breaking wave that occurs on flatter shores. Because the wave enters the shoreline on a gradual slope, it dissipates its energy more evenly and basically spills onto the shoreline. A plunging breaker is a type of breaking wave that occurs on steeper shores. Because the shore is steep, the wave crest curls and plunges down over the front of the advancing wave. Plunging breakers are the waves preferred by surfers. Waves are powerful forces that continually pound on the shoreline. They cause the erosion of shoreline features and the transport of sand and sediment along the coast. Yet waves rarely strike the shore directly. Instead, we see a phenomena called wave refraction, which is the bending of waves as they travel toward the shallow waters of the shore. This causes the wave's energy to spread out, and we see that shoreline features that project out into the water, such as headlands, receive the full force of the wave's energy, subjecting them to the most erosion. While this erosion tends to break down outcroppings and straighten coastlines over time, it also creates some of the most interesting and unique shoreline features. As waves attack headlands, they chip away at the rocky structures, leaving behind steep, rocky cliffs, hollowed-out caves and sea arches, and pillar-like sea stacks. The sand and sediment that comes from the eroding coastal structures settles into recessed bodies of water along the shoreline where wave energy is low. If this sand and sediment settles on land, it forms a beach. If it settles out in the water, it forms a type of sandbar, such as a spit, tombolo, or barrier island. Let's review. The highest part of the wave is called the wave crest, and the lowest part of the wave is the wave trough. Waves travel together, and this movement of waves as a group is known as a wave train. There are different types of ocean waves. Wind waves are waves that are created by wind. If heavy winds from tropical storms or other wind systems drive the waves, they can create ocean swells, which are mature undulations occurring in open ocean waters. A tsunami is a series of waves caused by an earthquake, underwater volcanic eruption, landslide, or other abrupt disturbance. A tidal wave is a wave caused by the tides. As ocean waves reach the shallow waters near the shore, they break. A spilling breaker is a type of breaking wave that occurs on flatter shores. A plunging breaker is a type of breaking wave that occurs on steeper shores and is a type preferred by surfers. Waves rarely strike the shore directly. Instead, we see wave refraction, which is the bending of waves as they travel toward the shallow waters of the shore. Because of this, we see that headlands, which are shoreline features that project out into the water, receive the full force of the wave's energy. This creates unique shoreline features such as cliffs, caves, sea arches, and sea stacks. The sand and sediment that comes from the eroding coastal structures settles on land to form a beach, or in the water to form a type of sandbar, such as a spit, tombolo, or barrier island. There are few things in nature as predictable as the tides, which are the periodic rise and fall of ocean waters. Tides are so reliable because their movements are based on the positioning of the moon and sun in relation to the earth. These celestial bodies do not change their patterns, so it's easy for us to predict when the tides will rise and fall today, tomorrow, and even next year and beyond. In this lesson, you will learn more about how the moon and sun cause the tides and the effects tides have on coastal regions. Because the moon is closer to the earth than the sun, it has the most influence on the tides. In fact, it's fair to say that tides would not occur if the earth and the moon were not attracted to each other. Of course, I'm not referring to a love-hate type of attraction, but rather the gravitational attraction between the two bodies. The gravitational pull of the moon causes the oceans and other major water bodies to bulge out toward the moon. When the gravitational pull is at its highest point, the result is high tide, which is the highest level of the tide. When the pull is at its lowest point, we see low tide, or the lowest level of the tide. The Earth itself is also pulled toward the moon, but with less strength. This pulls the Earth away from the water on the opposite side of the Earth, making the water on that side bulge as well. Therefore, high tide occurs on both sides of the planet at the same time. Meanwhile, the Earth is rotating,
so we experience tides throughout the day. Now, if the Earth were perfectly round with no big land masses, all bodies of water in the world would experience 2 nearly equal high tides and 2 low tides each day. This tidal pattern is known as semi-diurnal tides. However, the continents of Earth disrupt water bodies, and so this can produce different tidal patterns. For example, some bodies of water, such as the Gulf of Mexico, have diurnal tides, which means only 1 high tide and 1 low tide each day. You can recall these terms by remembering that the word diurnal means happening daily. Therefore, we see that diurnal tides happen once a day, and if we add the prefix semi, which means half, we can understand that semi-diurnal tides happen every half a day. The Earth and Moon are constantly in motion around the Sun, and all have their own gravitational pull. So when the alignment between the 3 bodies changes, it changes the strength of the overall gravitational pull and therefore the size of the tides. Spring tides are tides that occur when the Earth, Moon, and Sun are aligned and the tidal range between high and low tide is at its maximum. This happens basically twice a month, during the full and new moon phases. At these times, the 3 bodies are in line and their gravitational pulls reinforce each other. When the spring tide is happening, we see higher than average high tides and lower than average low tides. It's important to point out that spring does not refer to the season. Instead, you can recall the meaning of spring tides by thinking of them as the tides that spring out and then spring back with the most intensity. A few weeks after the spring tides, we see the neap tides. These are tides that occur when the Moon and Sun are at right angles to the Earth's orbit and the tidal range between high and low tide is at its minimum. The neap tides occur when the Moon is in its first and last quarter phase. Because of the position of the Moon and Sun, their gravitational pulls on the waters of the Earth partially cancel each other out, resulting in smaller differences between the high and low tides. Tides affect coastal regions in different ways. High tides push large amounts of water far up onto beaches and leave the sand and sediment mixed with the water behind when the tide goes out. Therefore, tides transport sand and sediment and shape shorelines. Tides feed estuaries. Estuaries are coastal areas where fresh water mixes with ocean water that is delivered by the tides. High tides bring nourishing sediment and sea life into estuaries. Estuaries are home to biologically diverse and unique plant and animal communities because their waters contain a mix of fresh water and salty ocean water. Tides can present challenges to coastal regions, especially during storms. Storms that form out in the ocean intensify waves. If the storm waves come ashore at high tide, tides can worsen damage and erosion caused by storm waves. Tides can also be a source of energy. Tides provide tidal power. Tidal power is energy obtained from the rise and fall of tides. Tides move massive amounts of water toward and then away from shore. The energy of the moving water can be harnessed by placing turbines in the path of the moving water. These turbines can be connected to generators that create a renewable source of electricity. Tides are the periodic rise and fall of ocean waters. The gravitational pull of the Moon and Sun create the tides. When the gravitational pull is at its highest point, the result is high tide, which is the highest level of the tide. When the pull is at its lowest point, we see low tide, or the lowest level of the tide. Tides are predictable, and there are different tidal patterns in different areas of the world. Some areas experience semi-diurnal tides, which are 2 nearly equal high tides and 2 low tides each day. Other areas may experience diurnal tides, which are only 1 high tide and 1 low tide each day. Spring tides are tides that occur when the Earth, Moon, and Sun are aligned and the tidal range between high and low tide is at its maximum. This happens during the full and new moon phases. Neap tides are tides that occur when the Moon and Sun are at right angles to the Earth's orbit and the tidal range between high and low tide is at its minimum. The neap tides occur when the Moon is in its first and last quarter phases. Tides affect coastal regions in different ways. For example, they transport sand and sediment and shape shorelines. They also feed estuaries, which are coastal areas where fresh water mixes with ocean water that is delivered by the tides. Tides can worsen damage and erosion caused by storm waves, but they can also provide tidal power, which is energy obtained from the rise and fall of tides. Let's say you and some friends were playing volleyball on the beach, and the ball got knocked out of the court and landed in the swash zone, which is the area at the water's edge where waves lap up onto the beach. If you watched the ball for a few minutes, you would probably notice that it not only moved in and out with the waves, but it also got carried down the shoreline. The volleyball moving down the beach represents part of something called the longshore transport. Longshore transport is defined as the movement of sand and sediment parallel to the coastline. In this lesson, you will learn how processes such as beach drift and the longshore current contribute to longshore transport, and how these processes shape the shorelines of the world. The shoreline is constantly changing as sand and sediment is picked up and deposited along the shore by waves. Waves tend to come ashore on an angle, as opposed to straight on, because they're pushed and bent by influences such as the wind and the shallow waters near the shore. As these angled waves come ashore and break, they create the longshore current, which is defined as the ocean current that travels parallel to the shore. You might see the longshore current referred to as the littoral current. The word littoral comes from the Latin language and means shore. So whether it is called the longshore or littoral current, it is the current that flows along with the shore. As the angled waves reach the shoreline, they push water, sand, and sediment in one direction, down the length of the beach. Longshore currents occur along any beach that is exposed to breaking waves, and the currents vary in strength depending on the shape and characteristics of the beach. For example, on a long, straight beach with prominent waves and swells, the longshore current can be very strong and pose a threat to swimmers and surfers. A strong longshore current can sweep a person down the coast and make it difficult for that person to make it back to shore. This is one reason it's a good idea to swim at beaches manned by lifeguards. The longshore current is part of the longshore transport that moves sand and sediment down the coastline. But there is another process that contributes to the longshore transport called beach drift or longshore drift. Beach drift is defined as the progressive movement of sand and sediment along the beach. This is an easy term to recall if you remember that beach drift is what causes sand and other particles to drift down the beach. In fact, beach drift is what carried our volleyball down the beach at the beginning of our lesson. As the water waves continually lap up on the swash zone of the shore, they carry with them stirred up grains of sand and other particles. The water that moves on shore from the waves is referred to as swash. This is one of those fun terms to learn because you can think of it as if the ocean is taking a bucket of water from its vast supply and splashing or washing it onto the beach, in other words, swashing it ashore. Swash comes up on shore at an angle because the waves that carry the water strike the shore at an angle. So we see that the sand and other particles caught up in the wave get carried ashore in the same direction as the wave's motion. But the swash is pulled back into the ocean under the force of gravity, so it returns to the ocean in a straight path that is perpendicular to the shoreline. The receding water moving off of the beach and washing back into the ocean is referred to as backwash. So we see that the swash flows onto the beach at an angle carried by the waves, but the water returns to the ocean in a direction that's perpendicular to the shore. Because of this, the sand and sediment is continually deposited in a zigzag pattern down the beach. This is the beach drift in action. And because the waves that wash up on shore are driven by the longshore current, we see that beach drift and longshore current work together to create the longshore transport, resulting in a net overall transport of sand and sediment down current along the coast. Let's review. Waves tend to come ashore on an angle, and this helps create the longshore current or littoral current, which is the ocean current that travels parallel to the shore. The swash zone is the area at the water's edge where waves lap up onto the beach. and the term swash is used to describe the water that moves on shore from the waves. Swash comes ashore at an angle equal to the angle of the waves. However, backwash, which is the receding water moving off of the beach and washing back into the ocean, returns to the ocean in a straight path that is perpendicular to the shore. This creates the zigzagged pattern of beach drift or longshore drift, which is the progressive movement of sand and sediment along the beach. Beach drift and the longshore current contribute to the longshore transport, which is the movement of sand and sediment parallel to the coastline.
Humans have always had a thing for being near the water. In ancient history, many of the greatest civilizations used seas and oceans for trade and conquest. Crossing the Atlantic Ocean opened the idea of globalization for all people. Most recently, coastlines have been transformed into high-priced real estate. However, this has all come with quite a bit of impact. In this lesson, we are going to look at the impact of humanity on the coastlines of the world. We will see how our interest in that thin strip of surf and sand has, in many ways, endangered its survival, as well as some of the steps that we are now taking to solve those issues. Every year, millions of people go to the beach. If you're like me, it's all about the seafood, but I guess there's something to be said about lying on the sand and getting sunburned. Regardless, places like Daytona Beach in Florida and the Costa del Sol in Spain transform into stunning grounds for those who just need some time to get away from it all. However, the huge number of visitors have many impacts on beaches. Litter is the most obvious impact, as many people are not exactly considerate when it comes to disposing of their waste. Still, other impacts are less evident. People also have the potential to disrupt fragile processes like sea turtle births and sand dunes. For example, artificial lighting near beaches can hurt the chance of survival for sea turtle hatchlings because it disorients them, making it harder to successfully reach the ocean. Also, sand dunes are hills of sand shaped by wind and found along some shorelines. They act to protect the inland from abnormally high tides, all while harboring their own delicate ecosystems. But they cannot do so nearly as well after being trampled by beachgoers. To stop all this from happening, many beaches are starting to take action. Littering fines have been raised, as have protections for marine life. Stretches of beach are often closed when sea turtles are laying eggs, and when those eggs are hatching so as to not impede on other life. Sand dune ecosystems are also gaining significant protections. In some jurisdictions, even walking on protected areas of the dunes is illegal. Still, more people live in cities on the waterfront than ever visit the beaches. Simply put, a waterfront is part of a city that borders a large body of water. From Shanghai to New York, many of the world's largest cities have waterfront properties. For years, this meant that coastlines suffered. The idea of out of sight, out of mind governed many cities' approach to how to get rid of waste, and dumping it into the ocean seemed to be the perfect idea. Also, as transportation across the waves grew into a bigger practice, there were more waste products near the water. Finally, with the construction of large factories, some businessmen simply dumped hazardous chemicals onto the shoreline. Now things in most places are very different. Strict rules govern what can go into the water. Cities get publicly ranked on water pollution, and citizens are unlikely to stand for a smelly waterfront. Also, cities grew to embrace their shorelines as a place to be proud of. Today, you'll often find some of the nicest buildings of a city along its coastline. From beaches to waterfronts and everywhere in between, a constant worry along coastlines is erosion. Coastal erosion is the removal of land along a coastline. Remember those sand dunes being protected? It wasn't just that the sand dunes kept water from flowing inland, but they also stopped eroded materials from going out to sea. While it may sound harmless, all that dirt could really mess up the coastline, not allowing any fish to live out there because the water was too dirty. On the other hand, in places where the shoreline was not well taken care of, a strong storm could simply wash it away, leaving houses and businesses that were once safe very vulnerable to the next storm. To this end, defeating coastal erosion is now on the top of many people's agendas. Sand dunes remain a very valuable tool in order to keep erosion from happening. However, it's not just the height of the sand dunes that helps reduce erosion. Sand dunes have many grasses and shrubs, and even sometimes trees growing on top of them. These help secure the sand, making sure that it can do a better job of guarding against erosion. This also reduces the chances that a shoreline will be washed away. The layout of the beach may change, but the sand dunes provide a wall against further change. In this lesson, we looked at how humans interact with coastlines. Beaches are a popular place to relax, but can become vulnerable to change without proper protection. Many cities have a waterfront, a part of a city that borders a large body of water, and human activity along these waterfronts impacts their coastlines. We have improved how cities interact with coastlines, but one of the biggest challenges is reducing coastal erosion, the removal of land along a coastline. Erosion is something that can really damage coastlines. Sand dunes are hills of sand shaped by wind and found along some shorelines, and they can help limit the effects of erosion by securing sand.
There are certain parts of science that are considered to be cemented in stone. For instance, no one really questions that gravity is what keeps us from floating around or that red blood cells carry oxygen. However, when science dabbles in the theories of man's origin, there is a lot left up for grabs. In other words, many different theories or suppositions abound, and more often than not, more questions are asked than answered. Keeping this in mind, our topic for today, the prehistoric migration of humans, is based in archaeological theories that often have the habit of being overturned as new discoveries are literally unearthed. For this reason, we'll stay rather general, realizing that even the dating of human migration is a hotly debated topic. After all, since prehistoric actually denotes the time before written record, most scientists admit they are working to put together a puzzle, oftentimes with little solid evidence on which to hang their hats. Beginning our discussion of human migration, paleontology, the study of fossils of animals from ancient times, specifically prehistoric times, asserts that human life began in Africa. Working to support this assumption, some of the earliest fossil records of Homo sapiens, or modern humans, have been found in the country of Ethiopia. With their dating being rather up for grabs, they are placed as belonging to a time frame of over 200,000 years ago. Moving away from origin and digging deeper into migration, archaeological record asserts that humans began migrating out of Africa about 60,000 years ago. Although no one can be certain why this migration occurred or when it occurred, many believe that a severe climate change may have been the catalyst, specifically the Ice Age, a prehistoric period marked by intense glacial activity. Continuing with this theory, it is asserted that the human population of the Earth drastically dropped during the first migration out of Africa. As the climate of the Earth started to stabilize, many believe that some humans began moving out of Africa, going into what is often coined Eurasia, the landmass made up of Europe and Asia. During this migration, it's believed that they crossed into Eurasia by way of a strait between the present-day small African nation of Djibouti and Yemen. From here, it's believed that these rather adventurous humans moved eastward into places like India, Southeast Asia, and even eventually Australia. Bringing our discussion back to the lands of Africa, some scientists believe a second wave of migrators left Africa a little bit later. However, these guys decided to travel by land, moving into the regions of today's Middle East and Central Asia. From these locations, these early humans were able to move into Europe and the more northern regions of Asia. Sticking with our travelers heading into North Asia, it's believed that these risk-takers braved the hazardous weather and continued north toward the East Asian Arctic region. It's asserted that there they found a large landmass that had most likely been created by the tumultuous weather of the Ice Age. Moving across this landmass, which connected Asia to the Americas, these travelers began the human trek, which would eventually find humans inhabiting from modern-day Alaska to the tip of Argentina. The word prehistoric denotes the time before written record. It is the job of paleontology, the study of fossils and animals from ancient times, specifically prehistoric time, to explain this era. According to paleontology, modern humans, or Homo sapiens, originated in Africa. However, it's asserted that the Ice Age, a prehistoric period marked by intense glacial activity, was an eventual catalyst for human migration out of Africa. With this, it's theorized that a first group of migrants moved out of Africa by way of a strait between modern-day Djibouti and Yemen. This saw the first human movement into Eurasia, the landmass made up of Europe and Asia. From here, the migrants moved into India, Southeast Asia, and even Australia. It's also theorized that a second group of humans later migrated out of Africa. However, it's asserted that this second wave saw humans moving by land into the modern-day Middle East and into Europe and more northern parts of Asia. Eventually, some of these migrants braved the weather of the Arctic and discovered a land bridge, which allowed them access into the Americas. From here, human migration continued all the way from Alaska to the tip of South America.
The term Ice Age refers to a period of time in which the surface of the Earth is covered with sheets of ice called glaciers. This does not mean that the Earth is one big snowball for an entire ice age. While this happens on occasion, most ice ages are made up of a series of warm and cold spells. In cold periods of glaciation, glaciers extend from poles toward the equator. And in warm periods of interglaciation, the glaciers retreat back to the poles. So while the term Ice Age might bring to mind images of woolly mammoths and saber-toothed tigers, it is important to remember that we are currently in an ice age, and have been for about 2.8 million years. We just happen to be in a period of interglaciation. Ice ages create new challenges for life by significantly altering the environment in which life forms compete. Ice ages lower the world's temperature, making it hard for cold-blooded animals to survive. Ice ages also tend to make the world a drier place by locking up the moisture in ice. This makes it difficult for plants to survive on land. This, in turn, makes it very difficult for land-dwelling animals to find food. Yet these challenges also present new opportunities. Mammals owe their current primacy to ice ages, wiping out much of their competition. And while most primates suffered from the reduction of lush rainforests into arid grasslands, one sub-branch of this family would abandon the protection of trees to wander the earth in search of food. These were the first hominids, ancestors of modern humans. I will spare you the details of our development as a species. What is important for this lecture is that at some point we stopped simply foraging and scavenging and began hunting, because at the time the most reliable sources of food were migratory herds. To keep up with these herds, our ancestors had to be as mobile as the animals they were hunting, so we developed longer legs and an upright form of walking. To outsmart and track those herds, we developed bigger brains. To take down large game, we combined those bigger brains with finer hands and teamwork and started making tools. In short, the challenges presented by the Ice Age forged man into the hyper-intelligent, highly adaptable, upright-walking, tool-generating creature we know today. And so now, we come to the latest period of interglaciation, a great thaw that began around 10,000 BCE. Human beings have been following the migrations of herd animals for thousands of years. The scarcity of plant life required herds to move constantly. The herds moved to find new vegetation to eat. The humans moved to follow the herds. With the thaw, plant life thrived again. Herds no longer needed to move such long distances to find fodder. Yet countless generations had made these migrations instinctive to herd animals. Human beings, on the other hand, had no such instincts to constrain them. They quickly realized that the animals they hunted would survive just as well without walking for thousands of miles every year. Now if only they could find a way to convince the animals to abandon their instincts. This marks the beginning of the domestication of animals. Human beings did whatever they could to break animals of their migratory habits. This proved easier with some animals than with others. Likely the first herd animal to be domesticated was the sheep. Sheep are smaller than humans and do not move very quickly. When a herd of sheep began to migrate, all it took were a few humans to restrain them and drive them back to more convenient pastures. Humans might have been helped in this process by the domesticated animal, the dog. The dog makes an excellent shepherd. He's fast, he's intelligent, he's deadly, and he's absolutely terrifying to your average herd animal, who thinks he's a wolf. These factors combined to make the dog an appealing ally even during our early days as hunters, which is probably when we first formed our alliance with the canine species. With the dog for an ally and ample vegetation for grazing, humans came to domesticate many of the large species on the planet: the sheep, the goat, the pig, the cow, the horse, the donkey, the water buffalo, the wide variety of camels, the yak, the reindeer, and even the elephant. Still, many species evaded domestication, being too ornery, too fierce, too independent, or too prone to panic to be controlled. Others required very specific diets that humans could not replicate, and still others simply refused to breed in captivity. Nevertheless, humans were able to break enough of the species of their migratory habits to allow us to settle in one place. Instead of humans following herds through their endless migrations, the herds would now follow the humans, leading them from pasture to pasture. This system is called pastoralism. Yet despite these advances, the shepherd must still move about, albeit in a much smaller circuit than migratory hunters. Though domestication had made these animals dependent on man, man was still dependent on those domesticated animals. The warming earth would soon provide another option: the domestication of plants through settled agriculture. Yet it is important to remember that without the domestication of animals, human beings would likely never have been able to stay put long enough to raise a crop of wheat without starving to death. So we've seen how humanity developed in response to the extraordinary challenges presented by the Ice Age. Equipped to survive the utmost scarcity, our species entered this warm period of abundance. The same adaptations that had allowed us to survive the depths of glaciation would enable us to dominate in this interglacial period. The brains we developed to find food would later come up with ways to make food. The hands we developed to make and use knives and spears would go on to construct the millions of tools we use today. Finally, the teamwork we needed to pull down a mastodon would allow us to build cities, states, and empires. Most of us are familiar with the tale of Noah and the flood. For those of you who aren't, here's a quick recap. God decides to flood the earth. So he warns Noah of the impending flood. God orders Noah to build an ark, providing specific instructions about the dimensions and materials to be used. In the ark, Noah is to gather his family and 2 of every animal. Noah does as he is told. He builds the ark, gathers his family, and marches all the animals on board, 2 by 2. Then it starts to rain. God makes it rain for 40 days and 40 nights, flooding the earth. Noah, his family, and the animals he'd gathered are the only survivors. After the rains had stopped, Noah released a raven, which never returned. 7 days later, Noah released a dove, which returned, having found nothing to land on. 7 days after that, Noah released the dove again. This time it returned with a sprig of olive. Another 7 days, and Noah released the dove. It never returned. Another 7 days, and Noah released the dove one last time. It never returned. Noah knew this meant the dove had found land. The water subsided, the ark landed in a mountain, Noah and his family and the animals left the ark, and God promised never to flood the earth again. And he left us the rainbow as a sign of this covenant. Neat story, yes? But what if it's not just a story? What if I were to tell you that this story shows up across numerous cultures, spaced across much of the world? We find a similar tale in one of the oldest myths recorded, the Atrahasis, a Sumerian myth written on clay tablets more than 1,000 years before the story of Noah, around 1800 BCE. The myth tells how Atrahasis, the hero of the story, was warned by the god Enki of the goddess Enlil's plan to flood the earth. In this version, it was not man's wickedness that drove the gods to flood the earth. It was simply an attempt to control the human population, which they thought was growing out of control. Enki also tells Atrahasis to build an ark, and gives him almost the exact same instructions, even down to the materials and dimensions. Atrahasis builds the ark, boards it with his family and a bunch of animals, and survives the flood. This story is found again in the Babylonian Epic of Gilgamesh, written 8 centuries later, also on clay tablets. Here the similarities to Noah run even deeper. Like before, a god, Ea this time, tells the hero Unapchin to build a massive ark and bring into it all his family and all the animals of the field. The gods then flood the earth to punish humans for their sinful ways. The storm lasts for 6 days and 6 nights and wipes out the rest of the human race. Like Noah, Unapchin gets stuck on a mountain. Like Noah, he releases birds, first a dove, then a sparrow, then a raven. The first 2 return quickly. When the raven does not return, he knows it is safe to leave the ark. The goddess Enlil promises never to flood the earth again, and rewards Unapchin with eternal life. Thus it seems like we've been telling the story of the flood, as a species, for almost 4,000 years. Most interpret this similarity as evidence that the Noah story is very old and was borrowed from earlier cultures. This is probably true, but that does not explain the fact that a great flood features in the mythology of almost every ancient culture. The Greek author Hesiod wrote of a flood, and it is mentioned in several ancient Hindu texts. Even the distant Mayans had their own unique flood myths. Now I can understand Greeks and Indians retelling a story they heard from a Babylonian, but how on earth would the Maya on the other end of the world have known the story as well? Well, that returns us to our earlier question. What if it's not just a story? What if there actually was a flood sometime in our history, but so long ago that the accounts survive only in myth? Some scholars believe they have found just such a flood. When we look back in the geological record, we find around 8,200 years ago, 6,400 BCE, global temperatures dropped drastically. Scientists believe this sudden drop in temperature occurred when Lake Agassiz, a vast prehistoric glacial lake that covered much of North America, finally melted out of the glacial walls that had contained it and poured into the world's oceans. Sea levels may have risen by as much as 2 meters. Now imagine you're farming in a fertile basin near the Black Sea. Miles to the west, the Mediterranean has been steadily rising. Suddenly it tears a hole through the Bosphorus and begins pouring into the Black Sea basin. Over the course of a week, the water level rises 3 meters, submerging millions of acres. The entire world as you know it is suddenly under water. Hundreds of thousands of people who had settled to farm the area would be drowned. Those who'd survived would need to find new homes. Linguistics, the study of languages, offers support to the Great Flood theory. Many have suggested that such a disaster might have been responsible for the Indo-European diaspora. Study of languages suggests that around 8,000 years ago, a huge human migration took place. A tide of people poured out of the Black Sea basin in all directions. These people all seem to have spoken a common language at one point, but as they settled across Europe and the Near East, they lost contact with one another, and their languages diverged. Today we call the original common language Proto-Indo-European, and almost every European language and all Near Eastern languages are descendants of Proto-Indo-European. While this common language no longer exists, it lives on in its children. For example, every Indo-European language uses the sound ma to refer to mother. Yet different groups of languages have different sounds for father. We and the Germans make a fa sound, while cultures along the Mediterranean use a pa sound. Linguists use these differences and similarities to break languages into families. Those that are most similar, like Spanish and Italian, separated most recently, about 2,000 years ago. Those that are most different, like Hindi and English, must have separated long ago. By tracing these similarities and divergences, linguists have traced the paths of our ancestors across the Western world, back across space and time, to the Black Sea Basin, where the mother of Indo-European languages, Proto-Indo-European, was spoken around 6400 BCE. So from the perspective of these Proto-Indo-European people farming along the Black Sea, the Great Flood was the greatest catastrophe they had ever known. We can still sense their terror in the myths that survive to this day. Yet with the benefit of hindsight, the Great Flood may well have been the best thing that ever happened to our species. Without the Great Flood, agriculture, civilization, perhaps even man as we knew him, might have remained a localized affair for 1,000 more years, spreading only by small increments as time progressed. Instead, a relatively small group of dedicated agriculturalists was abruptly broken apart and quickly spread around the world. We can still see traces of this flight in the languages we speak today. With agriculture to support them, these groups of Indo-Europeans came to dominate the regions they settled. Within a few thousand years, settled agriculture had replaced nomadic hunter-gathering from the Strait of Gibraltar to the Himalayas, from the Scottish Highlands to the Nile Valley. One of those groups of refugee farmers would come to settle in the Fertile Crescent and found the Sumerian civilization. It would be another 3,000 years before the Sumerians developed writing. Yet after all those generations, they still remembered the flood, and they wrote it down, giving us the story we still tell our children to this day.
Living in the northeastern United States, many of my community members trace their ancestry back to Europe. For instance, on any given spring or summer weekend, I don't have to travel too far before I hit a Polish dance competition or a German folk festival. Although this seems just like everyday life to me, it's an excellent example of how migration has played a huge role in our modern world. In today's lesson, we'll take a look at migration and its effects on our world, specifically migration since the 1500s. For starters, migration is simply defined as movement from one place to another. When speaking of human migration, historians often consider anything after the 1500s to be more modern human migration. Also, due to the relative isolation of Asia during this time period, this topic usually deals mostly with European migration. With this in mind, today's lesson will break this very large time span down into 3 general time frames, giving a very brief survey of each. These time frames will be colonization and persecution, industrialization, and the 20th century. To get things going, we'll start with the period of colonization and persecution. When speaking of colonization, all one needs to do is open up any American history textbook and read page upon page of European powers establishing colonies in the Americas. For example, the late 15th century saw Columbus sailing the ocean blue, which rather quickly led to the rush toward colonization. With this rush toward colonization, the 1600s saw the English, the Dutch, the Germans, and several other European powers migrating to the Americas. Not simply limited to the Americas, the period of colonization also saw European powers colonizing Africa, parts of Southeast Asia, and even Australia. However, migration across the Atlantic was not the only human movement occurring during this time period. Internal migration was also occurring in Europe as people moved from their European countries of origin to other European countries. According to historians, one of the main catalysts for internal European migration was religious and racial persecution. This is known as forced migration, in which people are coerced away from their home regions. Excellent yet tragic examples of forced migration were the Atlantic slave trade systems and the thousands of Jews and Muslims who fled Spain during the infamous Spanish Inquisition. The time period also saw Eastern Europeans moving westward to escape the ever-expanding Ottoman Empire of modern-day Turkey. With this brief summary of colonization and persecution, we move our way up to industrialization, the process in which a society moves from a mainly agricultural society into one centered on the manufacturing of goods and services. Being usually linked to the late 18th and 19th centuries, industrialization was a huge catalyst for labor migration, people moving from their home regions in search of employment. An excellent example of this was the influx of Irish immigrants into the United States, most of whom were looking for work after the devastating 19th century potato famine which devastated their lands. The industrialization of the global economy also saw migration greatly affected by urbanization, the movement from rural to urban areas. In other words, thousands upon hundreds of thousands of farm workers left their fields and moved to the cities in search of employment. According to many historians, the process of urbanization had its origin in the United Kingdom and then spread throughout the world. With this, we come to the 20th century. According to many sources, the late 19th and 20th centuries saw unmatched levels of human migration. For instance, it's estimated and rather well documented that this time period saw millions of European immigrants coming to the U.S. In addition, immigrants from Asia also made their way to the American shores. Turning our eyes away from migration to America, it's recorded that internal migration also occurred in Asia during this time period. For instance, the region of Southeast Asia saw immigrants coming from places like India and southern China. Migration is defined as the movement from one place to another. Since the 1500s, human migration can be discussed in the time frames of colonization and persecution, industrialization, and the 20th century. When speaking of colonization and persecution, the 1600s saw many Europeans migrating to the Americas. This general time frame also saw Europeans moving into Africa, Southeast Asia, and Australia. As for persecution, this same time period also saw many examples of forced migration, in which people are coerced away from their home regions. Industrialization, the process in which a society moves from a mainly agricultural society into one centered on the manufacturing of goods and services, was another catalyst for human migration. This was seen in the form of labor migration, or people moving from their home regions in search of employment, and urbanization, the movement from rural to urban areas. The 20th century saw unprecedented levels of migration as millions upon millions of Europeans and Asians came to the shores of America. However, it also saw internal migration occurring in Asia. Often being called the Great Melting Pot, American history textbooks are full of accounts of immigration into the U.S. With immigration meaning the action of coming to live permanently in a foreign country, these accounts often discuss what these new people groups did once they came upon the American shores. However, they tend to give much less column space to why they left their country of origin in the first place. Today's lesson will speak to this topic as it focuses on emigration, the act of leaving one's place of residence or a country to permanently live in another. For starters, immigration and emigration are very closely tied together. They can sort of be thought of as two sides of the same coin, since immigration is the idea of coming into a new land, while emigration is the act of leaving your old one. Putting this more succinctly, people emigrate from their country in order to immigrate into another. When speaking of the reasons for, or characteristics of, emigration, social scientists usually like to discuss the idea of push and pull factors. To break this down, we'll start with pull factors. Keeping things simple, pull factors are defined as the things that attract a person to a new place. In other words, they're the things that pull them toward the new land. For instance, the opportunities for better employment or higher pay are excellent examples of pull factors. Another very common pull factor is the chance for a higher education. Interestingly, some studies note that those who emigrate due to pull factors tend to already be more educated than the average person within their country of origin. Adding to this, they tend to be already employed prior to leaving. Getting even more specific, some studies note that the majority of those who emigrate due to pull factors tend to be young married men. Noting all of this, it would be very easy to assume that emigration due to pull factors has a very negative effect on the country of origin, that emigrants sort of leave and never look back. However, some studies say the opposite may be true. For instance, many who emigrate actually send back what are coined remittances, or funds sent back to one's country of origin. Stated plainly, they often send money back to their families still living in their homeland. This in turn boosts the homeland's economy. Adding to this, some studies note that as these emigrants leave, the loss of them in the workplace allows for better paying jobs for those left behind. In other words, when the supply of skilled labor drops, the demand and the willingness to pay for it increases. Leaving pull factors, we now come to push factors. Push factors are things that drive one away from their homeland. As the name implies, these are the things that sort of push them out. A great example of a push factor is famine within one's lands. Probably one of the most famous of these famines was the 19th century potato famine of Ireland that saw thousands upon thousands of emigrants leaving Ireland and coming to America. Along with famine, there are many other push factors. They can include, but are not limited to, lack of suitable farmland, struggling economies, fear of war, oppressive political structures, and even the threat of religious or racial persecution. Tragic examples of emigration due to religious and racial persecution were seen by the world as thousands of Jews emigrated out of Nazi Germany. When speaking of emigration, it's also important to note that many countries do their best to restrict emigration. This was definitely seen in the old Soviet bloc countries who began heavily restricting emigration in the early 20th century. Going further back in time, the Chinese empires of the 17th centuries also went to great lengths to keep their people from being able to emigrate out of their lands. Immigration and emigration are very similar in that immigration is the action of coming to live permanently in a foreign country, while emigration is the act of leaving one's place of residence or country to permanently live in another. Stating it plainly, immigration is the coming while emigration is the leaving. Keeping them straight, many like to think of emigrating as making an exit. When speaking of emigration, social scientists assert it occurs due to both pull and push factors. Pull factors are the things that attract a person to a new place, things like better employment or educational opportunities. Interestingly, studies note that those who leave due to pull factors tend to be young, educated, married men who tend to keep ties with their homeland. One of these ties comes in the form of remittances, or funds sent back to one's country of origin. Push factors are things that drive one away from their homeland. As the name implies, these are the things that sort of push them out. Some examples of push factors are famine, lack of land, fear of war, oppression, and racial or religious persecution. Although humans have been moving from place to place since the creation of time, the 19th and 20th centuries saw an explosion in human migration. This explosion of sorts will be the topic of today's lesson as we discuss modern migration patterns, specifically discussing the concept of forced migration. To begin, migration is simply defined as the movement from one place to another. It's a farmer putting down his plow and moving from Ireland to America, and it's a German Jew fleeing his country in the World War II era. With these examples, historians usually cite three concepts that have greatly affected modern migration. They are labor migration, urbanization, and forced migration. We'll kick things off with labor migration. Labor migration can be quickly explained as people moving from their home regions in search of employment. When discussing labor migration, the example usually given is the massive influx of Irish immigrants into the United States during the 19th century. Being devastated by the infamous potato famine, the farmers of Ireland came to America's shores looking for employment in the towns and cities of the more industrialized United States. Interestingly, the U.S. also experienced considerable internal 20th century movement due to labor migration. For example, it's estimated that millions of African Americans left the poorer areas of the rural southern U.S. in search of the higher-paying urban jobs of the Northeast. With this mention of cities, we come to our next concept that affected modern migration: urbanization. As industry started replacing agriculture, the industrialization of the world's economy led to urbanization, the movement from rural to urban areas. In other words, millions of agriculturalists left their farms and moved to the cities in search of work. According to those who study migration, the process of urbanization had its origin in Britain and then spread throughout the world. Leaving urbanization, we come to our last concept, forced migration. Forced migration is the process in which people are coerced away from their home regions. Unlike labor migration and urbanization, forced migration is not considered voluntary. On the contrary, it's often necessary for survival. Probably one of the most famous, yet horribly shameful modern examples of forced migration occurred as Jews fled Nazi Germany. Often referred to as diaspora, or a large people group who moved from their homeland to another area of the world, many of these Jews relocated to modern-day Israel, which in turn caused the forced migration of many Palestinian people. Adding to this, forced migration occurred heavily following World War II. For instance, after the war, many Eastern European ethnic groups, for instance millions of Estonian, Ukrainian, and Polish people, were forced out of Western Europe, pushing them further into the former Soviet Union. Leaving Europe and turning our eyes toward Asia, the mid-20th century saw forced migration occur in India and Pakistan, as religious wars between Hindus and Muslims saw thousands upon thousands of people killed, while others fled for their lives. Migration is defined as movement from one place to another. When discussing modern human migration, many cite labor migration, urbanization, and forced migration as main catalysts. Labor migration is defined as people moving from their home regions in search of employment. One of the best examples of modern labor migration was the huge influx of Irish immigrants into the U.S. after the famous potato famine devastated their homelands. Urbanization is the movement from rural to urban areas. Believed to have begun in Britain, urbanization occurred across the globe as the global economy moved from one of agriculture to industrialization. Forced migration is a process in which people are coerced away from their home regions. Forced migration is not voluntary. As people leave an area due to forced migration, they are often referred to by the word diaspora, which is a large people group who move from their homeland to another area of the world. There are some parts of science that are agreed upon by pretty much everybody. For example, no one really questions the idea that trees help oxygenate the earth. However, there are some parts of science that are heavily disputed. One of the best examples of this is the topic of today's lesson, the regional continuity model of human origin. Since I'm pretty sure most of us are rather unacquainted with this model, we're going to take some time to try to break it down to its basic components. However, before we do this, we really should spend some time discussing the concept of theory. Getting started, a theory is a supposition used to account for a situation or justify a course of action. As I'm sure is familiar to most of us, a theory is studied yet still unproven. It is not solid fact. In fact, many theories are often overturned as new findings shed light on things once thought pretty much set in stone. This is especially true when it comes to the topic of human origin. With this disclaimer in mind, we'll move on to the regional continuity model of human origin. Speaking rather formally, the regional continuity model of human origin asserts that modern Homo sapiens developed from different regional populations of archaic Homo sapiens that had previously evolved from regional populations of Homo erectus. That was a mouthful. Let's break it down. First, this model has at its foundation the work of Charles Darwin, who theorized that humans advanced over a vast amount of time, moving along the evolutionary ladder from apes to Homo sapiens. Second, Homo sapiens are the species of humans that exist today. Putting it plainly, you and I are Homo sapiens. Third, Homo erectus is theorized to be an extinct species of primitive man able to walk upright. Using these three things, let's simplify the regional continuity model of human origin. As a quick reminder, the model states that modern Homo sapiens developed from different regional populations of archaic Homo sapiens that had previously evolved from regional populations of Homo erectus. Breaking this down, the first part of this, modern Homo sapiens developed from different regional populations, simply means that modern humans developed in many different regions, not just one. The last part, which states that they evolved from regional models of Homo erectus, means that the modern Homo sapiens we're talking about had evolved from the more primitive Homo erectus. Really oversimplifying matters, the regional continuity model asserts that modern humans evolved from more primitive humans, and that this occurred in more than one region of the world. In other words, it theorizes that modern Europeans evolved from primitive Europeans, while modern Chinese evolved from primitive Chinese, and modern Africans evolved from primitive Africans. Those who support the regional continuity model use fossilized remains of humans to support their claims. In doing this, they lean on the physical differences in the human remains of these fossils, as well as modern physical differences found in the world today. For instance, they use the fact that the average European human skull has a very pronounced brow, while the average Asian brow does not. Getting even more specific, they also point to the differences in the actual teeth structure among the different races. Despite these findings, and remembering that most theories of human origin are rather controversial, the regional continuity model has some serious critics. In fact, it's in direct contradiction to the out-of-Africa model of human origin, also known as the replacement model. This model theorizes that Homo sapiens only emerged in Africa and then migrated to the regions of Europe and Asia and replaced the more primitive species. In other words, it believes all modern humans originated in Africa, not different regions. In fact, those who agree with the out-of-Africa model have evidence of their own. They assert that DNA evidence points to the fact that there is a common genetic code in all humans that leads straight back to Africa. However, as there is always at least two sides to an argument, the regional continuity supporters claim that the genetic data collection and testing of the out-of-Africa supporters is flawed and therefore unreliable. There are many different theories or suppositions used to account for a situation or justify a course of action about the origin of humans. Many of them are based on the work of Charles Darwin, who theorized that humans advanced over a vast amount of time, moving along the evolutionary ladder from apes to Homo sapiens. These theories also assert that Homo sapiens are the species of humans that exist today, while Homo erectus is theorized to be an extinct species of primitive man able to walk upright. Building on these theories, the regional continuity model of human origin argues that modern Homo sapiens developed from different regional populations of archaic Homo sapiens that had previously evolved from regional populations of Homo erectus. This is in direct contradiction to the out-of-Africa model of human origin, also known as the replacement model, which theorizes that Homo sapiens only emerged in Africa, then migrated to the regions of Europe and Asia and replaced the more primitive species of Homo erectus. I'm guessing that today's lesson on the replacement model of human origin will be very new to most of us. For this reason, we're going to stick to the very basics of this rather complex theory. However, before we get to these basics, we need to spend some time digging into the word theory. A theory is a supposition used to account for a situation or justify a course of action. A theory is not set in stone, nor is it proven fact. Due to this, science, especially archaeology, often finds itself unearthing things that call old theories into question. Today's lesson on the replacement model will be an excellent example of one such theory, as many scholars disagree with the validity of its suppositions. Stating it plainly, some would consider it incorrect at best. With this little warning of sorts, let's get down to business. I'll first give the scholarly definition of the model, then we'll work to break it down into more digestible terms. The replacement model asserts that there was a single origin of Homo sapiens in Africa, and that these anatomically modern humans migrated out of Africa and replaced all other lesser evolved humans throughout Europe and Asia. Hence the name replacement model. With the official definition fresh in our minds, let's try to break it down a bit. First of all, when science uses the term Homo sapiens, it's referring to the species of humans that exist today. In other words, you and I are Homo sapiens. When science uses words like less evolved humans, they're referring to the theory made famous by Charles Darwin that humans advanced over a vast amount of time, moving along the evolutionary ladder from apes to Homo sapiens. Putting this all together, the replacement model asserts that Homo sapiens originated or evolved only in Africa, then spread out over Europe and Asia. When speaking of this theory, the word only is probably one of the most important words, since the hallmark of the theory is that Homo sapiens only evolved in Africa. Then, as these Homo sapiens migrated out of Africa, the model asserts that all lesser evolved human species somehow became extinct, leaving Homo sapiens as the only remaining human species. For this reason, the replacement model is also referred to as the out-of-Africa model. Drawing from this, proponents of the replacement or out-of-Africa model assert that all humans alive can trace their ancient ancestry back to Africa. Leaning greatly on biological science, some studies have seemed to support the idea that all modern-day humans originated from Africa. These studies assert that the DNA records of humans does in fact seem to lean toward the idea that there is one main branch of human DNA from which the other more modern branches sprung from, and that this main branch did originate in Africa. These findings have helped to elevate this theory to one of the most agreed upon within the scientific community. However, opponents of the replacement model argue that the computer and data entry programs used in these studies were flawed and therefore unreliable. Adding to the criticism of the model, most of those who champion it are willing to admit they really can't give any solid dating on when or why the emergence or migration of these Homo sapiens took place. A theory is a supposition used to account for a situation or justify a course of action. The replacement model of human origin is an excellent example of a theory, since many agree with it, but many others do not. Building from the theories of Charles Darwin, who theorized that humans advanced over a vast amount of time, moving along the evolutionary ladder from ape to Homo sapiens, the replacement model is also referred to as the out-of-Africa model. It gains this name from its assertion that there was a single origin of Homo sapiens in Africa, that these anatomically modern humans migrated out from Africa and replaced all other less evolved humans throughout Europe and Asia. In short, it holds that all Homo sapiens, or the species of humans that exist today, evolved only in Africa and then spread throughout the world. When this occurred, all lesser evolved humans somehow became extinct. Supported by some scientific studies in DNA, replacement model theorists assert that all modern humans are of African origin. However, critics of this theory argue that the testing models used to determine this were faulty and therefore inaccurate. Opening up for more criticism, the model has no solid dating for the emergence or migration of these ancient Homo sapiens.
Today's lesson on the partial replacement model of human origin will probably be pretty alien to most of us. Making this a bit more difficult, we'll need to understand the actual replacement model of human origin in order to have any hopes of grasping the partial replacement model. For this reason, a lot of our time will be spent on the replacement model. However, since both the replacement model and the partial replacement models are highly contested theories, we'll need to back up even a bit further and cover the more familiar, generalized concept of theory. In science, a theory is an explanation that accounts for a wide range of observed facts and phenomena. For example, the theory of general relativity is an explanation of how massive objects warp the fabric of spacetime. Uncontested facts, such as dropped objects fall to the ground and the Earth orbits the Sun, are explained by Einstein's general theory of relativity. Since we're always discovering more facts, scientific theories remain open to revision as our understanding of a subject grows. However, as soon as scientists agree that the facts disagree with a theory, that theory is either modified or thrown away. With this nailed down, let's move down the path to the partial replacement model of human origin. Our first stop will be the actual replacement model. Stated academically, the replacement model asserts that there was a single origin of Homo sapiens in Africa, and that these anatomically modern humans migrated out from Africa and replaced all other less evolved humans throughout Europe and Asia. Hence the name replacement model. Knowing that this definition is rather heady, let's break it down. First, we'll tackle what we mean by Homo sapien. Simply stated, Homo sapiens are the species of humans that exist today. Walk down any street in any land, and every human that passes by will be a Homo sapien. When our rather wordy definition of the replacement model discusses less evolved humans, we're referring to the theory made famous by Charles Darwin, the man who asserted that humans advanced over a vast amount of time, moving along the evolutionary ladder from apes to Homo sapiens. Putting all these pieces together, the replacement model theorizes that all Homo sapiens evolved only in Africa, then spread out over Europe and Asia. As these Homo sapiens migrated out of Africa, the replacement model believes that all the lesser evolved human species somehow became extinct, leaving Homo sapiens as the only remaining human species. In other words, the Homo sapiens coming out of Africa did not breed or intermix with less primitive human species. The less primitive species just somehow ceased to exist. Making it easy to remember, somehow the Homo sapiens coming out of Africa just replaced them. With this nailed down, let's move on to our final destination, the partial replacement model of human origin. As an offshoot of the replacement model, this theory asserts that all modern Homo sapiens originated in Africa alone. These modern Homo sapiens then migrated to Europe and Asia and interbred with the more primitive human species in existence there. Breaking this down, the partial replacement theory and the replacement theory both assert that all Homo sapiens originated in Africa alone. On that point, they shake hands in agreement. They also both give a nod to the fact that these Homo sapiens then migrated out of Africa and into Europe and Asia. However, when it comes to what happens next, the two models drop hands and part ways. Disagreeing with the replacement model's assertion that the more primitive populations of Europe and Africa somehow just ceased to exist, the partial replacement model holds to the idea that the more modern Homo sapiens mixed with the primitive human species of Europe and Asia. In other words, and way oversimplifying, the more primitive populations didn't become extinct. Instead, they became sort of improved. In doing this, the products of this mixing sort of branched off into Homo sapiens, which had distinctly African and European traits, and Homo sapiens who had distinctly African and Asian traits. Remembering that these are all just theories, the replacement model camp criticizes the partial replacement model's idea of interbreeding. Using the DNA record of modern humans, they argue that there's one main branch of human DNA from which all the other more modern branches sprung from. These findings also seem to indicate that the DNA strands come only from what seem to be the more modern Homo sapiens, not mixed with any of the more primitive species. A theory is an explanation that accounts for a wide range of observed facts and phenomena. When it comes to how humanity originated, there are many different theories. Many of them have their foundation in the works of Charles Darwin, the man who asserted that humans advanced over a vast amount of time, moving along the evolutionary ladder from apes to Homo sapiens. Two of these theories are the replacement model and partial replacement model of human origins. The replacement model asserts that all Homo sapiens evolved in Africa, then spread out over Europe and Asia. As these Homo sapiens migrated into Europe and Asia, the replacement model believes that all the lesser evolved human species became extinct, leaving Homo sapiens as the only remaining human species. Being very similar to this, the partial replacement model asserts that all modern Homo sapiens originated in Africa alone. In this, it agrees with the replacement model. However, differing from the replacement model, the partial replacement model asserts the modern Homo sapiens migrated to Europe and Asia and interbred with the more primitive human species in existence there. This is in contradiction to the replacement model, which asserts the more primitive human species became extinct.
When the word evolution is used, many people tend to think of the theories surrounding the origins of humanity. However, when speaking of cultural evolution, this is not the case. On the contrary, having very little to do with physical traits, cultural evolution simply denotes cultural development and progression. Keeping this difference in mind, today's lesson will center on the theories of cultural evolution, specifically the theories of Edward Tyler, Karl Marx, and Thomas Robert Malthus. We'll get things rolling with Edward Tyler. One of the main scholars in the fields of early cultural evolution was Edward Tyler. Living from 1832 to 1917, Tyler believed that cultures move through three definite stages of progression: savagery, barbarism, and civilization. Sort of like a man climbing up a ladder, he asserted all societies climb up these three stages of cultural evolution. Some are just simply further along in the climb than others. Adding to his rather controversial theory, Tyler asserted that the cultures he deemed savage continued to resemble the ancient past because they simply hadn't figured out how to manipulate their environment. When they gained the know-how to do this, they too would progress. Unfortunately, his use of the words savage and barbarism served to add to the culture superiority that was already all too prevalent among the modernized West. Leaving the stages of Tyler, we now come to the work of Karl Marx, the author of the historical materialism approach to cultural evolution. According to his historical materialism approach, culture evolved due to the necessity to produce in order to survive. Stating it very simply, culture progressed as populations increased, and thus material needs increased. With this increase of needs, man began entering into social relationships with one another. However, these relationships weren't random, existing in a vacuum. Instead, they were based on division of labor, the assigning of different tasks of the manufacturing process to different people in order to improve efficiency and productivity. Unlike Tyler, who staged progression from savagery to civilization, Marx asserted that cultural evolution moved through the three modes of production. They are primitive communism, or group ownership, to feudalism, or power based on land ownership, to eventually capitalism, or the free market economy. Leaving the works of Marx, we now land on the theories of Thomas Robert Malthus, the originator of the Malthusian catastrophe. With its rather ominous name, the Malthusian catastrophe theory asserts that inevitably cultural progression will be halted by famine and disease due to overpopulation. Ironically, while many scholars were asserting that human culture was moving toward great advancement, if not mere perfection, Malthus asserted that overpopulation would bring this to a screeching halt of sorts. In other words, the natural resources of the earth would not be able to keep up with population growth. Sooner or later, this would lead to famine and disease, which would in turn check population growth and cultural development. As an offshoot of the Malthusian catastrophe has sprung the Neo-Malthusian principle. Those who hold to this principle agree that population growth is a major concern. Therefore, Neo-Malthusianism supporters assert that population growth must be curbed through the use of contraception and birth control. To those who hold to the Neo-Malthusian principle, this is the best way to ensure that there will be enough resources handed down to secure the survival of future generations. When speaking of cultural evolution or cultural development and progression, there are many different theories and viewpoints. Edward Tyler, one of the main scholars in the field of early cultural evolution, asserted that all cultures moved up almost a ladder of progression through three main stages of progression, which were savagery, barbarism, and civilization. When faced with the many differences between the world's cultures, he asserted that some are just further along in the evolutionary process than others. Karl Marx was the author of the historical materialism approach to cultural evolution. According to his theory of historical materialism, culture evolved due to the necessity to provide in order to survive, that human relationships evolved based on division of labor, the assigning of different tasks of the manufacturing process to different people in order to improve efficiency and productivity. With this evolution, cultures move through different modes of production. These modes are primitive communism, or group ownership, feudalism, or power based on land ownership, and capitalism, or the free market economy. Differing from these theories are the works of Thomas Robert Malthus, the originator of the Malthusian catastrophe. The Malthusian catastrophe asserts that inevitably cultural progression will be halted by famine and disease due to overpopulation. From this catastrophe theory has sprung the Neo-Malthusian principle, the assertion that population growth must be curbed through the use of contraception and birth control.
Throughout history, people have been grouped, and people have placed themselves into groups. From the tragedy of Nazi Germany dividing people by race, to the benign grouping of preschoolers who like chocolate or vanilla, people have been grouped. When speaking more scientifically or anthropologically, groupings have often been based on culture, race, ethnicity, and gender. In today's lesson, we will explain these terms. To begin our lesson, we'll start with culture. Culture is a set of learned behaviors, attitudes, and beliefs that characterize a society or people group. It encompasses both the intangible and tangible things of a population. They are things like how a society defines family, or how people worship. It's people's favorite pastimes and their music. In short, it's what binds a people group together as a people group. It's what makes them, them. With all this in mind, it's important to remember that although culture may be affected by biology, it is not determined by it. In other words, culture is learned. Unlike, say, hair color, a person is not just born with culture. With this, we have a nice transition into our next term, race. Race denotes a people group who have differences and similarities in physical and biological traits that are considered to be socially significant. Unlike culture, race is based very heavily on biology. However, these biological traits must be seen as socially significant. Speaking in terms of race, eye color is usually not seen as socially significant. For instance, those considered Caucasian can have brown, green, or blue eyes. This is not significant. However, skin color is. Using the same example, those who are considered Caucasian are of fairer complexion than those who are not. Unfortunately, assumed differences in race have been cause for great prejudice. Adding to this, most sciences do not even recognize the concept of race as being empirically valid. Next, we come to ethnicity. Being closely linked to culture, ethnicity is based on shared cultural practices and perspectives that set a people group apart from others. Breaking this down a bit more, ethnicity is a shared cultural tradition and heritage. With this in mind, ethnicity goes a bit deeper than culture, dealing with a long sense of shared history, a common language, and even dress. Making the difference between culture and ethnicity a bit easier to dissect, I'll use an example from my own life. One of my closest friends is from Puerto Rico. However, she has lived in the continental United States for many years. For this reason, we are both part of the American culture. However, our native languages, our ancestral history, and even our diets are very different. In other words, we are not of the same ethnicity. Last, we come to grouping by gender. According to the American Psychological Association, gender refers to the attitudes, feelings, and behaviors that a given culture associates with a person's biological sex. Gender is a social construct and a social identity. Recognized across the globe and in all known people groups, grouping by gender has occurred throughout time. With gender identity extending beyond male and female, these groupings have evolved to include people who do not identify as male or female. When speaking of human grouping, the terms culture, race, ethnicity, and gender are often used. Culture is the set of learned behaviors, attitudes, and beliefs that characterize a society or a people group. Being very important to remember, culture is learned. Being heavily tied to biology, race denotes a people group who have differences and similarities in physical and biological traits that are considered to be socially significant. The concept of race has been a catalyst for prejudice, even though many scientists consider it to be empirically invalid. Linked closely to culture, ethnicity is shared cultural practices and perspectives that set a people group apart from others. In other words, it is a shared cultural tradition and heritage. Lastly, gender is the social state and identity of being male or female.
Have you ever noticed cultural differences based on geography and/or climate? Surely you have. For example, when I was a kid, I lived in Michigan, and the sport of hockey was huge there. Everybody played hockey and watched hockey. Then, when I was a teenager, my family moved to Charlotte, North Carolina. Suddenly, I felt like the only guy in the city who followed hockey. Hockey just wasn't a big deal there. Most people didn't care about it. See, hockey has a bigger following in the North than it does in the South. The climate of the North is more suited to the sport, and the North just has a greater appreciation for the sport than does the South. There are all kinds of other examples. Surfing is a big deal on the West Coast, but not so much in St. Louis. A farmer in Iowa lives a very different lifestyle from a banker on Wall Street in New York City. See, geography and climate play a powerful role in affecting culture. Over the course of history, they have also played a major role in where civilizations spring up and what those civilizations look like culturally. So why do civilizations spring up in one particular place as opposed to another? Well, it's actually pretty simple. Civilizations tend to arise in regions that are inhabitable and capable of sustaining life. See, after the Neolithic Revolution, human beings began practicing settled agriculture and pastoralization. This means instead of wandering around hunting and gathering food, they began raising livestock and harvesting crops. Naturally, they wanted to live in regions suitable to these ends. So oftentimes, civilizations arose along rivers in fertile land. Some of the earliest civilizations, such as the Sumerians, sprang up between the Tigris and Euphrates rivers in a region called Mesopotamia. This region consists of the current countries of Iraq and Iran. This area is often called the cradle of civilization because it is believed the first civilizations arose here. Another common example of civilization springing up along a river is ancient Egypt. While much of Egypt is desert, the fertile Nile River Valley provided the ancient Egyptians with the means to sustain life. In India, the Harappa civilization developed in the Indus River Valley. In the Americas, the Chavin civilization sprang up in the Andes Mountains along the Mosna River. So we see, time and again, river systems and fertile soil were vital to early civilizations. Access to other resources also determined where civilizations emerged. For example, the Hittite civilization of Asia Minor relied heavily on iron ore and used iron tools and weapons to expand its power. Jumping ahead a few thousand years, Germany rose to power in the late 19th century, in part because of its rapid industrialization stemming from iron production. In the 15th to 17th century, Spain grew wealthy from the gold stolen from Mayan and Incan tribes of North and South America. So, in addition to river systems and land quality, other natural resources like iron ore, copper, and gold affected where civilizations developed. Areas with plentiful hunting game also tended to be prime locations for settlement. In time, civilizations adapted to the specific geography and climate around them. For example, for the ancient Egyptians, life revolved around the Nile River. Every spring, the Nile would flood, depositing rich soil through the valley. Because of this, the planting and harvesting of crops coincided with seasonal river movements.
In the Egyptian religion, the Nile River god Hapi was worshipped as the giver of vegetation. Climate, too, is a powerful agent in cultural adaptation. Think of the Inuit tribes that inhabit the Arctic regions. The extreme cold weather dictates how they sleep, what type of shelters they live in, and just about every area of life. Their art and religious beliefs also center on the nature surrounding them. In time, civilizations developed the technology to overcome nature and establish dwellings even in formidable locations. For example, in present-day Peru, the Incas' Machu Picchu settlement is carved into the Andes Mountains. The 15th century Incas built the settlement in succeeding steps or elevations, allowing for irrigation and agriculture. Today, modern technology allows civilizations to be built on even the most difficult terrain. Perhaps someday there might even be a settlement or civilization on the moon. It sounds crazy, but it could happen. Every civilization has to confront the geography and climate surrounding it. Some locations are better suited to development than others. In places that are poorly suited to life, technology must make up for what is lacking. In time, civilizations advance to the point where geography and climate affect even minor and trivial aspects of life. And that, my friends, explains why some people call it pop and others call it soda. Or maybe it's all just Coke, right? Let's review the key terms contained in this lesson. The Neolithic Revolution was an important development in human history because it marked the transition from hunting and gathering food to producing it. The Neolithic Revolution allowed for the establishment of advanced civilizations. The region of Mesopotamia between the Tigris and Euphrates rivers is often called the cradle of civilization because it is believed that the earliest civilizations first arose here. One example of geography determining where civilizations develop can be seen in the ancient Egyptians who lived in the Nile River Valley. Similarly, the Hittite civilization prospered partly because of their reliance on the natural resource of iron. The Incas overcame geography and climate by using technology to build an advanced settlement called Machu Picchu in the Andes Mountains of South America.
When you speak your native language, do you find that you use different words than your older relatives? Are there certain phrases that you say that they don't understand? Or sometimes is it the reverse and your family members use words that are no longer used by your generation? This is an example of a language evolving and changing even from one generation to another. Yet you still carry on many of the elements of the language, such as sentence structure and overall vocabulary. In this lesson, we'll look at the world's major languages and how they spread, change, and develop over time. Linguists estimate that the world's languages number somewhere around 6,000 total. Some languages are especially prominent because of how diffuse they are throughout the world. According to the United Nations, the most widely spoken languages are Mandarin Chinese, English, and Spanish, as well as Hindi, Arabic, Bengali, Russian, Portuguese, Japanese, German, and French. The people who are counted in this listing include both native speakers of a language and those who speak it as a second language. So how did these languages become the most commonly spoken? Mandarin and Hindi are widely spoken in countries that have large populations, like China and India. Non-native speakers may also have an interest in learning the language of countries that are strong economic powers, such as China and the United States. Sometimes large and even sudden events can cause a language to spread rapidly. For instance, war and invasion, waves of migration, and the spread of religion dramatically influence the diffusion of a language. In particular, the British Empire was responsible for much of the spread of the English language, while Arabic was impacted by the spread of the Muslim religion. Spanish is also spoken in much of the Americas due to invasions and expansion. Trade among various regions and the sharing of farming practices as humans developed agriculture affected the language spoken in certain regions. A nation will often choose an official language or more than one in which to conduct business. This choice of an official language can impact how widespread that language becomes. As schools teach the official language, the next generation learns these standards. Cultural changes, such as the rise of Hollywood and new technologies, have also impacted how people communicate with one another locally and globally. Linguists use some categorization of languages to help them have meaningful conversations about the origins and evolution of the ways people speak. A term used by some linguists is language family. A language family is a set of languages that share a common ancestry. For instance, English is in the same language family as German and Dutch, as part of the Indo-European family, which includes many other languages as well. Languages in a language family that have diverged in their development will typically evolve to be more and more different over time. New languages will emerge and some will go extinct. Some languages may also be more likely to change than others, depending on the cultural context of that region. Languages are always evolving. English, for instance, is not one fixed set of words and sentence structures that have stayed the same throughout time. It's changed to a great degree and is still changing as you watch this lesson. We have standards created for its official use in government and business, such as dictionaries which aim to describe what words mean and how they're used. Yet the actual usage of a language can vary from region to region and person to person. Consider your own first language. As you age, you may notice different ways younger groups of people or those from different regions and backgrounds than your own speak. In school, we learn that there's a set of standards for how to speak our language, and this helps us communicate with one another in work and life. In practice, these standards will change over time based on the needs of those speaking the language and the impact of interacting with those who speak differently than we do. The ability to switch between different ways of expressing oneself can help create new opportunities to connect with others, as often occurs when someone is bilingual. The major languages in the world have gained in their influence due to many different political, economic, and cultural trends, from invasions and the spread of empires and religions to new forms of entertainment and technology, as well as patterns of migration. Linguists may use the term language family to describe a set of languages that share a common ancestry. Experts estimate that the world's languages number somewhere around 6,000 total, with new languages emerging at times and other languages becoming extinct. The most widely spoken language in the world is Mandarin Chinese, due in part to the large population of China. Languages evolve and change over time, sometimes abruptly when major events trigger shifts in communication. Languages fluctuate with the needs of the speakers and with the context of the world around them. What will you do with your time today? What will you wear? How do you understand the meaning of your life and your existence? Who will you marry? For many people in the world, religion shapes much of their daily life, as well as the big questions, like why am I here, how should I behave, and what happens when I die? This lesson explores the geography of religion, including the distribution of religion in different regions of the world. We'll take a look at the political and social impacts of beliefs, and how they can contribute to or alleviate conflict and violence. Geographers don't look at religion with the goal of altering, judging, or influencing the beliefs of others. Their aim is to more fully understand how religious beliefs and practices affect the people of that society and region. For instance, a geographer might observe how laws and social norms vary by region, and how this is connected with the religiosity of that area. At the time of this lesson, a debate over same-sex marriage has divided certain states, while other states have allowed marriage licenses to be issued. Some states have taken up the mission to ban it. Whether a person should be able to marry a person of the same sex is often discussed within religious context. Some states will have more citizens that find same-sex marriage against the beliefs of their religion, and this will affect which candidates get their vote. Similarly, abortion often raises intense political debate among those from different religious perspectives. Geographers take an interest in how religious a certain area is based on factors such as professed belief, attendance at services, and other measures of religiosity. Non-believers and atheists will also capture the attention of geographers who seek to understand both the adherence to and the rejection of religion. In many cases, numbers of people in a particular religion are not easy to measure. For instance, in one region, a person may be considered a certain religion at birth, whether or not they ever participate in the activities of that religion. Another religion may only count those who experience a certain rite of passage. What is more certain is that some regions of the world are more likely to have high numbers of one religion over others, while some regions will be more diverse. For instance, in the Americas and in Europe, Christianity is the religion of the vast majority. African countries overall are roughly split between Christianity and Islam, with ethnic religious and non-religious people making up a minority. Asia as a continent includes many different religions as part of the whole area, although certain areas have concentrations of those who are Muslim, Hindu, or Buddhist. Looking at this data can help geographers understand the distribution of certain beliefs and practices, particularly when they look into more detailed levels of information beyond just continental trends. Religious identity is not always separate from concepts such as ethnicity. In the case of someone who refers to themselves as Jewish, for instance, this could mean their religious beliefs, or it could mean their ethnic identity, even if they do not practice the religion. It could also refer to both religion and ethnicity. Religious and ethnic identity can affect every aspect of a person's world, from how they spend their time to how they dress and eat, what values guide their everyday actions, and what meaning they give to life and death. It can also influence the politics of the world around them and how a person perceives their reality. Imagine that each person is holding up a certain lens between themselves and the world around them based on their past experiences and beliefs. This shapes how we understand people and events and even the meaning of life and death. There are many ways of practicing any one religion. Most religions place a good deal of attention on sacred religious texts. They may also value the wisdom of leaders in the faith. Different interpretations of what the texts mean and different approaches of leadership can influence how a person expresses their beliefs. Whether a particular region is dominated by one religion or another may also influence the politics of that area. In the case of same-sex marriage, not everyone who considers themselves religious will share similar views, even within the same overall religion. Some denominations of Christianity have opened their doors to same-sex couples, while others debate how to address the issue of acceptance in their community. For instance, at the time this lesson was created, the United Church of Christ holds a position of accepting and sanctioning same-sex marriage, while some other Christian churches, such as the Methodist Church, American Baptist churches, and the Southern Baptist Church, prohibit this. The population of citizens within each state that holds a particular religious view can influence the politics of that state and impact whether a particular state issues same-sex marriage licenses. If a person believes that their religious texts and leaders advocate for the use of aggression, they may use force to promote their viewpoint, particularly if they have access to weapons. This can involve actual war and terrorism, or it can mean persecuting or restricting those who disagree, depending on where they live in the world and the political context in which this occurs. Conflicts can arise between regions due to strong differences in ideology, disputes related to historical ties to lands and resources, and memories of past persecution and violence. Add up these factors and you have groups that become embroiled in territorial conflict that can last a very long time, as with conflicts between Jews and Muslims in Israel and Palestine. On the flip side, for many individuals, religion is a guiding force in moral behavior, shaping whether they choose to participate in violence and injustice for their own gain. Many religious leaders have advocated for political and social justice through nonviolent means. An example in the United States is the Reverend Martin Luther King Jr.'s call for Christians and others in the South to peacefully protest the immorality of racial segregation. Mahatma Gandhi also used this approach of civil disobedience to ultimately lead India to gain independence from colonial rule, while promoting cooperation between Hindus and Muslims. Today, the current Dalai Lama, leader of Tibetan Buddhism, raises awareness of the plight of the people in that region of the world. Geographers seek to understand this complex impact of religion in a person's life and in the different regions of the world. Religion can impact all aspects of society and is one of the lenses used to interpret the world around us. Some religious labels, such as being Jewish, can even refer to one's sense of ethnic identity rather than a set of spiritual beliefs. Religions vary in how their believers are distributed throughout the world. There are also many ways of practicing any one religion. Most religions focus on sacred religious texts and the wisdom of leaders in their faith. If a group believes that their religious texts and leaders advocate for the use of aggression, they may use force to promote their viewpoint. Conflicts can arise from strong differences in ideology, disputes related to historical ties to lands and resources, and memories of past persecution and violence. Alternatively, religions may also be interpreted as limiting violent behavior and promoting social justice through nonviolent resistance. Geographers aim to more fully understand how religious beliefs and practices affect the people of societies throughout the world.
Material culture includes the objects or belongings of human beings, including a wide range of physical items. Just about anything you can see, feel, or touch that is not human has the potential to be an item of material culture. Architecture, photographs, documents, artwork, gardens, a can of soda, or the electronic device you are using to read this lesson are all examples. Some theorists argue that entire cities and the surrounding geography are elements of material culture. Even human motions such as dance may be described as material in that it has shape and a physical form. Studying the physical objects of a culture gives us a better understanding and appreciation for the complex lives of the people who interacted with those objects. Material culture provides us insight into non-material culture, which includes the ideas, beliefs, habits, and values of a people. While an object starts off as simply a physical item, over time it comes to represent non-material and symbolic aspects of a culture. For some, a can of soda may represent an epidemic of obesity, while for others it may be viewed as a fun and pleasurable drink. In the past, some early historians, archaeologists, anthropologists, and museum directors had a way of presenting material culture that showed their ethnocentrism, the tendency for one culture to view itself as superior to another, and to judge the other culture by one's own values. For instance, a British explorer visiting a society in Africa might have returned from his travels with an African mask that held spiritual significance to those who created it. Instead of viewing it as having cultural significance of its own, the explorer may have labeled it as an example of the culture being backward. He viewed it as an inferior form of expression, despite the complex and nuanced meanings given to the mask by the culture that created it. In academic disciplines, the practice of simply taking objects of material culture from other places and judging them in an ethnocentric way is no longer accepted. We are more interested in preserving cultural heritage than at other times in history, which requires us to observe aspects of material culture without judging them based on our own society's standards. This practice of viewing a culture based on its own standards is known as cultural relativism. As best as they can, scholars today aim to study the material items as a way to learn more about another culture, rather than to use them to promote ethnocentric ideas about their own culture. While the study of the culture of human beings started in the fields of anthropology and archaeology, material culture studies has also emerged as a discipline in its own right. The scholars that work in all of these fields ask questions about the changing meaning of objects over time, the details of an artifact, such as when and where it was created, and the influence a material item had on the people in that society. If a material culture scholar hundreds of years from now were studying the late 20th and early 21st centuries in the United States, he would notice something interesting about our material culture during this time. He could see through physical artifacts and documentation how we went from larger electronic machines, computers that could fill a room, to smaller and smaller devices, personal computers and cell phones. These devices then took on new shapes and designs, such as laptops and tablets, and even became a pair of eyewear, Google Glass. The scholar would explore what impact these developments had on our society, what challenges we faced as a result of the new technologies, and what meaning we derived from the items. Studies in material culture have revealed several key concepts that the field still uses today to help understand what is happening when it considers the impact of a physical object on its culture. In 1957, William F. Ogburn discussed his theory of cultural lag. He pointed out how it takes time after a material item is invented until the people of that society see it as a normal component of their world, and that conflicts and challenges may arise during this period. Another way to describe cultural lag is a type of maladjustment that a culture has when a material item is still new, and the people of that culture have not yet fully utilized and integrated the new material item into everyday life in a functional way. Ogburn pointed out the process in which a material item takes on non-material meaning as a part of a culture, with an associated set of ideas, beliefs, and practices. He noted that over time, a technology is diffused or spread throughout a culture, as well as from one culture to another, often on a global scale. This study of technology now helps us look at specific areas, such as the evolution of early cell phones into smartphones, and what meaning and ideas we attach to these items as a culture. Other theorists have applied the concepts of material culture to a broad range of topics, from comparing different types of buildings to one another, to viewing a city as its own object, to exploring how gender relates to material culture. Have you heard of the Stanley Cup, the championship trophy given to the team that progresses and wins the final cup of the National Hockey League playoffs? The Stanley Cup is a trophy, a physical object, yet it represents something much larger, years of practice and competition, as well as national and regional pride, among other symbolic ideals. It is an object of material culture that has powerful non-material meanings. As it gets passed each year to the new winning team, so with it follows a set of rules, history, values, emotions, and even superstitions. I have a friend who, as a child, touched the Stanley Cup while it was on display, only to later regret it because of a belief by some hockey fans that this will put a curse on their team. Since his team has not won the Stanley Cup since he touched the trophy, he wonders, mostly humorously, if he should not have touched it years ago. This is an example of a non-material belief that emerges from a material item. Although in this case, his regret at touching it is mostly lighthearted, the other non-material meanings of the Stanley Cup are even more powerful. Winning the Stanley Cup represents values of sacrifice, determination, talent, and teamwork. Other examples of material culture in sports taking on non-material meanings include how a baseball represents elements of culture in the United States, how a hockey stick means a great deal to most Canadians, or a football, soccer ball, carries weight for much of the rest of the world. These symbols have significant meaning in history and evoked powerful emotions and responses from those who view the material object as having great non-material meaning. Even a simple bicycle can generate significant discussion for those looking at it as an object of material culture. Bicycles are gendered as male or female, with a male bike having a higher crossbar than a female bike. If you want to understand how this came to be, you can investigate the bicycle at a deeper level and learn about an earlier time in history where clothing worn by women influenced the height of the crossbar. If you look a layer deeper, you can learn how the increased mobility, independence, and freedom that bicycles gave women opened up many new opportunities. In fact, the non-material impact of the bicycle was so powerful that in 1896, Susan B. Anthony, the famous women's rights advocate, stated that bicycling had done more to emancipate women than anything else in the world. This is an example of why it can be so enlightening to study material items in relationship to the larger society. An everyday object we take for granted, such as a bicycle, could be a puzzle piece affecting the course of history. Material culture involves all the physical items and forms that we encounter that ultimately transform into non-material culture. This non-material culture includes the ideas and beliefs we hold in our society. Sometimes this process of making an object picking up non-material meaning takes time due to cultural lag and delays in the diffusion of a new technology from one area of society to another. The impact of material objects can be significant, such as the development of personal computing technology and electronic devices. Each item of material culture develops meaning beyond the item itself. In some cases, a simple object can have a global impact and transform our world as we know it.
Take a minute and think about all of the different people you interact with in a given day. For most people, this would include family, friends, co-workers, and strangers. A population is often described as a group of individuals of the same species that inhabit the same area. Therefore, all of the people you encounter each day are part of your population. Other examples of populations include the dandelion plants growing in a field, or the cockroaches that inhabit a single house. On a larger scale, you can think of all humans on Earth as the human population. As of 2011, the human population exceeded 7 billion people. Although the human population has been around this size for most of us for our entire lives, the population has not always been so large. Around 10,000 years ago, before the invention of agriculture, it is estimated that the human population was only a few million people worldwide. After the invention of agriculture, the human population began to grow slowly until the 1900s, when a rapid increase in the human population began. With increases in technology and medical advances, the human population was able to reach 3 billion in the 1960s. Since that time, the population has more than doubled and continues to increase. Now that we know how the human population has changed over time, it is important to investigate the factors that have influenced these changes. There are many factors that can influence the size of a population. Some factors result in an increase in the population, while others can cause a decrease in population size. There are two factors that result in an increase in the size of a population. First, there is natality, which is the number of individuals that are added to a population over a period of time due to reproduction. This term is often used to describe reproductive rates over a variety of time periods. The term most commonly used when describing natality in the human population is birth rate. Birth rate is the number of individuals born per 1,000 individuals per year. An example of birth rate would be if a population of 5,000 people resulted in the birth of 50 children in a year, which would yield a birth rate of 10 individuals per 1,000 per year. Birth rate is often reported as a percentage of the population. In 2010, the birth rate in the United States was 1.38%, which is considerably lower than the birth rate in many developing countries. For example, in 2010, the birth rate in Ethiopia was 4.34%. Birth rates can vary a great deal by region and can have drastic effects on the overall human population. The second factor that can cause a rise in a population is immigration. Immigration is the migration of an individual into a place. When an individual immigrates to a new location, they increase the population within that area. Immigration is a factor that can influence the size of a specific population of humans, but does not influence the overall human population. For example, if an individual decides to move from London to New York, they would be immigrating to the United States and would therefore increase the population of the U.S. Their immigration would have no influence on the overall human population because no matter where they live, they are included in the size of the human population. The only way that immigration could influence the overall human population on Earth is if humans lived on a different planet and immigrated to Earth. In that scenario, the human population on Earth would increase. Now that we have learned about the factors that increase population size, let's investigate the factors that have the opposite influence. The first factor that results in a decrease in the population size is mortality. Mortality is the number of individual deaths in a population over a period of time. In terms of human population, mortality is often described as the death rate, which is the number of individuals that die per 1,000 individuals per year. Death rates are often used to describe how many individuals die in specific age groups. For example, the death rate of infants is often an important statistic to investigate when looking at changes in the population. Similarly to birth rates, the death rate is also often described as a percentage of the population. In 2010, the death rate for infants in the United States was 0.6%, while in Ethiopia, the infant death rate was 7.1%. The second factor that can decrease the size of a population is emigration. Emigration is the migration of an individual from a place. When an individual emigrates from a location, they decrease the population within that area. If you think back on the immigration example, with the person moving from London to New York, we said that the person was immigrating to the United States. Using this same example, the person would also be emigrating from England. Similarly to immigration, emigration also does not have an influence on the overall human population on Earth, because people are not leaving Earth to move to a new planet. Although there are factors that either increase or decrease the human population, when these factors are combined, they represent the overall population growth rate. The population growth rate is the rate at which the population changes in size. The rate of change is determined by subtracting the number of people that leave the population through death or emigration from the number of individuals that enter the population through birth or immigration. This calculation makes it possible to combine all of the statistics that influence population size and to determine how the overall population is changing over time. The population growth rate can result in either a positive or negative rate depending on the factors. Let's review populations, which are a group of individuals of the same species that inhabit the same area, and the factors that influence changes in populations. Over time, the human population has increased, which results in a positive population growth rate, which is the rate at which the population changes in size. Although the human population has increased overall, there are many factors that contribute to the rate. The two factors that increase the size of a population are natality, which is the number of individuals that are added to the population over a period of time due to reproduction, and immigration, which is the migration of an individual into a place. The two factors that decrease the size of a population are mortality, which is the number of individual deaths in a population over a period of time, and emigration, which is the migration of an individual from a place. For the human population, natality is often described in terms of birth rate, which is the number of individuals born per 1,000 individuals per year, and mortality is described in terms of death rate, which is the number of individuals that die per 1,000 individuals per year. When you combine the rates of births, deaths, immigration, and emigration, you can determine whether a population is growing, shrinking, or is remaining the same. All of these statistics are important because they make it possible for us to determine how our population is changing and may provide insight into how our growing population may influence the environment we live in. Have you ever held a baby or seen ducklings in a pond? Both of these are examples of offspring of a specific species. Offspring are very important because by producing offspring, a species is able to pass along genetic material to the next generation and continue the existence of the species. Now, think about the baby and the ducklings again, but this time think about how many you would normally see. In most circumstances, a human produces 1 or 2 babies at a time, while a duck has several ducklings at a time. This difference in the number of offspring produced can be referred to as a difference in biotic potential, which is the rate at which a species produces with unlimited conditions. Biotic potential describes the number of offspring a species can produce when they have ideal circumstances, including unlimited food and water, safe habitat, and any other conditions that would promote successful reproduction. As we learned with the example of the baby and the ducklings, biotic potential can vary a great deal by species. Similarly to humans, many large mammals only produce 1 offspring per year or breeding season. On the other hand, many plants and insects can produce much larger numbers of offspring. In particular, many moths can lay hundreds of eggs, which given the correct conditions could all hatch and turn into successful offspring. There are also many species that fall between the two extremes, including geese, which produce between 10 and 12 offspring each year. Biotic potential is applied to circumstances where organisms live in an ideal habitat with all of the conditions and materials they need. As most people would agree, you do not always have everything you need or want. The same is true in nature. In natural ecosystems, there is environmental resistance, which are factors that can limit the increase in a population. Common factors include predators, disease, competitors, and lack of food, water, and suitable habitat. Due to factors that contribute to environmental resistance, not all individuals that are born can survive to adulthood or reproductive age. As a result, the overall population of the species does not grow uncontrollably, but instead is limited and controlled. This control, caused by environmental resistance, leads to the establishment of a carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. When carrying capacity is reached, a population can survive on the resources available without depleting the overall availability of the resources. When a population is below the carrying capacity, the individuals have access to more than enough resources to survive. As we learn from biotic potential, if individuals have the ideal circumstances, they can reproduce without limit, which causes population increases. When a population grows and begins to reach the carrying capacity, the population begins using resources at an equal rate to which the resources are created. This often creates competition between individuals for the available resources. As a result, some individuals will die when they cannot get enough resources, and others will not reproduce because they do not have the resources to support offspring. Eventually, the birth rates will decline and death rates will increase. This will lead to an overall population decline until the population returns to a state where the number of individuals alive can survive successfully on the resources available, which will be the carrying capacity of the population. A common example to help explain carrying capacity is the number of people that could survive a shipwreck on an abandoned island. Let's say that the ship had 10 people on board when it crashed. If the island is large and has plenty of resources, then the population of humans would be below carrying capacity, and all 10 people would have a better chance of surviving. If the island was small, the resources would be limited, and not all the people would survive. The population would decline until it reached the carrying capacity, which would be when a certain number of people were able to survive on the resources available on the island. Let's review populations, how they grow, and how they are controlled. First, populations grow by producing offspring, and biotic potential is often used to describe the rate at which a species reproduce with unlimited conditions. A species can reach biotic potential when they reproduce the maximum number of offspring possible with access to ideal circumstances, including unlimited food and safe habitat. Due to the large variety of species found on Earth, biotic potential has a wide range across all species. Biotic potential for large mammals is quite low, while insects can have a very high biotic potential. In a natural ecosystem, ideal conditions are not always available, and there is environmental resistance, which are factors that can limit the increase of a population. Factors can include predators, disease, competitors, and lack of food, water, and suitable habitat. Environmental resistance limits the number of individuals that survive and leads to the establishment of a carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. When a population is below carrying capacity, there are more than enough resources available to ensure the survival of each individual. If a population grows too rapidly and exceeds the carrying capacity, resources will become limited and the population will decline until the carrying capacity is reached. When carrying capacity is reached, a certain size population can survive on the resources available without depleting the overall availability of the resources. Now, think back on the baby and ducklings from the beginning of the lesson. Although the number of offspring produced may have originally seemed random, now you know there are factors that control the production of offspring and the size of a population an ecosystem can support. How many people do you think the human population grows by each year? Maybe 1 million, 10 million, more? As of 2012, over 80 million people were added to the human population each year. To give you perspective, this would be equivalent to the populations of California, Texas, and New York combined. On a shorter scale, we add 2.6 people to the population every second. This would mean that each day you could fill 2 large football stadiums with the number of people that were added to the human population. As of 2013, the human population is around 7 billion people, and it has taken many years for the population to grow to this size. Over this long amount of time, some periods have had slow growth, while others have had more rapid growth. Due to these fluctuations and how large the human population has become, scientists have begun to investigate the growth of the human population. Demography is the study of the size, density, and distribution of the human population. This area of study takes into account birth rates, death rates, age distribution, and any other factors that influence the size and growth of a population. Demographers have identified 3 distinct periods of human population growth that help explain the history of how our population has changed. The pre-agricultural period is the first period of human population growth. This period is considered anything before 10,000 years ago. During the pre-agricultural period, human population growth was very slow, and it took tens of thousands of years for the human population to double. Although growth was slow, the population was able to increase due to the development of tools. As people developed more advanced tools, they were able to travel to new land and use their skills to adapt. This made it possible for people to spread to new regions of the world and expand the coverage of the human population. When the pre-agricultural period ended around 10,000 years ago, the human population was estimated to be somewhere between 5 and 10 million people. The agricultural period is the second period of human population growth. This period ranges from 10,000 years ago to about 1,000 years ago. During this time period, the human population started to grow more rapidly due to advances in agriculture. It was during this time that plants and animals were domesticated for farming. There were also advances in irrigation and plowing techniques that increased overall crop yield. As a result of increased food availability and more nutritious food, the human population grew faster than ever. Unlike during the pre-agricultural period, when it took tens of thousands of years for the human population to double, during the agricultural period, it only took around 1,000 years for it to double in size. At the end of the agricultural period, the human population had increased a great deal to around 500 million people. The industrial period was the third period of human population growth. This period is from 1,000 years ago to current day and is characterized by advances in technology. Although there were advances in technology during the early part of this period, it wasn't until the Industrial Revolution in the 1800s that the advances in technology started to have a profound influence on the human population. During this time period, there were technological advances in agricultural techniques that made it possible to grow crops on land that had previously been unusable. This resulted in another increase in the amount of food available and therefore increased the number of humans that could survive. Technology was also used to improve medicine and sanitation, which helped save lives and increase the lifespan of the average person. As a result of the technological advances of the industrial period, the human population grew at a rapid pace. Over the industrial period, the time it takes to double the population decreased a great deal. During the beginning of the period, it took around 500 years to double the population, but more recently the number has decreased to 50 years to double. During the industrial period, the human population grew from 500 million people to the 7 billion people we now have on Earth. Now that we have examined the history of the human population, what do you think the future holds? Will the human population continue to grow at the same rate, slower, or stay stable? For most species, their population growth is controlled by their carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. For example, if a forest only has enough food to support 50 individuals of a species, and the population grows larger, not all the individuals will survive. The population will decrease until it is at or under the carrying capacity, which is where there would be enough food for all individuals. Although many people are interested or concerned about the future growth of the human population, unfortunately, it is not possible to precisely determine the carrying capacity of humans on Earth. Some scientists estimate that the world could support between 1 to 2 billion people if they are living prosperously and in a healthy environment. On the other hand, they also estimate that the world could support over 33 billion people if people are living in extreme poverty with very degraded environments. There are many factors and characteristics about human life that make it difficult to determine how many people Earth can support, but the most powerful factor is technology. Humans have the intelligence to create technology that helps save lives, increase food availability, increase lifespan, and therefore challenge the carrying capacity. There were times in human history where there were mass starvations, and some thought we had reached our carrying capacity. But, due to technology, we were able to combat the starvation by producing more food, and therefore helping the population continue to grow. Now, let's review the history of human population growth and the human carrying capacity. Demography is the study of the size, density, and distribution of the human population. This area of study has been used to determine 3 distinct periods of human population growth. The pre-agricultural period is the first period of human population growth and was characterized by the development of tools. With new tools and skills, humans were able to adapt to new environments and expand their range to new habitats, which resulted in a slow population increase to between 5 to 10 million people. The agricultural period was the second period of human growth and was characterized by advances in agriculture. As a result of increased food production and healthy food, the human population grew more rapidly to around 500 million people. The industrial period was the third period of human population growth and was characterized by advances in technology. This period brought about technological advances in medicine, food production, and sanitation that helped support a rapid increase in the human population to the nearly 7 billion people that now inhabit the Earth. Due to the rapid increase in the human population, many people wonder about the carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. Unlike other species, humans have been able to exceed their estimated carrying capacity due to technology. Human intelligence and advances in technology have made it possible for humans to find ways to support the population and ensure increase despite natural pressures to decrease the population. This might always be the case, or someday our population may become so large that the Earth cannot support us all. The human population has been growing for thousands of years, and as of 2013, there are over 7 billion people on Earth. What do you think will happen to the human population in the future? Will it continue to increase, or maybe decrease, or stay the same? Over the years, there have been many opinions on how the human population will change over time. During the 1700s, philosophers proclaimed that the human population would be maintained because human knowledge and moral constraint would make it possible to establish a world where resources are abundant. They believed that humans could control the Earth and would make sure that all humans had all of the supplies they needed to survive. It was also a common belief of the time that if the population started to grow too rapidly, that people would immediately stop having sexual intercourse to help limit population growth. During the 1700s, there was one man who was very interested in the future of the human population and had an opinion very different than most. Thomas Malthus, an English philosopher who lived from 1766 to 1834, was the first man to publicly predict the limits of the human population and how population and well-being are connected. In 1798, Malthus wrote an essay on the principle of population, which explained his predictions and changed the view of many people. Thomas Malthus believed that the human population exhibits exponential growth, which is when the increase is proportional to the amount already present. With exponential growth, the rate of increase becomes more rapid in proportion to the increasing total size. An example of exponential growth would be if a population increased from 2 individuals to 4, 8, 16, 32, and then 64 individuals. Now we know what exponential growth is. You might wonder what this has to do with human well-being. Thomas Malthus found that food production did not increase at an exponential rate, but instead increased more slowly. As a result of these differences in population and food growth rates, Malthus predicted that the human population would eventually grow too large to be sufficiently supported by the food available. As a result of the growing population and limited food, Thomas Malthus thought that the world would begin a downward spiral. Overall, he predicted that the uncontrolled population growth would lead to a depletion of resources, increased pollution, overcrowding, and increased unemployment. He thought these problems would then lead to larger problems, such as starvation, increased diseases, crime, poverty, and eventually war. Malthus predicted that these unfortunate circumstances would be how the Earth would control the human population. He thought that these problems would lead to increased death rates and lower birth rates, which would help return the human population to a manageable size where there would be enough resources to support the entire population. In areas of the world that suffer from extreme poverty, you can currently see Thomas Malthus's predictions coming true. In these areas, populations have increased rapidly and without control. This has led to famine, diseases, and wars, which have all caused decreases in the population size of the region. When designing his predictions, Thomas Malthus did not foresee how much the world would change in a short period of time, and how advances in technology would influence human population growth. In developed countries with highly advanced technology, Thomas Malthus's predictions have not come true. In these areas, the advances in technology have made it possible to produce more food and keep people healthy, which have only helped increase the population. Malthus also did not predict that when the population started to increase, that people would migrate to areas that were previously not settled, such as the Americas and Australia. Let's review Thomas Malthus and his theory on human population growth. Before the time of Malthus, many philosophers believed that the human population would be controlled by human knowledge and moral constraint. They thought that human intelligence would make it possible to control the earth and produce all of the resources needed. They also thought that due to moral constraint, people would stop having sexual intercourse if they needed to limit population growth. With the publication of Thomas Malthus's An Essay on the Principle of Population, the view on human population growth was altered. Malthus believed that the human population exhibits exponential growth, which is when the increase is proportional to the amount already present. Overall, he predicted that due to the rapid and excessive growth of the human population and the slow growth of food production, the human population would outgrow its food supply. He thought this would eventually lead to starvation, increased diseases, crime, poverty, and war. These issues would then be the factors that would reduce the human population until it returned to a healthy number. Thomas Malthus's theory was controversial when written and is still debated in the science community. Some believe that Thomas Malthus's predictions did come true in areas of extreme poverty, where excessive population growth has led to famine, diseases, and wars. His predictions are thought to have not come true in more developed countries that have used technology to produce more food and that continue to increase in size. Whether or not you believe that Thomas Malthus's theory was correct or not, it does raise some interesting thoughts on the history and future of the human population.
One of my husband's closest friends has been living in China for the past decade. Whenever he travels home to our rather rural area, he always remarks how shocked he is to remember how few people live here. This is a stark difference to his home in China, where the city streets are teeming with people. This contrast is an excellent example of the differences in population density found throughout the globe. Today's lesson will cover this topic as we discuss the concept of population density. To begin, population density is a measurement of the number of people in an area relative to the size of the area. When speaking of population density, it's important to note that it's not an exact number. Instead, it's much more of an estimate or average. This is simply due to constant fluctuations caused by births and deaths. When speaking of population density, the terms sparse and dense are often used. If an area is sparsely populated, this simply means that it contains few people relative to its size. Conversely, if an area is densely populated, this means it contains a large amount of people relative to its size. According to geographers, areas that are sparsely populated are usually very difficult places to live. For instance, they may have difficult climates, such as the Mojave Desert or the tundra of the North Pole. They also may have very high elevations, as in the mountain regions of the Urals or the highlands of Tibet. On the contrary, areas with more temperate climates and lower elevations tend to be more densely populated. A good example of this is the densely populated areas of the northeastern U.S. Population density is also affected by more human factors. For instance, if an area is politically unstable or war-torn, it will usually have a very low population density. This is seen in areas like Syria and Afghanistan. Another human factor that affects population density is the availability of employment. For instance, industrial cities like Beijing, China, or Philadelphia, Pennsylvania, offer job opportunities. For this reason, they are more densely populated. Now that we've covered the definitions of population density, let's move on to specific areas of the world. As we do this, please remember that population density doesn't just mean the number of people in an area. It is the measurement of the number of people in an area relative to the size of the area. For example, the state of New Jersey is the most densely populated state in the U.S. Yes, its actual population is lower than that of New York, but its people are crowded into a much smaller space. When speaking of high population densities, the word cluster is often used. The highest population densities, or primary population clusters, are found in the regions of Europe, East Asia, South Asia, and Southeast Asia. Some of the countries in these regions are Germany in Europe, India in South Asia, Thailand in Southeast Asia, and of course China in East Asia. The secondary population clusters are found in southern Brazil, the center of Mexico, and the eastern United States. Areas of the world that are very sparsely populated are places like Australia, Canada, Mongolia, the Saharan, and Russia. Population density is a measurement of the number of people in an area relative to the size of the area. Population densities are usually defined as being either dense or sparse. Sparsely populated denotes containing few people relative to size, while densely populated denotes containing a large amount of people relative to size. Population density is often affected by several factors. There are physical factors such as climate and elevation. There are also human factors such as political instability and lack of employment opportunities. When speaking specifically, the world's primary population clusters are found in the regions of Europe, East Asia, South Asia, and Southeast Asia. The secondary population clusters are found in southern Brazil, the center of Mexico, and the eastern United States. When speaking of very sparsely populated areas, we have Australia, Canada, Mongolia, the Saharan, and Russia. I live in a very small town where there's one traffic light. Now, if you are traveling near this traffic light at about 4:30 in the afternoon, you may find yourself having to wait about 6 to 7 minutes to get through it. Since I live in a sparsely populated area, this is our rush hour. Now, if you're listening to this and you live anywhere near a big city, you're probably thinking I'm crazy for calling this rush hour when you are accustomed to freeways that resemble parking lots. However, living in a relatively sparsely populated area, we country folks aren't used to bumper-to-bumper traffic unless there's an accident or some local chickens escaped from their pens and are hanging out on the road. Today we're going to discuss areas like mine as we dive into a study on sparsely populated world regions. For starters, sparsely populated simply defines an area that contains few people. Generally speaking, sparsely populated areas are usually rather challenging places to live. When discussing these challenges, geographers usually break them into physical factors and human factors. For our purposes, we'll start with physical factors. To begin, the relief of an area has a lot to do with its population density. In geography, relief is defined as the difference in elevation between parts of the Earth's surface. When speaking of relief, regions of the world with high elevations tend to be very sparsely populated. A great example of this is the Himalayan region of the Asian continent. This mountainous area makes travel to and from it very difficult. Its mountainous terrain also makes food production extremely challenging. In other words, this area cannot support a lot of people. Therefore, it's very sparsely populated. Natural resources, natural materials such as minerals, forests, water, and fertile land that can be used for economic improvement are another factor that go into population density. Areas that are rich in resources, like the northeastern U.S., tend to be densely populated. However, Areas like the Saharan Desert, which have very little natural resources, are usually very sparsely populated. Speaking of the Sahara Desert, climate also affects population density. Being rather obvious, areas with extreme climates, whether freezing like the Arctic Circle or sweltering like the Sahara, tend to be sparsely populated. Moving away from physical factors that affect population density, let's take a look at the human factors that cause some areas to be sparsely populated. For this, we'll focus on political and economic factors. When speaking of political factors, areas of the world that suffer from political instability tend to be sparsely populated. Being pretty easy to understand, if given the choice, most people would not want to live in a war zone. Examples of areas that are sparsely populated due to political instability are places like Afghanistan, Syria, and today's war-torn Iraq. Moving to economies, the scarcity of employment opportunities will also cause an area to be sparsely populated. Being pretty obvious, in today's modern world, people need a way to make a living. If this is not available, they will often move to find it. An excellent example of this is the U.S., where the cities of the Northeast offer large job markets and therefore have higher population densities. This is in sharp contrast to the southern U.S., in which job opportunities are less and therefore the population is much sparser. Now that we've covered some of the factors that cause a sparse population density, let's take a minute and just point out some specific areas that are sparsely populated. In our lesson, we've already mentioned places like Afghanistan, Syria, Iraq, the Arctic Circle, and the Sahara, as well as the Himalayan region of Asia. However, there is also the island nation of Iceland, the arid area of northwest Africa, the harsh land of the Australian outback, and landlocked Mongolia. Sparsely populated simply means an area that contains few people. Areas are usually sparsely populated due to physical and human factors. Physical factors that affect population density are relief, which is defined as the difference in elevation between parts of the Earth's surface, and the availability of natural resources, or natural materials such as minerals, forests, water, and fertile land that can be used for economic improvement. In addition, areas with extreme climates, whether hot or cold, are usually sparsely populated. Population density is also affected by political and economic reasons. Areas which are politically unstable are often sparsely populated. Also, areas which offer little opportunities for employment are also sparsely populated. Some of the more sparsely populated regions of the world are found in Afghanistan, Syria, Iraq, the Arctic Circle, the Sahara, the Himalayan region of Asia, Iceland, northwest Africa, the outback of Australia, and Mongolia. Besides the skyscrapers, the Broadway shows, and the plethora of yummy food choices, one of the most amazing things to me about New York City is the massive waves of people that are continually moving along its streets. Whether at 3 in the morning or 3 in the afternoon, the streets are always humming. With this massive amount of people, New York City is a great example of a place with a very high population density. Today we're going to take a look at this concept of population density. Stated rather simply, population density is a measurement of the number of people in an area relative to its size. Like many geographical concepts, it's not an exact number. It's usually more of an average or even an estimate. With this in mind, population density is most often calculated by the number of people per square kilometer. Population density is often measured in 3 different ways. There is arithmetic density, physiological density, and agricultural density. We'll get started with arithmetic density. Arithmetic density is what most people think of when they hear the word population density. It's simply the total number of people divided by the total land area. Also called real density, arithmetic density does not take into account whether or not the land is rural, urban, or whether it is desert or frozen tundra. It just gives the straightforward measurement of people divided by land. I like to think of it as just being simple arithmetic. With arithmetic density under our belts, let's take a look at physiological density. Physiological density is the number of people per unit area of arable land. Explaining this a bit, arable denotes land that is suitable for growing crops. In other words, arable is much the same as being fertile. With this in mind, a simpler definition of physiological density might be the number of people divided by land that is suitable for growing crops. Physiological density is often used to estimate how long a land and its resources can sustain its population. Making this easy to hold on to, I like to think of physiological density as a look at how long the physical land can support its people. Last, we come to agricultural density. Being sort of similar to physiological density, agricultural density measures the number of agriculturalists per unit area of arable land. Remember that arable means that land is able to be farmed. And since agriculturists are often called farmers, this one is easy to remember. We can simply say that agricultural density is simply the number of farmers per farmable land. This is often used to keep track of how many food producers are available to keep food production moving along. Population density is a measurement of the number of people in an area relative to its size. Population density is often quantified as arithmetic density, physiological density, and agricultural density. Arithmetic density, also known as real density, is very simply the total number of people divided by the total land area. Physiological density is the number of people per unit area of arable land. Arable describes land that is suitable for growing crops. This measurement is often used to estimate how long a land and its resources can support its population. Lastly, agricultural density measures the number of agriculturalists per unit area of arable land. This is often used as a means to ensure food production can continue.
When you walk around almost any city or town, you can see different sized houses, different types of cars, and different activities occurring. These differences can be indicators of economic inequality, which is the difference between individuals or populations in terms of their wealth, assets, or income. Although most frequently you see differences in economic levels around your town, economic inequality can also be applied on a larger scale to the nations of the world. Based on economics, the world has been divided into two types of countries. The two categories are based mainly on per capita income, which is the average income per person. The per capita income is calculated by taking the total national income for a country and dividing it by the number of people that live in the country. For example, if a small country has a total national income of $800,000 and a population of 20 people, then the per capita income is $40,000. The first economic category is developed nations, which can generally be categorized as countries that are more industrialized and have higher per capita income levels. To be considered a developed nation, a country generally has a per capita income around above $12,000. Also, most developed countries have an average per capita income of approximately $38,000. As of 2010, the list of developed nations included the United States, Canada, Japan, Republic of Korea, Australia, New Zealand, Scandinavia, Singapore, Taiwan, Israel, countries of Western Europe, and some Arab states. In 2012, the combined populations of these countries accounted for around 1.3 billion people. The populations of developed countries are generally more stable, and it is estimated that they will grow at a steady rate of around 7% over the next 40 years. In addition to having high per capita income and stable population growth rates, developed nations are also characterized by their use of resources. In developed countries, people consume large amounts of natural resources per person and are estimated to consume almost 88% of the world's resources. The second economic category is developing nations, which is a broad term that includes countries that are less industrialized and have lower per capita income levels. Developing nations can be divided further into moderately developed or less developed countries. Moderately developed countries have an approximate per capita income of between $1,000 and $12,000. The average per capita income for moderately developed countries is around $4,000. As of 2012, the list of moderately developed nations is very long and accounts for around 4.9 billion people. Some of the most recognizable countries that are considered moderately developed include Mexico, China, Indonesia, Jordan, Thailand, Fiji, and Ecuador. In addition to these specific countries, many others from Central America, South America, Northern and Southern Africa, Southeastern Asia, Eastern Europe, the former USSR, and many Arab states are all considered moderately developed countries. Less developed countries are the second type of developing nations. They are characterized by having the lowest income with a general per capita income of approximately less than $1,000. In many of these countries, the average per capita income is even lower, at around $500. The countries listed as less developed are found in Eastern, Western, and Central Africa, India, and other countries in Southern Asia. In 2012, there were around 0.8 billion people who lived in these countries and survived on very little income. Overall, in 2012, developing nations accounted for a total of 5.7 billion people. Even though the income range is quite large, there are still nearly 3 billion people that live on less than $2 a day. Can you imagine living on less than $2 a day? That would be a very hard task for most of us to do. In addition to low income levels, developing countries are also characterized as having high population growth rates. It is estimated that these countries are going to increase by 44% over the next 40 years. By 2050, it is predicted that over 86% of the human population will live in developing countries. Now, let's review economic inequality and how it relates to developed and developing nations. First, economic inequality is defined as the difference between individuals or populations in terms of their wealth, assets, or income. This difference can be looked at on a small scale in individual regions or on a large scale across the world. When discussing economic inequality on the global scale, it is important to know that countries are divided into two categories based on their per capita income, which is the average income per person. The two categories are developed nations and developing nations. Developed nations are generally categorized as countries that are more industrialized and have higher per capita income levels. In general, the per capita income of a developed country is above $12,000 and has an average of $38,000. Some common developed countries include the United States, Canada, Japan, Australia, Israel, and countries of Western Europe. Developing nations are generally categorized as countries that are less industrialized and have lower per capita income levels. This category is divided into moderately developed and less developed countries. Moderately developed countries have an approximate per capita income of between $1,000 and $12,000, with an average of $4,000. The majority of countries on Earth are considered moderately developed, including Mexico, China, Indonesia, Jordan, Thailand, Fiji, and Ecuador. In general, less developed countries have a per capita income of less than $1,000 and an average of $500. These countries are found in Eastern, Western, and Central Africa, India, and other countries in Southern Asia. Although the range of economic inequality around the world is very large, the income of all people is of equal importance. The world and the economies of every country are intertwined and depend on each other. Due to this fact, it is important to remember that not everyone lives at the same economic level, but that everyone can work together to help those less fortunate. Take a minute and think about major cities in the United States. There are some regions of the U.S., such as the Northeast and Southwest, that have very large cities. On the other hand, there are areas of the U.S., such as the Midwest, that have much smaller cities. This example of uneven distribution would be a topic of demography, which is the study of the size, density, and distribution of the human population. This area of study takes into account birth rates, death rates, age distribution, and any other factors that influence the size and growth of a population. Over the course of human history, there have been many people who have been interested in the characteristics of the human population and the future of population growth. After analyzing how Western populations have changed over time, one pattern was discovered that indicated there was a connection between population growth and the economic development of a country. It was observed that in countries with high standards of living, the population grew at a slow rate, while in countries with low standards of living, the population grew more rapidly. This discovery resulted in the creation of the concept of demographic transition, which is a series of stages that a country goes through when transitioning from non-industrial to industrial. The demographic transition concept involves 4 stages that are based on changes in population size and social behaviors. The first stage of the demographic transition is the pre-industrial stage. During this stage, the population is stable, with both high birth rates and high death rates. The death rates are high because there is increased disease, minimal medical care, poor sanitation, and limited food supplies. As a result of the high death rate, people tend to produce more offspring to try to compensate for the mortality. Although the birth rate and death rate can fluctuate slightly, overall they remain equal, which results in 0 population growth. Following the pre-industrial stage is the transitional stage. During this stage, the human population begins to increase due to high birth rates and declining death rates. The death rates are decreasing because as the country transitions into an industrial country, there are improvements in the economy and social conditions. These changes lead to the control of diseases, the production of more food, better jobs, and improved medical care and sanitation. As the death rates decrease, the birth rates remain high because people are still accustomed to producing more children, and during this stage, they have more food and resources to support larger families. As a result of the declining death rates and high birth rates, the human population will increase at a rapid pace. The third stage of the demographic transition is the industrial stage, which is characterized by an increasing population with declining birth rates and low death rates. The death rates remain stable and low during this stage due to the continuation of the economic and social changes that improved the standard of living during the previous stage. During this stage, the birth rates begin to decline for many reasons. For the most part, people realize that they no longer have to produce large numbers of offspring because the offspring they do produce have a higher chance of surviving to adulthood. Many people also start to prefer smaller families, where they can concentrate more resources on less people and increase overall livelihood. The decline in birth rates also correlates with an increase in employment opportunities for women and the increased access to contraception. Although the birth rates are declining, the population continues to increase due to the low death rates and the momentum of the population from the previous stage. The high birth rates in the previous stage produced more overall people that will reach reproductive age, and even if they produce fewer offspring than previous generations, they are still adding to the population. Following the industrial stage is the final stage of the demographic transition. This stage is referred to as the post-industrial stage and is characterized by a stable human population with both low birth rates and low death rates. The birth rates and death rates remain low due to the economic and social changes of the previous stages. As the gap is closed between death rates and birth rates, the human population will stop increasing and remain at a stable level. Now, let's review demography, which is the study of the size, density, and distribution of the human population, and the concept of demographic transition. Demographic transition is a series of stages that a country goes through when transitioning from non-industrial to industrial. The concept is used to explain how population growth and economic development of a country are connected. The concept of demographic transition has 4 stages, including the pre-industrial stage, the transition stage, the industrial stage, and the post-industrial stage. The pre-industrial stage is characterized by a stable population, with high death rates due to low standard of living and high birth rates due to the need to compensate for deaths. The second stage is the transition stage, which is when the population begins to increase due to continued high birth rates and declining death rates as a result of an increase in the standard of living. The industrial stage follows and is characterized by continued population increase despite the declining birth rates and low death rates, which result from increased standard of living and changes in social views. The final stage is the post-industrial stage, which is when the human population stabilizes due to low birth rates and low death rates. The concept of demographic transition is a good predictor of how a country will change both in population size and socially as it transitions from non-industrial to industrial. Although the concept has proven true in many Western countries over the years, it is only a model and cannot absolutely determine how countries will respond to future changes. If you were to take a road trip across almost any country, you would travel through big cities and long stretches of rural towns. On your trip, you might notice that there are varying numbers of people in these different types of areas. This would be an example of a difference in population density, which is the number of people per unit of land area. In most cases, the big cities would have more people in a small area of land and would therefore have a high population density. On the other hand, most rural areas would have fewer people over more land area and would have a lower population density. Before discussing the population trends in rural and urban areas, let's examine these terms. According to the United States Census Bureau, an urban area is a city with a population size of more than 2,500 people, and a rural area has a population of less than 2,500 people. This definition can be tricky because it does not include information about the size of the area or the density of the population. Due to the vague nature of this definition, function is also considered when differentiating these terms. In general, an area is considered rural if most of the residents survive on agriculture or rely on natural resource-based occupations, such as logging or fishing. On the other hand, an area is considered urban when it has residents that do not directly depend on natural resource-based occupations. Now that we have a better understanding of what makes an area rural or urban, let's explore the populations of these areas. Although the population density in urban areas is generally higher than in rural areas, the overall size of the population in each location has fluctuated over time. For the majority of human history, most people have lived in rural areas and have survived by hunting, gathering, fishing, farming, or other occupations based on nature. It wasn't until around 300 years ago, during the Industrial Revolution, that the population began to shift. People began to move to urban areas in search of jobs, food, housing, education, healthcare, and more social activities. Urbanization is the term used to describe the shift from rural to urban living and the increased concentration of the human population in densely populated cities. In the mid-1800s, only 2% of the entire human population lived in urban areas. By the 1950s, the percentage of the human population living in urban areas was up to around 29%, and by 2009, that number had reached 50%. This number is expected to increase rapidly, and by 2050, it is predicted that over 70% of the human population will live in urban areas. Similarly to the overall human population, the percentage of people living in urban areas has also increased in the United States. In the early 1900s, around 21% of the United States population lived in urban areas. This number has increased steadily, and in 2013, around 82% of the United States population lived in urban areas. As more people move to urban areas, there has been a population explosion in some cities. For example, in 1900, there were only 13 cities worldwide that had a population of over 1 million. In 2007, there were over 300 cities with populations over 1 million, and many of those cities had much higher numbers. Due to this population explosion, a new term has been created for very large cities. Megacities is the term used to describe urban areas with a human population over 10 million people. As of 2013, there were 25 megacities across the world, including New York, Los Angeles, London, Buenos Aires, Rio de Janeiro, Tokyo, Beijing, Cairo, and Mumbai. In the United States, the urban areas between Boston and Washington, D.C. are often referred to as a continuous megacity. The region is called Boswash and has around 35 million residents. Now, let's review populations and how they are distributed between urban and rural locations. In general, an urban area is a city with a population size of more than 2,500 people and is characterized by having residents that do not directly depend on natural resource-based occupations. Rural areas are described as areas with a population of less than 2,500 people and where most of the residents survive on agriculture or rely on natural resource-based occupations. For most of human history, the majority of the population has lived in rural areas. However, since the Industrial Revolution, there has been an increase in urbanization. Urbanization is the shift from rural to urban living and the increased concentration of the human population in densely populated cities. From the mid-1800s to 2009, the percentage of the entire human population living in urban areas has increased drastically, from around 2% to over 50%. In addition, urbanization has also been prevalent in the United States. As of 2013, around 82% of the population lived in urban areas. The large and constant influx of people into urban areas has resulted in the creation of megacities, which are urban areas with a human population over 10 million people. As of 2013, there were over 25 megacities across the world. It is predicted that over the coming years, the populations in urban cities will only continue to increase, and urban living will be the normal lifestyle for most people on Earth. Imagine a big city in the United States and a small village in Ethiopia. What are some differences between these two locations? Some differences might include climate, population size, culture, and diet. The economies of these two countries are one major characteristic that set them apart. The United States is considered a highly developed country, which is a general category for countries that are highly industrialized and have high per capita income levels. Ethiopia, on the other hand, would be considered a developing country, which is a general category for countries that have limited industrialization and have low per capita income levels. Although highly developed and developing countries are often compared based on economy, they also vary a great deal in population characteristics. Some of the most commonly analyzed population characteristics include infant mortality rate, total fertility rate, replacement level fertility, and age structure. Unfortunately, not all children that are born will survive, and the rate of survival can vary a great deal by the type of country. Infant mortality rate is the term used to describe the percentage of infants that die before the age of 1 year. Although sad, this statistic is very important because it influences the overall population growth rate, replacement level fertility, and the age structure of the population. The infant mortality rate varies a great deal between highly developed and developing countries. On average, developing countries have an infant mortality rate that is 18 times higher than the rate of developed countries. When comparing the 10 most developed countries with the 10 least developed countries, the infant mortality rate is daunting. The most developed countries have an infant mortality rate of less than 1%, while the least developed countries have an average infant mortality rate of around 10%. These differences in infant mortality rate are shocking, and the high rates are due mainly to limited access to medical care, poor sanitation, and increased prevalence of diseases. One of the most important population characteristics of a country has to do with births. The total fertility rate is the average number of offspring born to a woman in a population during her reproductive window. Now, you might ask yourself, what is a woman's reproductive window? The reproductive window is the period in a woman's life when she can physically become pregnant, starting with sexual maturity and ending with menopause. In a world with unlimited resources and no problems, a woman could produce up to 25 offspring during her reproductive window. This would mean that her total fertility rate would be 25 children per lifetime. Although it is physically possible to produce 25 children per lifetime, the total fertility rate is often much lower. In developing countries, the fertility rate ranges from between 3 and 7 children per woman. On the other hand, the total fertility rate in developed countries is normally between 1 and 3 children per woman. In general, these differences in total fertility rates are due to varying levels of access to contraception and cultural practices. Another important population characteristic that relates to births is replacement level fertility. Replacement level fertility is the fertility rate that will result in the replacement of the parents in the population. Again, in an ideal world, the human replacement level fertility rate would be exactly 2. This would mean that each couple would produce 2 offspring that would replace them in the population. If this occurred, then the human population would stay at a stable rate. Of course, the world is not ideal, and not all offspring that are born will survive to reproductive age and replace their parents. The replacement level fertility rate is greatly impacted by the infant mortality rate. As we now know, the infant mortality rate is much higher in developing countries. As a result of this, the replacement level fertility rate is also higher in developing countries than in developed countries. On average, the replacement level fertility rate is around 2.1 in developed countries. This value includes 2 children to replace the 2 parents and an additional 0.1 for the risk of a child dying before reaching reproductive age. For developing countries, this number is slightly higher, at around 2.6, with an additional 0.6 due to the higher risk of infant mortality. Although the most commonly discussed characteristics of a population have to do with births and deaths, there is another important characteristic that combines these statistics. This characteristic is the population's age structure, which is the distribution of the population based on age categories. The age structure of a population is often displayed using age-sex pyramids, which graphically represent how the population is distributed by both age and sex. The pyramid is comprised of many horizontal bars, representing the size of the population at each age category, with young categories at the bottom of the pyramid and old at the top. Due to the variation in infant mortality and fertility rates between developed and developing countries, the age structure is always quite different. In developed countries, the population is distributed relatively evenly over all age categories. This results in a median age in the late 30s and an age-sex pyramid with very straight sides due to the evenly sized horizontal bars. Due to high fertility rates and low survivorship, developing countries often have a skewed age structure, with a higher percentage of their overall population being in the lower age categories. This results in a median age in the late teens and an age-sex pyramid with very sloped sides due to larger bars at the bottom of the pyramid. This type of age structure has a large proportion of the population being at reproductive age and leads to an increase in overall birth rates. Now, let's review some major population characteristics that differ between highly developed countries and developing countries. To start, a highly developed country is a general category for countries that are highly industrialized and have high per capita income levels. And a developing country is a general category for countries that have limited industrialization and have low per capita income levels. Although economy is one major difference between these types of countries, they also have varying population characteristics in terms of infant mortality rate, total fertility rate, replacement level fertility, and age structure. Infant mortality rate is the percentage of infants that die before the age of 1 year. This unfortunate statistic is on average 18 times higher in developing countries than the rate in developed countries. There are two population characteristics that relate to births and fertility. The first is total fertility rate, which is the average number of offspring born to a woman in a population during her reproductive window. The second is replacement level fertility, which is the fertility rate that will result in the replacement of the parents in the population. Both of these statistics are higher in developing countries in comparison to developed countries. In terms of total fertility, the rate in developing countries is between 3 and 7 children per woman, and only between 1 and 3 children per woman in developed countries. In terms of replacement level fertility, the rate is around 2.1 in developed countries and slightly higher at 2.6 for developing countries. The last population characteristic is the population's age structure, which is the distribution of the population based on age categories. The age structure in developed countries is evenly distributed, while the age structure of developing countries is skewed towards younger age categories due to high fertility rates and low survivorship. These characteristics are a general overview of differences between developing and developed countries. Populations are very complex, and each country has unique components of their own population. Think back on the last trip you took to a big city. How would you describe the city in terms of the size of the human population? Many of us would describe a big city as crowded, with a very densely packed population. Cities were not always so crowded. It wasn't until around 300 years ago that the population size began to rise due to urbanization, which is the shift from rural to urban living and the increased concentration of the human population in densely populated cities. In fact, in the mid-1800s, only around 2% of the entire human population lived in cities. By the 1950s, the percentage of the human population living in urban areas was up to around 29%, and by 2009, that number had reached 50%. This number is expected to increase rapidly, and by 2050, it is predicted that over 70% of the human population will live in urban areas. Although we often think of a city as a busy and productive place, many problems have arisen in cities due to the rapid population growth rates. One major problem is the lack of adequate housing. As more people move to cities, the amount of housing available decreases. The increased demand for housing can often lead to inflated real estate costs. As a result, many people end up living in cheaper neighborhoods and rundown areas or becoming homeless. In many cities, the lack of adequate housing has led to the creation of slums and shantytowns. The term slums is often used to describe areas with multifamily tenements that are inadequate in size and function. Shantytowns are illegal settlements in cities that are created when people move onto unoccupied land and build their own houses or shacks. The most extreme result of the lack of adequate housing is people becoming homeless. In 2011, it was estimated that nearly 100 million people worldwide were homeless. In addition to a lack of adequate housing, insufficient sewage systems are also another major problem faced by growing cities. Many cities built their sewage systems to handle a certain population size, and as the population increases, the systems are overloaded and cannot properly function. For example, the city of Cairo, Egypt, built its sewage system over 50 years ago to handle waste from around 2 million people. In 2011, the population of Cairo was over 10 million people, and the system had been overwhelmed. The major problem associated with insufficient sewage systems is that it often leads to water pollution. When water sources are polluted with human waste, it can lead to outbreaks of diseases such as dysentery, typhoid, and cholera. It can also cause economic problems for people because if the water is contaminated, people may be forced to purchase bottled water. Another major problem occurring in growing cities is the increased abundance of cars. When you visit any city, you see many cars lining the streets. As more people move to cities, they bring more cars with them. One problem with the increased abundance of cars is that it increases traffic congestion. The city of Bangkok, Thailand, has extreme traffic congestion, and it is estimated that each year the average resident spends the equivalent of 44 days sitting in traffic. Not only does the person have to waste time in traffic, they also use up around 20% of their fuel while sitting. This burning of fuel leads to increased air pollution and can cause respiratory diseases. Now that we know some problems associated with the rapid growth of the population in cities, what do you think are some ways to handle these issues? One way that these issues are being addressed is through compact development, which is a development method that focuses on building in a more compact way that promotes a more livable urban community. Although we often think of compact as crowded, and maybe in a negative way, this development method implements the positives of things being closer together. Compact development focuses on using pre-existing structures and preserving open space. By renovating pre-existing structures, housing can become more affordable. Compact development also incorporates more public transportation options, which can limit the reliance on cars and decrease air pollution. Another benefit of compact development that make the city more livable is the fact that more communities are walkable. This is good for the health of the residents and the environment. This can also create a stronger sense of community because people are able to have easier access to the local resources around them. Now, let's review population growth in urban areas, problems that can arise, and possible solutions. The high population growth rate in cities is attributed to urbanization, which is the shift from rural to urban living and the increased concentration of the human population in densely populated cities. The first major problem with the growth of cities is the lack of adequate housing. This can lead to the establishment of slums, which are areas with multifamily tenements that are inadequate in size and function, and shanty towns, which are illegal settlements in cities that are created when people move onto unoccupied land and build their own houses or shacks. Lack of adequate housing has also contributed to the high rates of homelessness, with 100 million people homeless in 2011. The second major problem is the insufficient sewage systems, which can lead to water pollution and diseases. The final major problem is the increased abundance of cars, which can lead to traffic congestion, wasted fuel, and increased air pollution. One potential solution to the problems associated with city growth is compact development, which is a development method that focuses on building in a more compact way that promotes a more livable urban community. Compact development will help make cities more livable by reducing housing costs, increasing public transportation, and making cities more walkable. People are always going to want to live in cities, and development and planning needs to be done in a way that helps preserve cities, the health of the residents, and the environment in general. How many people do you think will be on Earth in 50 years? It is hard to predict the answer to this question because the human population has been growing at such a rapid pace over recent years. In the 1960s, the population was 3 billion people, and after around 50 years, in 2011, the population had exploded to over 7 billion people. Based on this trend, the human population might double again in the next 50 years. As the human population continues to increase, there is a great deal of concern about whether or not the Earth can sustain the large and increasing population. One of the major concerns related to population growth is overpopulation, which is when the number of individuals of a species exceeds a certain threshold. In most cases, the threshold that is exceeded is the carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. When the human population is below the carrying capacity, there are more than enough resources available for all individuals to survive without depleting the availability of the resources. As the population approaches the carrying capacity, resources become more limited because more people are relying on the same amount of resources. If the human population was to exceed their carrying capacity, the rate of resource depletion would increase rapidly. This would lead to an inability to provide basic resources such as shelter, food, and medical care, which could lead to increased competition for resources and increased mortality. Although overpopulation is a major concern, there is another problem associated with population growth that puts humans in danger. The second major concern related to population growth is overconsumption, which is when resources are used in excess and at a rate that is higher than the production rate. We live in a world of material objects, and our culture has been referred to as a throwaway society, meaning that we are accustomed to utilizing products that are short-lived or disposable. This is especially true in wealthy countries where individuals consume the most natural resources. The average American citizen uses over 10 times more resources than the average citizen of Zimbabwe or Zambia. When discussing consumption of natural resources, the term ecological footprint is often used. An ecological footprint is an estimate of the amount of land that is needed to supply a person with the resources they need to survive. The resources included in the ecological footprint include all materials and services that a person needs, such as housing, food, energy, and land to dispose of waste. Although the Earth might be able to support 7 billion people now, that number can be greatly influenced by how we use resources and individuals' ecological footprints. If we continue to use large quantities of resources and our ecological footprints continue to grow, we will use up our resources quickly. If humans continue the overconsumption of resources, our population will be limited by the amount of resources we have left. Now, let's review population growth and some concerns associated with it. The human population has been steadily increasing and reached over 7 billion people in 2011. As a result of this rapid increase, several concerns have been raised about the future of the human population. The first concern is overpopulation, which is when the number of individuals of a species exceeds a certain threshold. The threshold that is exceeded is the carrying capacity, which is the maximum population size of a species that an ecosystem can support indefinitely. If the human population grows too large and results in overpopulation and the exceeding of the carrying capacity, resources will become limited. This could lead to basic needs not being met and increased competition and mortality. The second concern is overconsumption, which is when resources are used in excess and at a rate that is higher than the production rate. Many individuals and societies consume large amounts of natural resources and have large ecological footprints, which is an estimate of the amount of land that is needed to supply a person with the resources they need to survive. If humans continue to consume resources at such rapid rates and do not reduce their ecological footprint, then resources will deplete quickly and the Earth will not be able to sustain the growing population. Although overpopulation and overconsumption sound like bleak outcomes for our species, they are an important lesson. They demonstrate the value of conserving resources and living in a sustainable manner to help ensure the survival of ourselves and future generations.
A group of individuals of the same species living in the same area is called a population. The measurement of how the size of a population changes over time is called the population growth rate, and it depends upon the population size, birth rate, and death rate. As long as there are enough resources available, there will be an increase in the number of individuals in a population over time, or a positive growth rate. However, most populations cannot continue to grow forever because they will eventually run out of water, food, sunlight, space, or other resources. As these resources begin to run out, population growth will start to slow down. When the growth rate of a population decreases as the number of individuals increases, this is called logistic population growth. If we look at a graph of a population undergoing logistic population growth, it will have a characteristic S-shaped curve. The population grows in a size slowly when there are only a few individuals. Then the population grows faster when there are more individuals. Finally, having lots of individuals in the population causes growth to slow because resources are limited. In logistic growth, a population will continue to grow until it reaches carrying capacity, which is the maximum number of individuals the environment can support. We can also look at logistic growth as a mathematical equation. Population growth rate is measured in number of individuals in a population, N, over time, T. The term for population growth rate is written as dN over dt. The D just means change. K represents the carrying capacity, and R is the maximum per capita growth rate for a population. Per capita means per individual, and the per capita growth rate involves the number of births and deaths in a population. The logistic growth equation assumes that K and R do not change over time in the population. Let's see what happens to the population growth rate as N changes from being smaller than K, close or equal to K, and larger than K. We will use a simple example where R equals 0.5 and K equals 100. If N is very small compared to K, then the population growth rate will be a small positive number. This means the population is slowly getting larger because there are a few more births than deaths. For example, if N equals 2, the population growth rate is 0.98. Remember, the units are individuals per time. We didn't specify time in this example because it depends upon the species, but it is often measured in years or generation times. For a while, as N increases, so does the growth rate of the population. If N equals 50, then the growth rate has increased to 12.5. This means the population is rapidly getting larger. However, remember in logistic growth, the population does not continue to grow forever. As N gets closer to K, the population growth rate decreases and approaches 0. In our example, if N equals 98, then the growth rate has decreased to 0.98 again, which means the population is still getting larger, but not as quickly. A growth rate of 0 means that the population is not growing, which is what happens at carrying capacity because the birth rate usually equals the death rate. When N is equal to K, a population has reached carrying capacity. If N happens to be higher than K, then the population will lose individuals until N is equal to K. Population growth will be negative during this time because there will be more deaths than births. If N equals 105, the carrying capacity is 100. Then the growth rate will be negative 2.6. The growth rate will continue to be negative until the population has decreased in size to carrying capacity. Then remember, at carrying capacity, the population growth rate will be 0. Let's review. Logistic population growth occurs when the growth rate decreases as the population reaches carrying capacity. Carrying capacity is the maximum number of individuals in a population that the environment can support. A graph of logistic growth is shaped like an S. Early in time, if the population is small, then the growth rate will increase. When the population approaches carrying capacity, its growth rate will start to slow. Finally, at carrying capacity, the population will no longer increase in size over time.
Like frosting on a cake or crumb coating on a pie, soil is the top layer of the Earth's surface. However, rather than being made of yummy sugars, soil is comprised of broken down rock mixed with organic material, water, and air. Although rather unappealing to me, it's as good as chocolate icing to plants. To learn more about soil, let's take a look at its development. There are 5 main factors that affect soil development. They are parent material, living organisms, climate, topography, and time. Keeping things simple, parent material is the rock material from which soil formation begins. The rock material can be as varied as volcanic ash to sand to limestone. Usually the parent material has been moved around by wind, water, and erosion. Interestingly, as this rock material breaks down into soil, it becomes harder and harder to tell what the original parent material was. Of course, just like a cake needs more than one ingredient, soil needs more than parent material. This leads us nicely to our next factor in soil development, organic material, or things that are alive, were once alive, or are byproducts of life. Things like microorganisms, decomposing plants, animals, and animal waste are organic material, which serve to create nutrient-rich soil. However, living things also help soil to develop. For instance, earthworms, snakes, and rodents create tunnels that carry water and air deeper into the soil. Mix this with some rotting plants and some animal carcasses, and you have a recipe for nutrient-rich soil. Throw in some microorganisms, and you have vegetation heaven. Of course, just like the heat of an oven affects baking, climate or weather conditions affect soil development. For instance, if an area is very windy, its soil will be dry. Temperature has a huge impact on soil development and characteristics. In warm climates, dead vegetation and animals decompose quickly, causing richer and deeper soil. Just like roadkill on a summer day starts to smell gross pretty quickly, but in the winter it can stick around for days without being stinky, warm climates help create rich, deep soil, while colder climates tend to create more shallow soil. Topography, or the physical features of an area, also plays a part in soil development and characteristics. It's rather easy to understand why. If an area is flat, it's easier for soil to be deep. Rain may come and wind may blow, but the soil tends to stick around. However, if an area is steep, it's sort of like dumping a bucket of soil down a slide and hoping it will stick. You might get some to stay, but you're stuck with a rather thin layer. Dump water down the slide and your thin layer is in some real danger. It's just a matter of time before it erodes away. Speaking of time, it's our last factor in soil development. No matter the climate, no matter its parent material, no matter the topography, no matter the organic material, soil needs time to develop. Just like a cake needs time to bake, soil needs time for water and air to break it down. It needs time for dead critters to decompose, and it needs time for rock to break down. Soil consists of broken down rock mixed with organic material, water, and air. There are 5 main factors in soil development: parent material, living organisms, climate, topography, and time. Parent material is the rock material in which soil formation begins. This material has usually been moved from place to place by wind, water, and erosion. Organic material is composed of things that are alive, were once alive, or are byproducts of life. It includes things like microorganisms, decomposing plants, animals, and animal waste, which serve to create nutrient-rich soil. Climate or weather conditions affect soil development. In warm climates, dead vegetation and animals decompose quickly, usually causing richer and deeper soil. Topography, or the physical features of an area, also affects soil development. If an area is flat, it's easier for soil to be deep. Time is our last factor in soil development. Like a cake needs time to bake, soil needs time to develop. If I'm hungry, I can just pop into my car and go to my favorite fast food joint. But when a plant's hungry, it's stuck where it's planted. For this reason, the soil it's rooted in better have the right chemistry and fertility to take care of its needs. Known as its overall pH level, it's the topic of today's lesson. For starters, soil is like a grocery store to plants. Comprised of broken down rock mixed with organic material, water, and air, it's where plants get their nutrients. One of the main factors in determining soil fertility is the amount of organic material it contains. Organic material is anything that is or was alive or is a byproduct of life. It's things like decomposing plants, animals, and animal waste. Yes, the stuff your dog drops in your yard that your mom forces you to pick up is organic material. Organic material creates fertile soil. That's why farmers sometimes spread manure on their fields. Mix it with some rotting plants, some earthworms, and a few dead rodents, and you have the recipe for fertile soil. It's like a buffet for plants. When discussing soil chemistry and fertility, pH is used. pH is the measurement used to determine the acidity or alkalinity of soil. Speaking rather academically, it determines the solubility of nutrients in soil. Speaking simply, solubility is how easily something dissolves. pH is measured on a scale from 1 to 14. A 7 on the scale denotes that soil is neutral. Most plants prefer neutral soil. As Goldilocks would say, it's just right. If a soil's pH is greater than 7, it's considered alkaline. Since the higher the number, the higher the alkalinity, I like to remember it by thinking that alkaline means above the line. Alkaline soil tends to be low in minerals like iron and zinc, but high in salts. Since salt acts as a preservative, this makes it hard for things like dead plants and animals to decompose and dissolve. This leaves the soil nutrient deprived. Of course, some plants dig this. For instance, cauliflower and cabbage thrive in more alkaline soil. A pH level below 7 indicates that soil is acidic. If plants had to choose between alkaline and acidic soil, most would choose acidic. Acidic soil usually contains more nutrients. It also has high levels of carbon dioxide from decomposing plants. To use one of our terms, acidic soil tends to make things more soluble. However, if soil is too acidic, nutrients will dissolve too quickly. Just like my son scarfs down anything left in the fridge, nutrients like calcium, potassium, and magnesium can disappear before plants have a chance to enjoy them. Keeping this in mind, most gardeners think a soil pH of between 6 and 7 is the sweet spot. Although plants like carrots and potatoes enjoy more acidic soil, most would prefer to rest in the range of 6 to 7. Soil is comprised of broken down rock mixed with organic material, water, and air. It's where plants get their nutrients. Fertile soil contains organic material. Organic material is anything that is or was alive or is a byproduct of life. pH is the measurement used to determine the acidity or alkalinity of soil. It determines the solubility of nutrients in soil. Solubility means how easily something dissolves. pH is measured on a scale from 1 to 14. A soil pH of 7 is neutral. If pH is greater than 7, it's considered alkaline. Alkaline soil is usually low in minerals like iron and zinc, but high in salts. Salt makes it difficult for nutrients to dissolve. A pH level below 7 indicates that soil is acidic. Acidic soil usually contains more nutrients. It also has high levels of carbon dioxide from decomposing plants. If soil is too acidic, nutrients may dissolve before plants have a chance to use them. Most plants and vegetation prefer soil that is neutral to slightly acidic.
Remember playing in the dirt as a kid? You probably didn't put too much thought into how that dirt was formed or even what it was made of. Dirt is dirt, right? Well, actually, that dirt is called soil, and soil is a mixture of mineral and organic material that sits just below Earth's surface. Soil is far from the simple dirt you may be picturing. There are over 20,000 different kinds of soil just in the United States. How do scientists tell the difference between them? They can look at the soil's physical characteristics such as pH, color, particle size, permeability, and water holding capacity. Soil is very important because it provides a place for plants to grow and contains a lot of living and non-living material like rocks, minerals, bacteria, animals, and nutrients. It takes a very long time to make soil, sometimes 1,000 years or more. Basically, when surface rocks break down, they mix with decaying organic material like plants and animals. As this organic material breaks down, it returns nutrients back to the ground, which provides food for plants. Specifically, there are 5 main factors that create soil: parent material, climate, biology, topography, and time. Let's start with parent material. This is the material that new soil forms from. Parent material includes both mineral and organic material. The organic material is usually very dark and spongy and is also known as humus. The mineral material comes from sediments and weathered rocks, and the type of mineral material present helps determine which type of soil will form and how long it will take to form. Climate affects soil formation because temperature, moisture, rainfall, and wind influence mineral material weathering and the production of organic matter. In climates that are warm and moist like rainforests, plants grow much faster and more consistently throughout the year. This creates a soil with more organic matter than a climate that is dry and cool, but this organic matter also gets broken down faster, so there is less accumulation in the soil. Soil formation is also impacted by biological influences such as plants, animals, bacteria, and fungi. As we saw before, plants help recycle nutrients by decaying as well as by taking up nutrients. Plants also put down roots into the soil, which helps anchor the soil in place and prevent erosion. There are millions of tiny organisms in the soil that you can't even see, and they help mix the soil and recycle nutrients. Topography is the shape of the land, including the steepness and features like mountains, depressions, and floodplains. Remember that soil is affected by water and the sediments and rocks that are present? Well, if the land is very steep, there will be more runoff from rainfall, which will transport more rocks and minerals. This increased level of erosion also means that there will likely be less organic material, and as we know, this also influences the soil. Finally, time plays a critical role in soil formation because the interaction of all the previous factors is a slow and continuous process. It takes a long time for sediments to be transported and weathered, and organic material needs time to decay. As soil forms, it becomes sorted. Horizons develop, which are the layers of soil with distinct characteristics that are parallel to the surface of the ground. To determine the types of soil present, scientists will use a soil profile, which is a vertical section of soil from the surface. There is no limit to the number of horizons a soil profile can have, but there are 6 major horizons that are typically used to describe the soils in a profile. The thin uppermost layer of soil above ground is called the O horizon because it contains organic material like branches, leaves, and animal waste. The A horizon is the top level of soil underground, so it's also known as topsoil. It contains inorganic mineral components mixed with organic matter from the ground above. Topsoil contains a lot of nutrition for plants and is important for ecosystems. The horizon below A is the E horizon, so named because this is the alluviation horizon, where minerals and organic matter are leached out and carried down into other horizons below. This leaching occurs when rainfall carries the components away, much like water carries away components from coffee in a filter to your cup below. The B horizon is next, and you can remember its place because it is below the E horizon. This is where all of those leached components from the E horizon end up. What comes after B? The C horizon, of course. The C horizon contains parent material that soils form from. Directly below the C horizon is the R horizon, which is named for the bedrock it contains. Soil is an important component of our Earth because it is where decaying matter gets recycled into usable nutrients. This supports both plant and animal life as well as provides a medium for material to get broken down. Soil is a mixture of mineral and organic material that sits just below Earth's surface. Over a long period of time, soil forms from parent material through the effects of climate, biological influences, and topography. The physical characteristics of soil, things like pH, color, texture, and permeability, help us identify which type of soil is present. Once formed, it can be divided into horizons or layers of soil with distinct characteristics that are parallel to the surface of the ground. Horizons can be identified through soil profiles and are usually classified as one of the 6 major horizons: O, A, E, B, C, or R?
I have dear friends who love to garden. Planting tulips and lilies has always been one of their favorite hobbies. Unfortunately, these dear friends recently moved to the Southwest, where things like pretty tulips and tall eastern lilies have no chance at growing. To see why, let's take a look at some of the infertile soil orders of the United States. For starters, when we say soil orders, we simply mean different types of soils. Keeping this in mind, let's get to some of our infertile soils. As we do this, keep in mind that we're using the term infertile rather loosely. Some types of vegetation do grow in these orders. We'll kick things off with soils classified as aridosols. Aridosols are soils that are too dry for most plants and vegetation. We can remember this one by linking it to its root word, arid. Arid simply means too dry to support vegetation. Not too surprising, aridosols are found in the deserts of the Southwest, places like Arizona and New Mexico. These are the soils my garden-loving friends now have to contend with. Endosols are soils that are shallow due to erosion. Keeping things simple, erosion is the wearing away of soil by nature. Erosion tends to be rapid in places that have steep slopes. Linking the E in erosion to the E in endosols, these soils are found along the Rocky Mountains. To keep this one simple, think about dumping buckets of garden soil down a slide. No matter how rich the soil, the steep slope of the slide is going to make it pretty hard to get the soil deep enough for planting. Now, just imagine adding mountain range. You'd never get any soil to stick. Gelisols are soils that exist in very cold climates. Found in places like Alaska, soils that are gelisols are frozen through much of the year. They are often found in areas that are called tundras. Tundras are areas where the subsoil is permanently frozen. As you can imagine, getting vegetation to grow here is about as easy as getting plants to grow in your freezer. Using some alliteration and some slight mispronunciation of the letter G, wear winter gloves if you're digging in gelisols, really pronounced gelisols. Soils that fall in the spotosols category have been stripped of organic material. Organic material is simply anything that is alive, was once alive, or is a byproduct of life. Things like dead rodents, roots, and animal waste are all organic material that can make for great plant food. Since the spotosol order has been stripped of these things, this type of soil tends to be very acidic and not great for growing. The forest floors of New England contain this order of soil. Using some more alliteration, we can remember that spotosols have been stripped. Our last soils for today are altisols. Altisols are found in very humid areas. The humidity of their environments causes these soils to be very weathered. Weathered simply means broken down by wind, water, and air. Altisols have been so pummeled by their environments that most of their minerals have been leached away. Found in the southeastern U.S., altisols are the ultimate weathered soils. In order to get these soils to support crops, they need lots and lots of fertilizers. For this reason, we've kept them with our infertile soils. The term soil orders means different types of soils. There are several infertile soil orders in the U.S. Aridosols are soils that are too dry for most plants and vegetation. They are found in arid places that are too dry to support vegetation. Endosols are soils that are shallow due to erosion. Erosion is the wearing away of soil by nature. Gelisols are soils that exist in very cold climates, or tundras. Tundras are areas where the subsoil is permanently frozen. Spotosols are soils that have been stripped of organic material. Organic material is anything that is alive, was once alive, or is a byproduct of life. Altisols are found in ultra-humid areas. These soils have been very weathered. This means broken down by wind, water, and air. If you traveled from Alaska to Florida, you'd see some serious differences in vegetation. Interestingly, if you traveled underground, you'd also see some extreme differences in the soils that make vegetation possible. To explain what I mean, Today's lesson is going to discuss the different fertile soils of the United States. Before we get into the names of the soils, we need to nail down some terms often used when discussing soils. First, we have organic material. Organic material is anything that is alive, was once alive, or is a byproduct of life. Things like bugs, decomposing roots, and animal waste are all organic materials. Our next term is weathering. For our purposes, weathering is when the air and weather break down rocks, minerals, and organic materials in the soil. Leaching is our last term. This term occurs when minerals dissolve from or through the soil. Things like moisture and precipitation cause leaching. Now that our terms are out of the way, let's turn to our different types of soil, which are referred to as soil orders. There's a bunch of them, so we'll keep our explanations brief. Alpha soils are our first soils. Soils that are alpha soils are found in places that are semi-arid to moist. Since they're semi-arid, which means semi-dry, to moist, they provide enough moisture to grow crops and forests. Trying to remember this one, we can say that plants think alpha soils are all right. As for the U.S., alpha soils are found in states like Ohio, Indiana, Michigan, and Wisconsin. Andisols are found in areas with lots of precipitation. They're also found in areas with volcanoes. The ash from the volcanoes mixed with precipitation makes for very fertile soil. Found in places like Hawaii, we can remember that andisols get an A+ for growing. Soils that are histosols are rich in organic material and full of water. Found in the bogs and swamps of places like Florida and Louisiana, I tried to remember that histosols are heavy with water and organic material. Inceptisols are soils that have moderate soil development and soil weathering. They are found in a wide variety of climates. In a Goldilocks sort of way, these soils are not too moist and not too dry. I like to say that inceptisols are intermediate soils. In the U.S., they're found in places like Pennsylvania, New York, Northern California, and the Oregon coast. Mollisols are very high in organic material. Mollisols tend to be very dark soils found in grasslands. Making them stand out even more, they're found in areas that undergo seasonal droughts. Located in the Midwestern plains, we can say that soils classified as mollisols are dark as midnight. Soils that are classified as oxasols have low fertility and are usually found in subtropical areas. These soils are highly weathered and tend to have low natural fertility due to leaching. The soils of Puerto Rico are oxasols. Knowing that oranges grow in the tropics, let's use the O in oxasols and oranges to remember that oxasols are often found in tropical zones where oranges grow. Our last soil order is vertisols. Soils that are classified as vertisols swell when met with water. This causes the leaching process to be very slow. In other words, water moves very slowly through vertisols, and this causes them to be very fertile. When studying soils, the terms organic material, weathering, and leaching are very important. Organic material is anything that is alive, was once alive, or is a byproduct of life. Weathering is when the air and weather break down rocks, minerals, and organic materials in the soil. Leaching occurs when minerals dissolve from or through the soil. Things like moisture and precipitation cause leaching. There are many different types of soil or fertile soil orders in the U.S. Alpha soils are found in places that are semi-arid to moist. They are semi-dry but provide enough moisture for vegetation to grow. Plants think alpha soils are all right. Andisols are found in areas with lots of precipitation and in areas with volcanoes. They are very fertile soils. Andisols get an A+ for growing. Soils that are classified as histosols are rich in organic material and full of water. Histosols are heavy with water and organic material. Inceptisols are soils that have moderate soil development and soil weathering. Inceptisols are intermediate soils. Mollisols are very high in organic material. They are usually dark soils found in grasslands. We can say mollisols are dark as midnight. Oxasols have low fertility and are usually found in subtropical areas. Oxasols are often found in tropical zones where oranges grow. Vertisols swell when met with water, causing leaching to be very slow. Water moves very slowly through vertisols. This causes them to be very fertile.
Phil and Angie took a trip around the world together. They're so excited about all the cool things that they saw, they'd like to share some of their experiences with you. The first stop on their trip was the temperate deciduous forests of the eastern United States. Temperate deciduous forests are forests in temperate climates that are characterized by broad-leaved deciduous trees. These forests are found at mid-latitudes in areas that get significant rainfall in the warm summer months, which can support fast-growing species like birch, hickory, maple, and sycamore trees. However, at mid-latitudes, the winters are often too cold for the leaves of these trees to survive. So when the temperatures start to drop, the leaves of these trees die and fall off. The trees themselves then go into a dormant phase to survive the winter, and the lack of leaves helps to prevent the buildup of snow on the branches that could weigh them down to the point of breaking. Trees that lose their leaves all at once in a seasonal cycle are called deciduous trees. Phil and Angie decided to start their trip in the autumn because the deciduous forests of the United States are famous for the spectacular display of color in the fall. As the leaves begin to die, the chlorophyll, which gives most leaves their green color, is broken down and disappears. This absence of chlorophyll allows us to see other pigments in the leaves, which can make the leaves appear red, yellow, orange, or brown. The next stop on the trip was the tropical rainforest in South America. Tropical rainforests are forests in the tropics that receive over 100 inches of rainfall per year. Most types of forests can support large populations of plants and animals. However, tropical rainforests support the greatest number of species of any other type of biome on the planet. This incredible species richness is due largely to the combination of a tropical climate and high year-round rainfall, which provide optimal growing conditions for the largest number of plant species. In turn, the high number of plant species can support a high number of animal species. With such high productivity in the tropical rainforest, you might expect the soil to be rich with nutrients. However, it's just the opposite. The warm, wet conditions in the tropical rainforest causes rapid decomposition of any detritus, and because sunlight and water are plentiful, any nutrients released into the soil are rapidly used by the fast-growing vegetation, leaving the soil amazingly poor considering the high productivity of the biome. However, as long as the forest remains intact, nutrients will quickly cycle through the ecosystem. This rapid cycling produces a steady input of nutrients into the soil that plants can use, and that is how the poor soil can support such a massive amount of biomass. After the tropical rainforests of South America, Phil and Angie hopped on a plane to Tanzania to visit the Serengeti National Park. Angie really likes giraffes, and although she has seen giraffes in zoos, she thought it would be really cool to see them in their natural habitat, the African savanna. Savanna is essentially grassland interspersed with trees. It is sometimes found in temperate climates, usually in areas that are transitional zones between grassland and forests. However, savanna is mostly found in tropical regions of the world, where the climate changes in a seasonal pattern from cool and dry to hot and dry, and then warm and wet, before starting the cycle again the following year. This is the type of savanna found in the Serengeti National Park, which is famous around the world for supporting so many large animals such as giraffes, elephants, rhinos, zebras, wildebeest, cheetahs, leopards, and lions. While Phil and Angie were in Africa, they decided to take a few days to visit Lake Malawi, which is a very large lake located just south of Tanzania. Phil in particular wanted to visit this lake because he had an aquarium at home, and some of his favorite aquarium fish are found only in Lake Malawi. Lakes, ponds, streams, and rivers are all examples of freshwater aquatic biomes. Since lakes, ponds, streams, and rivers are often naturally isolated from each other in many ways, species of freshwater fish are often found only in one particular lake or river system or even a single stream. These species are said to be endemic, or only found in one particular area. Lake Malawi is a good example. It's the 8th largest lake in the world and is home to an estimated 1,000 different species of fish. There are so many different species in the lake that most of them haven't been fully described and identified. However, of the approximately 350 described species of rockfish, or Mbuna, in the lake, only 5 of them are found in other bodies of water. Overall, it's thought that over 90% of the fish species in Lake Malawi are endemic and found nowhere else in the world. The next leg of Phil and Angie's trip took them to Australia. One of Angie's life goals was to go on a walkabout in the Australian outback, most of which is considered to be desert. Desert biomes are characterized by very little rainfall, so any landscape that gets less than 12 inches of rain per year can be considered desert. They occur at all latitudes, and although the popular depiction of deserts is a vast expanse of nothing but sand for miles, deserts can have a variety of soils, plant life, and animal life. In the Australian outback, drought-resistant plants with small leathery leaves are common, and some plants, like the desert bloodwood tree, store large quantities of water in their roots to survive prolonged periods of drought. Animal density is not very high in deserts, but even so, insects, arachnids, lizards, snakes, mammals, birds, and even some amphibians can all be found in the Australian desert. Each of these animals has its own methods for conserving water and making use of specific food sources in what might seem like uninhabitable conditions. And finally, what trip to Australia would be complete without visiting the Great Barrier Reef? Coral reefs occur in tropical marine environments where sunlight can reach the ocean floor or any other solid structure that corals can attach to. Coral reefs are pretty much the complete opposite of deserts. First off, coral reefs are the most productive biomes on Earth on a per-acre basis, compared to deserts, which aren't quite the least productive, but pretty close to the bottom. There's also the obvious main difference that deserts contain very little water, and coral reefs are submerged in water. And then there's the striking difference in the amount of visible animal life. Desert animals often remain hidden in burrows during the day, and many also use camouflage. In contrast, the fish, corals, and other animals of the coral reefs are abundant and include many of the most brightly colored species in the world. However, while the animal life is prominent, plant life is strikingly absent. Sure, some corals look like plants, but they're actually animals. So where do all these animals get their energy from? Where are all the producers? It turns out that most of the producers in coral reefs are symbiotic dinoflagellates that live within the corals themselves. Dinoflagellates are single-celled organisms that are capable of photosynthesis. Dinoflagellates are fairly unique among organisms because they can thrive either as free-swimming ocean dwellers or as intracellular symbionts, while most other species have only one type of life cycle. In summary, there are many types of ecosystems around the world that can be categorized into different biomes. Several factors determine what type of biome is present in a given area, but two of the most important factors are water abundance and latitude, which is basically how far a place is from the equator. Temperate deciduous forests are forests in temperate climates that are characterized by broad-leaved deciduous trees. These forests are found at mid-latitudes in areas that get significant rainfall in the warm summer months. Tropical rainforests are forests in the tropics that receive over 100 inches of rainfall per year. Tropical rainforests support the greatest number of species of any other type of biome on the planet. Savanna is grassland interspersed with trees. It is sometimes found in temperate climates, usually in areas that are transitional zones between grasslands and forests. However, savanna is mostly found in tropical regions of the world where the climate changes in a seasonal pattern from cool and dry to hot and dry and then warm and wet, before starting the cycle again the following year. Lakes, ponds, streams, and rivers are all types of freshwater aquatic biomes. Since lakes, ponds, streams, and rivers are often naturally isolated from each other in many ways, species of freshwater fish are often endemic to a particular lake, river system, or even a single stream. Desert is any landscape that gets less than 12 inches of rain per year. Deserts occur at all latitudes and can have a variety of soils, plant life, and animal life. And finally, coral reefs occur in tropical marine environments where sunlight can reach the ocean floor or any other solid structure that corals can attach to. On a per-acre basis, coral reefs are the most productive biomes on Earth.
Jenna is in a museum dedicated to the study of the Earth. In the museum, there is a series of rooms that lead into one another. As she wanders through, Jenna notices some distinct differences. In some rooms, there are lots of trees and other types of plants. In other rooms, there's nothing but ice. Jenna is looking at different vegetation regions, or areas with distinct types of plants, soil, and weather patterns. The word vegetation just means plants, so a vegetation region is an area with a specific type or types of plants. A vegetation region is determined by a number of factors, including climate, soil, and the slope or angle of the land. There are 5 vegetation regions in the world: forest, grassland, tundra, desert, and ice sheet. Let's take a walk with Jenna through 5 rooms representing each of the 5 vegetation regions and look at what makes each one unique. The first room that Jenna enters is very familiar to her. There are lots of trees and it is cool and shady. It reminds Jenna of where she grew up, in the Northeast. An area with trees grouped so that their leaves shade the ground is called a forest. Forests can have many different climates, from very warm to very cool. Where Jenna grew up, the seasons changed throughout the year, so that sometimes it was warm and sometimes it was cool. There are 2 types of forests, deciduous and evergreen. Deciduous forests are made of trees whose leaves change with the seasons. In the northeastern United States, where Jenna is from, deciduous forests are common. Tourists flock to that area every fall to watch the leaves change colors. They couldn't watch the leaves change color on the other type of forest, evergreen forests, which are made of trees whose leaves don't change color and are green year-round. Evergreen forests can sometimes resemble a Christmas tree farm because there are evergreen trees everywhere. Whether at the equator or in the Arctic Circle, whether deciduous or evergreen, a forest always has trees grouped closely together so that the leaves shade the ground. Jenna moves out of the tree room and into a different room. Here she notices that the room looks very open. There is grass and some flowers, but only a couple of trees. A grassland is a flat and open area where grass is the predominant type of vegetation. As its name suggests, grasslands are full of grass. Jenna recognizes the grassland room as being similar to the place where her cousin is from, the plains of North America. Indeed, much of the Great Plains region of the U.S. is grassland. Standing in the plains, you can see for miles and miles because the land is flat and there aren't very many trees to block your view. The plants in the grasslands vary depending on the temperatures in the area where they are located. In cold climate grasslands, like in northern Europe, the land is covered with tough vegetation that thrives all year, like oats and weeds. Warmer climate grasslands, like those in the Great Plains, are covered with seasonal vegetation that changes as the seasons change. Finally, a tropical grassland that has a very hot climate is called a savanna and is common in Africa. The savanna is covered with grasses that can survive very hot temperatures. Jenna moves into the next room and is surprised to see a place with no trees and only a few shrubs. It looks to her like the area near the top of a mountain that she once climbed with her father. A tundra is an area where tree growth is difficult because of cold temperatures. Tundras are covered with mostly shrubs, grasses, and mosses. There are no trees in a tundra, and in general there are fewer types of vegetation than in forests and grasslands. This makes sense. If a tundra is in a very cold area, there are fewer types of plants that can survive the freezing temperatures. There are two types of tundras in the world. An alpine tundra can occur anywhere on Earth at high altitude. When Jenna was climbing the mountain with her dad, she remembers that he said that the tundra was above the tree line. That is, it was above the place where trees could grow. This is an alpine tundra. That is, a tundra created by the conditions at high altitude. The other type of tundra is the Arctic tundra, which occurs at or near the Arctic Circle. As with an alpine tundra, the Arctic tundra is classified by very cold temperatures. But instead of the cold being a result of high altitude, in the Arctic tundra the cold is caused by being near the top of the Earth. Jenna is cold in the tundra room, so she moves into the next room. This one is warmer. In fact, it feels pretty hot. But more than that, it is dry. There are very few plants, and those that are there look pretty odd compared to what she's seen in the forest, grassland, and tundra. Jenna is in a desert, or an area with less than 10 inches of rain per year. Because of the lack of rainfall, the soil in a desert is often sandy or rocky. Both the unique soil and the dryness of the desert lead to plants with long roots, small leaves, and stems that store water. For example, Jenna notices some cactus plants in the desert. These are very common. Jenna is relieved to be out of the cold tundra and in a nice, hot desert. But deserts aren't always hot. In fact, the largest desert in the world is the Antarctic Desert, which takes up the entire continent of Antarctica. There, the land is barren and made up of mostly rock. Jenna makes her way from the desert room into the very last room. Here, the temperature is very cold, and the ground is slippery because it is covered with ice. An area where a glacier covers the land for more than 20,000 miles is called an ice sheet. Because of the cold and ice, there is no vegetation on an ice sheet. Notice that there's more to being an ice sheet than simply having ice or glacier around. There has to be ice covering the ground for a very big area, at least 20,000 miles. Because of that, there are only two ice sheets in the world: in Antarctica, where the ice sheet covers the desert, and Greenland. Anywhere else in the world, there may be glaciers and ice covering the land, but it's not an ice sheet vegetation region. A vegetation region is an area with a distinct type of plants, soil, and weather patterns. There are 5 major vegetation regions in the world. A forest is an area where the trees are grouped so closely that their leaves offer shade. Forests can be deciduous, covered mostly with trees whose leaves change with the seasons, or evergreen, covered mostly with evergreen trees. A grassland is a flat and open area where grass is the predominant plant. A tundra is an area where tree growth is difficult because of the cold weather and can be divided into alpine tundra, which occurs at high altitude, and Arctic tundra, which is in or near the Arctic Circle. A desert gets less than 10 inches of rain every year, so its plants have long roots, small leaves, and stems that can store water. Finally, an ice sheet is an area where a glacier covers the land for more than 20,000 miles, leading to no vegetation. There are only 2 ice sheets in the world, in Antarctica and in Greenland.
So you may remember that latitude and rainfall are 2 major factors that determine the type of biome that is present in a given area. But there are a couple of other very important factors that also help to determine which biome is present in an area, and those are elevation and oceans. So let's take a quick trip from the Pacific Ocean across California and into Nevada to see just how much biomes can change based on these 2 factors. Most of the world is covered by oceans, and 65% of the world is considered to be an open ocean biome, where the water is deep and land is far away. On a per-acre basis, open oceans are one of the least productive biomes because they are nutrient poor. Photosynthetic phytoplankton, which includes cyanobacteria, dinoflagellates, and other similar organisms, do live out here in the open ocean. However, their growth is limited by scarce nutrients. Dead organic matter falls to the seafloor and takes its nutrients with it, leaving the water at the surface nutrient poor. Despite this relatively poor productivity, open oceans cover so much surface area that on a total net basis, they outproduce any other single biome, even tropical rainforests. If we now head towards shore and find a place where a river enters the ocean, we'll find a much smaller, yet very ecologically important biome, an estuary. Estuaries are areas where freshwater streams or rivers merge with the sea. They often take the form of large salt marshes, where the salinity of the water can vary based on the tides and freshwater input rates. Estuaries are enriched with nutrients washed downstream by the rivers, which makes them very productive ecosystems and active breeding grounds for many types of fish, shrimp, and other aquatic animals. Estuaries are also the gateway to freshwater breeding grounds of still other marine animals like salmon. Because of these key roles that estuaries play in the reproductive cycle of many aquatic organisms, their health can have major consequences for lots of marine populations. Unfortunately, estuaries are popular sites for human developments and are also where pollutants dumped upstream end up. As a result, many estuaries have been almost completely destroyed, and many others have been polluted. The consequences of estuary destruction and pollution affect not only the populations of species that use the estuaries, but can also have major effects on predators of these species as well. As we move onto the dry land of California, if we're in the southern part of the state, we're almost certain to encounter hilly terrain. These hills experience moderately cool, wet winters and long, hot, dry summers. The dominant biome here is called chaparral, which you may remember is composed mainly of dense, evergreen, drought-resistant shrubs. A little further inland, the hills give way to a very large inland valley. The sea breezes from the ocean don't reach this valley because they are blocked by the coastal hills, which are sometimes high enough to be considered mountains. As a result, the Central Valley experiences colder winters and hotter summers than the coastal hills, but it collects water from both the coastal ranges and the Sierra Nevada range, or at least it used to a little over 100 years ago. Back then, the Central Valley contained a vast tule marsh, which supported herds of tule elk and antelope, as well as semi-aquatic mammals like beavers, otters, and muskrats, huge flocks of waterfowl, and even fairly large numbers of bears, mountain lions, and coyotes. But in the early 20th century, the vast majority of the marshland was drained and turned into farmland. With the disappearance of the marshes went the tule elk, antelope, beavers, otters, and bears from the Central Valley. Now, most of the valley is farmland, but what isn't farmed is mostly temperate grassland. Fertile soils and frequent winter rains provide enough water and nutrients to support rapid growth of grass species in the winter and spring. In the summer, the soil dries up and the annual but mostly introduced invasive grass species die in the dry, hot summers. While the grasslands of California may not be exactly like those of the central United States, both share the key features of temperate grasslands, which are temperate climate, seasonal drought, occasional fires, and grazing by large herbivores, even if the herbivores are now mostly domesticated cows, sheep, and horses. As we reach the eastern edge of the Central Valley, the elevation rises and the valley gives way to foothills, which are probably best described as temperate savanna, because they're mostly grassland interspersed with trees and some stands of chaparral. As the elevation increases, oak trees that are abundant at lower elevations, where their drought resistance gives them an advantage, begin to give way to conifers. Conifers, like fir and pine trees, grow much faster than oaks, but also require more water and are better equipped to handle colder winter temperatures. These are exactly the reasons why conifers are more abundant at higher elevations, because as elevation increases, the temperatures get colder and the precipitation increases, so at around 3,000 feet in elevation, more or less, the predominant biome becomes taiga, which is more commonly known as coniferous forest, or a forest composed of evergreen conifers. Conifer forests support an extremely large biomass, most of which is in massive trees, but they also support large populations of many species of insects, spiders, birds, reptiles, amphibians, and mammals. In fact, these forests are just about the only places where bears are still abundant in California. For the sake of classifying major world biomes, taiga is considered a single biome, but there is great diversity within conifer forests. Between elevations of about 3,000 to 8,000 feet in the Sierra, the forests include species like ponderosa pine, Douglas fir, and giant sequoias, which are the most massive organisms on Earth and are only found on the western slopes of the Sierra Nevada mountain range. If you look really closely in this picture of a giant sequoia, you might see a light blue speck near its base. That little speck is a person, just to give you some scale. Between about 8,000 to 10,000 feet in elevation, the trees get much smaller and grow into more twisted shapes. These trees are growing at the very limits of altitude that can support tree growth, but they live exceptionally long lives. One species found here, the bristlecone pine, is the longest living species on the planet, living up to 5,000 years. Between 10,000 and 12,000 feet in elevation, the growing season isn't long enough to support the growth of trees. Only very small plants, most of which are perennial herbs, can grow in an environment that is so cold for such long periods. This biome is classified as tundra, or extremely cold environments with very short growing seasons that can barely support small plant growth. While this particular tundra is found in mid-latitudes at very high elevations and is called alpine tundra, most tundra is found in Arctic regions, where the topsoil thaws just long enough for plants to grow. The similarities between Arctic and alpine tundra illustrate an important point. Increased elevation mimics the effects of increased latitude, which means that as we travel higher in elevation, we should see changes in the ecosystem that are similar to the changes a person would expect to see if they were traveling to higher latitudes. Indeed, the biome that is found at latitudes just below the Arctic tundra is in fact taiga, just like the biome found at elevations just below alpine tundra is also taiga. This effect allows for a high stratification of biomes on the slopes of tall mountain ranges. At elevations higher than 12,000 feet, which is only a few mountaintops in the Sierra Nevada, the environment is similar to the polar ice caps. This biome is called extreme desert and is characterized by extremely cold temperatures and a complete absence of plant growth. There's one last point that I need to make about rainfall and elevation. As the moisture-laden air from the ocean passes over the Sierra Nevada mountain range, it releases more precipitation at higher elevations. But on the eastern slopes of the mountain range, most of the moisture has been released, so the eastern slopes of the mountains receive significantly less rainfall, and the amount of precipitation continues to decline with lower elevations down the eastern slopes to the desert climate of western Nevada. In summary, 65% of the world is covered by open ocean, which is nutrient poor and one of the least productive biomes. In contrast, estuaries are areas where freshwater streams or rivers merge with the sea. These estuaries are enriched with nutrients washed downstream by the rivers, which makes them very productive ecosystems and active breeding grounds for many different types of aquatic animals. As we move inland across the coastal hills of Southern California, which are mostly covered in chaparral, we eventually reach the Central Valley, which used to contain vast tule marshes, but is now mostly farmland with some temperate grassland. The foothills of the Sierra Nevada mountain range are best described as savanna because they contain a mixture of grassland, scattered oak trees, and stands of brush. As we climb in elevation, the oak trees give way to conifers, and from about 3,000 feet to 10,000 feet in elevation, the landscape is covered with taiga, which is more commonly known as coniferous forest, or a forest composed of evergreen conifers. This change in vegetation is partially due to lower temperatures and partially due to increased rainfall as elevation increases. From about 10,000 to 12,000 feet in elevation, the landscape is tundra, which occurs in extremely cold environments with very short growing seasons that can barely support small plant growth. Very few mountains in the Sierra Nevada range are taller than 12,000 feet, but for the few that are, their peaks are examples of extreme desert, which is characterized by extremely cold temperatures and a complete absence of plant growth. Precipitation increases with increased elevation all the way up the western slopes of the Sierra Nevada range, but it rapidly declines down the eastern slopes of the mountains as most of the moisture is already dropped on the western slopes.
How did you come to be where you're living right now? Did your ancestors move, or were you forced to move to the region? Did you pursue work, education, or social connections in another area? What led you to live where you do now? This movement from one place to another, and the sequence of events it took to get here, is an example of a process in geography. This lesson focuses on spatial processes and explains why geographers are interested in how you got to where you live today, along with other distributions across the Earth. Geography involves the study of why things vary from place to place on the Earth, also known as spatial distributions, or anything that can be mapped. Spatial distributions that can be mapped can include anything from temperatures in an ocean, the language of a country, the spread of forest fires in a region, and the ethnic demographics of a particular city. A specific question a geographer might ask is why people of a certain ethnic background have migrated to another area of the world. Once a geographer knows what phenomena they want to study, they'll look at the underlying process for how things came to be a certain way, such as how the migration occurred. They also try to predict what is going to happen in the future, like whether people will continue to migrate to a particular area or not. The underlying process that geographers study is known as a spatial process. A spatial process explains how people came to live in a certain area, because it answers the question, why does this spatial distribution exist? That sounds pretty broad, doesn't it? That's because the concept is as vast as the variety of phenomena on Earth. Even geographers themselves sometimes have a hard time using the term spatial process because it can describe so much. A process is involved in every spatial distribution that can be mapped, from temperatures in an ocean, the language of society, the spread of forest fires in a region, and the ethnic demographics of a particular city. Let's focus on one example to see how a geographer might connect a certain spatial distribution with the spatial process involved. The Irish potato famine in the 19th century contributed to Irish migration to the United States during that time. People were starving and sometimes without work, and they were looking for an opportunity in another region. Looking at these events as spatial processes helps us consider how and why the numbers of Irish people in the United States increased and why people chose to leave Ireland. In this case, the spatial distribution is the Irish American population in the United States, and the spatial process was the series of physical, environmental, and human events that led to this change. According to National Geographic, there are three general types of spatial process: natural physical systems, environment-society relationships, and human systems. These different systems help to explain how a spatial distribution came to be, such as the distribution of Irish Americans in the United States. Natural physical systems include processes caused by natural laws of energy and matter, such as temperature. These phenomena are local and measurable and relate to the physical Earth. Environment-society relationships are the processes that involve the impact of society on the environment, such as soil erosion and the destruction of rainforests. Finally, human systems describe processes related to human behavior and innovation, such as language, technology, and religion. In our example of Irish immigration to the United States during the potato famine, an example of a natural physical process is the water mold that ultimately caused the potato crop to develop a disease that destroyed it. An environment society process was human beings planting crops in that region. An example of a human process was the public response to this crisis by migrating in some cases. When geographers aim to look at patterns and processes, they observe the movement of people and resources through space, which we've just described as spatial processes. They also look at these changes and shifts over a period of time. A temporal process involves events that can be observed in a particular order. It may help to remember the term temporal as one relating to time, both beginning with the letter T. As you consider an event like migration due to the potato famine, you might notice that the process is both spatial and temporal, relating to both space and time. The two ideas are highly related, and this connection has led geographers to consider the two types of processes to be interconnected as they study their subjects. Temporal processes, or looking at the timeline associated with events, can help explain why spatial shifts have occurred. For instance, if you looked at the migration to the United States from Ireland without considering the time period associated with it, you might miss that people were moving in part due to the famine. A geographer might also notice that immigration from Ireland was still happening even before the famine, since conditions in Ireland were quite harsh earlier in the century too. Looking at how different trends changed over time can help understand those trends and why they spread. Geography involves the study of why things vary from place to place on the Earth, also known as spatial distributions, or anything that can be mapped. A spatial process aims to answer the question, why does this spatial distribution exist? Three types of spatial process include natural physical systems, such as the water mold that killed potato crops, environment-society relationships, such as the planting of crops, and human systems, such as the human decision to move location. A temporal process involves events that can be observed in a particular order. A temporal process is one relating to time. Spatial and temporal processes are highly related, and geographers typically use these concepts together to help explain the differences we see in the various areas of our world. Imagine there's been a major hurricane and a whole region has been affected by the damage. A woman named Dahlia watches the news coverage from her home many states away and learns that there's a group of people in her area headed to a town that's requested help from volunteers. She debates whether she's willing to travel the distance to the area, trying to decide whether it's too far to go or not. As Dahlia considers the distance, she also reflects on how her grandparents used to live in the area where the damage is worst, and how she remembers visiting there as a child. She can see the streets where she used to play, and they're underwater. These memories will factor into whether she decides to travel the distance to the area. This lesson looks at the field of behavioral geography, the study of how individual human beings make decisions in relationship to their spatial environment. We'll focus on the question of how a person perceives distance and discuss the contributions of this school of thought. To better understand the roots of behavioral geography, let's look at some concepts that came before it. Geography considers how things and people move through space, which can often be tracked and shown through data. For instance, we can determine how many people take a particular highway or use a certain subway line or flight path based on records about these behaviors. Geographers have historically spent a good deal of time on this type of aggregated data, the kind of data that shows many people's behaviors put together to reveal trends. Once you look at this level of human behavior, you start to notice patterns people have. For instance, one of these patterns is the gravity model, which at a basic level states that movement declines with increasing distance. In other words, the further away something is from your home, the less likely you are to travel there. In this model, a person who lives in Dahlia's area is less likely to travel to the hurricane site than someone who lives closer to it. Yet over time, some geographers also notice that the concept of distance is relative to the individual person. What's close to you may seem far to your neighbor. Although distance can be measured in feet or meters, the way a person understands distance in their own mind will be different than the person next to them. For example, to some people, a city like Paris is a world away, somewhere they may never travel, while for others, Paris is a familiar place and a place they've been many times before, a place they can afford to travel, so a lot closer in their minds. This matters a great deal when determining how likely a person is to travel there. This perspective that the individual's own mind matters in how they make decisions and move through the world is a very important aspect of behavioral geography. Behavioral geographers are interested in disaggregated data, data that focuses on the individual. A behavioral geographer would be interested in how a particular person chooses whether to go to Paris or not, along with many other questions about movement of human beings. Why would it be useful for a behavioral geographer to understand the perspective of an individual, such as Dahlia, who's deciding whether to travel to the hurricane site? One of the major contributions that behavioral geography can make by looking at the individual is in gaining a more realistic view of how human beings make decisions. Let's say, for instance, that researchers assume that the further away a person is from the site of a natural disaster, the less likely they are to volunteer to travel there to help with relief efforts, based on the gravity model. What about Dahlia's family background in that region, or her passion for volunteering? These factors would also influence whether she views the site of the disaster as close or far away, worthy of her energy to travel there or not. Human beings do not make decisions based on the literal distance of miles or kilometers alone. Assuming they do, misses out on the complicated reasons people actually act. Behavioral geographers recognize that people make decisions and behave in certain ways because of their beliefs and understanding of the world, not just based on judgments of facts such as distance. One criticism of this approach is that a behavioral geographer can be too focused on the individual in research and ignores trends that could provide valuable insight. For instance, in the example of Dahlia volunteering to visit the site of a natural disaster, her own story sounds unique and individualized. But what if a survey of volunteers in the area revealed that many people in that area had family roots in the disaster site, making it more likely that many individuals would combine their efforts to travel there, encouraging one another based on their shared memories of the area and passion to help a place that matters to them? The collective aggregated data of their family background would be very useful in this case, demonstrating the demographics of the people in the area and that many of them share characteristics in common, such as family roots in the region of the disaster. One of the strengths of behavioral geography, on the other hand, is its interdisciplinary nature, or the fact that the field is made up of researchers with backgrounds in a variety of areas, from psychology and other social sciences to the humanities and education. This collaboration helps the field to address areas where it could become stronger and avoid too narrow a focus. Behavioral geography is the study of how individual human beings make decisions in relationship to their spatial environment. While geographers have historically spent a good deal of time on aggregated data, the kind of data that shows many people's behaviors put together to reveal trends, behavioral geographers take a different approach. They typically look at disaggregated data, data that focuses on the individual. In this view, the individual's own mind matters in how they make decisions. Although distance can be measured, the way a person understands distance in their own mind will be different than the person next to them. One criticism of the field is that it has the potential to be too focused on the individual in research, but its interdisciplinary nature opens it up to contributions and insights from many other fields. Finally, your favorite musical artist is coming to a city within a day's drive from where you live, and you couldn't be more excited. After calculating the cost to travel to attend the show, stay overnight, and the price of the ticket, you determine that you need at least 2 other people to go with you to make it affordable to attend by splitting some of the costs. In this lesson, we'll look at your trip to the concert as an example of spatial interaction, or the flow of information, products, and human beings from one location to another. We'll look at what will make it possible for you to go, or what could stop you from attending. This lesson will focus on 3 principles of spatial interaction, as proposed by transportation geographer Edward Ullman: complementarity, transferability, and intervening opportunity. After you hear about the concert, you decide to go online to check out the tickets and discover that there's a good number left, hopefully leaving you time to work out where the money will come from so you can attend. The availability of tickets suggests that the city where the concert is being held has fewer fans within its radius than want to attend, can afford to attend, or were willing to buy their ticket as early as you. This surplus of seats makes it possible for you to come from an outside area to enjoy the concert. One area having a surplus while another area has a deficit or need is known as complementarity. You can remember this idea by thinking of how you, the eager concertgoer, are a good complement to the concert that has a seat available to you. In order to get to that concert, you need to be able to afford it. Perhaps if someone has a tight budget, going to the concert will be made possible by sharing the costs with others for the overnight stay and for putting gas in the car. This is an example of transferability. Transferability is the cost of movement between 2 places, such as the cost for you to get to the concert. Other examples include the price to send a package in the mail, or what it costs to commute to work. Transferability is important to understanding spatial interaction because it determines what movements are most likely to occur. When the price is too high, movement from place to place may not happen after all. This may be the case even in a situation where there is complementarity, such as the surplus of seats available at a concert. Finally, an intervening opportunity will also factor into whether a particular movement occurs. An intervening opportunity is an alternative supply point. In the example of the concert, the supply point is where the concert is being held. If you could attend the concert somewhere more convenient, that would be an example of an intervening opportunity. You would be more likely to attend the concert that's closer to you, rather than the one that's further away. Another example would be a less expensive concert ticket becoming available at another time and place, or another concert that you decide is a better use of your time and money. These are all intervening opportunities. Geographers are interested in each of these principles because it can help them predict what's likely to happen in terms of the movement of people, things, and information. They can use spatial interaction models to try to visualize trends and examine the likelihood of movement occurring. These insights go beyond the movement of physical objects and human beings to also include the flow of information from place to place, such as via the internet. Other technologies, such as the capacity of your phone to indicate your location, can contribute to models of spatial interaction. Spatial interaction is the flow of information, products, and human beings from one location to another. Three principles of spatial interaction, as proposed by transportation geographer Edward Ullman, are complementarity, transferability, and intervening opportunity. One area having a surplus while another area has a deficit or need is known as complementarity. Transferability is the cost of movement between two places, and an intervening opportunity is an alternative supply point. Geographers use these principles in spatial interaction models that can help them predict what's likely to occur in the movement of things, people, and information. If you spend some time online, you've probably run into internet memes. These are concepts such as photos or videos that are spread among users online, often repeating similar themes and styles. One example is Harlem Shake videos, which went viral in 2013. During this time, people from all over the world duplicated and expanded on themes that became a major sensation, at least in the short term. Geographers want to know how ideas like this are distributed across distances. In this lesson, you'll learn how culture gets diffused among people and what terms a geographer would use to describe viral videos and other trends. Cultural diffusion is the spread of cultural trends across locations. Beliefs, practices, and ideas get shared from person to person and sometimes even around the world through this diffusion, as happens with viral videos. Many cultural practices are spread by a type of cultural diffusion called expansion diffusion. This is when a trend is spread from its originating place outward. There are several forms of this type of diffusion: contagious, hierarchical, and stimulus diffusion. Harlem Shake videos are a great example of contagious diffusion, or when a cultural trend is transmitted from person to person from an original source to numerous others, similar to a virus. Even the name viral videos speaks to the idea of a contagion, spreading an idea almost like an illness would spread through contact and interaction. As cultural trends gain in popularity and draw our attention, profit may become a motive in perpetuating the trend. Think of how viral videos add advertising, or companies pick up on internet memes to sell more products as a result. Another form of expansion diffusion is hierarchical diffusion, or when a cultural trend is spread from one segment of society to another in a pattern. Consider how hip-hop culture emerged from within urban areas, but is now known in all regions of society, including suburban and rural areas as well. When information is known by government officials before the public, hierarchical diffusion is the method the news is spread. Think of how information about a major event, Osama bin Laden's death, spread from the highest levels of government to eventually get shared with the public. Finally, stimulus diffusion is when a cultural trend spreads, but is changed by those adopting the idea. For example, many in the United States practice yoga, but make use of it in a different way than the regions where this activity originated. In fact, most of us associate yoga with a particular form of exercise involving poses, but these movements are only one dimension of the practice of ancient forms of yoga. To help you remember the name of this type, think of stimulus as a stimulating new idea that sparks another culture to use it and also motivates them to adapt it for their own purpose. Expansion diffusion in its various forms are not the only way that ideas and practices are passed along to others. Another way that culture spreads is by relocation diffusion, when a person migrates from their home and shares their culture with the new location. Relocation diffusion accounts for much of the folk culture that can be seen in different regions based on migration patterns. If a person grows up in a large city, for instance, They may have lived near a neighborhood such as Little Italy or Chinatown. The communities surrounding these cultural enclaves then have the opportunity to learn about and even participate in the cultural traditions of these groups. Traditions may also be passed on to family members, neighbors, and friends. Folk culture is viewed as retaining its connection to an original place. When you experience folk culture, you typically know it relates to a particular region or people. Folk culture is often contrasted with popular culture. With viral videos and many other forms of expansion diffusion, the connection to the culture's origins are often less clear, and so they're labeled as mainstream popular culture or pop culture. Folk culture frequently contributes new ideas to pop culture. Before the internet craze, the phrase Harlem Shake had referred to an actual dance that had roots in the Harlem neighborhood of New York City. However, the dancing you see in the videos is not based on this at all. Is the end result that the folk origins of the phrase Harlem Shake were lost? Not necessarily. Some argue that the real, original Harlem Shake dance is now more well known due to the overall publicity of the videos and everything related to the name. Consider how many people may have looked online for the pop culture video and discovered the folk culture dance in the process, bringing the dance to mainstream awareness. In many ways, the internet can blur the lines between folk and pop culture, since there is less literal distance to travel to share cultural information and practices. From viral videos to enclaves of other cultures, such as Little Italy, culture is diffused through society using many different methods. Cultural diffusion is the spread of cultural trends across locations and involves both expansion diffusion and relocation diffusion. Relocation diffusion occurs when a person migrates from their home and shares their culture with a new location. Expansion diffusion occurs when a trend is spread from its originating place outward. There are several forms of this type of diffusion, including contagious, hierarchical, and stimulus diffusion. Contagious diffusion will happen when a cultural trend is transmitted from person to person from an original source to numerous others, as in viral videos. Hierarchical diffusion is when a cultural trend is spread from one segment of society to another in a pattern, such as hip-hop spreading from cities to less populated areas. Stimulus diffusion is when a cultural trend spreads but is changed by those adopting the idea, such as American practitioners of yoga poses. Popular culture encompasses mainstream ideas and practices, while folk culture continues to be associated with a particular region or origin. At times, the internet may blur the boundaries between the two.
Humans might be creatures of habit, but historically we tend to move around a lot. Most families in the USA, for example, did at one time live elsewhere. Human migration is the seasonal or long-term movement of humans from one area of the Earth to another. For example, if you move from the United States to Europe, you have just migrated. Or if you travel across the country to find a summer job, you also have just migrated. Or if your family were, several generations ago, from the country of Poland, your family is said to have migrated, or immigrated, which is a similar word. There are many possible reasons that humans might migrate: economic reasons, social reasons, and physical reasons. Economic factors include things like searching for jobs or higher pay. Social and physical reasons usually involve forcible migration, like fleeing from persecution or intolerance, or a natural disaster. But reasons for migration can also be split into push or pull factors. Today we're going to talk in more detail about this way of categorizing the reasons for human migration. A push factor is a reason for migration that relates to the area the person comes from, something that is pushing them out of an area. Examples of push factors include economic factors like a lack of economic opportunity and jobs. For example, the seasonal migration of Mexicans and Central Americans to the United States. But there are also social factors, like escape from religious or cultural persecution, such as the Huguenots in 16th century France and Jewish refugees from Nazi Germany. And then there are physical push factors, like natural disasters, towns and villages being destroyed by volcanoes, hurricanes, flooding, drought and earthquakes. Wars also tend to lead to a lot of push factors. Most wars lead to large numbers of refugees. A pull factor is a reason for migration that relates to the area of destination, something that is attracting them to an area. Examples of pull factors include an area being economically prosperous, having lots of jobs, or a particularly large amount of freedom, making it a haven for those who are escaping from religious or cultural persecution. Sometimes this can be accidental, but countries have at times advertised themselves specifically to encourage migration. For example, a lot of countries were short on workers after World War II. An area can also be economically attractive if it has lots of natural resources. For example, finding gold and oil attracted people to the west of the USA. Both businesses looking to make money and miners and engineers looking for work. A thriving new industry can also be attractive. Then there are environmental pull factors like a pleasant climate. Human migration is the seasonal or long-term movement of humans from one area of the earth to another. For example, if you move from the United States to Europe, you have just migrated. There are many possible reasons that humans might migrate. Economic reasons, social reasons, and physical reasons. Economic factors include things like searching for jobs or higher wages. Social and physical reasons usually involve forcible migration, like fleeing from persecution or intolerance, or a natural disaster. But reasons for migration can also be split into push and pull factors. A push factor is a reason for migration that relates to the area the person comes from, something that is pushing them out of an area. A pull factor is a reason for migration that relates to the area of destination, something that is attracting them to an area. Examples of push factors include economic factors like a lack of economic opportunity and jobs, escape from religious or cultural persecution, and natural disasters, towns and villages being destroyed by volcanoes, hurricanes, flooding, drought, and earthquakes. Examples of pull factors include an area being economically prosperous, having a particularly large amount of freedom, a lot of natural resources, a thriving new industry, or a pleasant climate.